8.3. Tribal and traditional soil. Classifications. From the Ecologist 14, 4, 1984. Tribal and traditional people classify their soils on a great variety of characteristics based on asterisk color, indicates humus content. Asterisk taste, agrees with our pH measures. Asterisk moisture capacity and water retention. 185. Asterisk sand content. Asterisk general texture. Asterisk firmness. Asterisk structure, dry soils. Asterisk wet season structure. Asterisk vegetative indicators, health of a specific crop. Asterisk drainage. Asterisk slope. Asterisk elevation. Asterisk animal indicators, e.g. termites, the shape and size of their mounds. Asterisk plant indicators, for acidity, drainage, fertility. Asterisk katina, types of soils based on slope. Relationships. Asterisk hot and cold soils relative fertility, not temperature, can also indicate water retention. Asterisk usage, e.g. pigments, pottery, salt extraction from reeds. Asterisk work needed for crop, and energy input. Asterisk suitability for specific crop, e.g. yam soil, taro soil. Soils can be ranked for up to 12 crop types, giving a complex classification. Asterisk organic content, apart from color. Thus, sophisticated assessments of soils are available from most agricultural societies. However, modern classifications are more complex in terms of nomenclature and physical categories, and use standard color charts, Munsell and others, standard comparisons, standard sieves, and so on. 8.4. The structure of soils. Soil is a complex material, and if it has enough plasticity, usually clay or glue or fiber from organic sources, it can be pressed or compacted into mud bricks, hard pise, or baked to clay or stoneware. In any of these forms, it is of little use to plants. Uncompact soils are open, crumbly, or soft and less concreted by chemical solutes or compacted by plows, hooves, or traffic. Crumbly soils have, nevertheless, a definite structure. The soil particles are in nodules or clumps held together by roots, clay, minerals, and chemical bonds. If we speed a plow or drag harrows through these fragile assemblies, they may powder up as they do in a potter's ball mill, or on outback roads. Bull dust is the term used in the Australian outback. A soil scientist might speak of snuff dot. Dryland soils with a high salt content are particularly susceptible to loss of crumb structure, only partly relieved by application of gypsum. The mantle of soil and subsoil that covers the earth is as thin as the shine on the skin of an ant. This mantle extends as living mud below the waters of earth as well as on land. It is composed of these elements. 186. Asterisk minerals, mainly silica, oxides of iron and aluminium, and complex minerals. Asterisk soil waters, fresh, saline, with differing pH, and dissolved minerals and gases. Asterisk gases, some from the atmosphere, others emitted by the breakdown of rocks and the earth's interior. Asterisk life forms, from fungal spores and bacteria to wombats and ground squirrels, from massive roots to minute modal algae. Asterisk once living remains, the humus of the earth. Decayed, compressed, and fossil organic material. Soils rarely extend much below 1 to 2 m, and are more often a living system 6 to 12 centimeters deep. Subsoils, lacking the life components, and buried soils or deep washed silts are rare and confined to valley floors and deltas, or glacial mounds. To estimate the proportion of clay, silt, sand, and coarse in soil, a sufficient first test, for judging the suitability of soil for dam building, mud brick construction, and crop types, mix a sample of soil from a few typical sites, and pour a cup of soil in a tall jar, filled almost with water. Shake vigorously and let the sale fraction settle out over a day or a week. Clay can remain in suspension for up to a week. 40% or so. Clay is needed for dam walls, and less than that for good mud bricks, without lime or cement added. Of these fractions, the coarse particles are inert, although useful in fine soils as a wind erosion deterrent. Sands are 0.05 to 2 mm, silt 0.05 to 0.02 mm, clay particles less than 0.002 mm. 1 g of clay has a surface area of up to 1,000 times that of 1 g of sand. Soil crumb structure, aided by lime, calcium, aids the bonding together of these fractions and creates 20 to 60% pore space. The organic materials and gels hold the structure open in rain, and where plant nutrients can become soluble for absorption by roots. The USDA classification of soil types by particle size. 8.5. Soil and water elements. Of the 103 known elements, only some are commonly dealt with in the literature on soils. And water. Soil itself is predominantly composed of aluminium, silica, iron, and, in certain shell, sand, or limestone areas, calcium. Only mineral ore deposits have large quantities of other elements. The modified form of the periodic table is given in the centerfold of the color section, and a more extensive annotation on specific elements is given in Table 8.1. T is essential that designers in any field have a basic knowledge of nutrients, poisons, and tolerable or essential levels of trace elements in food, water, and the built environment. The health of plants, animals, and the environment of soils and buildings are all dependent on the balance of elements, radioactive substances, radiation, generally, and water quality. Of particular concern in recent times is the level of radioactives in clays, bricks, paints, and stone, and both the emissions from domestic appliances, TV, microwave ovens, and microwave radiation from TV transmission and power lines. Thus, the annotations in Table 8.1 cover a range of topics, including short comments on human health. In this case, we are using the periodic table not as an aid to chemistry but as a guide to understanding the role of the elements in soil, water, plants, and animal tissue, and nutrition. The color coding and the dots on the periodic table. See centerfold, plus the following annotations of elements give some of their known effects on soil, plant, and animal health, or their special uses. 8.6. Feldspars. Kalium. /Ron. Silica. Laura Ely. Silica. Figure 3.2. Jar method of assessing crude soil composition, useful for classification, uses for mud brick or pise work. Soil sample is shaken in water and allowed to stand until layers form, 1 to 20 days. The volume of each fraction determines uses and a texture classification. See figure 8.1. Primary nutrients for plants. Soils are often analyzed as deficient in both PHOS, phates, and potash in heavily leached areas. Phosphates are supplied either by guano, bird Manures, from dry islands, or from older deposits. Found in sedimentary rock. Potash occurs in the mineral kyanite, formed in areas of evaporated waters. Desert salts usually contains 20 to 25% potash. Phosphatic rock is restricted in distribution, and contains 86 to 15% phosphorus in various combinations. With oxygen or water, hydrated. There are large reserves of potash in common minerals like orthoclase, a major constituent of granite. Nitrogen can be supplied by water or land plants, inoculated with rhizobia, or fixed by algae and water. Plants such as Cerpus or Azala. We can create the conditions for fixing nitrogen by growing these nitrogen-fixing plants, inoculated with the appropriate rhizobia. Much higher levels of nitrogen than were previously thought to be available are fixed by land plants, in a series of zones extending from the roots. Even after nitrogenous plants such as acacia, albizia, and elaeagnus are cut, the root zone will continue to release nitrogen for up to 6 years. $. That pioneer legumes or nitrogenous trees serve as cover crop for trees, and release nitrogen during their lifetimes and for some years after. Legumes may not be needed in older forests, and typically die out under canopy. Only a few larger leguminous trees, Samania, acacia, melanoxylon, persist as forest trees in a mixed forest. Both phosphate, concentrated by seed-eating birds, and potash, from burnt and rotted plants or compost, can be locally produced if birds are plentiful and their manures are used. The phosphates mined from marine guano, however, may contain concentrated levels of cadmium and uranium, either or both of which, and other heavy metals, can be taken up by the oceanic fish and shellfish used by marine bird colonies. Continual heavy use of such resources is likely to become polluting to soils. Our only ethical strategy is to use just enough of these resources, and to conserve them locally. Sources of minerals in soils. The sea. It makes sense to assume that as soils are leached, and so made mineral poor, these minerals later become more concentrated in the sea, in marine organisms, or in inland salt pans, seaweeds, seagrasses, and fish. Residues have always been part of agricultural fertilizers, and have maintained their place even in 187 modern times. As seawater evaporates, first calcite and dolomite, then gypsum and anhydrite separate out, all are used for soil conditioning, pH adjustment, or to restore soil crumb structure. Next, rock salts crystallize out, but only when tropical uplands may actually lack this common nutrient, although even their specific plants, often aquatic, concentrate salt which can be gathered or leached from their ashes. Lastly, potash, magnesium salts, and a host of minor elements remain, the evaporites, those already deposited, being the most soluble and therefore earliest deposited. The liquid that remains after the common salt content deposition is a rich source of minor minerals and trace elements. It is, in fact, sold as bitter urns, bitter oily fluids, for dilution and isolation in crop soils, or in low concentrations. Diluted 100-500:1, used directly as foliar sprays in strengths varying from 1 to 20 I/Ha. Very corrosive. Bitter urns, which include bromine and many of the early elements of the periodic table, plus some rare minerals, are safely held and distributed only via non-corrosive vessels and pipes. Today, polyethylene pipes and drums. Bitter urns are cheap and easily to leached areas, but their effects must be established by local trials on specific crop. As these evaporites are so easily dissolved, they are also those most likely to be carried to sea in rains. Rocks and rock dusts. Granites contain feldspaths yielding potash or sodium salts. Limestone and dolomite yield calcium and magnesium, and mineral deposits or their ores give traces of the basic minor elements. Of these, calcium, in all but highly calcareous areas, is most needed. Dolomite, except where magnesium is already in high ratio, is next. Phosphates and feldspaths follow, along with trace elements in small quantities, as low as 5 to 7 kg/100 Ha for zinc, copper, cobalt, and molybdenum. Field trials have established that cheap ores, finely ground, are as effective as more refined sulfates or oxides. Leeper 1982. Sometimes such minerals are given to animals as solid licks, in molasses, in water, or as injections or bullets of slow-release elements. Cobalt, in a pellet which lodges in the rumen. Some mineral elements also reach plants via urine, but foliar sprays are more rapid-acting and effective. Fine rock dusts of a specific rock suited to local needs are often cheaply available from quarries or gravel pits. Basalt dusts are helpful, for example, on leached tropical soils. Rock phosphate contains 8 to 15% phosphorus, but is very slow to release nutrient, and may in fact be absorbed completely onto leached clays and clay loams. Superacid phosphate added to compost, or to plants used in compost, may be necessary under such conditions. Rock dust as an unselective category can do as much harm as good on soils, adding excessive or poisonous nutrients in some cases, or excessive micronutrients. 8.7. The distribution of elements. In the soil profile, there seem to be two important determinants of the concentration of elements or nutrients through the soil profile, that vertical column of soil from the surface to 2m or so deep. The first is the penetration of water. Water is a universal solvent, enabling compounds to dissociate into ions, and transporting them, firstly, to various deposits at microsites in the soil. This effect works in 3 dimensions. Water travels by infiltration to varying depths, soaking in from the surface down. Water can also rise from the soil water table upwards, either by flooding, by capillary action. Continued on page 195. Permeable substrate. 188. Area, DF or SOS. Waterlogging CH solution CoLLARE. I. T. Soil. Creep ANP Sa will. Sol. Aharon Peepins. Sol. Acidity decreases, alkalinity increases /. 60 cent. Plus. PEPOST New York V. HD. Breakaway NREA Sol MEV air NT. Lobulate. EI eroding. A. I. T figure 8.3 few trees. Remember CA soil. Cat Ha. A typical profile across a valley, rainfall, erosion, and leaching create. Tributary sand clogged, distributaries fairly predictable sol sequences. CONF8 detailed section shows precession in arid areas. Sea soil erosion cells, degree of erosion and extent of erosion processes. Can be analyzed from aerial photographs. 189. Table 8.1. Key to plates 12 and 13, the periodic table. 1 hydrogen, H, is an extremely mobile and reactive gaseous element. The number of free ions of this element determine the pH of soils, together with the hydroxy O2 radical in alkaline areas. Hydrogen combines with several other elements and organic substances to form acids. It is a potentially INF flammable ionic gas, now replaced by helium in balloons and airships. Some plants, especially algae and rushes, can transpire hydrogen, and in so doing break down the halogenated hydrocarbons that are used in pesticides and herbicides. Hydrogen combines with oxygen as hydroxyl, O, or water, H0, the basic gaseous and liquid elements. HT is the concentration of H and or O ions in solutions that decides the pH of soils and water. Hydrogen, combined with carbon as methane, CH, is emitted by decaying humus in anaerobic, airless environments, such as underwater or in compacted of body soils. Such soils usually have a mottled profile, and are often bluish, yellow, of contain iron stains and nodules. Methane is a component of marsh gas, a biogas from digesters, usually associated with carbon dioxide and sulfur dioxide, the gases of decomposition. A. Sulfurous me in subsoils is a guide 10 WEL season. Waterlogging, and should be noted for plants intolerant of stagnant waters. 3 lithium, Li, the lightest metal, is prescribed medically as tablets in cases of hyperactive and disturbed people. It may moderate nerve impulse transmission across synapses. Lithium is found in plant and animal tissue. 5 boron, B, is a trace element, necessary to, e.g., the brassicas and beets. As many detergents also contain boron. Boron pollution or poisoning can build up in gardens or affect plant health adversely. Use soap, especially in drylands where citrus and grains in particular can be boron poisoned in dry seasons. Borax at 160 G/H is used on beet and brassica, cauliflower, turnip, crops where soil levels are low in boron. Boron seems to be essential to the transport of sugars in the plant, to pollen formation, hence, teardility, and to call wall structure, like calcium. Borax is poisonous to seed and to insects, and is used with dilute honey as an ant and cockroach poison. Sea sediments, and the sea, contain high boron levels. Surplus boron can cause anemia in people. In soils, 0.75 ppm is ideal, but 1.0 ppm can be toxic to plants. It is likely to be at toxic levels in dry years, where soils have been derived from marina sediments. Oral research, XRO, Autumn 86. 6 carbon, C, is the basic building block, with hydrogen, oxygen, of 5 hydrocarbons, of life forms. It is added to soils as humus, compost, and mulch. Pitted or buried waste need nitrogen or oxygen, therefore, ALR, for decomposition. 10 to 20% humus ensures good structure in both clays and sands. More than 50% humus inhibits uptake of polluting heavy metals, lead. Cities, less than 7% may not improve soil structure unless calcium is added. Carbon combines with oxygen to form carbon dioxide gas, which is released from agriculture, forest felling, and industry to create the greenhouse effect and subsequent earth heating. This may be a critical adversity for human survival on Earth. Plant ES. Do not use bare fallow and add humus to soil. Carbon in soils is about 58% of organic matter, combustible, existing mostly as colloids. Assess nitrogen and multiply times 20 to obtain the carbon content of soils. 7 nitrogen, N, is a major plant nutrient, 80% of the air itself. Legumes and many non-legumes, alder, casuarina, that have root associates, fungi, bacteria, will fix nitrogen from air if molybdenum is present as a catalyst to convert nitrogen to ammonia. Nitrogen is a foliar spray of urea can, however, increase DHA protein content of grains such as rice by 40%. Nitrogen is part of all amino acids, hence proteins, of chlorophyll, and of enzymes. It is very mobile in plants, and has dominant effect on other nutrient use or uptake. Plants absorb nitrogen in the form of nitrates or ammonium, and the plant converts this to ammonia to create proteins. In water or with bacteria, nitrogen forms nitrates, which at low levels are beneficial, but at high levels, more than 80 ppl, are lethal to young animals and children. Also, mouth bacteria and sewage bacteria turns nitrates into nitrites, hence nitrosamines, which are cancer-associated. Nitrates are building up in all soil waters below agricultural land, and occur naturally in many desert-poor waters. Thus, fertilize plants in the garden at minimum nitrogen levels. Do not use heavy doses of nitrogen fertilizer, but rather a modest legume interplant. Check water levels for human health, especially in deserts. Too much animal manure also releases surplus nitrogen. Thus, reduce cattle and run them on pastures, not on feed-its. Dispose of sewage in forests to aid in tree growth. Constantly measure nitrate levels in leaves, water, soil. In particular, do not inflict high nitrate levels on people with malnutrition. They can be killed by an excess of nitrate in their food. Accepted levels in Europe, EEC standard, are 50 mg/L in water, 50 to 80 ppm. These levels are being exceeded where nitrate fertilizers and even natural manures are spread on soils. Ammonia from cow dung is now 115,000 T-bar in Holland, accounting for 30% of the acid in rain. From Dutch sources, NS February 686. In humid areas, 70% of human intake is from vegetables, and 21% from water. Some nitrite, or nitrate, levels, ppm, 0 to 50 safe for human consumption. 500 spinach grown from compost. 2.000 to 3,000 chemical fertilizer grown spinach. 190. And oxygen is necessary for respiration, energy, release in blood. Soils also need oxygen, air, and thus good open structure and soil pores as 12 to 30% of the soil bulk. Aeration in soils TS achieved by using calcium. Trees, worms, ripping, humus, of sometimes by blowing air through subsurface irrigation pipes. Waterlogging reduces pore space and thus root oxygen. Crops such as walnuts, oranges, chestnuts, and potatoes require deep blue soil and plenty of oxygen. Pear trees and marsh grasses, Yorkshire fog, imperative grass, require much less oxygen and can grow in more compacted or wet soils. Soil loosening and draining, conditioning, improves oxygen supplies to soils. Soils need to have good open pore spaces too. 1 to 2 m, 3 to 6 feet deep. Large salt pore spaces are only Achieved by soil life and perennial crop. 9. Fluorine. Although beneficial in small amounts, as in seaweed fertilizer, it is a serious poison at high levels. It is commonly found in bore water, or in downwind pollution plumes from metal processing works, zinc, aluminium, copper, causing bone deformation in animals, stunted growth, and serious metabolic disturbance. Check water, especially bore water, for high levels and use tanks for drinking water. Fluorine is useful at very low trace levels only. Surplus can cause anemia. High levels are found in, e.g., marine phosphate deposits, hence fluorine can be high in fertilizers derived from these. The fluorine level sufficient for normal growth and bone development is about 1 mg per day. Tea drinkers ingest this from tea leaves, as the chief source is in water. 1 mg/L, 1 ppm, is sufficient. Seafoods, fish, oysters, can contain 5-10 ppm fluorides. Problems of excess fluorine occur where dusts from mineral processing fall out on vegetation, where hard waters, common in deserts, contain more than 1 ppm. Fluorine, actual levels can reach 14 ppm, and where diet is mainly seafood, the bones, spine and ligaments can become calcified in areas where excessive fluorine is present in the diet. Teeth may be case hardened by fluorine, and show little outer sign of decay while the tooth itself rots. 41 sodium, Na. With chlorine, it makes up common salt. At low levels, it is necessary to plants and animals' cell health and function of the nervous system. At high levels, sodium causes collapse of soils and loss of pore space, displaces calcium and disperses colloids. Beets and some other crops need adequate levels, likely to be absent or low in wet tropical uplands only. Elsewhere, enough sodium comes in with rain as salt crystals in raindrop nuclei. Real problems occur when soil salts are mobilized by irrigation, potash fertilizer, or soil flooding in dryland areas. Excessive salt causes circulatory and kidney problems in people, especially those in sedentary occupations. Salt in vegetable cooking water blocks uptake of some heavy metals on plant proteins, so if lead pollution is suspected, add salt to cooking waters. 12 magnesium, Mg, with calcium it is found in dolomite. HT is needed by plants, and common in most subsoils. It forms the central atom of the chirophyll molecule, activates enzymes, and concentrates in seeds. Like nitrogen, it is very mobile in the plant. Magnesium is likely to be deficient only in sands and sandy soils. It is present in the clay fraction of soils, and is released by soil acids and humus. It is supplied by dolomite application on farmlands, as tablets of dolomite for animals, and mixed in animal foodstuff. Magnesium carbonate from dolomite buffers plant and sol acids, as does lime, but it can cause plant poisoning if not balanced by high lime, calcium, levels. Magnesium is essential for chlorophyll and in the mitochondria of human calls, hence energy metabolism. It is present in all green plants. Deficiencies do not normally occur where people are healthy and are not subject to diarrhea. When required by people it is given as an intravenous fluid at 10 millimoles per kg m. Body weight. 13 aluminium, Al. A Jekyll and Hyde element. It forms a large part of soils and red clays, with iron, or at S or bauxitic dry van deposits. Foot is poisonous as aluminium sulfate, formed in acid rain or sulfur polluted soils, e.g. in industrial areas, and is also released when cooking onions in aluminium cookware. Heavy aluminium silica uptake in humans may assist the development of senile dementia, thus calcium in the soil and S tablets is a partial defense. Some areas are naturally high in acid aluminium soils. An adequate level of calcium is needed in all gardens, and even in rainwater tanks, as marble or limestone chips, whole seashells, gravels of lime. Avoid aluminium utensils, use iron, enamel, stone, steel, if cooking salty, acid, or sulfurous substances. Vinegar, onions. Soluble aluminium in concentrations of 0.1 to 1.0 ppm is tolerable, but above this level, susceptible plants start to die, at 15 ppm or higher. Many plants dia. 14 silicon, Si, is an important part of cell walls in many grasses, bamboo, and is essential in soil cation exchange capacity of deep, red, heavily each tropic soils. An application of kamut dust can assist this exchange. Pine trees and conifers generally are poor nutrient recyclers, and can produce nutrient deficient silica soils under their litter, thus losing calcium and other elements to leaching. Therefore, use grasses and broadleaf, leguminous, or soil building trees with conifers. Many trees deposit salt, phosphorus, manganese, zinc, potash, etc. at high topsoil levels due to good nutrient recycling via lead tall. Silica is normally at 20 to 40 ppm in soil waters, and in highly alkaline, wet, warm areas can be leached away altogether, hence the use of cement, calcium silicate, to restore some silica to plants. In such areas, tree crops are the only sustainable solution. Silicates make up much of the bulk of normal soils, but very high silica in rock may produce acid soils in high rainfall areas. Silicic acid. Bamboos are good sources of calcium and silica as a garden mulch in the tropics. In ponds, diatoms need silica to proliferate. These are an excellent fish food. 191. 15 phosphorus, B, as phosphate, is an essential common plant element, recycled by many trees and fixed by the root associates of several trees. Casuarina, Pultenia, Banksia, by algae, in the mud of ponds, in bones, and in freshwater mussels. High phosphate levels in bird manures are derived from fish bones and seeds. Phosphorus is essential to the energy metabolism of plants, hence photosynthesis and respiration. Cell division, root development, and protein formation are regulated by phosphorus. It is highly mobile in plant tissue. In some oceanic guano deposits, phosphates can be contaminated by cadmium, mercury, uranium, 40 ppm, and fluorides. All heavy cropping demands phosphate for production, and there is a general world soil phosphate deficiency, especially in poorer countries. Most West Stem soils are now oversupplied with a very large unused swat bank of phosphorus. Hence, with the pollutants of phosphatic rock, cadmium levels in inorganic market garden crop may commonly exceed health limits. Bird islands, areas of volcanic volcanic ash, and some soils over phosphatic rocks are not phosphate deficient. Sandy, bare cropped, wet, and water logged soils, old soils, and alkaline soils may show deficiencies. On the latter, try sulfur to adjust availability. Superacid phosphates are used to make phosphate available to plants, albeit expensively. Most soils, superphosphate since the early 1950s, may have 750 ppm in the top 4 centimeters, and most of the rest of the applied phosphate is bound up and unavailable in the top 20 centimeters. Only on deep, coarse, leached treeless sands with heavy rains or in bare soil fallows is a lot of phosphate lost. Drainage water contains 0.2 ppm in clay or loam soils, a minute loss. In natural systems, phosphates are supplied by fish and bird manures. Calcium, iron, and aluminium immobilize phosphate. A pH of 6.7.5 releases it. Basic superphosphate, phosphate and lime, finely ground, is available, soluble, to plants. The home gardener can use bone dust, phosphate and lime, and mulches, which area all effective. About 45 ppm phosphate in soil is needed for grains, optimum pH 6.0 to 6.5. Pelleting seeds with basic superphosphate provides phosphorus. In soils, phosphorus combines with iron, aluminium, and calcium as insoluble compounds, and with living materials or humic compounds as available phosphorus. Despite folk stories to the contrary, superphosphate has not been found to acidify soils, unlike ammonium sulfate. Phosphate levels, native phosphate, fall with depth and are low in most subsoils. Generally, to increase phosphate availability, try humus in warm wet areas, sulfur in drylands, and adjust pH elsewhere with calcium, lime, or dolomite. For trees, apply light phosphate dressings regularly in sands. Phosphorus deficiency reduces growth in animals by depressing their appetite for herbage. Of all the elements of critical importance to plants, phosphorus is the least commonly found, and sources are rarely available locally. Of all DHA phosphatic fertilizers used, Europe and North America consume 75% and get least return from this input because of overuse, over-irrigation, and poor soil economy. If we really wanted to reduce world famine, the redirection of these surplus phosphates to the poor soils of Africa and India, or any other food-deficient area, would do it. Forget about miracle plants, we need global ethics for all such essential soil resources. As long as we clear cultivate most of this essential and rare resource, will end up in the sea. Seabirds and salmon do try to recycle it back to us, but we tend to reduce their numbers by denying them breeding grounds. Unpolluted phosphate deposits are found only in limited areas, in sedimentary rock. Trees do mind the rare phosphorus released by igneous rocks, and they are responsible for bringing up phosphorus to the topsoil wherever it is rare in more shallow-rooted plants. About 15 to 20% of the inessential use of phosphorus is in detergents. The oil potash soaps are the answer to that sort of misuse, or the recovery of phosphorus from grey water rather than a one-way trip via a sewer to the sea. Uncut forests may lose 0.1 kg/ha/year, while clear cropping can lose 100 kg/ha/year or more, a 1,000 times increase in lost minerals, never accounted for in logging and clearing, or added to the cost of wood chipping and newspapers. Phosphorus is found concentrated in seeds and in the bones of vertebrates, especially fish, in mussels, fresh water, and the mud they live in, and in the manures of animals eating fish, seeds, and shellfish. Bone meal from land animals is a traditional source, and most farms, up to 1940, kept a flock of pigeons as their phosphate factory, while in aquatic cultures, phosphorus was recovered from the mud of ponds, stocked with mussels and from fish and waterfowl wastes. Bat guano is also a favored source of phosphate in Holland. Even a modest perch in a bare-tiled will attract a few perching birds to leave their phosphates at a tree or along a crop line. Conservation farming, Cox and Atkins, 1979, p. 323. Loses about 1/2 to 1/3 the phosphorus of contemporary agriculture, even without non-tillage. Non-tillage farming would lose even less, but is rarely assessed except in dollar yield terms. By original farming, and home gardening with wastes returned to soils would lose even less, and finally, regional food supply, waste recycling, and a serious consideration of devoting 30% of land surface to trees might just be a sustainable system. Next to clean water, phosphorus will be one of the inexorable limits to human occupancy on this planet. We must not defer solving these problems or conserving of resources any longer, or we betray our own children. 16 sulfur, S dollar. Many anaerobic bacteria, thiobacilli, fix sulfur, which is why anaerobic ferment of plant and animal materials is rich in the sulfur-based amino acids, and of high nutritional value. The sulfur oxidized by anaerobic bacilli also removes, as 192. Insoluble sulfates, most heavy metals from such tow-through systems as sewage digesters. Some thick bacilli occur in all warm wet soils, and many can operate down to pH 1.0. With ammonium sulfate, soils tend to become acidic and so reduce plant yields. Sulfur is used in drylands to reduce pH and so make iron, zinc, and trace elements available. Clover, in particular, may show sulfur deficiency in the subtropics, wet summers. Sulfur is part of all proteins, and is present in the body as the two amino acids methionine and cysteine. The vitamins thiamine and biotin contain sulfur. Food intake by people is from the amino acids, and deficiencies do not occur if meat protein is sufficient, or if anaerobic ferment of feed materials is par of food preparation. Many vegetarians get their amino acids from yeast or bacteria rather than from fresh plant material. 17-chlorine, Cl, was used as a war gas, and today, to sterilize radars, it is a dangerous gas to inhale. Chlorine Js used by plants, and is normally available for salt. It is a trace element, and used only in minute amounts. It concentrates in crop, 6.9. 350 ppm in sol. Gives 1000 ppm in crop. In water, and in contact with organic materials, it releases chloroform, a carcinogenic gas. Avoid chlorinated water if possible. 19 potassium, K, is used in large quantities by plants. It is usually plentiful in N areas. Potassium is deficient on sandy, free-draining coast soils. Not much is removed by livestock, but potatoes, beans, flax, art. The export of hay may remove soil reserves to below plant needs. It is readily absorbed on colloids, and is usually plentiful in clays, especially lights, not in kaolin. Gardeners add ashes, bone, natural urines and manures or green crops for supply to heavily cropped ground. Earthworm castings commonly concentrate potash. Fat 11 times soil levels. Excess potash fertilizer can greatly increase soil sodium, and so block calcium uptake. Beware of this in alkaline or dryland soils. 20 calcium, Ca, is needed in all soils, and is removed by sodium in drylands. Even where calcium exists in an alkaline area, sodium may suppress its uptake by plants. Sometimes, gypsum is applied, 30 tons/ha, and the excess sodium then removed by flushing out as sodium sulfate. Plants need large amounts of calcium. It is an essential part of cell walls, enzymes, and in chromosome structure. The proper of the four major ions in ideal agricultural soils should be about calcium, magnesium, potassium, sodium, 50-35:6:5. Note that adding potassium can increase sodium. That sodium is antagonistic to, displaces, calcium, and that magnesium ions should always be less than calcium ions. Do not add too much dolomite if soils, as clays, already contain adequate reserves of magnesium. Many peoples have lactose intolerance and cannot get calcium on a milk diet, so lime or dolomite on gardens or aziables may be needed. Calcium is lost, excreted, in stress, and needs replacement after periods of prolonged stress. Low calcium areas produce predominantly male farm animals and humans. As a primary sex ratio, and lack of calcium produces skeletal and metabolic malfunction. Calcium phosphate is the chief mineral constituent of bones. Bony tissue is always losing and gaining calcium. BYT older women, in particular, suffer bone fractures from loss of calcium in the aging process. Immobilized limbs also lose calcium. Gross calcium and vitamin D deficiency results in rickets. 22 titanium, Ti, is not a nutrient, but in sands and the presence of sunlight it acts as a catalyst to produce ammonia for plants, often combined with iron, TiFA. NS and FIP 79, September 863. Ammonia is provided at 50 to 100 kg higher. Rain and moist soils make this available to plants a useful desert strategy. 24 chromium, Cr, is a poison to plants and animals, occurring in serpentine rock. It is used in the preservation of timber, and is to be guarded against from electrolytic and leather works as it poisons active biological agents in sewage works. It is easily removed or recycled at the source. As some chromium occurs in all organic matter, it is in fact a base element, related to glucose tolerance in humans, and necessitating insulin if absent or in very low quantities. Very little firm knowledge of the metabolic function of chromium is available. 25 manganese, Mn, is a readily available trace element on acid soils, except in sands. It may cause manganese poisoning below pH 6.5. On alkaline soils, or when pH exceeds 7.5, it may be deficient in grain, crop or vegetables, but seed soakage, seed palleting, or foliar saris supply this nutrient. Even flooding at periods will mobilize manganese. A typical deficiency situation occurs on poor sands heavily dressed with lime. Bacteria fix insoluble manganese, and can create problems in pipes and in concrete water raceways. Even at 2 to 3 ppm manganese. Aluminium sulfate from acid rain on soil may mobilize manganese. Mercury, cadmium to lethal levels. Manganese leaches out of acid soils, deposits in alkaline horizons as manganese-iron concretions, and on seafloors as larger nodules. 26 iron, Fe, is normally highly plentiful in soils, and is a critical element for plants and animals. Plants can show iron deficiency symptoms in alkaline drylands or on heavily limed garden soils. Sulfur in gardens, or iron chelates, remedies the situation. Iron can also be added as small amounts of ferric sulfate. Deficiency causes interveinal leaf yellowing in plants, and low blood iron in people, anemia. Ferrous iron spicules in soil assist the formation of ethylene. Ferric iron oxides are unavailable. F0. Iron concretions and iron staining in sands are often associated with microbial action along plant root traces or on deficiency anemia. In people is a common problem in deserts, or after blood losses in menses or dysentery. In humans, blood iron is as important in energy. 193. Transfers as is copper in invertebrates. Deficiencies era. Normally rare but must be watched in women of reproductive age, when lack of iron is widespread and causes ill health and lassitude. Anemia also occurs in infants and children. Meats such as veal, liver, and fish eaten with soybeans, lettuce, parsley, maize, etc. can provide dietary iron. Meat and ascorbic acid. Vitamin C, increase iron absorption from food. Iron in bone marrow is needed for new blood calls. Clinically, ferrous salts ingested can be used in cases of excessive blood loss. People brewing beer and wine or cooking cereals in iron pots often ingest excess iron. Alcoholism and diabetes exacerbate iron excess, although excessive iron is an unusual condition. 27 cobalt, copper and cobalt can be deficient on poor coastal sands. Cobalt is necessary to many legumes, and especially needed by livestock, who are unthrifty if it is deficient, as it can be in highly alkaline areas. Only an ounce or 2 per acre is needed, and this can be supplied as a cobalt bullet in the rumen of sheep. Cobalt is necessary for synthesis of vitamin B in ruminants. If deficient, fertile metabolic problems then occur, often diagnosed by B tests on blood levels. Deficiency can cause anemia. Toxicity can occur if excess is ingested. Radioactive cobalt is a serious poison. 28 nickel, Ni, is not noted as a plant nutrient or poison, but with copper can intensify poisoning in people. 6.9. In office rooms using urns, or in mining areas, many people demonstrate skin reaction, rash, if nickel is used as bracelets. 29 copper, Cu, is a necessary micronutrient which can become a poison at higher concentrations. Copper in plants is an enzyme activator, and is concentrated in the chloroplasts of leaves. Copper is deficient on shale grit dunes, acid peaty soils, coastal heaths over poor quartzite sands, and in deeply weathered basalts. Black sheep are good indicators, and if deficient, develop whitish or brown wool, or white-colored sheep will grow steely wool. Copper sulfate at 1 kg/ha every 5 years is a cure. Old stockmen put a few crystals into water holes. Deficiency, with iodine, can lead to goitre, thyroid imbalance, and anemia in animals. Levels above 12 micromoles are excessive in drinking water. High blood copper levels in deserts are are often as a result of zinc deficiency. While copper deficiency is rare or absent in adults, copper toxicity is of more concern, especially where copper sulfate is used to clear algae from drinking water, and also from foods or water standing in or boiled in copper utensils and pipes. Copper poisoning is serious, with liver deterioration, cirrhosis, and brain effects, tremors, personality changes. Once hopeless, such cases can now be somewhat alleviated by chelating agents. 30-zine, ZN, is deficient on leached sands, dunes, alkaline sands, and supplied by zinc sulfate spray on plants or zinc salts in seed pellets. It should be tested. For in all desert gardens, zinc is critical for both tree establishment in many deserts or dunes, and to human health, and is cheap to supply. In plants, zine is essential to the growth control hormones. Zinc deficiency causes gross metabolic imbalances and stunting of growth. People with malnutrition often have low zinc blood levels and poor wound healing. Diabetes is often linked with zine deficiency. Excessive zinc acts as an emetic, causes vomiting and weakness. Zinc is necessary to several enzymes in the body. Prostate, hence seminal, fluids are high in zinc. Diets of coarse grains, unleavened bread, and low meat intake contribute to zine deficiency in poor people, especially in high calcium soils. Oral zine sulfate can be given clinically. Alcoholism and diabetes, feverish, sweating and stress all lower zinc levels. Severe deficiency causes hair loss, moist eczema of the mouth area, impotence, apathy, diarrhea. 33 arsenic, as sometimes seems to be needed by horses, and is included also in chicken pellets, but is a poison to animals even at slight concentrations. Polluting sources come often from gold processing areas, or from chickens fed on pelleted foods containing high arsenic levels. 34 selenium, Se, deficiency in lambs causes white muscle or still lamb disease, which is cured by selenium and vitamin E injection. It also causes ill thrift in animals in many countries where a severe dietary deficiency occurs. 5 mg/year is sufficient for sheep. More can cause toxicity. Seaweeds may supply sufficient selenium to gardens. 38 strontium, senior, is becoming, as a long-term and very poisonous radioactive element, senior 90, a widespread danger from atomic plants. HT now pollutes many areas, milk, and is being used as a blackmail. 6.9 in New York water supply in 1985. One of the great pollutants of the future, it causes cancer at absorption site, leukemia in children, and is a hidden cost, very hidden, of the atomic age. It is excreted in urine of breastfed babies, and concentrates 4 to 8 times in cow's milk, thus levels in cow's milk must be monitored. After atomic fallout, there are no safe levels. Ordinary strontium is 4 trace element. 42 molybdenum, MO, is a trace element for clover establishment, and needed by all plants, rhizobia. A few ounces per acre is used on many acid soils, and rarely again needed. It is locked up not by alkali or lime, but by sulfuric acid, and may therefore be deficient in plants subject to acid rain. Legumes need molybdenum for nodulation, but non-legumes deficient in molybdenum can concentrate dangerous levels of nitrates, causing leaf burn. 48 cadmium, CT, is a poison that is concentrated by green leafy plants and shellfish. It is derived from traffic, tires, and superphosphate. It may already be in very high levels in acid soils of market gardens using artificials, as it is in Canberra. Cadmium causes painful human disease Japan, and permanent deformations. 50 tin, SN. Ores and wastes create plant 194. Establishment problems. It is not noted as toxic at low levels in diets, but can become toxic at high levels in canned food. 51 antimony, Sp, as for arsenic. 53 laudine. Deficiencies occur in withered basalts, causing growth problems and goitre. These are remedied by fish and shellfish, seaweed diet. 1131 now. A common radioactive fallout from atomic plants and tests, it poisons milk over wide areas, and affects thyroid function. Laudine can cause cancer, death of children from hyperthyroidosis, a real risk from atomic establishment and tests. 80 mercury, Hg, is a common poison released by mines, metal processes, acid rain, and is more active in organically polluted areas. It creates very serious coordination and sanity problems, central nervous system malfunction, bone deformity, insanity. 81 thallium, Ti, is a toxin, causing birth determites, thus very dangerous. 82 lead, Pb, is a common poison from petrol, old paints, battery burning. It is a serious urban soil pollutant, heating heavy organic soils to block uptake or removal of lead concentrating vegetation for disposal. Earthworms may concentrate lead to lethal levels in polluted soils. 86 radon, is a gas fraught on the decay of uranium. Seeps up in most soils, especially over volcanic areas, igneous rock, and can pollute super-insulated buildings if the air is not exchanged. Several million homes at the UK and USA have high levels of radon. Avoid building poorly ventilated homes in areas of radioactive ores, granites, and basalts, or the use of such rocks or crushed metals in buildings. If houses are to be super-insulated or draft-proofed, then adequate heat exchangers must be fitted to bring in clean air. From page 188. Soaking, or by being pressured upwards by an aquifer flow in permeable sediments. Asterisk water travels by through flow, traveling by the effects of gravity downslope in the profile. This fatter effect produces soil types called catinas, specific to slope, drainage, rock type, and landscape. Figure 8.3. Infiltration effects are most marked in soils where, for very long periods, a succession of light intensity rains have alternately wetted and then dried out in the soil. Out the wet-dry boundary we find concentrations of easily soluble salts and deposits of minerals and nutrients, sometimes in oversupply. The second set of effects on element transport are biological. Elements are actively sought out or selected, and either concentrated or dispersed by living organisms. These effects are myriad in total, but some of the ways this is known to happen are asterisk concentration by selective species of fungi, bacteria, and invertebrates which can seek out, assemble, and change specific compounds to stable new forms as concretions or nodules. Iron, manganese, calcium, phosphate, zinc, nickel, copper, selenium, cadmium, phosphate, and nitrogen are also selected and concentrated by one or other form of mycorrhiza, root fungi, bacteria, mollusks, or Concentration by accumulation of detritus, diatoms, swamp peats, whole forests, sponges, and their spicules of silica, mollusks, and vertebrates are at times buried by volcanism, sedimentation, or deposition in oceanic deeps to form specifically concentrated sediments, and eventually ore bodies or rock types, coal, rare earths, or manganese deposits. Dispersal by transpiration. Many water plants seem to be able to dissociate and transpire a great variety of substances to atmosphere. Reads do this with mercury, hydrogen, and other elements from phosphates to chlorine. Not all of these are vaporized to drift off in the winds. Many are deposited in special leaf repositories, or evaporated to a wax, dust, or efflorescence on the leaves and stems of trees, from where they are washed down again to earth by rain through fall. In this way, both major plant nutrients and minor elements are concentrated in the top 4 cmt 7 to 2 inches of soil below trees. Metals, oxides, halogens, acids, alkalis, and salts are also concentrated. Concentration by metabolic processes. We build our bodies up by ingesting a large range of complex foods, as do all living things. From these ingested bodies, materials are selected to build our bones, flesh, blood, and brain tissue or organs, nails and hair, fats and milk. Thus, our own bodies and those of other animals are complex storages of elements. Even our faces package very different concentrations of potash, nitrates, and pollutants from the different concentrations of foods that we eat. And by our behaviors, these are variously disposed of in a personalized, culturally determined, or species-specific way in the environment. Plants and animals ceaselessly ingest and defecate, reflect and exude over their whole lifetimes, thus altering the concentration of nutrients in their immediate environment. $8. pH and soils. Of the parent rocks of soils, we speak of acid rocks as containing 64% or more of silica, SiO5. Intermediate rocks at 50 to 64%, basic at 40 to 50%, and ultra basic at less than 40% silica. Of soils themselves, we speak of acidity and alkalinity in terms of a logarithmic scale, in which each point is 10 times the concentration of hydrogen ions less than the scale point below it, so that pH 8, alkaline, is 10x 10x 10x, 10 or 10,000 times less acidic than pH 4, and pH 3 195 times more acidic than pH 4. Table 8.3 serves to portray the availability to plants of some important elements with respect to pH value. Acid and alkaline waters and soils. We commonly speak of hard, alkaline, or soft, acid, waters. The latter used with soap lathers easily, and is desirable for washing. The former, including seawater or other alkaline waters, is difficult to use for washing, as soaps and detergents are themselves alkaline and so do not easily dissolve in other alkalis. Soaps, based on sodium or potassium, ash, and fats, will lather in soft acidic waters, and detergents based on phosphates or sulfur, lather in hard waters. Hard waters contain calcium, Ca, or magnesium, Mg, ions. Soft water contains hydrogen, H*, ions. The properties of alkali, soaps or carbonates, and acids, vinegar, citrus juice, have long been recognized and used medicinally or in village chemistry. The word for deserts in Arabic is alkali, the salt. Acids and alkalis arise from the solution of oxides, hydroxides, sulfates, or carbonates of metals and nonmetals in water and soil water, the common rock. Table 8.2. Nutrients in soil as mineral content. Primary sources comments removed available insoluble. Compost generally, rock by crop in soil. Dus, kg/ha equals kgb/ha. And nitrogen legumes, water plants, basic to crop growth, 120 to 200 1000 to 10,000. Urine. P potassium ash, predacicynide, basic to crop growth, 140 to 200 000-50,000. Bone. Camosfero bones, bird manures. Basic to crop growth, 2020 to 100 1000 to 10,000. Found in super. Phosphate, acid treated. Bone or rock phosphate. Sulfur elemental sulfur, adjusts pH towards acid. 3050 to 100 to 10,000. Volcanic mineral deposits. Swamps. Ca equals calcium limestone, some crops adjust pH toward alkaline. 4100 to 5000 10,000 to 100,000. 2.9 buckwheat, dolomite. Mg magnesium dolomite 100 to 1000 2000 to 100,000. Minor, trace, seaweed concentrate gen. Elements aerolite, sea algae. Fe equals iron, all of these are needed and likely to be deficient, with /0.5 10 to 200 2000 to 100,000. Minute amounts, and either Mg, at high pH. Mn made available by adjusting likely to be deficient in 022 to 200 100 to 10,000. pH or by adding oxides, suldunes. Fugopper fats, Ar sodium salts if likely to be deficient in a 44 to 22 to 200. The element itself. Most are coastal plain pastures. Se selenium present I'm seaweeds, or frequently deficient 0.01 0.002 to 1.0 0.5 to 5.0. Boboron seaweed concentrate. Frequently deficient, 0.21 to 54 to 100. Mb molybdenum deficient in deep, volcanics. 0.01 0.002 to 1.0 0.5-10. Cocoa ball 0.001. Mulch or compost of mixed materials supply all nutrients, plus if available, 200 g dry pulverized poultry manure per square meter. Gross deficiencies are likely to occur in the primary nutrients. Calcium and phosphates are usually low in old or leached or overworked soils. Rock dusts add potash, limestone adds calcium, dolomite for magnesium, and tree or clover legumes for nitrogen. Manures add most of these except calcium. NPK is ideally added in a 5:8:4 ratio, for sandy loams with 5 parts of lime to balance acidity, in a 5:6:6 ratio for clays. Fertilizer can be added to 5 manure teas sprayed on leaves, with seaweed concentrate, and in humid weather this is absorbed in from 24 to 56 hours. 196. And soil constituents are metals, sodium, potassium, magnesium, calcium. And minerals, iron, zinc, aluminium, copper. Nonmetals, silicon, sulfur, traces of phosphorus, boron, fluorine, chlorides. Carbon is also found in organic soils. In solution, metals release positive, H, ions. Nonmetals release negative, O, ions. Chalk. Limestone, calcite, dolomite, magnesite, and gypsum. are rocks and minerals giving rise to hard water, from air and water which gives carbonic acid. All of these are carbonates, sulfates, or oxides of calcium or magnesium, or both, e.g. dolomite. All these below are used to raise pH values in soils. Asterisk chalk and limestone are calcium carbonates. Asterisk gypsum, calcium sulfate. Asterisk magnesite, magnesium carbonate. Asterisk dolomite, calcium magnesium carbonate. In the table of elements, centerfold, groups, and 2. Table 8.4. Soil amelioration, a basis for trial plots. Soil location. Climate L1 L4. Alkaline acid. Sands _ general add magnesium sulfate as spray at 10 G/L, add dolomite, 4 Ca, mg, at 100 to 300 G/m2. Or at 45 G/m. Neutraliza with lime 20 G/m2. Humid add ammonium sulfate or fine dolomite, add water retaining polymers, add opsum, 4 Ca. N. Sulfur. Add zinc every 7 years at 1 G/m. Lisa copper based spray sparingly. Add water retaining polymers. Add neutralized superphosphate, 4P. Non-wetting add 10 G/m. Bentonite or monomineralite add bentonite, polymers. Clays, polymers. Deserts add ferrous sulfate, 4Fe, at 23 G/L as add dolomite, gypsum, polymers. A foliar spray. Add polymers. Coarse trial cobalt sulfate at 0.11 G/m2 or foliar add potash. Trial neutralist _ cobalt. Sprays of cobalt. Wet areas Lisa rock phosphate, dolomite. Coastal add copper sulfate, 4 Cu, every 7 to 14 add neutralized copper sulfate, 4 Cu. Years, F cropped, at 1 G/m2. Every 7 to 14 years, if cropped, at 1 G/m. Add zinc sulfate, 4 Zn, every 7 to 14 years do not add sulfur unless absent. At 1 Gm2. Add zinc sulfate 2:1 with lime at 1 G/m2. Every 7 to 14 years. Loams equals tropics add silicate or spray silica solutions. Coarse textures in tropics. Add cement. Calcium silicate, at 100 to 400 G/m2. Deserts add dolomite, gypsum. Loams add potash if cropped. Add zinc sulfate add potash if cropped. Coasts add copper sulfate 1 G/m2 every 7 to 14 add neutralized copper sulfate every 7 to 14 years. Years at 1 G/m. Clays acidify with sulfur, add manganese add gypsum to improve drainage, reduce. Sulfate. At 2-3 G/L as spray. Salinity in dry areas. Molybdenum needs trials at 350 G/Ha. Gravels iron oxides add copper sulfate at 1 G/Me. Present immobilized phosphates. Molybdenum at 350 G/Ha every 10 to 15 years. All soils blood and bone, manures, compost, acidic blood and bone, manures, compost. Phosphate, urine for potash. Foliar sprays dolomite, seaweed, pebble dust from. Of seaweed concentrate. Cement works. 197. Contain the nonmetals of which lithium, sodium, potassium, magnesium, calcium, strontium, and barium compounds give up alkaline, O, ions to soils. The usual soluble, solid, bases for alkalis are magnesium, calcium, potassium, barium, sodium, and selenium. The usual soluble, liquid or gaseous compounds for acids are silica and sulfur based, or derived from humus. The measurement of acidity, alkalinity, pH or hydrogen ion concentration, is basic to soil and water science. Of 5 it affects the availability, solubility, of other key or trace nutrients, and, at its extremes, the ability of life forms to obtain nutrition, or even to live. The pH scale ranges from % acid, to 14, alkaline. Although in nature we rarely find readings below 1.9 time juice, or above 11.0, alkali flats. In the presence of air, and in plowed and aerated soils, both metals and nonmetals form oxides, and these dissolve in water or soil water. The metallic oxides, bases, form alkaline solutions. The litmus reaction is high. There is an excess of hydroxide tons, O present in solution. The nonmetallic oxides form acidic solutions. The litmus reaction is red. Excess hydrogen ions, H*, are present in solution. Common acidic substances are citrus juices and battery acid. Common alkaline substances are sodium, bicarbonate, baking soda, and washing soda. As rain falls, carbon dioxide in the air combines with water to form weak carbonic acid, as in soft drinks. This helps to dissolve metallic oxides in soils, and to bring the minerals of rocks and soils into solution. Sulfur from industrial processing, or from pyrites in rocks or soil can form sulfuric acids, and these also aid the solubility of metallic oxides. Phosphorus and nitrogen can form phosphoric and nitric acids with water. Silica in soils dissolves to silicic acids, and chlorine to hydrochloric acid. Weak nitric acid is a plant growth stimulant, New Scientist May 22, 86. All of these acids, in moderation, are helpful in nutrient supply to plants. pH is not a constant for soil or water. Not only does it exhibit diurnal or seasonal changes due to rain, growth, and temperature changes, but it is essentially a mosaic in soil crumb structure, on the surface of colloids, and at microsites. Further, pH exhibits vertical soil gradients, being more acid in surface mulches and more basic or alkaline where evaporation, worm casts, and capillary action draw up bases to the surface of the soils, dry or wet dry areas. Mosaics on a larger scale are imposed by slope, and both rock and vegetative types. As long as people are aware of this, and realize that root hairs can both create and seek out ideal pH environments if there are no gross imbalances, then gardens are likely to contain every sort of O level. Somewhere in the sale. Only by grinding mixed samples of soils to damp pastes, or measuring conductivity, can we average pH and obtain some idea of net balance, but, as usual, our measuring methods alter the thing we measure. If 198 pH stromg for CE neutral Lil AO4 FO5 O65 to 75 60 65 FO1 MO equals E at AEOE C page BS A SAR 202I hence PSESESOE A and FER Huey. Figure 8.4. Influence of pH on availability of plant nutrients and inorganic, mineral, soils. The widest parts of the black areas. Prop maximum availability of each element. The curves represent pH values. Adler Nelson, L.B., ed. Changing Patterns of Fertilizer Use, Sale. Science America, Madison, Wisconsin, 1968. B in organic soils. The widest parts of the black areas indicate Maximum availability of each element. After Lucas, R.E., A.M.T.J.F. Davis, relationships between pH values of organic soils and availability of 12 plant nutrients, Sod Science. 92-17-1682, 1961. We keep the average pH value to between 45 and 10. We can grow a wide range of plants and rear aquatic organisms if calcium is present. If we narrow the range to pH 6.0 to 7.5, most vegetables grow well in gardens. Outside these ranges, less than pH 4.0 or more than pH 10.0, only specialized bacteria or higher organisms can cope. Moreover, soil humus is itself a buffer as is. Calcium, lime, humus will grow plants at satisfactory levels even if the pH changes, so that limed and mulched gardens rarely show plant deficiency. Symptoms. 8.9. Soil composition. We think of soils as mineral compounds, but the pie diagram in table 8.4 will alter that impression. It does not, of course, represent any one soil, but is an average sort of figure for a good loam with adequate humus. Outside the pie, have noted some of the possible ranges of variation from peats to sands in old dunes. The humus content of soils. Soils in nature can vary from a humus content of 2% to close to 100%, as peats. In gardens, 40% or more. Humus helps block heavy metal uptake by plants, holding heavy metals bound in colloids. Many compost-fed or mulched garden soils contain 10 to 30% humus, some much more. The effect of adequate soil. Humus is both physical, in affecting good water retention and in preventing erosion, and chemical via colloid formation. The breakdown products of humus, including the mineral content of the donor plants, form the readily available and biologically active components of soil that are of value to newly established plants. If these plants are perennial or, in part, mulch producing, and if we return food wastes to the garden, including urine and well composted faces, then very little humus loss occurs. On the broad scale, humus can only be provided by the root and the above ground mass of grasses, trees, and plants. Prairie grasses and broadleaf trees are particularly effective at this job. When we aerate, plow, soils, we turn up humus and oxidize it to carbon dioxide, thence to atmosphere. It is lost. Burning the vegetation is worse, with a host of additional pollutants, terpenes, creosotes, nitrogen, and dust particles, and a rapid loss of soil humus. Where soils are not tilled or burned, soil humus lasts a long time, hundreds or even thousands of years, and provides for a complex soil life. Organic soil additives. Mulching is here defined as covering the soil surface with 15 centimeters or more of organic material, as a loose uncompact mulch, cm of tight rolled sawdust. Does not qualify. Mulching is more generally applied to loose dust mulches, plastic sheet mulches, and so on, and these may have specific local value in soil amendment, heating, sterilization, weed suppression, or pest reduction, but as here considered, the object of mulching is to add plant nutrients, buffer soil temperatures, prevent erosion, promote soil life, and restore soil structure. Plastic mulches, soil gels, polyacrylamides, herbicide-treated soils, and organic or natural mulches may all achieve the result of preventing erosion and helping soil crumb structure develop. Only long periods of natural mulches stabilize nutrient supply and complex the soil life. None can be judged over 1 or 2 seasons, as it can take 3 to 5 years to create a balanced soil under mulch from a compacted or mined out soil. Even longer periods are necessary to develop humus in tea crops assessed for yield. On the broad scale, where added mulch is not carried to the site, but derived from tree wastes and specially sown crop, green manures, produced on the site itself, used in areas such as wet tropics and arid lands, or on dry coarse sands, mulches may prove to be ephemeral, even if their effects continue, as ants, termites, and leaching reduce the mulch to humic acids, or underground storages in fungi and bacteria. In particular, water absorption is improved under mulch, both as field crop mulch and imported garden mulch. Thus water needs are reduced. Jeanette Conacher, in Western Australia's Organic Gardening, 1979, reporting on extension trials in Nigeria, records 11% better water infiltration on low to no tillage and mulched plots. Under mulch, excessive soil temperature ranges are buffered, being cooler by day and warmer at night or in winter. Seed germination is enhanced, and over the long term, major nutrients, N, P, K, remain at satisfactory levels. Only under mulch does the population of important soil organisms, such as earthworms, increase. Mulches need some selection for minimal weed seed, minimal residual biocides, and for best effect on specific crops, tested as row by row comparisons. Plastic mulches, black for heat and weed control, silver for aphid repellency, have a more limited role. Important in the short term, but often expensive or impractical in poor countries, or rejected by growers who suspect that many plastics release persistent chemical polymers of unknown effect on the soil life. Mulch is an excellent way to add nutrients to soils. The cool decay loses little nitrogen, while stimulating soil life generally. There are some problems with compost, where hot, aerobic heaps heat up and nitrogen, ammonia, losses are severe. Cold heaps, pitted or silage, do not lose nitrogen, but neither do they kill weed seeds. 1% of superphosphate added to a hot compost heap prevents ammonia escape. Chinese scientists get the best of both worlds by first building an aerated heap with bamboo poles as holes to create air tunnels. This is then covered with 199 mud, and the heap heats up to 55 to 60 degrees Celsius, 130 to 140 degrees Fahrenheit, for a few days. Then all holes are sealed, and the rest of the decay is anaerobic. With sealed boxes, either hot or cold processes can take place. Compost or mulch is critical to preserving soil crumb structure, buffering pH, and, in taste tests, improving sugar content and the flavor of vegetable product. The gums and gels produced by soilisms create crumb structure, aerate the soil, and darken at 50 that it heats up faster in spring. The humic acids assist root development dramatically even at levels of 60 ppm. Carbon. Inorganic, chemical, and mechanical farming. 10 as easily destroy soil structure. In the UK, New Scientist November 3, 79, liquid manures sprinkled on straw in silos or tanks, together with a forced air draft, produce compost in about a week. Efficient open piles encased in straw need 10 days. The liquid effluent system plus straw is suited to treatment of ammonial sludge, still full of seeds, such as that we get from biogas digesters. it is best to use. Table 8.6. Pie chart of total volume components of an average soil. Lives. 70%. Composition of an average soil. 1 to 100%. 2-70%. Roots, animals. Humus. Most as. Humus, INES. Content. 30%. Pore space. And gases. 50%. 2 to 45%. Colloids, gels. The composition of a garden loam with 10 to 25%. Mulch and a rich soil biota. A range of estimated topsoil volume, proportions. From wet peats to compact mineral soils is given in brackets. Equals. 12 to 15%. 5 to 95%. 200. This with dry twiggy or straw material as hot compost. To both kill weed seeds and to produce useful heat. After the compost pile has been made. However, in severe winter areas, such efficiency is counterproductive as a slower heat release from large compost piles of 10 to 50 cubic meters, 12 to 59 cubic yards, can provide heat over a long period in winter and greatly reduce glasshouse and house heating costs. While the compost itself is best applied to soil in spring. Care and selection of compost materials. Even using organic residues, or natural wastes, soil problems can arise from a concentration of nitrates in manures, or toxic mineral residues. Leaf material cut and mulched, or composted, green will contain more nutrients than fallen leaves, although the latter are still useful for humus production. Kevin Handreck. Organic Growing, Autumn 87, Australia, has identified potential mineral contamination from these sources. Asterisk galvanized, copper, or brass containers containing wet residues of manures, or Montreal teas, clay. Stainless steel, glass, or iron are preferable. Zinc and copper are produced in excess from galvanized or copper/brass containers. Asterisk manures from pigs, poultry, cattle, or sewage. Sludges can add excessive zinc, nickel, boron, lead, or cadmium to soils, and especially acid sandy soils. Where such elements are naturally deficient, such manures may initially help, but heavy or constant application will build up a toxic soil condition. Excess zinc can be built up by using earthworm casts from contaminated pig, sheep, or domestic wastes. Animals. Penned in galvanized areas can produce excess zinc in pen wastes. It is in poultry mixes that such contaminants show up, with excess zinc inhibiting plant growth and health, so that the urban gardener should test and use safe mixes, or proceed via plant trials. Handrek recommends a limit of 10% worm casts in a potting mix. In such cases, nitrogen and potash can be supplied by dilute urine. Note that copper, arsenic, and other minerals are commonly added to stock feeds, and therefore try to buy clean natural feeds from organic sources. After initial soil treatment, and a continuing watch for foliage deficiency symptoms, see deficiency key. This chapter, the safest course is to grow our own green manures as the foliage of leguminous hedgerow, windbreak, or intercrop, and to use these as mulch and compost materials. 8.10. Soil pores and crumb. Structure. The structure of soil, whether compact or open, depends on the soil composition itself, the way we use it, and the presence or absence of key flocculating or ionic substances, synthetic or natural. Crumb. Structure in well-structured soils permit good gaseous exchange and free root water penetration without the creation of excessive anaerobic conditions by waterlogging. In free sands, and in the krasnozems, developed over deeply weathered basalts, crumb structure is either not a factor, or else is so well developed that it permits leaching to immobile clay sites of almost all applied fertility source. However, in most other soils, we would like to see a good crumb structure develop as in our gardens or crop soils. Where crumb structure is poor, we can use a great variety of coulter and rip time machines, soil additives, and deep-rooting plants such as trees or lucerne to reopen and keep open the soil structure, which in turn allows adequate water penetration and drainage, and eventually develops the oxygen ethylene processes that make bound nutrients available. Soil crumbs of 0.2 to 2 mm diameter can form as little as 10% of the total soil volume, and still produce crop. Below this, crop is greatly reduced and impoverished. The same soils can, when not plowed lifeless, contain 92 to 95% of such crumbs. Leeper, 1982. We destroy crumb structure by destroying permanent vegetation, flooding soils for long periods, using high-speed or heavy vehicle cultivation, stocking with sheep or cattle, in especially wet periods, using fertilizers that deflocculate the soils, e.g. too much potassium where soil sodium levels are already high, or by burning in hot periods. The whole set of disasters outlined above can collapse soils to the cemented, dusty, hydrophobic, salted and desertified areas typical of wheatlands on desert borders. It is a question of improper use, disastrous planning, or mob planning, and a total lack of applied goodwill to earth. Given a good structure, pores develop for the diffusion of gases and exchange of ions, provided that we make the transition to perennial, low cultivation systems of forest and crop. Colloids and gels. Colloids are stable aqueous gels or suspensions of clay, organic, or long-chain polymer particles in a finely diffused aqueous state in soils. These are particles so fine that they stay in suspension unaffected by gravity, and become active sites for ionic bonding and interchange. Colloids also form gels which hold soil water reserves, and are in part formed by or derived from natural, and more recently, artificial, substances, some of which form hygroscopic gels by water. 201. Table 6.5. Schematic of compost materials. Compost materials. Tote spray emit. To biogas. Bit all 30 to 35 degrees Celsius. Dry. LRD. E. Add liquid. Concentrates. If any. 1, 2, 3, 4, 5. Which directly on soil use as manures on spread on soils of drill below soil spray as liquid on surface at greater than 12 cm gardens. Intensive plots and J surface. Fields, foliage, or use. Deep. Energy use but good seed beds. Good results, no in aquatic systems. Least effort for best results obtained. Most effort and most pollution. Little effort for good results in gardens. Nutrient, ammonia, results. Controls weeds, loss, but effective for energy yields as lessens labor. Specific materials. Biogas. Energy yields as biogas, heat. Examples. A. Nut husks and shells, coffee, teas, and cocoa raising. Dews, shredded paper and branches, bark, wood chips, and sawdust, and old carpets, underfelled, not pesticide. Treated ones, bags, canvas, all made of natural materials. B. Hay with seed heads, weeds in flower, bulbils or roots of weeds. C. Sewage and silage, liquid manure and urine, meat. And animal pond CHES and trimmings, general household wastes. Add lime and superphosphate, 1%, to hot compost, teas of seaweed and manure. D. Sludge from digestives and weed-free manures. E. Chicken and bird manures, litter from animal sheds. Blood, bone, feathers, hide scraps, seaweeds. F. Dissolved minerals, urine, seaweed and manure. T's. 202. Table 8.6. Equals R scale of soil particle sizes. Mem. After McDonald ETI. Fine clay equals 0.002. Clay particles 0.002. Silt 0.002 to 0.02. Sand 0.02 to 2.0. Fine 0.02 to 0.2. Coarse 02-2. Gravel 2 to 60. Fine 2 to 6. Medium 6 to 20. Coarse 20-60. Cobble 60 to 200. Stones 200 to 600. Boulders greater than 600. Absorption. Natural. Humus or humic decay and bacterial products provide. Colloids, as do finely ground graphite and silica, fine. Clays, particles of 2 to 200 millimicrons, such as elites. Bentonite, usually deposited on clay pans from evaporation of clays in suspension, grain flours and animal, gelatinous, flours, e.g. from hooves, horns, sinew wastes, albumin and so on. Bacteria also secrete polysaccharides which form soil gels. Synthetic soil conditioners which form stable colloids are sold under a variety of trade names. Ask a local agricultural supplier, e.g. AgroSoc registered, Ictagel registered, Terrasorb registered, which are hydrophilic, attract water, as are many natural gels from grain products and seaweed. Water conservation of up to 50% is claimed for some of these additives. Most artificial gels are acrylic-based, acrylamide polymers, and supplied as granules able to absorb hundreds of times their weight in water. They are used to great effect in nursery plants, row crops, new tree plantings in deserts, and in transplanting. The acrylics are applied to soils at 6 kg/hot or more, and conserve irrigation water by preventing evaporation. Small Farmer, New Zealand, August 84. These substances are of value in seed pelleting. Colloids also form hydrophobic, repel water substances such as those of clays and some soil fungi products. The surfaces of colloid particles are usually negatively charged, as are root hairs, and thus attract positive ions to their surfaces, e.g. the positive ions of sulfates, nitrates, and of metals, sodium, calcium, magnesium, iron. About 99% of such ions are so held in soils. Leeper, 1982. Colloids from humus are hundreds of times more effective than clay colloids in ion exchange in soils. Ammonia and sodium can dislodge these ions, and they can become available to plant roots, which attract them by producing negative H charges. With too much flushing by sodium, the calcium and metallic ions can be lost to leaching processes and carried to streams, hence to seas or lakes. Colloids used in water softening capture calcium ions and release sodium ions, allowing soaps to lather. Ferric oxide colloids have positive charges and give water a brown stain, typical of waters issuing from acid peats and pine forests. The colloid particles can be flocculated, aggregated, AMD settle out if alumine and some salts, sulfates, are added, and this may happen as a result of acid rain, or can be induced with the acid forms of any negative particles. Salt also flocculates colloids up to the point where excess sodium deflocculates clays with calcium and other ions, which is the effect of high salt concentrations in dryland soils. Over 1 to 5 ppm salt burning destroys the colloidal properties of surface clays, and is another reason why desert soils leach out after fires. Burnt clay particles no longer form colloids and become poor in mineral nutrients, which are then found only in deep soil profiles. Organic humus forms black slimy pools on top of the collapsed soils. It is the clay particles and colloids, organic and inorganic colloids, that bind water and nutrient in soils. In the tropics at least, most of these colloids are in the biomass of the soil as cellular gels, or are produced as sheathing material by soil bacteria. Without colloids, soil minerals rapidly leach out and become poor in nutrient. Fire, clearing, plowing, and cultivation destroys such colloids and soil structure, as does excess sodium ions. Thus, to hold and exchange nutrients, we, as gardeners, need to develop natural or artificial colloid content in soils, from where plant roots and soil fauna or flora derive their water and essential nutrients. Very/little clay is needed in sandy gardens to create a colloidal soil environment, and life forms are encouraged and developed by humus, mulch, and plant crops. Good soil structure, to hold good colloids, is developed by careful earth husbandry, together with flocculating additives such as gypsum and harness. Soil water. The water content of soils is a soup of free-living organisms, dissolved gases and salts, minerals, gels, and the wash-off from through fall in trees, waxes, frass, tree body wastes. Organic and inorganic particles are held in soil water. Soils have a widely variable water-holding capacity dependent on their composition and structure, so that sands absorb and retain water more quickly than clays, but clays hold more water per unit volume. Available water thus varies from 2% surface sands to 40% or more of soil volume. We can assist the quantity held in dry sites by swaling, contouring, or terracing, loosening soils, adding flocculants, introducing artificial or natural gels, seaweeds or plastic absorbers, or by placing a clay or 203 plastic sheet layer 30 centimeters below the surface of gardens. In soils that become waterlogged, we can resort to raised beds or deep drains to reduce infiltrated water build-up, or plant trees to keep active transpiration going, and so reduce soil water tables and rehumidify the air. Two factors at least affect soil water availability. Asterisk the strength of molecular bonding of water to particles in the soil ionic bonds. Plant root hairs cannot remove this bound water at pressures above 15 atmospheres. Registered the salt content of the water. Too many salts, and the soil water exerts reverse osmotic pressures on plant roots, and will take water from the roots. 8.11. Gaseous content and processes in soil. Soils are permeated, where not waterlogged, by the gaseous components of the atmosphere, 80% nitrogen, 18% oxygen. This enters the soil via pore spaces, cracks, and animal burrows, and diffuses via pore spaces to plant roots. The exchange of gases, atmosphere to soil and soil to atmosphere, the breathing of Earth, is achieved by a set of physical and biological processes, some of which are earth tides. The moon tides, much subdued on continental masses, nevertheless affect ground waters. In cobbles or boulders, the earth itself, about 25 centimeters, rise and fall across the continental USA, and of course the soils of estuaries and mudflats, where air can be seen bubbling up for hours as the tide rises. Everywhere, low or high pressure cells and turbulent wind flow creates air pressure differentials that draw out or inject air via crevices and fissures, or burrows. These same effects assist or retard the diffusion of water vapor across soil surfaces, and just as the wind dries out surface soil, so it also, by fast flow, draws out other gases from soil. The gases of soil respiration: carbon dioxide, oxidation, aerobic and anaerobic metabolic processes, radon from radioactive decay, and simple or complex hydrocarbons from earth deposits, or humus decay, pass to air. Much of the ammonia and carbon dioxide in the atmosphere, and at least 16% of the methane, is supplied by soil. Biological exchange. A single large, broadly free, actively transpiring, may increase the area of transpiration of 1 acre of soil by a factor of 40. A forest may do so by hundreds of times. So, oxygen, carbon dioxide, water vapor, metallic vapors, ammonia, and hydrogen or chlorine gases are transpired by algae, rushes, crops, trees, and herbs or grasses. Plant groups vary tremendously in the volume and composition of gases transpired. Although we much of our atmospheric oxygen FO trees, a great many non-woody plant species consume more oxygen than 204 they produce. Thus, the plant is a gaseous translator, trading both ways with air and soil. Some specifics of this trade are given in the section below on oxygen ethylene processes. Animals, too, are very active in opening up soils. With small or large burrows, these act as pump pistons, like a train in a tunnel, to draw in and exhaust both their waste gases and atmospheric gaseous elements, which are then diffused to roots via soil pores. Many burrows, ants, crabs, termites, prairie dogs, worms, land crayfish, raise up mounds or chimneys which then act as pitot tubes for airflow or to create pressure differentials which draw air actively through their burrows. Or they erect large surface structures of permeable sediments across which waste gases diffuse, e.g. termite mounds. By a great many such devices, animals contrive to live in aerated or air-conditioned undergrounds, and increase gaseous exchange in the soils. Figure 8.5J. Pitot tube constructed by a land burrow. Airflow ventilates burrow and removes waste gases. Gases manufactured in soils. By way of titanium or rutile, TiF, ammonia is manufactured in sands in the presence of sunlight. By way of ferrous iron, ethylene, CH4, is manufactured in anaerobic 50 IL microsites. In anaerobic soils and waters, carbon dioxide, methane, sulfur, hydrogen, ethylene, and sulfur dioxide are formed and escape to air as biogas or marsh gas. The same products are present in the mottled soils of hydrophobic clays in winter, soils where crumb structure has been destroyed by misuse, where salt has deflocculated clays and caused soil collapse, or where water periodically floods the soil. Many of these gases are found as a result of humus decay and thiobacillus sulfur bacteria action. Ammonia is released from actively nodulating legumes, trees, and herbs, and is used in unploughed soils as a plant nutrient. Thus, gaseous compounds are continually made in the soil itself by process of metabolic growth and decay in the presence of metallic catalysts and microorganisms. Molybdenum, vanadium, and xene all assist root bacteria in the creation of available soil nitrogen as catalysts. Gaseous mosaics over time. Soil microsites. Like pH, cation exchange, and structure, natural soil is always a mosaic of aerobic and anaerobic patches, called microsites, where either oxygen, aerobic, or ethylene, anaerobic, sites develop. Ethylene inhibits, in the sense of suspending, microbial activity, and like carbon dioxide, is present as 1 to 2 ppm in soils. Smith, 1981, as the ethylene at an oxygen exhausted site diffuses out, oxygen floods back and reactivates the site. Under natural forests and grasslands, this cycle, or dance, of oxygen ethylene is continuous, and most nitrogen there occurs. As ammonia, useful to plants. And plant roots. When we cultivate and aerate, nitrogen becomes a nitrate or a nitrite, which then inhibit ethylene production, and ferric rather than ferrous iron forms, thus making ethylene formation difficult. The process from decaying leaf to ethylene production requires a ferrous iron catalyst. Also, plant nutrients are tightly bound to ferric iron and become unavailable for root uptake. It follows that the production of ethylene is essential to plant health and the availability of nutrients. It is important to realize that the aerobic condition of soils such as we get from plowing or digging not only creates a condition of unavoidable nutrients and ferric iron, but also oxidizes humus, which goes to air as carbon dioxide. Also, most plant root pathogens require the aerobic condition. As well, the nitrate form of nitrogen, which is highly mobile, leaches out when bare soils, not plants, occupy the site. In all, plowing and earth turning create a net loss of nutrients in several ways, thus atmospheric pollution, stream pollution, and low soil nutrient states. Smith, Ibid, therefore recommends Jesse soil disturbance, the use of surface mulch, not incorporated, as an ethylene precursor. Old leaves are best for this, and very small but frequent ammonia fertilizer, until soil balances are recovered. The ideal conditions would be permanent pasture, forests, orchards with permanent green crop as mulch, no dig or mulch gardens, no or low cultivation of field crop, or field crop, between strips of forest to provide leaves and nutrients, and the use of legumes in a similar proportion to that occurring in natural plant associations in the area, at all stages of the succession. Under these conditions, soil mineral availability is made possible and soils do not lock up nutrients in oxides or produce pollutants. When we achieve this balance, soil loss and mineral deficiency become yesterday's problems. And when plant leaf, not soil, deficiency can be adjusted with aqueous foliar sprays, nature then starts to function again to obtain nutrients from soils via microbes and Root mycorrhizae at the microside level. Smith, A. 1981. The Living Soil, Permaculture Journal No. 7, July 81. 8.12. The soil biota. On semi-arid and poor pasture, it is difficult to keep sheep at a stocking rate of 3-6/ha. The very same pasture may support 2 to 5 t of pasture grubs, or up to 6.5 t of earthworms/ha, so that, like grasses, most of the animal biomass or yield is underground, out of sight. Even where wheat cropping is carried on continuously for 140 cycles, Rothamsted, UK, the plow layer supports 0.5 t of living microbial biomass. New Scientist, 2D82. About 1.2 t/high of organic carbon is returned annually to the soil as root and stock material from grain crop. So large is the soil biomass that its growth must be very slow, sporadic, and based on a turnover of humus/food within the soil rather than a food input from the wheat crop wastes. Humus in the soil has a mean age of 1,400 years, and probably derives from forests that long preceded the wheat. It yields up its nutrients very slowly, and is resistant to bacterial attack. However, it is equally clear that there are periods of sudden food supply from root masses at harvest, and from root exudates during the growth of wheat. 30% of plant energy may be lost as sugars or compounds released to the soil by roots. However, the soil biota achieve it. They exist on a very meager food supply for such a biomass, rather like an elephant eating a cabbage once a day. Of the total biomass at Rothamsted, 50% is fungi, 20% is bacteria, 20% yeasts, algae, and protozoans, and only 10% the larger fauna, such as earthworms, nematodes, arthropods, and mollusk fauna, the micro and macrofauna, and their larvae. Such classes of organisms are found in soils everywhere, in different proportions. Anderson, New Scientist, October 6, 83, gives some idea of the complexity. Below ground, where every square meter of forest topsoil can contain 1,000 species of animals, and 1 to 2 kilometers of fungal hyphae. Very small animals are able to live a basically aquatic life in soil, in the water film attached to soil crumbs, while larger species are confined to pore spaces and the burrows of macrofauna. A wheat field is not the place most likely to produce high levels of soil biota, and plow cropping has, in Canada, reduced humus levels to 1% of the original levels over much of the wheat country. Climatically, the balance and proportion of soil biota varies greatly, with the acid soils of coniferous and oak forest yielding few earthworms, and the humic peats even less, so that the soil recycled by worms also varies from 2 to 150 t/ha, 0.5 to 25 centimeters depth of soil/year. 205. Ecological disturbance or imbalances by predation, aeration, disturbed soils, low oxygen levels, and compaction favor the bacteria over the fungi. Fungi are certainly more effective in wood or large plant material breakdown, and can transport materials not only from place to place, e.g. move nitrogen into decaying wood, but also move nutrient into higher plants via their intimate contact with the root cells of the host plant. Usually, such translocations are modest, a few meters, but occasionally a fungal species can send out many meters of hyphae to invade a tree, as a pathogen and decomposer. Thus, it pays higher plants to give energy to their fungal root associates as sugars, and to gain minerals or nutrients in return. Over time, the death of these soil organisms returns nutrient to new cycles. Even termite nests die out in 20 to 30 years, and new colonies start up. Larger animals can have a profound effect on primary litter breakdown. Millipedes, woodlice, and are typically plentiful in mulch, but rare in compost. As one can imagine, any accurate account of the relationship between such dynamic mass of species awaits decades of work, but some broad facts are emerging. For example, turnover of nitrogen by earthworms exceeds that of the litter fall of plants. Few species fall into clear-cut classes of food relationships, and the chain of events of predation, fecal production, and burrowing are further complications, as it is probably impossible to research at a species-specific level, and as the gross compartmentalization of ecosystem analysis is inappropriate. Anderson, Ibid, suggests a more possible study-based. Figure 8.6. Food web of a compost pile. Energy flows in the direction of the arrows, lengths in millimeters. 1 equals first level consumers, 2 equals second level, 3 equals third level. 206. After Daniel L. Dindal. On the interactions between the broad functional groups of organisms, or a size food community. Here, he laments, we know 50 little about so much. Asterisk. Large animals, earthworms to wombats, can create major changes in soils locally, by burrowing, soil turnover, fecal production from vegetation, waste products, and even alterations to forest successions. After fire. In general, gross disturbances by colonies of larger fauna as in deserts, where rodent biomass can reach 1,000-10,000 kg/ha, shift the balance from soil fungi to bacteria. We can think of the soil biota as a reserve of other wise easily leached nutrients, nitrogen, sulfur, both of which elements they gather, store, or concentrate. Their cycle of life and death, which in turn depends on soil temperature and season, releases small or large amounts of these essential elements at multiple microsites. Termites, in addition, may store calcium from subsoils in their mounds, and bacteria store a number of soil minerals. These are held in the mobile living reserves of the soil biota, and are released by their death for slow uptake by plant root associates. Many plant forms directly eat bacteria, algae in water, fungi, or insects and nematodes, so that plants are either direct predators of the soil fauna, or scavengers of the bodies of the soil organisms. A useful classification of soil biota based on size is as follows. New Scientist, October 6, 83. Asterisk microflora and microfauna, size range 1 to 100 millimicrons, e.g. bacteria, fungi, nematodes. Rotfers. Asterisk mesofauna, size range 100 millimicrons to mm. E.g. mites, springtails, small myriapods, inchytriid worms, false scorpions, termites. Asterisk macrofauna, size range 2 to 20 millimeters, e.g. woodlice, harvestmen, amphipods, centipedes, millipedes, earthworms, beetles, spiders, slugs, snails, ants, large myriapods. Asterisk megafauna, size range 20 millimeters upwards, e.g. crickets, moles, rodents, wombats, rabbits, etc. In terms of sheer numbers per square meter. Nematodes, 120 million. Mites, 100,000. Springtails, 45,000. Inchytriid worms, 20,000. And mollusks, 10,000. Greatly outnumber any other species in temperate grasslands. Fungi, however, may be 50% of the total living biomass. While the tradition of soil science has been to treat and analyze soils as mineral matter, the living component being carbonized or burnt off in analyses. C or humus content, the preoccupation of sound farmers, biodynamic groups, mulch gardeners, and no-dig croppers has been the quantity and quality of soil life, both as indicators of soil health and as aerators and conditioners of soil. Another factor which deserves more treatment in science is the mass, distribution, migration, and function of roots and root associates, and the role of burrows, not only earthworms, but larger mammals, reptiles, and a host of insects. The soil, if not sterilized, overworked, or sprayed into lifelessness, is a complex of mineral and active biological materials in process. No soil scientist myself. I rely on soil life and the health of plants to indicate problems. Diseases and pest eruptions can be the way we are alerted to such problems as overgrazing, erosion, and mineral deficiency. Removing the pest may not cure the underlying problem of susceptibility. Certainly, strong plants resist most normal levels of insect attack. Soil analysis, helpful though it is, can help us very little with soil processes. Until very recent years, we have underestimated the contribution of nitrogen by legumes or soil microfauna. In addition, the measures of soil carbon has rarely been related to the soil biota, whose lives and functions are not fully known. It seems curious that we know so much about sheep, so little about those animals which outweigh them per hectare by factors of 10 or 100 times, and that we do not investigate these matters far more seriously. Our most sustainable yields may be grubs or caterpillars rather than sheep. We can convert these invertebrates to use by feeding them to poultry or ash. We can't go wrong in encouraging a complex of life in soils, from roots and mycorrhiza to moles and earthworms, and in thinking of ways in which soil life assists us to produce crop, it itself becomes a crop. Earthworms. Worms have played a more important part in the history of the world than most persons would at first suppose. In almost all humid countries they are extraordinarily numerous, and for their size possess great muscular power. In many parts of England a weight of more than 10 tons, 10,516 kilograms, of dry earth annually passes through their bodies and is brought to the surface on each acre of land, so that the whole superficial bed of vegetable mold passes through their bodies in the course of every few years. Thus the particles of earth, forming the superficial mold, are subjected to conditions eminently favorable for their decomposition and disintegration. The plough is one of the most ancient and most valuable of man's inventions, but long before he existed the land was in fact regularly plowed, and still continues to be thus plowed by earthworms. It may be doubted whether there are many other animals which have played so important a part in the history of the world as have these lowly organized creatures. Charles Darwin, The Formation of Vegetable Mold through the Action of Worms, 1881. From the time of Darwin, and probably long before, copious worm life in soils has been taken as a healthy sign, and indeed more modern reviews have not reversed this belief. Satchel, 1984. Worms rapidly and efficiently recycle manure and leaves to the soil. Keep 207. Soil structure open, and, sliding in their tunnels, act as an innumerable army of pistons pumping air in and out of the soils on a 24-hour cycle, more rapidly at night. Of themselves, they are a form of waste recycling product, with a dry weight protein content of from 55 to 71% built WP from inedible plant wastes. Only a few peoples eat worms directly, but a host of vertebrates, from moles to birds, foxes to fish, depend largely on the worm population as a staple or standby food. Cultivated worms are most commonly used as an additive to the diets of livestock, fish, poultry, pigs. However, to aid processors of large quantities of plant wastes and soil particles, worms can also accumulate pollutants to extraordinarily high levels. DDT, lead, cadmium, and dioxins may be at levels in worms of from 14 or 20 times higher than the soil levels. Eaten in quantity by blackbirds or moles, the worms may become lethal. That is, if the pests that are moles, blackbirds, and small hawks abound on farms, there is at least some indication of soil health. Where these are absent, it is an ominous and obvious warning to us to check the soil itself for residual biocides. As non-scientists, most gardeners deprived of atomic ray, a battery of reagents, and a few million research dollars must look to signs of health such as the birds, reptiles, worms, and plants of their garden farm. For myself, in a truly natural garden I have come to expect to see, hear, and find evidence of abundant vertebrate life. This, and this alone, reassures me that invertebrates still thrive there. I know of many farms where neither birds nor worms exist, and I suspect that their products are dangerous to all life forms. All modern evidence agrees on the value of worms in fields as decomposers and manure recyclers. They may be even more valuable as garbage disposal systems, and as fish or poultry food, providing a mass of high-protein food from vegetable wastes. 8.13. Difficult soils. Concretions and pans. Several types of concretion or cemented particles occur in soils. These are commonly the following. Calcrete, caliche, platin, cougar, is a hard, mainly level subsurface concretion about 0.5 to 1.0 m below a granular or sandy topsoil, typical of coral islands, calcium triphosphate, and the downwind areas of desert borders. Calcrete must be broken open to plant trees, or the roots will spread out laterally, allowing wind throw to occur. On atolls, freshwater deposits develop below the caliche. Broken caliche can be used as a building material, and also forms a safe roof for tunnels or dugouts. Calcium/magnesium concrebion, worsened by the addition of superphosphate, is whitish to creamy. In 208. Acid, vinegar, calcrete releases bubbles of carbon dioxide. Silcrete, cangagway, is a great red shiny hard layer developed below some tropical forest soils, which gives a glassy surface if forests are cleared. The soil is concreted by silica deposits. If such deposits lie below forests, it is unwise to clear the forest itself. Durian. Silica cemented non-wetting horizon, earthy, brittle. Found only in volcanic areas. Red-brown hardpan. Occurs in many soil types, not volcanic, semi-arid, and Is 10 cm 30 m, 4 inches to 98 feet, thick. Asterisk ferricrete, iron cemented pans and soil layers. Of varying thickness, sometimes as thin sandy layers of 5 to 10 millimeters, also alumina iron laterites, often capping. Desert hills with veins of silcrete, or iron manganese. Nodular horizons in soils. Ferricrete may lie over pale bauxites, and is also called ironstone, plintite, ortstein. Occurs in podzols as iron organic hard B horizons. Coffee rock is a thick sandy coffee-colored horizon. Low in iron and easily broken, it is a common horizon. In humic podzols. Duricrusts form hard silica iron. Caps on hills in deserts. Asterisk plow pans are usually clay-based calm. Packed layers developed below croplands in wet periods. These can be caused by moldboard plows. All of the above need ripping, explosive shattering, or deep mulch pits to establish trees. Sodium in soils. May develop a collapsed cemented, grayish, gravelly pan, sulcrete, impermeable to water. Only. Trees, reduction of salt, and humus relief. These cemented conditions. Deep drainage of 1 to 2 m is essential for salted soils. Concreted soil layers, calcium or silica cemented, are the calcretes, caliche, platin, of dry islands and coasts, or the ferricretes, iron cemented, of deserts. Any or all may form duricrusts, hard layers, in eroded areas. Under some tropical rainforest, St. G in Ecuador. An iron silica pan which follows hill contours, locally termed Cangagua, lies 3 m below the forests. It is a daunting sight to see this glassy and impermeable surface after the removal of forest and a consequent loss of topsoil, where Cangagua is known to exist. Perpetual forests used for products other than their wood, honey, fruits, medicines, are the only sustainable use of land. Non-wetting sands and clays. Some classes of very fine blackish sands, and sands invaded by hydrophobic soil fungi, are difficult to wet. The water sits on top as droplets. There are several remedies for this in gardens. Asterisk rich soil to make basins. Every square meter, core out sand and drop in a loam or clay loam plug, 4 to 10 centimeters by 30 centimeters deep. Asterisk compost thoroughly and build up organic material to 8% of surface soil. Add a handful of bentonite per square meter, or powdered clay from clay pans. Asterisk mulch thoroughly, and plant. Keep surface mulch supplied. On the broad scale, deep plowing in autumn, to 45 euro m, is used, followed by rotary plow or chopper. Mixing of the top non-wetting profile of 10 to 20 centimeters, 4 to 8 inches, with subsoils. A cover crop is immediately sown to prevent erosion, and this used as a cover crop, or green manure for deep-rooting crop or tree species. The successful establishment of trees permanently curbs the problem. Clays which seal on the surface in light rains are often sodium-rich and melt in rain. Remedies are: asterisk make low banks across runoff. Asterisk add gypsum at 2 to 3 handfuls per square meter, and if possible flush out with fresh water, removing sodium as sulfate. If practical, place sand over the surface to 4 centimeters. For deep cracking clays and lumpy soils, add a sand layer. Scatter gypsum at a handful per square meter, and mulch. For acid or deep silica sands, it is best to add clay and mulch, and to lay plastic at 0.5 m deep in garden beds. Figure 8.7. Figure 8.7. Laying plastic in deep sands. Plastic sheet prevents deep leaching, clay's hot water at root level. Mulch prevents surface evaporation. 8.14. Plant analysis for mineral deficiencies, some remedies. Figure 8.8, after Clark and Smith, leaf analysis of persimmons, growing today, New Zealand, February 86. pp. 15 to 17, illustrates the seasonal levels of important plant nutrients, as 90% dry matter, and micronutrients, as microgram/pm, in leaf. The figures illustrate several things. 1. Seasonal change JN levels. Thus, the potential for early intervention in adjusting levels before it is too late to save the crop. 2. Very different behavior of nutrients. Type 1, zinc, iron, copper, high in new spring growth, falling over summer, and finally as leaves on a lost to the tree, becoming more concentrated in the last leaves, as uptake by roots concentrates these elements in the last leaves. N. Increase. Gutizio is AEW on CEA not mobile. Once in the plant. ITRP, rapid. Early uptake, ring degradation L decline over the season. T main steady over the year. Then declines as wood storage and root reserves build up. As persimmons are not atypical plants, these findings have implications for preemptive adjustment, e.g. bifoliar sprays, and selective mulch, e.g. the season at which leaves are taken for compost. I4 equals I. Spring SUMMGA, top is spring. Figure 8.8. A typology of the elements in leaf tissue in winter. Trees are bare. Behavior of basic nutrients in the lead analysis of 4 deciduous tree. Here a persimmon. Levels vary across the growing season. After growing today, NZ Tree Crops Association, February 1986, c. 4. F on me Sol Spring Semi OA. pp 16-7 for actual prafs. ACU, Fe, ZN, PN, and similar curves, slight increases in late C50N, BB, MN, MG, and CA. The non-mobile elements increase steadily in concentration. MgES nat normally regarded as Navi Neal. CK remains fairly steady, and is withdrawn from leaves in autumn. 209. Table 8.7. Key to mineral deficiencies. How to use, read the first set of choices, A, make 1, and follow on to the latter group in the right-hand column. Then make a second choice, or find the answer. Some ring ties follow, and are given under the numbers in brackets. First choices, underscore 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 go to. A equals leaves, stems, or lead stalks are affected. 8. Flowers or fruits are affected. E. Underground storage organs, roots, bulbs, tubers, etc., are affected. N. OOFLOPN shows PG or variable. Yields, WL. B youngest leaves show most effect, or early effects. C. C plus pale yellowish or white patches on the asterisk. Pale patch is not the worst symptom, but death of tips or growing points, or storage organs. D plus leaves uniformly color affected, yellowish or pale, even the veins, poor and spindly plants. Especially in heavily IEEE or celery sandy areas, acid or alkaline, is soft 1. Equals leaves not uniformly affected, veins, or guardias. E leaves wilted, then light colored, then start to dia. If onions, crop is undersized. If peas, seed in pods. Barely formed, match head size. Coastal sands. Black. Sod rock, Risu A2 Niger SESRE. Are often used as testers 42. Asterisk wilted and dying leaves not the problem. Asterisk at first, color loss is interveinal, between veins. And only later may include veins. Mature leaves little. Affected, dying not a feature, and common on calcar, eos or coral atolls, desert soils. Distinct yellowing. See also J. 3. Veins remain green, pale areas not so zero yellow. Autumn whitish or lack color. G areas near veins still green, affected leaf areas. Became transparent, brown, or start to die. Young. Leaves first affected. Peas and beans germinating in. Sol show brown roots and central brown area on leaf. Cotyledons. pH usually greater than 7.0. 4. Plus leaves smaller than normal, stems shortened. Growth retarded. Beans and sweet corn, several tree. Seedings most affected. Soils acid, leached sands. Alkaline, high in humus, coastal. Leaves may develop a. H equals plants brittle, leaves die or are distorted, growing. Points die, stems cracked, rough, short between. Leaves, split lengthwise, cabbages, cracked, celery. Probable on acidic sands, or on heavily limed. High humus soils. 6. Equals plants not brittle, but stunted, tips dying, feeder. Roots die, and leaf tips and terminal bud margins dying. Cabbage or cauliflower have young cupped or dead. Margins, old leaves. Alright. Young enfolded leaves? Brown edged, rotting, jelly-like decay. Check on. Overwatering, excess Na, K, Mg in water, or in. Of dolomite. Tomatoes show blossom and rot. 7. L equals plant with marked yellow, chlorosis, D. Yellowing not the main problem, leaves. Brown to purple OO, cease SSC enatini sinis L. JT plus yellowing between veins or on margins of. Plus yellowing affecting whole plant, ranging from light green to yellow, plant gets spindly, older leaves drop. Off. Prevalent in cold peaty soils, leached sands, soils. Subject to water logging. Turnips show purpling on. Leaves. Peans flower or mature at early, -8. K plus margins yellow, or blotched areas which later join. Up. Leaves can be yellowed or reddish, purple. Progressing to death of leaf area. Later, younger leaves. Effect had. Affected areas curl or become brittle. Brownish. Common on acid sandy or soil with high K or GA readings. Growth CL, plant stunted. Asterisk interveinal yellowing, looks at first like N. Deficiency. Old javis blotched, veins pale green, leaf. Margins rolled or curled, progresses to younger leaves. Leaf margins of cabbage, cauliflower can die, leaving. Central tissue only, whiptail, cauliflower will not form. Curds. Common on acid or leached alkaline soils, e.g. shell sand dunes, corals. Difficulty in establishing. Clover, equims, xcusc cs sessons rare season as any2. L plus leaf margins brown, scorched, can cup down. Wards, dying target spots near in leaves, spots of a. Dark centers, yellow edges, general mottled. Appearance. Growth reduced, first on young matured. And then on older leaves, finally to young leaves. May. Appear late in plants growth if a root crop, K is. Translocated to roots. Leached acidic or organic clay. Soils. Tomato leaf margin pie. Oxus escusari P1. Leaves wilt, droop, die at tips and edges. Sodium excess. Asterisk leaves dull, dark green, or red purple, especially. Below, under surface, and at the midribs. Veins end. Stems may also purple, growth is much reduced. Common in very acid, alkaline, dry, cold, or peaty. Soils. WF12. Leaves at tips wilt early as soil dries out, then. Become bronze, then die. Not often seen. Check water. Supply, salt content of soil, chlorine excess. M fruit rough, cracked, spotted, few flowers. Tomatoes with internal browning, seed chamber open. Uneven or blotchy ripening, stem end reddening. On. Acid soils, lodged sands, humus rich and limed soils. Terminal buds may die in laterals then develop. Top. Leaves thicken, can roll from tip 10 base. 6. Plus fruits rot on blossom end, opposite stalk, or. Show sunburnt dark areas there. Affects tomato. Peppers, watermelon, seed ed. 210. N plus internal dying or water soaked areas, uneven in. Shape, in beet, mine rutabaga if soil acid, leached, or. WER free lime. We 6. Asterisk cabbages in tooth core, then outside collapses as. Pits, common in carrots, beans S on acid by soils. Roots may split open. Onchus spini MN. Copyright plus areas of affected crop test acid, soils may be. Sandy, pH 7.5, alkaline. Tri-sulfur. Asterisk soil at depth mottled, smells of sulfur. Waterlogged, arranged drainage. Leaves tattered and dying at crown. Salt winds. Try shelter. Plus check for viral disease in grasses, try a plant. Pathologist. Remedies from the key. For gardens. First, keep a fertilizer diary for your garden, and leave it for the next person. Tell them what you have done for the soil. Equals if you are on leached, washed wool, sands, dig up your garden beds, place a plastic sheet liner below. Then add a bucket or so of clay and 2 handfuls of dolomite per square meter. Also, try a sol gel. Then, add compost, and a complete fertilizer like blood and bone. Mulch thickly and replant, then return to the key. If symptoms recur. If you are on peats, or have piled on the compost. Add some urea or blood and bone, raise your beds. And lime the area. Equals if you have lots of lime in the soil, or are on coral. Sands or dry desert coasts with calc-reedy, spray weak. Zinc and copper sulfates on plants, iron sulfates in. Very dilute solutions, 12 and 9/10 square meters with lots of water, or add it to a liquid manure. Make pits of compost and grow on the edges of these, use sulfur. Add about a handful per square meter, or add trace elements and sulfur to compost pits. Or, lay a sheet of plastic on the ground, build up logs around this to 25 cm high, and fill the area with humus, composi plus 50% sand, then mulch heavily. Add blood and bone. On atolls, dig down to near water table and then mulch. Thickly, make a big grope at 3 to 4 m wide by 10 to 12 m. Long by 3 m deep. Use any mulch, especially casuarina, palm, house wastes. 1 sulfur. Add plain sulfur, not of medical quality, add 1 handful per square meter. If you are near a city, you could have enough from fallout. 2 copper. Add as fine crushed ore, or in water as copper sulfate at 7 kq/hectare or spread, 1 g/square meter, every 5 to 7 years. 3 iron, try sulfur first, then if necessary add iron. Sulfate or spray foliage with very dilute iron solution. Bury old iron in humus pits near trees, e.g. pieces of galvanized iron, old wire, or car parts. 4 manganese, try sulfur first, then use very dilute foliar spray of manganese sulfate. 5 zinc. Add zinc oxide in acid areas, sulfate in alkaline, also sulfur in alkaline areas. Zinc at 7 kg/hectare or equivalent every 7 to 10 years. 6 boron. Be careful not to add too much, it one's poisonous in large quantity. First, lime acid areas and peats, and add sulfur to alkaline areas. If this doesn't work, add borax, sodium borate, at 1 gram/square meter and try cabbages to test reaction. Try not to buy detergents with borates, they can poison your soil. Boron excess, poisoning, can occur on sea sediments, and are common in reclaimed marine areas. Holland. Raise garden beds, lime, and flush out with fresh water. 7 calcium. Use lime as limestone in areas where manganese is plentiful, dolomite if not, or as camant powder in deep red hot tropical soils, then continue to add mulch and use lime only if deficiencies occur. Use gypsum in alkaline salty soils, then flush with fresh tank water and continue to use lime. Bone, bamboo mulch, buckwheat straw are all calcium sources. 8 nitrogen. Make sure the soil is well drained to 0.5 m for vegetablas, 1 to 2 m for trees. Check for cobalt levels, deficiency. If legumes are used, make sure they are inoculated, and that manganese levels are not too high. HF all this is satisfactory, add dilute urine, 20 parts. Water 1 part urine, ammonium sulfate in alkaline areas, or use legume mulches or interplant, about 48. Small acacia or tagaceous trees per 1/4 acre will do. Use compost, then surface mulch. Build up worms. And sail life, use dilute bird manure. Don't overdo it, or nitrates will build up in green plants and kill your kids or piglets with blue baby syndrome. Just relieve the symptoms, then get good soil life going. Use cobalt for severe nitrogen deficiency, poor clover growth or establishment in peaty or coastal soils. If manganese is high, just add lime to balance the soil. 1 handful per square meter, or in alkaline soils. Spray on at very low dilutions at 1 9/10 square meters. 9. Magnesium. Check if potash is not too high, or add clay to sandy acid soils, plenty of magnesium in most clays. Use dolomite for first dressing, then limestone. Epsom salts were used around citrus by old timers, or diluted in water for foliar spray in very severe deficiency situations. 10 molybdenum. Get some sodium molybdate, about 10.9, and mix well with 5 kilograms of sand. Take 1/100 of this, weigh the sand, and put it on per square meter. 11 potassium. Use ashes on green crop, diluted urine in early growth, then build up mulches, including dried or fresh seaweeds, flue dusts from cement works. TLY ash, also teas of bird manures, palm tree. Potassium is found in the mineral kyanite, 20 to 25%. Potassium, in evaporite deposits of deserts. 12 phosphorus. Bring pH to 6-6.5 or thereabouts. Using lime in acid soils and humus in alkaline. Use bone meal, berry bones, or use tested rock phosphate, free of cadmium or uranium. Stop deep digging and start mulching with least soil disturbance, build up narrow beds. Encourage soil lifa, add mulch on top. Water with comfort tea, dilute bird manure on the leaves of plants. Keep this up each time symptoms appear, they will eventually disappear if you have clay in the beds, add some if not. If you have high iron clays, you will need a lot of bone meal to start with, but it will slowly release later on. If desperate, use a few 211 handfuls of superphosphate per square meter, then continue with other sources. Feed a patch of comfort with bird manure and make a comfort tea in a drum of cold water. Water the plants with this. All animal manures, including yours, contain some phosphorus. Calc and roasted rock phosphate is effective on acid soils in high rainfall. 13 chlorine poisoning. Sue your counsel, or let tap water stand with a handful of lime in it for a day, then use on the garden. Don't take a shower. Developed and modified alter a formal developed by English John E. and Don N. Maynard, Mort Science 13, 1, February 76. And with data from the author and Handrek, Kevin A., 1976. Food for plants, XRO Division AF soils. Mineral fertilizers or soil amendments. The present testing method used on specific soil types is to sow down mixed legume, clover, brassica, and grass crop, or any important crop that may be grown. This sowing is then divided into trial plots which are treated at varying levels, and with soil or foliar spray amendments, to test plant health and response, based on a soil test for pH and mineral availability, or on a leaf analysis such as given in Table 8 to 7. For the home gardener, or keen observer, a deliver 8 wander through the system, and a good key to mineral deficiencies may be all that is needed to spot specific problems. Problems are in any case rare in well-drained garden beds using compost and organic molds, and where one species cropping is not on a broader scale, as in prairie or forestry establishment and erosion control, land reclamation, or plantation, every practical farmer and forester uses test strips of light to heavy soil treatments, from soil loosening to fertilizer, micronutrient, and grazing, cutting, or culling trials. When such field trials, as side-by-side strips, are none, it is wise to include typical areas of soil and drainage, and to avoid areas under trees, or at the sites of old stockyards or haystacks, intense fire scars, watering points, and gateways and roads, all of which have minor but special features and need a separate assessment from the open field situation. Have often noted, for instance, the colonization of chicory, thistles, and tough and deep-rooted weeds on the inhospitable areas of old roads and traffic areas. This sort of data is of use for some cases, but does not need to suggest that we compact the whole field in order to grow chicory. Rather, that chicory is a useful pioneer of compacted soils. Plant response on the test strips, which can be as little as 1% of the total acreage, may quickly indicate how modest and innovative soil treatment, minute amounts of micronutrients, or the timing of grazing or browsing can be managed to give good effects at least cost. There is no assurance as certain as the actual assessed plant response. To see 2 small plots of pines, coconuts, or cabbages side by side, the one healthy, vigorous, and productive, and the other lacking a key nutrient or on compacted soils, stunted, sickly, and unproductive, is a definite guide to future treatments. The same sort of trials are applied to plant mixtures or polycultures, pest controls, and the benefits or otherwise of mulch for a specific soil or crop. Assessment can be casual, in clear-cut cases, or 212. Analytic and careful where only slight differences appear. Such test strips are best securely marked by stout picks for long-term visits, as effects of some treatments persist or become evident over several seasons. Not until trials are assessed is it wise to widen the area treated, although in common sense it may always be wise to add humus or manures to non-peaty soils, or dolomite to acid sands. In alkaline and heavy clay soils, trace elements may become insoluble, and these are best added as foliar sprays to mulch or green crop, or to trees. 8.15. Biological indicators of soil and site conditions. In any local area, the composition, shape, or size, and distribution of the plants give many clues to soil type, depth, and extrinsic factors. Some specific factors indicated are soils, 1 depth, 2 water reserves, 3 pH, 4 mineral status, see preceding section, 5 fire frequency, 6 frost, drainage, mineral deposits and rock type, 9 overgrazing and compaction of soil, 10 animal, macrofauna, effects, site, 1 soil depth, shallow soils dry out quickly and hold few nutrients. A very good indication of soil depth is to look at one species of tree, e.g. acacia, Prosope, honey locust, over a range of sites. A height and spread estimate will reveal areas of deeper soils where the largest specimens grow. The same species will be dwarfish on shallow soils of the same derivation or rock type. 2. Water reserves. Deep-rooted trees which need water. The large nut trees and candle nuts. Aleuroides are good examples which occur naturally only in well-drained but water-conserving sites. Often show water lines not associated with valleys and stand over springs or aquifer discharge areas. In sands, a great variety of deep-rooted shrubs and trees indicate where a clay base lies at 1 to 2 m down. This situation is common on desert borders and hills in drylands. In brief, large tree stems reveal well watered sites, small stems drier sites. Armed with these observations, we can create sites by water diversion and select sites for large trees or shrubs. 3 pH, sorrel and oxalis in pastures may indicate compact or acid conditions, whereas several fen and limestone species establish in alkaline areas. Large snails and dense snail populations occur only over alkaline soils or in alkaline water. No snails or minute species occur in acid water, pH 5.0. In the garden, our cultivated plants demand acid or alkaline soils, e.g. alkaline intolerant, pH 4.5 to 6.0. Asterisk blueberry, chicory, asterisk chestnut, asterisk endive, asterisk potato, asterisk fennel, asterisk tea, asterisk coffee, asterisk rhubarb, alkali tolerant, asterisk oats, asterisk rye, asterisk kale, acid intolerant, pH 7.0 to 8.5, asterisk cauliflower, cabbage, equals, asterisk green peas, bush beans, asterisk celery, leek, asterisk beet, asterisk onion, asterisk chard, asterisk parsnip, registered spinach, acid tolerant, asterisk lupin, asterisk oats, asterisk white clover. This will have a profound effect on our home garden planting, but providing garden soils are mulched, and a little lime is added to compost, plants thrive in high humus soil supplied with same lime at modest levels. It is the perennial species that may need more care in site selection, or with mulch and compost in alkaline areas. Almost all our pollutants, and many of our fertilizers, tend to make soils acid, as does continued cropping or overgrazing. 5 fire frequency. East-west ridges often reveal abrupt species changes at the ridge wherever fire occurs. Fire produces dry, scrablet, summer. Deciduous, thick-seeded species, lack of fire develops. Broadleaf, winter deciduous, small-seeded plants with thin seed capsules and a deep litter fall. Cross-sectional cuts of trees will reveal fire scars as gum pockets or charred sections, and these can then be counted to get the fire frequency of the site. Figure 8.9. If tree stem sections are marked for directions before sampling, the direction of fires can also be judged. Registered shallot, watermelon, asterisk lucerne, asterisk broccoli. Figure 8.9. Fire direction scars on tree rings show frequency and severity of fires on any one site. 6 frost. Many species of trees and plants will indicate frost lines. It is a matter of observing focal flora, or planting frost-susceptible species down a hill profile to measure frost intensity. Tomatoes, bananas, and potatoes are all frost-sensitive and will reveal frost lines on hills in subtropics and deserts. 7. Drainage, mosses, sundews, and fine-leaved heaths indicate poorly drained soils, as large trees, such as chestnuts, which require 2 meters of well-drained soil, indicate good drainage. These indicators assist survey before pits are dug or drainage measured. 8. Mineral deposits. Davidov, Sputnik, December 12, 79, gives data on plant systems over mineral deposits. For Russia, the analysis of plant residues often indicates concentration of ores in the underlying soil or rock. Lead and copper molybdate are so indicated. Leaves or humus from birch, cherry, honeysuckle, St. John's wort, wormwood, juniper, and heather reveal the above loads plus tungsten and tin concentrates. All-purpose plants so discovered are rue or violets, zinc, catchfly, cobalt, aspots.oxyrine, selenium, milk vetch, 0, selenium and uranium, Russian thistle, boron, alias sum size, nickel, honeysuckle, silver and gold, horsetail, 0, gold and silica. General plant ash analysis may reveal more specific plant or associations. This has further implications for the rehabilitation of mine waste areas, and also to select plant sources for the supply of trace mine rice in compost. As plants have the ability to both concentrate and tolerate unusually high levels of specific minerals, there seems to be a field here for the biological concentration and subsequent removal of metallic soil pollutants like lead or uranium, and the use of concentrator plants to mine or collect locally rare trace 213 elements. In fact, some patents have apparently been granted for mining gold deposits using banana or citrus plants deprived of some common elements. Potash, phosphate, their leaves then concentrate sparse deposits of gold. Oysters will concentrate zinc to 11% dry weight in emetic dose, abalone concentrate cadmium, and several large fish concentrate mercury and biological poisons from corals to inedible levels. There are obvious implications for the removal, collection, or use of such species-element relationships, and lead cadmium or mercury levels in fish or plants need careful monitoring for public health reasons. 9. Overgrazing and soil compaction. Both the levels of grasshopper and pasture grub activity, high on overgrazed landscapes, and the presence of patches of poisonous, inedible, thorny, and unpalatable plants, e.g. Sodom apple, oxalis, capeweed, indicate an overstocking problem or range mismanagement. The effect is a synthesis between changing soil conditions, plant stress, and the heavy selection by livestock of palatable species, so favoring the survival and spread of spiny or inedible species. Too often, the pastoralist blames the weeds and seeks a chemical tather than a management solution. Too seldom do we find an approach combining the sensible utilization of grasshoppers and grubs as a valuable dry protein supplement for fish or food pellets, and a combination of soil conditioning, slashing, and destocking or reseeding to restore species balance. 10. Macrofaunal effects. The site of a sea bird rookery, a rabbit warren, the ground nest of a goose or eider clutch, the pellet pile of an owl, or the decay of a large carcass will cause a sudden and often long-term change in the immediate vegetation, as will termite mounds and harvester ant colonies. Once such sites are recorded, and the plant assembly identified, similar sites can be located and recognized. The data can be used as an aid to conservation, an indication of soil drainage. Rabbits choose good drainage as a result of specific nutrient supply, guano on seabird rookeries, or as a way to establish tree clumps. Following natural indicators: a large proportion of windblown, nitrogen-loving, and inedible plants, or plants carried by birds as seed, depend on the specific habits of birds or mammals, on their dung, or on soil disturbances. The role of animals in the distribution of plant seed and plant root associates is well recognized, their role in soil change less commonly noted. 8.16. Seed pelleting. In pioneering the rehabilitation or stabilization of soils, many of the local deficiencies in soils can be overcome by seed pelleting, which is a process of embedding seed in a capsule of substances that give it a good 214 chance of establishment despite soil deficiencies in local sites or microsites. Asterisk seed pretreatment. If seeds have thick coats, or need heat or cold treatment or scarification to break dormancy, they must be treated before pelleting. Asterisk inoculation. Purchase and inoculate legume seed with their appropriate microbial or fungal spores. Soak the seed in inoculant solution, then dry the seed. Mix dried seed with the primary coat as below. Asterisk pelleting. Use a lime, clay layer, and a trace of fine rock flour, calcium, or phosphate mixed into a damp but plastic slurry around the seed. This is then extruded, e.g. via meat mincer with the cutting blades removed, to a shaker table or tray covered with dust, and on a slight incline. Dust is added as needed to dry and shape the pellet, or to set a desirable size of pellet, figure 12.18. The dust, or outer pellet coat, should incorporate a soil conditioning gel or polymer, a colloid forming substance, fine graphite, a bird repellent, green dye. Helps repel birds, and insect repellents such as powdered neem tree leaf, Azadirachta indica or Melia azedarac, or diatomaceous earth, and perhaps some swelling clay, such as bentonite. Tellies are now dried and scattered, drilled, or sown on sites to await rain. The protected seed germinates when the pellet absorbs water, and the emerging root finds its nutritional needs satisfied, while the root associates also become active in nutrient transfer to the plant. The same vibrating table that we use to pellet seed serves, when fitted with screens, to clean and sort seed from the soil below trees or from seed and husk mixtures, and the mincer can be returned to the kitchen. None the worse for wear. Fukuoka achieves the same result by pressing seed clay mixes of grains through a coarse sieve onto a dust-filled pan which is shaken to round off the pellets. 8.17. Soil erosion. As all else depends on a stable and active soil, soil creation is one of the central on-or-P's. Soil erosion or degradation is, in fact, the loss of production and hence of dependent plants and animals. Soils degrade in these ways. Asterisk by wind, by dust storm and the blowout of dunes and foreshores. Via water flow by sheet erosion, a general east. Surface flow off bare areas and croplands, gully erosion, caused by concentrated flow over deep but unstable sediment, and tunnel erosion, subsurface. Scouring of soils below. Asterisk via soil collapse or deflocculation following increased salt concentrations in clay fraction soils. Thus, the placement of windbreaks, tree crops, and fast-spreading grasses stabilizes erosion caused by wind, while permanent crop, terracing forestry, and, in the case of gullies, diversion and spreader drains plus gabions help reduce or heal scoured areas. Tunnel erosion may call for destocking, contour drainage, and the establishment of deep-rooted plants, while the problems of desalting need the combined factors of reforestation to lower groundwater tables, following deep interceptor drains to cut off salt seepages in surface soils, see Chapter 11. Erosion follows deforestation, soil compaction, disturbed soil water balance, increased overland flow, and rising water tables or salt seepages, overgrazing. Plow agriculture on the broad scale, episodes of high winds or rains in drought periods, or severe disturbance caused by animal tracks, roading, and advised earthworks. Insofar as landscape design is concerned, soil erosion repair is the priority wherever such erosion occurs. Apart from the physical factors, no designer or nation can ignore the economic or political pressures that inevitably create erosion by requiring or permitting inappropriate land use and forcing production or overproduction onto the fragile structure of soils. Third world debt and Western world overproduction are both primary factors in soil collapse. In a conservative society, the very basis of land use planning would encompass the concept of permitted or restricted use of soils, carefully plotted in regions following analyses of slope, soil stability, minimal forest clearing, or reforestation, and permitted maximum levels of crop production, or livestock density, following the procedures of good soil husbandry. In assessing erosion in the UK, Charles Arden Clark and David Hodges, New Scientist, February 12, 87, point out that many of the recent outbreaks of severe erosion are clearly linked to falling levels of organic matter in the soil. The more organic matter there is in the soil, the more stable it is. This stability is because of good soil structure and infiltration of water. whereas an inorganic soil may break down under rain. With the following increase in overland flow, most soils will then erode as rills or gullies, or the destroyed surface can powder and blow away without organic matter te bonded. On many delicate soils, over chalks, the only answer is to replace crops with pasture or forest intensive. Arable use and winter cropping both create more erosion. The very radical conclusion is that mulching, green manure, grass leaves on rotation, hedgerows, and minimal cultivation aid not only urgent but imperative. Thus, the time to examine the organic farming approach has passed, the time to adopt it has arrived. Ibid, at long last, some scientists are saying that enough evidence is of, we need to turn to known, effective land management based on permanence and organic methods. This will take the combined good will of farmers, scientists, financiers, and consumers. 8.18. Soil rehabilitation. Careful gardeners take care not to break up, overturn, or compact their valuable soils, using instead raised beds and recessed paths to avoid the destruction of crumb structure. Responsible farmers try to govern the speed and effect of their implements in order to preserve the soil structure, and can get quite enthusiastic about a dark, humus-rich, crumbly soil. We seldom give farmers time or money to create or preserve soil, but expect them to live on low incomes to serve a commodity market, whose controllers care little for soil, nutrition, or national well-being. No matter on what substrate we start, we can create rich and well-structured soils in gardens, often with some input of labor, and always as a result of adding organic material or green manures, cut crop. No matter how rich a soil is, it can be ruined by bad cultivation practices and by exposure to the elements. Wind, sun, and torrential rain. Worms, termites, grubs, and burrows create soil crumbs as little bolus or manure piles, and they will eventually recreate loose soils if we leave them to it in pasture. But we also have other tools to help relieve compaction. They can be explosives, speciae, implements, or roots. We use the expansive and explosive method rarely. Perhaps to plant a few valuable trees in iron hard ground by shattering. People like Masanobu Fukuoka are more patient and effective, casting out strong-rooted radish seed, daikon varieties, tree, legume seed, and deep-rooted plants such as comfort, lucerne, acacias, and eventually forest trees. Much the same subsurface shattering occurs, but slowly and noiselessly. The soil regains structure, aeration, and permits water infiltration. A measure of the change wrought by green manures, mulch, and permanent windrow is recorded by Eric van der Werf, Permaculture Number Newsletter. Queensland, December 1985 and Mars/APR 1986. Working in Ghana at the Agama Agricultural Project, he reports on the improvement of crumb structure by measuring the bulk density weight per volume rate height, G/cc, of soil samples, is given in Table 8.8. Table 8.8. Improvement in crumb structure. Soil treatment bulk. GIS density. Annually burnt bush 135. Bush left 2 years without fire 127. Farmland, cultivated 2 years 1.29. Farmland, permanently mulched. And cropped for 3 years 0.92. Even with cropping, the mulched soils show how humus alone restores good aeration. Soil temperatures were lower by 10 degrees Celsius, and both crop grain yields and a 3 times increase in organic matter production were noted. 215. We can use rehabilitative technology on a large scale, followed by the organic or root method, by pulling a shank and steel shoe through the soil at depths of from 18 centimeters, usual and often sufficient, to 30 or even 80 centimeters. Heroic but seldom necessary unless caliche or compacted earth is all we have left as soil. In field or whole site planning, a soil map delineating soil types can either be purchased or made based on local knowledge and field observation. In designing, it helps future management if uses, fencing, and recommendations for soil treatment and crop can be adjusted to such natural formation as soil types. An aid to soil typing can be found in basic books on soils. These publications give practical guides to landform, floristics, structural, typing, and soil typing, and taxonomy, categories or classes of soils. We can recommend low tillage systems, pay close attention to water control during establishment, and get soil or leaf analyses done. We can also make careful trials of foliar sprays, the additions of cheap colloids to sands, the frequency and timing of critical fertilizer applications, often and little on sands, rarely or as foliar sprays on clays. Crops suited to natural pH, it is often expensive to greatly modify this factor, and rainfall should be selected for trials. Close attention needs to be paid to the soil stability and thus the appropriate use for soils on slope. In particular, priorities should be set for erosion control in any specific soil or on specific sites or slopes, and earthworks or planting sequences designed to establish soil stability, for if we allow soil losses to continue or worsen, all else is at risk. The next stage in the design is to assess the capacity of soils for dams, swales, foundations, or specific crops. This may need further analysis, test holes by auger, or soil pit inspection. Thus, if we have adopted a predetermined set of values based on 5011 and water conservation and appropriate uses of sites versus erosion and high energy use, any site with its water lines and soil types, note it starts to define itself in usages. How we need to proceed in soil rehabilitation is roughly as follows. 1. Water control, drainage and sophisticated irrigation are needed to rehabilitate salted areas, and soil mounding or shaping to enable gardening in salted lands, as explained in Chapter 11 on arid lands. We need to rely much more on natural rainfall and water harvest than on groundwaters. Drought is only a problem where poor, or no, water storage has been developed, where tree crops have been sacrificed for fodder or fuel, and where grain crops are dependent on annual rains. Although many sands and deeply weathered soils are free draining, water logging can occur wherever soil water lies over an impermeable soil layer or where water backs up behind a clay or rock barrier. Anaerobic soil results. Remedies lie in any of 3 techniques. 1. Raised garden beds. Paths are dug down for drains, and beds raised. In very wet areas give paths a 216. 1:500 slope to prevent erosion. Figure 8.10.a. 2 deep open drains every 10 to 80 m. Clay sands. Upslope and downslope or on either side of garden beds. Figure 4.10.6. 3 underground pipes, tile drains, fluted plastic pipes are best, laid in 1.5 m deep trenches and backfilled at 1.5 m, 4.5 feet, deep and from 10 to 80 m. 32 to 262 feet apart, starting on a drain or stream end, with a gentle fall, 1:1000-1:600, to the ridge. Figure 8.10.c. Water retention in soil is now greatly aided by long-term soil additives. These are gels which absorb and release water over many cycles of rain. This is a practical system only for gardens or high-value tree crop, where the cost amortizes. 2. Soil conditioning. Compacted, collapsed, and eroded soils need rehabilitative aeration, and a change in land use. 3. Fertilization. We can reduce and replace past, wasteful or polluting fertilization by sensible light trace element adjustment by foliage sprays if undisturbed. Soil systems and permanent crop have been developed. Foliar spray of very small amounts of key elements greatly assists plant establishment, as does seed pelleting using key elements deficient in plants locally. We may then be able to utilize much of the phosphate that is locked up in clays, and using legumes, create sufficient nitrogen for food crops from sophisticated interplant and green manures. 4. Crop and plant species selection. Many older varieties of both annual and perennial crops will yield with less fertilizer and water applications than will more recently developed varieties. There is a growing trend amongst farmers and gardeners to preserve and cultivate these varieties not only for the reasons above, but also for flavor. Many older apple varieties, such as some of the Pippin and Russet types, are more flavorful than, say, the market variety red. Delicious. There is still a large diversity of food crops left in the world. The key is to grow them and to develop a regional demand. Many older apple or wheat species are not only pest resistant, but have higher nutritive value and can produce well in less. There are different species of plants that can live in almost any type of soil, starting the process back to rehabilitation. T is often the case that so-called noxious weeds will colonize eroded landscapes, beginning a slow march towards stabilization. These can be used as mulches. Soils can be created or rehabilitated by these basic methods. Asterisk building a soil, at garden scale. Registered mechanical conditioning, and asterisk life form management, plants and macro or microfauna. Building a soil. Gardeners normally build soil by a combination of Mia, Laurel Louse. Figure 8.10. Drainage of wet soils. A raised garden beds. B. Deep open drains. Sent underground pipes or ditches at about 1:200 stoke will drain fields. Ding. 70 c/0 U. 3 processes. 1. Raise or lower beds, shape the earth, to facilitate watering or drainage, and sometimes carefully level the bed surface. 2. Mix compost or humus materials in the soil, and also supply clay, sand, or nutrients to bring it to balance, and 3. Mulch to reduce water loss and sun effect, or erosion. Gardeners can, by these methods, create soils anywhere. Accessory systems involve growing such compost materials as hedgerow, herbs, or softleaf plots, or as plantation within or around the garden, and by using a combination of trellis, shade cloth, or palm fronds, glass house, and trickle irrigation to assist specific crops, and to regulate wind, light, or heat effect. By observing plant health, gardeners can then adjust the system for healthy food production. Many gardeners keep small livestock, or buy manures, for this reason. Large-scale systems, small farms, cannot be treated in the above way unless they are producing high-value product. Normally, farmers create soils by broad-scale drainage or by soil conditioning. As most degraded soils are compacted, eroded, or waterlogged, they need primary aeration, by one of the many available modern machines, or by biological agents. Then careful plant and livestock management to keep the soil open and provided with humus. Daikon radish, tree or shrub legumes, earthworms, root associates for plants, rhizobia, all aerate, supply soil nutrient, or build soil by leaf fall and root action. The management of livestock release compaction and overtasking is part of the skill of soil building and preservation. Many organic farmers introduce worm species to pastures as part of their operation, and sell deep-rooted chicory, radish, or comfort for green manures. 217. Soil treatment on compacted sites. Soil conditioning. On the common degraded soils of marginal areas, we can observe compacted, eroded, lifeless soils. They are overgrazed and often invaded by flatweeds and non-forage species of plants. They are boggy and wet in winter, and they are dry, cracked and bony in summer, having little depth. The reconstitution proceeds as follows. At the end of winter, or in autumn after some rain, asterisk. When the soil will carry a tractor, a chisel plow is pulled 5 to 10 centimeters, 2 to 4 inches, deep over the area, either on contour parallels or on low slopes, starting in the high valley bottoms and driving slightly downhill to the ridges. Unless there are absolutely no legumes or grasses already growing, no extra seed is applied. The response is increased penetration of roots, germination of seed, and a top growth of pasture. Bi. Ta 2 equals th. F. A. A. Ys. Teaspoon. Cae. Ss. Fs. I. Equals E. I. Ar. A frame. Underscore Ba. Bala. I. 4 IEBX Borigs. Asterisk. Reami EZFDF. Figure 8.11. Soil rehabilitation by mechanical methods. A chisel plow shank, Rom the Wallace soil conditioner. B in pasture 3 or 4 sequences with increasing depth of tines creates deep, 18 centimeters, humus soils over 1 to 2 growing seasons. 218. A chisel or soil conditioner is a rectangular steel frame, toolbar, towed by tractor or draft animals, to which a number of shanks are attached. These are narrow edge, axe edged, forward curved, vertical flat bars to the point of which a slip-on steel shoe is attached. The shanks clamp to the toolbar frame, and the points to the shank. Even one implement of 5 shanks, 25 to 50 bhp tractor, covers a lot of country. There are now at least 6 or 7 makers of sill loosening machines in the USA, Europe, and Australia. Jeff Wallace has produced a soil conditioner of great effectiveness. A circular coulter slits the ground, which must be neither too dry nor too wet, and the slit is followed by a steel shoe which opens the ground up to form an air pocket without turning the soil over. Seed can be dropped in thin furrows, and beans or corn seeded in this way grow through the existing grass. No fertilizer or top dressing is needed, only the beneficial effect of entrapped air beneath the earth, and the follow-up work of soil life and plant roots on the reopened soil. This new is then hard grazed, or cut and left to lie. The plants, shocked, lose most of their root mass and seal their wounds. The dead roots add compost to the soil, as does the cut foliage or animal droppings, giving food to the soil, bacteria and earthworms, and softening the surface. As soon as the grazing or cutting is finished, chisel again at 23 to 30 centimeters, 9 to 12 inches, on the same pattern as before. Graze or cut again, chisel. Again at 23 to 30 centimeters, graze or cut. During this process, often a matter of a 1 year cycle, the pasture thickens, weeds are swamped with grasses and legumes, myriad roots have died and added humus, and thousands of subsurface tunnels lead from valley to ridge, so that all water flows down into the soil and out to the ridges. Earthworms breed in the green manure, bacteria multiply, and both add manures and tunnels to the soil. At 23 centimeters, 9-inch blanket of aerated and living soil covers the earth. Dust, deep roots, rain, and the bodies of soil organisms all add essential nutrients. The compost soil is, in essence, an enormous sponge which retains air and water, and it only needs a watchful eye and an occasional chiseling in pasture or a forest to be planted to maintain this condition. If tree seed, soybeans, millet, or other crop is to be planted, the sequence is as follows. After a few hard grazings or mowings, a seed box is mounted on the chisel plow frame, and the seed placed in the chisel furrow. The grazing or mowing follows germination of the seed. These new plants, sunflowers, millet, melons, grow faster than the shocked pasture, and can be let go, headed, or combined harvested before the presses recover. There is never any bare cultivation, and grain growers can move to a minimum tillage method of cropping, with fallows of pasture between crops. Soil temperature is greatly modified, as is soil water retention. Jeff Wallace, PERSCOMM, recorded as much as 13 degrees Celsius 25 degrees Fahrenheit increase on treated versus untreated soils in autumn. This increased temperature is generated both by the biological activity of the soil and the air pockets left by the chisel points at various depths, and enables earlier and more frost-sensitive crops to be grown. Nodulation of nitrogen-fixing bacteria is greatly increased, as is the breakdown of subsoil and rock particles by carbonic acid and the humic acids of root decay. Methane generated from decayed seed germination and water, even in downpours, freely passes into, not off, the soil. After a year or so, vehicles can be taken on the previously boggy country without sinking in. Drought effects are greatly reduced by soil water storage. Water, filtered through soil and living roots, runs clear into dams and rivers, and trees make greatly increased growth due to the combined factors of increased warmth, water, root run, and deep nutrients. Fukuoka, in Japan, uses radish and acacia. Africans use Acacia albida or Gliricidia. New Guineans use Casuarina, and Mediterranean famers use Tamarix for biological chisel plows where land is too steep and stony for implements. Otherwise the graze or cut and let lie method is still followed. On such difficult terrain as boulder fields, dunes, steep slopes, and laterites, forests of mixed legume/non-legume crops, citrus, olive, pine, oak, are the best permanent solution to soil conservation. No matter how we aerate soil, or condition it, whether with humble implements like a garden fork, lavered slightly, by planting a daikon radish, or by sheer mechanical power, we can soon lose the advantage of looseness and penetrability by stocking, cropping, heavy traffic, or heavy hoofed animals stocked in wet weather. All of these pug or compress the soil into a solid state again. Final solutions lie only in following on with permanent and deep-rooted plants, forests or prairies, and by maintaining good management, minimum tillage, cropping. Any reduction in cultivation saves energy and soils. And wherever no tillage systems can be devised, and heavy hoofed animals kept to a minimum, soil structure can be repaired. Intense fire, intense stocking, intense cropping, and intensive production all threaten soils. Thus, mechanical soil rehabilitation can be a one-time and beneficial process, or another way to waste energy. Every year, it is the usages that follow on rehabilitation that are beneficial or destructive to soils. In the long term, mechanical loosening of soils is appropriate, on the broad scale, to almost all agricultural soils that have been compacted. Soils with coarse particles of cinder or dunes do not benefit from or need loosening, and very stony or boulder soil mixtures are appropriately rehabilitated not by mechanical but by organic root penetration methods, as are soils on steep slopes. Some soils, like volcanic soils with permanent pastures, may never lose structure, and will maintain. 219. Figure 8.12. Soil conditioning. A. Ideally, chisel lines run downhill from valley to ridges. B. Here, water flow crosses contours at right angles, no chisel lines, and creates sigmoid, 5, curves in the landscape. C. In conditioned landscapes, chisel lines prevent fast runoff and absorb overtand flow, leading water low ridges. 220. Free internal drainage after years or centuries of grazing. Thus, we use rehabilitative energy only where it is appropriate. Soil conditioning can be sequential, allowing a year between treatments, or all at once at 20 centimeters or so, in order to prepare for tree crop planted immediately. The time to use implements is also critical, and early spring, or at the end of a gentle rainy period is ideal, as the soil is not then brought up to the surface as dry clods, nor collapses back as being too wet. There is only one rule in the pattern of this sort of plowing, and that is to drive the tractor or team slightly downhill, making herringbones of the land. The spines are the valleys and the ribs slope out and downslope, figure 8.12. The soil channels, many hundreds of them, thus become the easiest way for water to move, and it moves from the valleys and below the surface of the soil, because the surface is little disturbed, roots hold against erosion even after fresh chisel plowing, water soaks in and life processes are speeded up. A profile of soil conditioned by this process is illustrated by figure 8.11. There is no point in going more than 10 centimeters in first treatment, and to 15 to 23 centimeters in subsequent treatments. The roots of plants, nourished by warmth and air, will then penetrate to 30 centimeters or 50 centimeters in pasture, more in forests. For disposal of massive sewage wastewater, Yeomans recommends ripping to 90 centimeters or 1.5 m, using deep-rooted trees or legumes to take up wastes. I have scarcely seen a property that would not benefit by soil conditioning as a first step before any further input. Pasture and crop do not go out of production as they do under bare earth plowing with conventional tools, and the life processes suffer very little interruption. In small gardens, the aeration effect is obtained in two ways. Asterisk by driving in a fork and levering gently, then removing it. Registered by thick surface sheet mulch, worms do the work. To summarize briefly, the results of soil rehabilitation are as follows. Asterisk living soil, earthworms add alkaline manure and act as living plungers, sucking down air and hence Ni7. Asterisk friable and open soil through which water penetrates easily as weak carbonic and humic acid, freeing soil elements for plants, and buffering pH changes. Asterisk aerated soil, which stays warmer in winter and cooler in summer. Registered the absorbent soil itself is a great water retaining blanket, preventing runoff and rapid evaporation to the air. Plant material soaks up night moisture for later use. Asterisk dead roots as plant and animal food, making more air spaces and tunnels in the soil, and fixing nitrogen as part of the decomposition cycle. Asterisk easy root penetration of new plantings, whether these are annual or perennial crops, and asterisk a permanent change in the soil, if it is not again trodden, rolled, pounded, plowed, or chemicalized into lifelessness. Trees, of course, act as long-term or inbuilt nutrient pumps, laying down their minerals as leaves and bark on the soil, where fungi and soil crustacea make the leaves into humus. 8.19. Soils in house foundations. Soils cause perhaps 60 to 80% of all house cracks and insurance claims for faulty construction and tree damage. About 20% of the soils we build on will subside or heave depending on water content. Specifically, black cracking clay, surface clays, and red-brown clay loams are subject to swelling and shrinking. Solid stone and brick houses are most subject to structural failure, with wood frame and veneer less so. Over-irrigation of gardens, causing the water table to rise, is a primary cause of soil swelling. The removal of trees assists this process, as do paved areas, and burst or leaking sewage and water pipes. Some notorious white or yellow clays collapse as dam walls when wetted. It is as well to consult your local soil expert for large constructions, as trials can be while the effects are most noticed to 2 m deep. Probes to 10 m deep need to be monitored for ground water levels. Soil subside and shrink with excessive drying, too many trees too near the house, and swell and heave with excessive watering and no trees. Adelaide, Australia, is an area where most damaged houses are on black soil clays, but several other areas also suffer these effects, and in some, large buildings need to be built on foundations capping deep piles, to RIT. Liatirate. Lu. Piles sunk into water table or bedrock. To stabilize house foundations in swelling clay soils. 221. 20 m, sunk to the bedrock or deep into the permanent water table, figure 8,13. Most Australian native trees have an efficient water removal by roots, so that eucalypts remove 2 to 3 times the water of pines or pasture, to 10 m radius. Generally, householders should keep large trees at least 1/2 the mature height from the house when building in high clay fraction soils. Sands and sand loams are usually stable, as are rotten or fractured rock and sandstones. 8.20. Life in earth. Before we ever learned to cut open the soil, it was thoroughly dug, aerated, and overturned by multitudes of industrious burrows. The unploughed meadows of Europe and America are as soft as a great mattress, and are well aerated due to the moles, gophers, worms, prairie dogs, rodents, and larvae, eternally at work below ground, even under the snow. Termites, ants, and crustaceans all do their part. The results are obvious from the good soils and great productivity of unploughed ground which has not been compacted by hooves or machines. Termites and ants are the earthworms of the deserts and drylands, carrying tons of organic material to underground compost piles, in some of which they may grow fungi to feed their colony. The upthrown earth, whether from ants or moles, forms a specific niche for annuals to seed on, and wind-blown pioneer trees to occupy. If birds are the seed scatterers of the forest, burrows are the gardeners. Underground and beneficial fungal spores eaten by squirrels or wallaby and activated by their digestive enzymes break hibernation to occupy new ground and help the new roots of acorns and eucalypts to convert soil minerals and liquids to food. Gophers and moles industriously carry roots and bulbs to secret stores and sometimes forget their hoards, so that sunroot, gladioli, daffodils and hyacinths spring up in unexpected places above ground. This is how comfort and sunroot spread, despite their lack of Bible seed. They depend not on bees, but on moles and gophers for their increase. Foxes eat fruits, and defecate on gopher mounds, which are the dug-over areas for new trees. Wombats may tunnel, overturn, and even topple many hectares of trees, leaving a richly manured, open, and fertile bed for new forest evolutions. Rabbits industriously garden thistles, and their tunnels give shelter to possum, squirrels, bandicoots, snakes, and frogs. Worms and crustaceans, in their damp and sometimes semi-liquid burrows, move up and down like a billion pump plungers, sucking in and expelling air, and thus nitrogen, to roots, and in effect giving the soil its daily breath. Many creatures mix up special mood brick soils with body secretions, and from 222. Figure 8.14. AE how a mound develops under a house. F slab plus beam construction helps stability. Swallows to termites create homes from stabilized soils. Seeds and spores are buried, excavated, hidden, activated, and forgotten by burrows, and recycled to life or humus as chance and nature dictate. Roots die seasonally, invade and retreat, and leave minute or massive tunnels for animals, fungi, and new roots to follow. I once tried to dig a parsnip out of newly drained swamp ground, following it along an old root trace, but gave up after 2 minutes. I did persist in following a 4 centimeters long Indian land crab or earth lobster to 2 m down and 2 m along, and have often dug out rabbit and mouse burrows to find their nests. Mating circuses, air vents, nursing chambers, disposal chutes, and escape hatches. Many old gopher burrows are filled with plant remains and fecal wastes. A few dedicated souls in the history of science, from Sir Albert Howard to modern ecologists, try to excavate and discover something of roots, but as a simple blucum, Eucalyptus globulus, can easily embrace an underground 1.5 ha. A forest is so complex, and even intergrafted below ground that the canopy seems simple. Many desert plants lead a long and sturdy underground life, while thin, straggly, and ephemeral in air. Some insects, like swift moths, Hepialidae, spend 7 to 8 years underground as large barty grubs, a succulent treat for Australian diggers. with only a few days of nocturnal foodless life in air, mating and laying eggs before disappearing again. 2. The root sheets and soil, as their near cousins the ghost moths and witch eddy grubs do in aerial stems. The barty grubs, 2, open thousands of shafts to the air, and cycle tons of nutrient underground, as do their relatives in air and sunlight. Their predators follow these hoarders and burrows below the soil, and hunt them in darkness and secrecy. The implications for designers are that many of these effects may be put to use, or their use is appreciated. It is as valid to plant an acacia for the considerable byproduct of swift moth or ghost moth larvae as it is plant a mulberry for silkworms, and to use moles instead of mole plows, or gophers as daffodil gardeners, unpaid. Even on shores and the bottom of lakes and seas, the burrows work to carry nutrients below to roots and to bring up fresh minerals for decomposition, while assisting the flux of liquids and gases across the surfaces of mud media. Roots have their own penetrations, depth, patterns or spread, schedules, seasonal migrations to or from the surface, and equivalents of deciduous drop or bark decortication, dying off and sloughing off root branches and bark. It follows that there is a topography of plants underground that parallels that of plants in air. There are also basic differences in that special storages or fire-resistant organs found underground as lignotubers, tubers, bulbs, and rhizomes are very common. Some species secrete phenols or creosoles to inhibit other plants, bracken, tamarisk, juglindacine, brassicas. Others encapsulate or surround hapless competitors, eucalyptus, willows, tamarisks. Some trap nematodes and other would-be predators, or poison them out. Marigolds, fungi, crotalaria. While agricultural crops exploit from 0.64 m, 2 to 12 feet, below the earth, some trees may penetrate to 50 m, 164 feet, in deep desert sands, around the roots of dune trees. Calcium and other minerals are deposited as stone-like secretions by is also scheduled, so that spring bulbs have fed, flowered, and died before the tree roots begin their upward thrust for nutrients and water, tap-rooted late. Starters such as thistles and comfort reach deep for late summer moisture, while a very few plants and fungi take advantage of the autumn rains for flowering and dispersal. Where there is no season of cold death, as in the low latitudes, aerial roots may develop, or strangler figs send down roots from high in the crotches of other trees to the earth, there to build great buttresses as they strangle their host tree in a root well. For designers, the diversity of roots in soil can be used as effectively as the diversity of crowns and canopies. Unstable slopes are pegged with the great root tree nails of chestnut and pine, oak, and walnut. Even after 100 years, the steep slopes of this island, Tasmania, are only just starting to collapse as the roots of the cleared forests rot, and could still be saved by pines, acacias, or chestnuts. Bamboo not only holds landslides, but for light structures provides an earthquake-proof mattress of roots. The root mats of swamp vegetation save bulldozers from watery graves, and the fibrous web of the prairie defeats the wind. Geology and life forms. Many rocks and strata on Earth arise from the actions of living organisms. Whether it is the nodules of manganese in oceanic depths, deposits of diatom, AC as earth, coal, or limestone, or opals and amber, all were once the products of living organisms. Much of the strata we see, except much changed granitic and volcanic deposits, were formed from or modified by life. All soils are life created, as are the corals and coral sands of many oceanic islands. Life is also busy transporting and overturning the soils of Earth, the stones, and the minerals. The miles-long drifts of sea kelp that float along our coasts may carry hundreds of tons of volcanic boulders held in their roots, have followed these streams of life over 300 kilometers, and seen them strand on granite beaches, throwing their boulders up on a 9,000-year-old pile of basalt, all the hundreds of tons of which were carried there by kelp. Round stones are dredged from great depths in the mid-Atlantic. This does not mean that they were formed there, but more likely that drift kelp carried them there in their roots. Before they fly to Japan and Alaska, some millions of petrels, Pagefinus, tenuirostris, annually fill their crop with Tasmanian pebbles, seeds, and charcoal, which will be voided somewhere in the Pacific. 223. Life moderates every erosion process, every river, basin, every cliff and rock fall. It shapes and reshapes Earth in 1,000 ways. The hydraulic weight of great forests, such as were once in the Americas, would have exceeded any water catchment weight we can now afford to build, and dispersed it over a greater area. This greatly moderates climate, and with it geological processes. It is possible in Iran, Greece, North Africa, USA, Mexico, Pakistan, and Australia to see how, in our short history of life destruction, we have brought the hard bones of the earth to the surface by stripping the life skin from it for ephemeral uses. We can, if we persist, create a moon landscape of the earth, so poor goat herds wonder where the fake forests stood and the forest deities were worshipped. The religions of resignation and fanaticism follow those of GPA, PTI. Man-built temples replace trees and tree spirits. 8.21. The respiration of earth. All of the skin and organs of the earth breathe. It is a regular respiration. The diaphragm or energy for this may be provided by the moon, tides, and water, earth, or air. Locally, the filling up of soil by rainwater forces an exhalation of air, the drying out and inhalation. Fast winds disturb boundary layers, create low pressure, and soil exhalation. Slow winds and high pressures force inhalation. Millions of earth animals open breathing tubes and arrange them for their own sake to force an exchange between the atmosphere and the waters, the soils, or sea sands in which they live. Water is aid much breathed as air. Deeper respirations come from deeper flows and fissures, and radon gas or methane seeps out from the earth. When the earth itself expands, great flows inward and outward must occur through the multitudinous fissures that open up in rigid sediments. This earth respiration and transforms fluids and their associated loads, solutes, states, and iotic potentia from earth to a to ocean, setting up. The potentials that create thunderstorms or hurricanes. We are of the same respiration. The burrows AF. Spiders, gophers, and worms are to the soil what the alveoli of our lungs are to our body. We can assist this essential respiration by assisting life and natural processes in soils. If you kill off the prairie dogs, there will be no one to cry for rain. Navajo warning. Amused scientists, knowing that there was MO conceivable relationship between prairie dogs and rain, recommended the extermination of owl-burrowing animals in some desert areas, planted to rangelands in the 1950s, in order to protect the roots of the sparse desert grasses. Today, the area, not far from Chilchinbito, Arizona, has become a virtual waste land. Fierce runoff, sale, compaction, and jack of fresh seedbed have carried the grasses away. Bartolkin. In Indian Science Quest 78. Sept/Oct. Using prairie dog burrows as water sinks, and causing water runoff to flood down them, thus germinating stored underground seed, had the opposite effect on the page. Ranch, now a dryland. Figure 6.15. General soil erosion processes in landscapes. P. A. Equals 224. Rehabilitation exhibit of the University of Arizona. Here, prairie dogs and a new and thriving patch of permanent bunch grasses thrive in an area where overgrazing, plowing, or soil compaction has ruined other grasslands. Water under the ground has much to do with rain clouds. If you take the water from under the ground, land will dry up. Hopi Elder Intellis, Fall 81. At Black Mesa, near the Four Corners area of the Hopi Indians, USA, a scientist studying thunder storm occurrence, using computer analysis, noticed an unusual number of storms occurred in that area. She was told by the Hopi of the area where the earth breathed, emitting air as the moon affected the groundwater tides. This air proved to be heavily charged with negative ions, which may have initiated the thunderstorms and ant rain. Of the breathing of the earth, there has been little study, although it was regarded as a known phenomenon to tribes people. The earth must breathe, by at least these processes. Asterisk the movement of burrows in their tunnels. Asterisk the movement of groundwater by tides or replenishment of aquifers, often seen in wells, especially near coasts and lakes, and asterisk the evaporation of moisture from soil surfaces by the sun. 8.22. Designer's checklist. 1. It is a primary design strategy to prevent topsoil losses and to repair and rehabilitate areas of damaged and compacted soils. 2. Permanent crop, soil bunds, terraces, and low tillage systems all reduce soil and mineral nutrient loss. 3. Soil rehabilitation and pioneer green crop should precede other plant system establishment. 4. Adequate soil tests, plus test strips of crop examined for deficiency or excess symptoms, leaf analysis, and livestock health should be assessed to guide soil treatments. 5. If soil types can be specified, fencing, cropping, and treatment should coincide with these specific soil assemblies, and specific crops for such type researched. 6. Soil life processes need to be encouraged by provision for green crop, humus, mulch, and the root associates, mycorrhiza, of plants. A useful earthworm may need to be introduced. 7. Drainage, hence pH and soil water capacity, need specific treatment or assessment, and will largely determine crop and tree types. 8. Minimal use of large livestock and heavy machinery is to be recommended on easily compacted soils, as is burning and clearing. 9. Use pigeon and animal manure where major elements are scarce, as in third world areas. Also use of gray water and sewage, or wastes. Et. Fe equals 1 message. 4. EESL re. Figure 8.16. Soil creation, AC, and factors aiding erosion and mineral loss, DF. E. E. A. 10. Before draining waterlogged soils, recommend crops to suit this condition. Never drain wildlife habitats, fens, or bogs which are species rich. 11. Choose the right soil shaping or earthworks to suit crop, drainage, and salt threat. 12. Using an auger, check soils for house foundations. Using a wetted soak pit, time the absorption of gray water for sewage disposal at house sites. 13. Preserve natural, poor sites for their special species assemblies, pay most attention to human nutrition in home gardens, and select species to cope with poor soil conditions on the broad scale. 14. Fertilize plants using foliar sprays containing small amounts of the key elements, or pellet seeds with the key elements which are deficient locally. Pelleted seed and foliar sprays are economical ways to add nutrients to plants. 8.23. References. Cox, George W., and Michael D. Atkins, Agricultural Ecology, and Analysis of World Food Production Systems, W. H. Freeman & Co., San Francisco, 1979. Davidson, Sir Stanley, F. Alia, Human Nutrition and Dietetics, Churchill Livingston, Anyon. 1979. Dunley, D.E.T. Alia, Earth Resources, A Dictionary of Terms and Concepts, Arrow Books, London, 1976. Fairbridge, Rhodes W. and Joanne Bugloy, The Encyclopedia of Sedimentology 6, Dowden, Hutchinson. And Ross, Stroudsburg, PA, 1978. Hendrick, Kevin A. 1978, Food for Plants, Xero Soil Division, Australia. Number 6. 1978, What's Wrong with My Soil, Xero Soil Division. Number 4. 1979, When Should Water, Xero Soil Division, Number 8. Acidity N. Leeper, G.W., Introduction to Soil Science, Melbourne. University Press, Australian, 1982. MacDonald, R.C.F. A.L., Australian Soil and Land Survey. Field Handbook, Incada Press, Melbourne, Australia. 1984. MacLeod, Edwin, Feed the Soil, Organic Agriculture. Research Institute, Grayton, California 95444, 1982. Radomski, 5. W. Heidi Cass and Norman Pickard. Elements of Chemistry, D. Van Nostrand Co., Canada. Ltd., 1966. Satchel, J.E., ed., Earthworm Ecology, Chapman and Hall, London, 1984. Vanderwerf, Eric, Sustainable Agriculture in Southeast Ghana and the Agomita Project. Permaculture Number Newsletter, December 1985 and March/April 1986. P.O. Box 650 Number, QLD 4560. Australia. $3 per newsletter. Weir, R.G., The Plant's Nutrient Requirements, Seed and Nursery Trader, Australia, July 1979, pages 55 to 57, 1979. Yeomans, P.A., Water for Every Farm, second back row. Press, Lura, Australia, 1981. Alkalinity. Humid region equals. Mineral soils. Extreme range for most mineral soils equals. Chapter 9. Earth working. And earth resources. Moving of the earth brings harms and fears. Men reckon what it did and meant. But trepidation of the spheres, though greater far, is innocent. Own done. And did the earth move for you? 9.1. Introduction. Few people today muck around in earth, and went on international flights, often find I have the only decently dirty fingernails. For the soil scientist, soil has endless classifications. To engineers, it is a material, to potters, their basic resource, and to housekeepers, footprints on the floor, or part of the eternal dust. However we look upon earth, we will all return to it, and help create the soils our ancestors made, ruined, or form part of. Climate, vegetation, animals, and soil are intimately connected, and each will have influences on the other. It is a great subject, like that of water, and this chapter will concentrate more on its use in structural design than on uses as a growing medium. People, and other animal species, have mined soils and earth deposits for specific earth resources since their inception. Examples are animal migrations to salt licks, and specific dusting sites in which birds and mammals roll or bathe to rid themselves of parasites. People have used silica minerals, obsidian, chert, chalcedony, as tools, and have ground iron oxides or graphites as pigments for many thousands of years. Soils rich in iron oxides have long been mixed with acorn meals to fix the bitter tannins as insoluble ferric tannates, black breads, or to supply missing elements in the diet. There are several clays: illite, smeltite, kaolin, ferrous oxide red clays, traditionally used by tribal and modern peoples to absorb poisons from selenum species. Yams, to reduce diarrhea and digestive upsets, or to relieve feelings of nausea. Kaolin clay, although little work has been carried out on this factor, we should record all uses when specific clays are so used, and how they are combined with specific food to reduce or eliminate poisonous or unpalatable toxins from foods. Some earths may be eaten to supply trace elements, as clay and clay salt licks are commonly visited by deer, kangaroo, cattle, and antelope. Earth eating, geophagy, is a widespread and seemingly natural habit of children and tribal peoples. As well as clays, the white, mineral-rich ash of trees is widely used as a food dip at campfires by Australian Aborigines. Cooking food in clay is prevalent throughout the world. Earth working for agriculture and monuments has existed for at least 17,000 years. Mineral smelting, pottery, and peat or coal mining for fuels increased the scope of earthworks, and this was quickly followed by the development of large machinery intended to remove vast amounts of ores and fuels for modern industry, which built quickly from 1800 on, so that the last 200 years of our existence has seen the greatest development of earthworking and mining. The common use of self-transporting machines really dates from the post-war years, 147 and on, following the wartime development of track tanks, earth scoops used for airfield construction, and large pneumatic tires for this type of equipment. While civil engineers have to some extent kept pace with these developments, neither the public at large nor those in architectural or agricultural fields have fully realized the potential of earthworking machines in the modern sense. Our power to move the earth with modern machines is now almost unlimited. We can, if we wish, raise new 227 hills or plane off existing ones, and create or obliterate minor landscape features. Small earthworks are so immediately effective, cheap, and permanent that it continually amazes me that people will suffer local drought, sea winds, noise, erosion, or even flooding without spending a few $100s on a well-built and planted earth bank that would solve the problem. They will build expensive tank stands or towers rather than a cheap hill, and suffer death by storm and fire rather than make a very safe earth shelter for their families. It serves as an outdoor cellar. At other times, earthworks are necessary and ethical where they reduce our need for energy, underground housing. In deserts, diversify our landscape for food production, fish, culture ponds, permanently rehabilitate damaged contour banks, interceptor banks, save materials, house site design, or enable better land use, or help revegetate the earth. As with all techniques, it profits us to make as many uses of earth shaping as we can. It is shameful to see quarries, mines, and roads serving a single purpose, and usually left as a sterile system, when they could be shaped or planted to assist landscape diversity. A whole set of skilled and well-tried waste or soil reclamation strategies has developed as methods of stabilizing devastated landscapes, both for natural instability and the carelessness of engineers. An excellent handbook for those involved in such painstaking work, and one covering many climates and areas, is that of Dr. Hugo Skiachtl, Bioengineering for Land Reclamation and Conservation, University of Alberta Press, 1980. Cannot too highly recommend this book. For would-be earth movers, earth can be moved for productive reasons, many of them classifiable as landscape restitution, registered to create shelter, to assist with foundations, and to make areas level for floors. To terrace hill slopes for stable potty crop, wet terraces, or gardens. To raise banks or to dig ditches as defenses against flood, fire, attack, or wandering vegetation eaters. To drain or fill areas, to direct water flow or runoff. To create access roads to those places we commonly visit. To get at earth materials, ochres, clays, minerals, fuels. To make holes for any number of reasons and of greatly varying sizes, from fence posts to dams, wells to deeply drilled bores. To create special storages and enlarge living space, cellars and caves. To stop erosive forces carrying off soils, soil dewatering and erosion control. To prevent noise pollution, embankments, and to permit recharge of groundwaters, swales, and 228. We also move the earth to play and to plant. For all these reasons, we have devised handheld and mechanical diggers, ditchers, augers, drills, blades, buckets, shoes, rakes, plows, rippers, delvers, scoops, earth planes, loaders, rock cutters, draglines, excavators, and dredgers. We also move earth with explosives, hydraulic jets, and as an unintentional result of erosive processes generally. Erosion has itself been used to build soil terraces on lower slopes in more than one culture, but it is debatable if the terrace idea was not as a result of attempts to stop erosion before the idea of using erosion to create terraces later developed. Until the Second World War, earth was moved by sheer numbers of people by hand or horse and car, or by a few people working with wheelbarrows or baskets. Over a long period, all this has changed. Why put up thousands of mud bricks when a machine can compact a 6 to 8 m thick wall immune to flood, fire, and earthquake in a few hours? Or labor long hours over a hole when we can blast a fence post in a hard shale base for a few cents? In this section, one will not attempt to deal with large, complex, or precise civil works, those necessary for sewage layouts, the landscape excavations for large buildings, or large dams, ports, or aerodromes. Will instead limit myself to those on-farm, private, useful, relatively small, and rehabilitative or sustainable earth-moving systems that an individual might employ to shelter a house or to control water in a productive landscape. 9.2. Planning earthworks. It is best to plan all aspects of the earth-moving process before the machines or laborers arrive on site. 1. Make an initial decision where you would like to place the, e.g., road, dam, house site, drains, etc., using a contour map and plan if necessary. 2. Test the soil by auger holes, soil samples, and soil pits to determine if the soil is good enough to suit your plans. A good clay soil for dams is essential. Seek professional advice or do more research before deciding conclusively on placement. 3. Peg out the site, using a level, which can be simple or complex, a measuring tape, and a good many stakes, with red or white cloth attached, so that the earth machine can follow them. 4. Plan a place to store all the topsoil removed during the excavations. Never allow topsoil to be mixed with subsoil, but carefully remove it, to be later returned to the site as a growing medium and to stabilize subsoil erosion. To stabilize the site immediately, have on hand as many seeds and plant materials as needed. These can be purchased from a nursery or grown in pots on the site several months before the planned earthworks. See 9.3. Planting after earthworks. When soil is moved, it becomes loose, so that soil air space and hence total volume may increase to 145% of the original. Even when compacted by machine, the fill may occupy a space 10% larger than the cut it came from. Although conscientiously compacted clay in dam walls may settle as little as 1% over time, loose fill will eventually settle to 75% or less of its uncompact volume. This has great relevance to house foundations and wall stability. When topsoil is replaced over fill, the area should not be overcompacted, or we risk waterlogging, but when it is replaced over deep or solid subsoil in a cut, we will probably need to first rip or loosen the base subsoil to allow tube penetration, just as we need to rip old roads, quarries, parking areas, or heavily traffic filled before planting trees and meadows. To prepare a house site with drainage, we can proceed as follows. Asterisk careful survey. Place pegs outside the site. Call in the bulldozer. Asterisk strip off topsoil carefully and mount above and at either end of the site. Asterisk cut house/garden level. Use subsoil fill for access. Toads only. Asterisk call in digger or backhoe to cut foundation and drainage trenches. Pour foundations and slab paths. Place drains and pipes. Asterisk call in small blade and bucket machine, a bobcat or wheel tractor, to replace topsoil and neaten the side where needed. Some soil can be mounted to the windward side for hedges. Asterisk plant or seed all topsoil to prevent erosion. Asterisk fine tune with harrow, rakes, check drainage. 9.3. Planting after earthworks. Every time we move soil, we should be ready to follow straight on with planting or seeding. That is, we need to have planned the planting and stabilization of the area, and to have the plant materials on standby to implement our plan as soon after disturbance as possible. There are 2 reasons for this. 1. To prevent erosion, which can be severe on bare slopes at only 2% slope, especially in rains, and 2. To prevent invasion by unwanted volunteer plants, which may become difficult to displace later. If a full set of ground covers, pioneers, and long-term plants can be set out in new earth, a great deal of time and work JS saved. A broad-scale scatter of mixed seed, raked in, will prepare the way for permanent placements. We are most fortunate if we can immediately mulch bare soil sites with hay, hessian, burlap, or wood chips, to break the force of rain and to suppress unwanted weeds. If you have prepared for bulldozing, you have seed divisions, cuttings, and potted plants ready to go before the machine pulls out. Seed can be garden collected or purchased. Just scatter and if possible rake in. 5 ohm mixes that work in most soils. Asterisk sunflower, or mix parrot seed with sunflower, millets, pulses, chard, parsley, lupin, and clovers. Asterisk parsnip, fresh seed, salsify, daikon radish, turnip, all of these spike the soil. Asterisk bulbs of lilies, grape hyacinth. Asterisk roots of sunroot, comfort, chicory, horseradish, ginger, sweet potato, turmeric. Asterisk divisions of bamboo, bandagrass, pampas grass, aloes, agave, New Zealand hemp. Asterisk seedlings or sets of elephant garlic, asparagus, globe artichoke. Asterisk cuttings of small fruits, elderberry, willow, poplar, mulberry, pride of Madeira, Echin fastiosum. Asterisk tubed seedlings of acacia, prosopy, tagacist, New Zealand mirror plant, coprosma, pines, eucalypts. Shrubs. All compete very well with self-sown weeds, and, with very little help or none at all, establish a varied and useful early and perennial crop system. A few annuals self-sow and seed down another year. Many species can be further divided or cutting set out, and sticks can be set at the perennial so they are easily located. Excess grass is cut back in the following years. Clover can be late sown FO allow vegetable seed to get away. Grasses are not sown, but will invade if spaces appear, and can be grazed by geese in a few years. Failed plants can be replaced with successful. Preparing a house site. Careful soil shaping provides many benefits to a house site. Plants late in the cycle. It is always an advantage to smooth finish banks and surround so that a mower or scythe can be used until the selected plants take over. Trees are a danger on dam walls, if they fall, and they often do in those conditions. They take part of the wall with them, but bamboos, ginger, sweet potato, pepino, and clump grasses assist bank stabilization. Trees at the base of walls are advantageous in shading, removing water, and reducing weeds. The net and pan planting pattern of figure 11.84 is an effective control in overgrazed, eroded, mined or bulldozed sites. If tires are available, the pans can be made from these, filled with mulch, and the diversion drains let in above the tread level. For people with access to logs, these can be staked cross-slope, on a slight downhill grade so that water is made to zigzag across the erosion face, and hence absorb into the even small logs and branches, pegged across erosion channels, build up a layer cake of silt and leaves, beside which can be planted willow, acacia, or any other fibrous rooted and hardy species, which then act as a permanent silt trap. Mulch behind logs and barriers quickly stabilizes the seedbed for planting. Fallen leaves and scattered dung also accumulate in these many diets to provide plant nutrients. Small wire netting fences, with stone-weighted hay uphill, will trap silt and spread water, as will cross swales of lemongrass or vetiver grass. On very steep slopes, there is often no recourse other than to plant pampas, bamboo, lemongrass, and root mat pioneers, and to make upslope plantings of chest, nut, acacia, carob, olive, or other large species which will cascade seed downslope over time. Where implements such as 5-chisel plows can be used, these are effective in erosion control. Plant chiseling and planting makes a permanent and stable change on hillside. Details on gully control in drylands and in tropical humid areas are given in subsequent chapters. 9.4. Slope measures. Slopes are measured and expressed in several ways. First, the slope can be measured as degrees from the horizontal, or the base angles of figure 9.2. This is expressed as a slope of 15 degrees, and is sometimes used by geologists to describe the dip tangle of rock strata. Next, the 90 degrees between horizontal and vertical can be divided into 100 parts, and expressed as 4 centages, a measure used by engineers. Finally, slope can be expressed in proportions or ratios of base to height, e.g. 1:4 is a slope 1 unit high, with a base 4 units long. This is the rise of slope over distance, often used for drains and pipes, in units used by hydrologists. Many irrigation drains use slopes of 230. Slope measurement. Slope predict day percentages, or proportion, 45 degrees equals. Underscore gravels, I-15 copyright 33.7% 377. Free drain clay, 1:2 plus 265%. 245%. Pag. Sands. I-3 I-4T. O20-5 F degree. I-414 asterisk. Figure 9.3. Slope measurement, proportions. Lila Bernlow and say for stable rest Queaton slopes angles over a 1:500 to 1:2,000, or a fall 1 minute 500 to 2000 m, and these are referred to as grades, figure 9.3. Coarse slopes are often expressed in degrees, low slope drainage across slopes as a proportion, 1:2,000. Any unit serve for or degree measures. There are suitable irrigation grades for soils and drains. Fine sands need very gentle drainage slope, 1/2000, and earth cuts in sand need an easy angle of rest, about 1:4.5. Table 9.1 makes clear some slope implications. Stable natural foothill slopes are not straight but down curved, concave. When building a road, it is well to remember that they will achieve a concave curve by slump over time, so it is best to cut this curve. Figure 9.4. Concave slopes. A. These duplicate the natural slump concavity of soil and are more stable than straight slopes. B. Straight slopes can be expressed as degrees O inclination or ER. BEAP4O dy. Figure 9.5 Outbanks. Slopes cut to dry out roads. Trees or steep banks to sunward may keep roads muddy in what climates? Into the slope to start with. Natural lower slope faces in humid areas are also down curved, and should be made to curve down or to be concave. Earth banks will assume this profile in time, indicated by a dotted line in figure 9.4. Soils have type-specific resting angles with concave profiles. Slope angle, the dotted line, is therefore a straight line approximation of real slopes. The notch at the top of a cutting runs water off the face to safer slopes, and is a standard feature in embankment stabilization. Average safe slopes used by engineers are asterisk gravels 1:1.5, asterisk clay, well drained, 1:2, asterisk clay, wet, 4. To dry road, the sun side should be cut further back, and so allow sun in. Conversely, to shade areas, banks can be as steep as the soil will stand, figure 9.5. When we cut or bench into a slope, the natural erosion processes try to re-establish the original slope. Fabi 9.1. Some features of coarse slopes, given as percentages. 100 vertical bank, safe only in stone or very dry. Stable sediments, soft rock. Vertical bank, the walls of dry desert dugouts. In stone can be quite stable at the slope. Precipitous. Safe only in stable rock or loss. Precipitous, safe only in stable rock or loess. Very steep, a bulldozer can be used up or down, not on the traverse, cross slope. Very steep, 1:1 proportion or 45 degrees. Strictly not. For tree clearing, needs permanent forest. Steep, the maximum attract machine, bulldozer, can safely traverse and work. Steep, as above, can be cautiously harvested. For firewood or coppice, also benched for and sent. 6. 8. $388. 8. Access. Moderate, usually accepted as the maximum slope for safe cultivation and erosion control. Wheeled tractors are used at about 18%. The maximum slope of good road surfaces is AC. Except as 1-3%, anything over this should be concreted or sealed. 10 moderate, may need contour banking and careful use, 4-6% is considered ideal for rail roads, without special cogs or cables, to assist the grip of the wheels. Low, can erode if soils are cultivated, but these slopes are usually stable for crop agri. 0 to 10. Culture, terraces, and swales. And if left to their own devices will do so. Benching at the base of sloping and unstable tilted strata will therefore bring down the whole hill, and incur endless cost in mad clearing and slump removal. Slumps in unstable hillsides will carry with them, or bury below them, houses and people. A great many film stars perched on unstable ravine edges in the canyon systems of Los Angeles will, like the cemeteries there, eventually slide down to join their unfortunate fellows in the canyon floors, with mud, cars, and embalmed or living film stars in one glorious muddy mass. We should not lend our talents to creating such spectacular catastrophes, but to the avoidance of obvious problems and by relocation before disasters occur. Lake Howe government often delineates areas of instability where building is not permitted due to mudslides, fire, and earthquake. In the dry hill scrublands of California and France, or on desert borders, intense fire upslope can generate sufficient heat to hexagls. When such fires occur in steep, unconsolidated shales and mudstones, the baked earth, heated to 6 centimeters deep, forms water-sealed slab surfaces. Such hydrophobic crusts will no longer form crumb structure. Valleys in such areas can then expect catastrophic mud flow unless early misty rains fall to restart vegetative growth, and to that end the ashes can be sown down with oat, lupin, and shrub seeds. But if 231. Table 8.2. Mass movement of soils. A. Avalanche. B. Landslide. C. Slump. And D. Debris flow. E. Earth flow. F. Mud flow. G. Soil flow. Slide. 1. Rock fall. 2. Rock slide. 3. Talus shift. 4. Rock creep. 5. Soil creep. 6. Frost heave. $end. Flow. Quick clays, fine lake sediment, and quicksands may liquidly in earthquakes and become colloids. Heave. J. Heavy rains fall before plants take hold. Water can penetrate below the glazed surface, and mags move. Ment. Bulking of mud and glaze will then occur. The wall of mud effect, and the inevitable cascade downhill may well block roads in any such mud flood. Emergency, threatening resources in the valleys. Mud flows are a feature of unstable sediments in wet dry climates. Thus, the water runoff after fire, as in Adelaide, Australia in 1984, can be catastrophic, and hot fires can have a long-term effect on soils and soil joss. The combination of fire in late summer, followed by a sudden autumn onset of rains is typical of Mediterranean lands, and of devastated soils. For a designer and town planner, areas of known soil instability should be avoided as settlement sites, and kept in permanent forest. Most are designated on soil maps, or can be researched. 9.5. Levels and leveling. Levels are taken to ensure that spillways work, drains run, and houses sit level so that one can play at marbles without them all falling towards one corner. There are tools of leveling, of which the most fancy and even the most reliable is that level assumed by the surface of water. One can always check a horizontal against the sea horizon, or make sure a drain 232 or gutter works by using a little water to flow down it. Even sophisticated instruments like the theodolite use a bubble level to set up the base plate, and then to check the telescope against this with its bubble before proceeding with tilt or swivel measures. There are a few simple levels that can be handmade and are of great use to farmers and homeowners. Hose, bunyip, level. A hose level can be made from easily purchased materials, and is useful to survey some meters or even kilometers of diversion. Drain, level a house site from comber to comber, or 5 ETA. Wall or spillway at a predetermined level. The materials needed are, as put together as in figure 9.6. Asterisk 20 m, 65 feet, or so of clear plastic hose, diameter about 10 millimeters, 1/2 inch. Asterisk 2 corks or stoppers that fit into the ends of the clear plastic tube, each with a breather hole. Asterisk 2 small cork balls that freely fit inside the clear plastic tube below the corks, optional. Asterisk 2 stakes, 2 m or 6.5 feet, marked with the measurement of your choice, centimeters or inches. Dressmakers tapes glued or screwed onto the stakes serve this purpose. Asterisk 4 clamps or tape to connect the clear hose to the stakes. To prepare for use, uncork one end and fill the entire hose with water. Be sure all the bubbles are out of the hose. This is only certain with a completely clear hose. Place both stakes together, tops level, on a piece of level concrete or wood, keeping the stakes vertical. Mark the water level in the clear tubes by unclamping and moving the measuring strips until the water level, or both cork floats, are at precisely the same measurement marked on the stakes. Recork the tubes. In the field, one person walks past the other, alternately, driving a stake every 6 or 15 m, 20 or 50 feet, to guide diggers or machine operators, and allow ing for the rise, or fall, of drains by allowing one cork ball to be an inch or so lower than the other at the next peg, moving the pole up or downhill to achieve this. The stakes must be kept vertical when measuring. 1 centimeter in 5 m is 1:100 x 5 equals 1:500 fall, ample for most diversion drains to carry runoff to dams. Dead level lines can also be run across landscape and dam walls checked for level, or, if used for roads, a gentle rise. I recently saw a 12 kilometers drain flowing gently all the way in sand at 1:2000, laden not by a skilled surveyor, but by 2 women hired for a week and trained in 30 minutes on a hose level. The plane table is a sturdy tripod which can hold a U-shaped piece of plastic tube or glass, corked and bubbled as for the hose level, except this can now be swiveled about to side in all directions. Figure. Sealed ends with small heel clamps. Fit ball with plastic bubbles. Clear tubes. 4 2 equal mid bikes. Figure 9.6. Bunyip hose level. Used by 2 pp, about 15 mf around a hill, apart FO peg out a can 4 fine. 9.7.b. Lacking tubing, a bowl of water on which floats a piece of painted wood with 2 nails of equal length. As sides will do, figure 9.7.a. Although model B is self-leveling, it may be necessary to tap in one nail a bit on model A by way of adjustment. To check a plane table, set up 2 marked stakes with easily visible white masking tape, a little uphill from the point you will stand at, driving the tops to level using the table. Viewing the stakes from position B with the plane table, check that the level shows new level marks, B, to be exactly the same distance, D, below the stake tops. Measure this. One can then proceed to level, from position B, anything that can be staked, painted, or nicked by another person, figure 9.8. This is a very handy across valley level to set in siphons, or to find out where the outlet of a dam will send water by pipe and gravity flow, or to see if a hill on which you want to place a tank at a distance is higher than your shower head at home. Leveling need only be done once if done right. If in real doubt, buy a dumpy level or theodolite, and read the instructions, or if wealthy and incompetent, hire a surveyor, whose real job is mapping. Thousands of miles of drains have been surveyed, and levels set, by very simple tools. Plane tables of various designs are used by surveyors, but these usually include a telescope. For long distance work, Ralph Long of Australia has devised a tractor mounted level which he has successfully used to cut the figure 9.7. The plane table. Simple water tables can give sites achnous valleys or overlog. Figure 9.8. Measuring for accuracy of the plane table. 2 sites and 2 pegs check on accuracy of a level. Drains, using the tractor itself as a check on levels. This is a bubble level which can also be fitted to any vehicle on farms, and is called the long inclinometer registered. Permaculture Journal number 22, 1985. Bay frame. This is made from two wooden or metal legs, nailed or welded firmly together at the apex, and fixed about 2/3 down their length by a welded or nailed and glued crosspiece. A plumb bob or weight hangs from a cord at the center of the apex, and a mark is made on the crosspiece at the cord line. The A-frame is then reversed, and another mark made where the cord touches the crosspiece. The midpoint between the two marks is the point where the cord hangs when the feet of the frame are level. Figure 9.9. In use, a person swivels the frame about one leg, and sets in the second leg to the place where the cord hangs. Vertical. A peg is put in, temporarily, to judge where to place the next leg. Many meters of drain have been set in using the frames, often made on the spot from lumber, cord, and a weight for the plumb bob. 9.6. Types of earthworks. Banks. It is cheaper to construct a bank than to step or retain the earth, if the bank can be made stable. Wherever a four-way bucket, bobcat or draught, or power shovel can be used to dish the bank, they will remain stable at greater slopes than a straight cut, as we have frustrated soil slump by giving it the profile it would achieve had it slumped. Banks or cuts of more than 4 m high need careful stabilization. Unlike dam walls, cuts for roads are not normally compacted, nor do they necessarily have much pressure on them. The greatest cause of slump is water flow through or over banks and the lie of strata and shaly. Fosti Inso. Conscience ONL. Figure 9.10. Essentials of water and soil slump control. Many methods can be used to prevent slump from cuts above terraces or roads. Vegetation helps all these systems. Figure 9.9. About 2 m wide, legs are reversed so that plumb line cuts. Level mark. On crossbeam. Used for centuries to lay out contours and dray. Desired slope or flow rate. Fiat drains at I. Fnger GEDS minimize runk FE Cosic. Figure 9.13. Kickdown systems and steep terraces. Using steep slopes to assist the movement of nutrients and water. 234. Figure 9.11. Benches on steep slopes. Trees stabilize bench areas, fill, or slope. Offer 900D harvest and access low sleep slow Georges. Figure 9.12. Benches cut into hillsides on contour ground. All normal soils with some clay and stony banks are fairly stable, given that the angle of rest of these materials is preserved. The banks cut somewhat concave, and drainage fitted. In severe slump areas, rerouting of roads or expensive drainage and concrete retaining walls may be last resorts, but figure 9.10 shows the essentials of water and slump control only. Some may be needed, but all can be used. Benching. A bench is a flat, near contoured cut made in a slope. Very severe slopes of 30 to 40 degrees can be bench cut if a bulldozer can start on safe ground, typically from a ridge of 20 degrees or so. Benches are used to make roads and house sites, and are very useful in jank-term forestry if a steep hill is benched every 100 m or so. Figure 9.11. Benches greatly aid access, planting, and eventually harvest. The first fast-growing trees to plant are those on the lower, loose soil side of the benches. These can be nut or fruit trees for harvest or for seed crop. Small hoiters on very steep hillsides must work with the slopes, or expend much energy on carrying water and fertilizer. Orchard and mulch about poultry above garden is the easiest system. All the better if the ridge or hill above that system is planted to mulch producing trees such as casuarina and pine, oak, and beech. Thus, mulch and bedding is thrown downhill as green feed and seed for chickens, and they kick down to the lower fence where the gardener accepts the manured and shredded mulch for the essential terraced garden. Thes. Os. Mel's. Beds. Figure 9.13. Benches can be fertilized, ripped, and sown to legumes or soft-leaf mulch plants, and periodically cut or grazed off. If cut, mulch can be raked to trees on either border. As benches on very steep slopes will rarely be traveled upon, they can slope slightly out wards to drain. Benching should not necessarily continue across water runnels unless pipes, pabions, or culverts are fitted in the watercourses. Small watercourses can be bridged. Benches are quickly made to a survey line pegged every 6 m, 20 feet, or so, followed by a bulldozer with blade set to side cast, angled. A run with a raised blade will shave back or slightly step the uphill bank. In stable soils, benches can slope into the hill and so form swales to infiltrate water for trees below the bench. Cross walls can be made every 20 to 30 m to prevent gutter flow. Such benches are not so much roads as tree shelves, and are a blessing in steep country. A quiet traverse with a donkey or cart serves to distribute plants and fertilizer, or mulch, and to gather in the crop. Narrow, 1.5 to 3.0 m, benches are quickly overhung by tree crop, shaded, stable, and accessible. Figure 9.14. Wherever benches cross drainage channels, pipes or rock-lined swales must be made to carry water across. And these, and their maintenance, are the greatest long-term expense, so they need to be well made and durable. Although the true finesse of earthworks is best and trusted to the experienced machinery driver, designers need to designate stages, spoil areas, topsoil stores, bank slopes, and so on. Also, they must remember that it is expensive for a bulldozer to travel far pushing a load before the blade to create banks, about 6 to 9 machine lengths is maximum, and that much faster and better work can be done cross-slope and downhill than upslope by any machine but a bucket digger. Side casting is a different matter, and graders and bulldozers both can bench soils effectively for miles, as no dirt is carried but rather cast out to one side of the blade, which is angled to the direction of travel to do so. Thus, a great deal of time, fuel, money, and timber can be saved if a side is carefully pegged out FO suit the machines called in. Imagine yourself as a driver, and make it as easy as possible to cut the shapes you want. On anything but a simple job, 2 or more machines may be called for, as in preparing a house site and its sewage lines, or in digging and carting a clay deposit. Bulldozers can loosen and pile up material but not load it, bench but not trench, of at least not smaller than the blade width. Terracing. Terraced lands, given a reserve of local green manures, or compost and adequate water, are potentially very stable production systems. Exceptions to this arise when we attempt to terrace in unstable soils or sediments. Risk hydraulic pressures on hill slopes from impounded or infiltrated water. Create terraces that are unstable at the bunt or wall face. Asterisk extend terracing as annual crop over too large a proportion of the landscape, and so lose leaf or tree nutrient input to crop, and asterisk make very large series of terraces in high rainfall areas, so that runoff is concentrated. 7. With a useful assessment of the above factors in to exclude animals. Horizon bank AE. With health and turin. PAXKAS of goop. Soil with hatroseed. PLAMTS. Figure 9.14. Road cut on mild slope. Benches greatly assist slope access if well drained and stabilized. Praying for surface abnor. Concave face. 236. Mind, we can gain long-term production from short series of polycultural terraces, wet and dry crops, with stable bunds, either rock walled or at a 1:3 slope. Trees on bunds and between, above, and below terrace series should form 40 to 60% of the total landscape plan. And both soils and installed water inlets and outlets should permit safe and controllable irrigation. The great benefits of terraces are these. Asterisk very easy crop access on slopes. Asterisk easily controlled and effective irrigation procedures. Registered minimal swat. Loss due to overland water flow, or to slope cultivation, and asterisk a potential gain in silts or nutrients in irrigation or runoff waters and from leaf fall. As with dams, terracing is most effective where slopes are least, as earth moved versus area of crop land developed becomes impractical or inefficient as slopes steepen. At about 30-degree slope, but preferably at 10-18, terracing becomes worthwhile. Terrace construction always begins on the lowest terrace level, with the removal and stockpiling of topsoil over the whole area of the lower terraces, and proceeds uphill as each terrace is made, so that the topsoil of the next highest level is cleared onto the preceding lower terrace. Stockpiled soil at the lowest terrace is finally carted or lifted to the last of the series. Uphill, figure 9.15. Underscore. Every terrace system is ideally designed to allow perennial bund and terrace wall plants, specifically for wall stability and green manure crop. As for the extent and series size in a terrace system, it is wise to limit both on the basis of asterisk heavy rainfall, hence expected runoff, in tropics, and expected rainfall harvest in arid areas, where total terrace areas should not exceed 1/20 of the catchment harvested, and where perennial or adapted crop, never water demanding crop, should form the selected species. Thus, all terrace systems should aim to occupy no more than 30% of tropical or 5% of dryland areas, and in the tropics tree crop should be developed to maintain fertility of the terrace areas. Water catchment areas should be developed to do the same for arid areas, so that runoff brings leaf mulch to terrace slopes. In humid cool or tropical areas, wet terraces, 10 to 20% of all terrace areas can be devoted to a fish plant polyculture, giving yields of fish, shellfish, and water plant products. Yields of protein from water cultures 10 exceed all land-based systems if managed at the same levels of husbandry and care. Wherever people occupy very steep sites, slopes of 20 degrees or more, especially in areas of high rainfall, it is preferable to abandon broad terracing for a series of 44 narrow production terraces, each series carefully drained to spill excess rain down permanently. Vegetated slopes, figure 9.12. Thus, by ridging the terrace tips, mulching paths, and staggering path spills in short series, we can get the advantages of terrace on quite steep slopes without risking erosion and soil loss. Needless to say, machines are inappropriate for such construction, and steep slope terracing of this nature is always hand cut. 9.7. Earth constructs. Wherever earth is dug, banks are raised. There is not a great concentration on the holes, and far less on the mounds, so that spoil in mining becomes a pollutant. This need not be the case, providing topsoil is first removed. Figure 9.15. Terrace series. Siege of garden terraces of sand provide a total growing surface. Maximum height. Between terraces. Zemetra. 237. And then return to cover the spoil, in stages or as a whole job. Just as land can be hollowed out, so roads and banks can be raised above marsh or flood levels, and due to deflect winds, noise, or water. Banks raised by machines can serve the following purposes. 1. Shelter for houses and fields. 2. Plant sites for windbreaks, on the crown of the bank and in its lee. 3. Walls of houses or storage barns. 4. Containments for large inflammable fluids, and ng. 5. Noise deflectors and absorbers, e.g. at airports and along highways. 6. Tracks and plant sites in marshes and on clay soils, subject to flooding. 7. Patterns to deflect and direct wind and water to storages or energy systems, flood or tide control systems, polders and levees. 9. Railways and road grade adjustment. 10. Earth ramps and stands, and 11. Earth walls or ha-ha fences. These are further elaborated as below. 1. Shelter for houses and fields. Either in flatlands or on high exposed sites, an earth crescent bout into the cold winds is the fastest way to create shelter and warmth on its lee side. Even a few blade side casts run along a field boundary provides cover for hedgerow and windbreak species and may act as a figure 9.16. Raised bank beside house. In areas of heavy rains, house sites must be carefully designed to swale for root water collection. High banks of 2.5 to 3.5 m, 9 to 12 feet, close behind house sites, whether excavated or raised, create instant shelter over the occupied site. Shelter which may be further reinforced with trees. Figure 9.16. This is a long-term and considerable heat energy saving in cold climates, and a shading or cooling wind director in warm climates. Figure 9.17 shows an actual ground design for a flatland site with cold southwest, hot northwest, and cooling northeast winds, all controlled by one earth bank and the pond formed by the excavation. 2 plant sites for windbreaks. Low side. Casts heap up topsoil, create shelter, and catch or delay runoff, as well as reduce root competition for a year or 2. All good reasons to side cast for long windbreak sequences, and in wetter ground to establish willows, poplars, and tamarisk above waterlogged ground. Figure 9.18. 3 house or barn walls. Unrealistic by most architects and home builders, machines exist which can raise and compact a complete house or barn wall in a morning's work. All we need to add is floor and roof. Another 2 days' work, to be in a long-term, fireproof, silent, energy-conserving, and sheltered house. This technique is suited to open space situations, cheap barns and large outbuildings. As the walls are raised, a smaller tractor and roller can compact them. Almost any earth will do, providing the compacted rest angle is washed. This technique is not suited to sands unless Wall corners are bagged, stabilized with soaked bags. Dry W. CAISM or. Deflect downhill over land flow. Figure 9.17. Raised bank around house. This structure modifies several external climatic factors and achieves privacy. 238. Figure 9.18. Banks for windbreak assistance. Shelter, floodproofing, fireproofing, noise reduction, and drainage. Adjustment. Filled with cement and sand or sandy soil. Figure 9.19. For containments. Whether for inflammable fluids or as fireproofing, and especially effective against radiant heat, earth walls can surround tanks. Above ground wildfire radiation refuges in bushland are earth covered and may be built off forested roads and near isolated bush houses. 5 noise deflectors or absorbers. Traffic. Noises are effectively blocked from housing by earth walls, and plants on these banks decrease noxious fume effects. Deflection of noise is effective for long wave length noise only. 6 tracks and plant sites in marshes. Earth banks, islands, and mounds in marshes give multiple opportunities to access and place trees and structures. Mounds and ponds isolate useful but ram patches species such as thorny blackberries and runner bamboo, while banks allow foot or vehicle access across and into marshes to place and service duck nest boxes, to harvest fruit and vine, and to attend to fish ponds. Figure 9.20. The raising of a bank in marsh is an interesting operation. The best tool is a very light swamp tractor with wide tires or tracks and a swivel bucket, an excavator. This unit, perhaps using mats in very soft or silty ground, can dig and raise an earth bank where the ground is too soft for the operator to walk. Equipment can be light for the first crossing, the aim. Figure 9.19. Earth compacted wall construction. Using modem earth moving equipment, a house or barn of this type can be completed in about 3 days. WIP. ATAM. Win PBREAK. ALM. I. RITAUE. APATT. NAPAIL. SEPT. PS. RA. E-root. NA. GLY. CMA PS. NN. BMOUS. Figure 9.20. PE stead and islands in marshes. Useful structures in and around water provide niches FO. Plants, animals, and people, */ being mostly to throw up a broad earth mound to dry out, so that a safe transit of heavier equipment can be made at a later date and a substantial bank raised for a roadbed or planting. It is easier, of course, and less harmful, to first raise banks, and then create a marsh by building a low berm. Natural marshes need protection for their unique values and for waterfowl. Mats are 3 bulky wooden gratings, made of 10 cm by 15 cm, 4-inch x 6-inch, timbers, which the bucket machine stands on. At each move the machine itself recovers one from behind and places it ahead. Once the first mound is built, larger excavator machines can reach out to dig deep channels and build high banks of great solidity, or the smaller mound can be leveled by light tractor for foot traffic. Are not really an alternative in mound building, and in timbered swamps are wind and water deflection. Figure 9.21 illustrates a design based on older Afghan mills of a Sadi or ridge wind tunnel for mill power systems. For water diversion are discussed in Chapter 11. 8. Flood and tide control, polders and levees. Well-maintained earth banks are the only protection of houses and villages in floodplains and below tide level. They are, in effect, reverse dams, the inhabitants living inside and the waters contained outside. Mounds can be built as flood refuge islands in many deltaic areas, containing storage barns and refuges in fields subject to periodic flooding, dangerous to people or animals. Causeways of earth are often used to access low mounds or islands near shore. Bangladesh and other deltaic areas need wooded refuge mounds just for the survival of POP. Such mounds can also be made in fire-prone sites, where villages and houses are safe in lakes or on moat islands. Peninsulas should be included in dam construction for this purpose by designers. Figure 9.22. 9 rail, canal, and road grades. These common banks and cuttings are all well known to all of us. 10 earth ramps and stands. Earth ramps and stands are of great use for at least these reasons. Asterisk to unload trucks from the side or back, heavy objects and will be these. Registered to load cattle to trucks, at various levels. Asterisk to unload hay or bales into the upper floors of a barn for use at lower levels, and registered to load and unload boats into water. Once built, they are permanent in use, and sometimes a whole district can use the facilities of one unloading ramp. The loading face itself must be stabilized with stand-at concrete or beams. Figure 9.23. 11 earth walls or ha-ha fences. The ha is a below-grade ditch, which acts as a fence. It is used in classical vista gardens where views are to be uninterrupted, and in zoos for direct viewing of large and potentially dangerous animals. It is also a defense for villagers against stock where the resources do not allow wire fences, but labor or a machine can be obtained. It is essentially a deep pit, dry or wet, with one steep wall faced by stone. Figure 9.24. It can be scaled T and size for the species excluded. The same machines that build roads will also build wetlands, swales, and small dams suited to wildfire control and wildlife. Underpasses and guide fences allow migrating wildlife to cross road and railways without accidents. Roadsides can be an area for the preservation of bunch grasses, sagebrushes, rangeland, and meadow plants, and remnant forest along their way, with pullover areas and vegetation maps, geological features, and archaeological or fossil remains clearly. TLA and a vertical AGS wind machine. Figure 9.21. Ridge wind tunnel for mill power. Walls of trenches on hilltops, sphere wind FO Mealy's and Ardurav systems. 246. Indicated. Such planning must precede actual construction. We pour kilometers of black bitumen surface, but fail to lay under it pipes for heat pumps that would heat the towns through which the road passes, and we fail to harvest and store road runoff for local irrigation and wetlands. All this will change only when well. Figure 9.22. Polders and levees. Off 0H. Figure 9.23. Earth ramps and stands. Cheap and permanent ramps ensure easier load and unload operations. Intentioned people govern the spending of public monies, or when road engineers are trained in permaculture, and look upon roads as a community resource. 9.8. Moving of the earth. People have always moved earth, to reach water in dry riverbeds, to mine pigments for their decoration, to excavate food, as bulbs, grubs, or fungi, and to bury their faces or their dead. The archetypal 2 is the digging stick, which gets food of greater variety and more nutrition than the spear. The basic hoe, rake, and shovel exist today in most cultures. Hand tools have moved most of the earth we see. Today shaped into mountain rice terraces, there are some very useful and cooperative ways to dig, effective in making miles of foul irrigation banks or uni. Gravels, the two-person shovel is useful here, one digging in, the other pulling over in a seesaw motion. Figure 9.26. Try it, and be surprised at how rhythm and cooperation will move mountains. Sing a little tune to pass the time and get the rhythm down among the dead men. Let me eat, etc. However, the exigencies of education have meant that designers and architects have seldom been personally involved in earth moving. A brief description and nomenclature of machinery and modern tools is not only needed but essential to earth design, given that when we move earth we should do so for permanent and beneficial ends. We can revolutionize eroded and arid landscapes by commencing the process with tools and consolidating it with life forms, especially trees. Earth moving machines. Justified, there are hand tools suited to particular ways of much used in areas where post and wire fencing AENG ones unavailable or haha fence. 241. Figure 9.25. Design for road enhancement. Roadways, roads can provide energy, inlets and conservation. Biological planners can make many productive accessories to plantings. 242. Digging, so there are large machines suited to special landscape tasks. Any of these can be supplanted by human labor where it is plentiful. The basic earth moving attachments are these. Asterisk blade, can be mounted on almost any vehicle, or toad, includes B-blades or delvers. Asterisk bucket, for lifting and loading loose material. Narrow and toothed for hard ground, or of special shapes for drains. Asterisk bucket chain, for foundations, pipelines. Harrow deep ditches, underwater dredging. Asterisk scoop, can be horse or bullock drawn, or articulated on an hydraulic or telescopic arm. Asterisk ripper, for breaking up compacted soils, usually towed or rear mounted on tractors. Asterisk delver, for drains, often mounted on a grader, or towed on a frame behind a bulldozer. Asterisk spinner, rear mounted on a special tractor, a fast revolving disc of about 2 to 3 m diameter with peripheral buckets. Asterisk borers and drills, holes, fences, explosives, peas, wells, bores, and the like. Asterisk jet pumps, to pump out silt and sand in wet places. As well as these, there are explosives, which are of special use in marshes and swamps, and some special is tools for rock and swamp work, for mines, and for massive tunneling. A. Figure 9.26. The two-person shovel. A simple, non-tiring digging system for drains, gardens, and terraces. Our concern here, however, is for the common tools of landscaping and water storage or water channeling. Each has appropriate uses, although most can do something of what the others do. To take them one at a time. The blade machines. The blade earth movers are the machines for leveling and benching or terracing, and ideally they should be able to lift, and drop, angle, and tilt. They can be mounted forward, bulldozer, in the center, grader, or at the rear, wheel tractors, for leveling. Tilted, the blade can make shallow V-ditches, or put crowns on roads. Angled, it spills earth to one side as steering whales, or makes long shallow drains. Blades are ideal for leveling house sites, for terraces, for benches on hillside, for side cutting roads, and for pushing up earth walls. Even a small tractor, 17 to 25 HP, patiently worked, can make very large dams and terraces at less fuel cost, but greater time cost, than a bulldozer, while large bulldozers are the most economical of time. They can work difficult, steep, or stony sites and move very large objects such as boulders. The bulldozer is a blade machine, mainly for pushing and planing earth. It is of greatest use in roading and for dams. It is an excellent machine to put up, roll solid, and spread earth, to dig large to low holes, move small hills, and bench. The blade tilts for road crown slopes and angles for casting aside windrows of earth. It also lifts to spread and release loads, and drops to delve out drains and ditches. Angled blades are used in long runs to cast earth out continuously to one side, called side casting. Tilted blades are used to cut channels or to bench slopes, and lift is used mainly for piling up or leveling loads. Blades are normally forward mounted for sight and control reasons, but on that special road machine, the grader, the blade is mid mounted to give even spreading, and on small farm or wheel tractors are often rear mounted. Some small blades rotate about their axis, 180 degree swivel. The grader can be used to make jong drains of shallow angle. These are miscalled spoon drains, but are effectively more angled than spooned in section. Thus, for all normal bench work, a bulldozer is useful, and for long flat road or leveling runs a grader is better. A scraper is a large, self-filling bucket or land dredge which can both fill and empty itself to plane off or dig out large areas. All large machines can now be laser guided to accurately level and grade fields at a preset slope. Lasers can also automatically work the hydraulics to lift and drop earth, but land forming is mainly restricted to large flattish irrigation areas or civil works, and is normally contracted out to specialists with large machines. The four-way bucket. This machine, sometimes called a draught, combines all four motions of lift, dig, push, and pull, and is a 243 E. A loss AEIG. Elevation. Elevating scraper. I equals 7. Figure 9.27. Large machines. On many machines, tilt, angle, and lift blades enable accurate work on roads and drains. A selection of blades and systems are shown. A. Grader. B. Delver. C. Spinner. D. Bulldozer. 244. Stoop, varying where i.e. trench straddle. Reedy abise. Rock bucket, for hard ground gravel, or loping. In chu arrie. For example, marshes stair. Geeshi. Side work. Reach digging and dumping. GPTH sides, 5 to 15. Wixinfo MTR AMIPO RT 1432 M degree. Figure 9.28. Bucket machines. A variety of land shaping operations can be carried out. Theus machines. Equals by bridging and universal machine between blade and bucket types. It is usually fitted to a bulldozer body, and is an excellent landscaping machine. It differs from some bucket machines in that it cannot swivel the blade separately from the body of the machine, nor can any of The above blade machines. It is sometimes called a clamshell bucket because it can close on loads of earth, or delicately pick up large stones, shave a curve in embankments, or fill a truck with soil. A small wheeled machine, the bobcat, is an excellent finishing tool or used alone for light work or for making swales in zones 2 and 3. Buckets. These can be simple and fixed or complex and swiveled. The former are often fitted to wheeled tractors as loading buckets of great use in quarries, nurseries, and anywhere loose material needs to be picked up and loaded to trucks at heights up to 4 m. They can lift and tip, but not swivel sideways. A very useful tool for drains, and as a tool in marshes, is the swivel or scoop bucket machines, which can scoop out, swivel around, and deposit loads. Some of these machines can dig wells to 9 m, 30 feet, using hydraulic extension arms, and all can dig sharp-edged pits or drains for special uses. They can normally reach out 6 to 10 m, 20 to 32 feet, and, standing on dry land, take silt from canals or ponds to reach out much further. There are two tools: the dragline, a giant fishing rod or crane which casts out a loose or tractor-tethered bucket dredge up to 18 to 24 m, 60 to 80 feet, and hauls it in full, and a two-tractor dragline, where one tractor hauls an endless rope with a bucket across greater distances than the crane dragline. Scoops are often used behind horses or oxen to excavate small ponds or clean out ponds of silt. Unless fitted with a rear spill door or chain tipper, they are very hard work to tip by hand alone, and tire one out quickly. A special tool of great efficiency in flatlands and on low slopes is the spinner, a large wheel with small peripheral buckets spun at high speed, which throw out the earth as small clods a considerable distance. They are much used in Holland to drain polders, and are the most economical and speedy machines for flatland, shallow drains. The spinner is one tool that distributes the spoil as small clods as it travels. There are therefore no banks beside spinner drains. A special trench digger is a chain bucket SYS 10 which continuously digs narrow trenches for pipelaying or to insulate foundations. Commercially, it is called a ditch witch registered or a trench wench registered. Augers and drills. These are hand or mechanical post hole diggers suited to most soils. Other uses are in tree and tuber planting, although care must be taken not to compact soils or to create water-filled holes in clay. The prime use is for posts and fencing at present. Augers have a limited lift, and are used to, normally, 2 m, 6 feet, or so depth. 246. Whereas drills which have extension tubes can operate to great depths. The borings are removed by liquid flushing or are simply compacted and tube-lined. Purely hydraulic drills work to great depths, and bores and hydraulic nozzles are often combined. Some of the largest vertical and horizontal earth holes, amines and quinats, were once hand-cut by primitive tools, and wells to 30 or even 60 m, 100 to 200 feet, are still hand-dug throughout the world. Special large bore bucket. V-bucket. Figure 9.29. Types of cuts and drains. Made by specific machines. Augers to 1 m, 3 feet, are used at mines, and most carry extensions to make a 2 m wide shaft. Very large pneumatic blowers are crane-mounted to remove loose materials, and are often locally made as at the Cooper PD opal mines in Australia. Large bore drills there are called Caldwells after the inventor and are used for underground housing, excavation, shafts, and tunnels. Up to 1.5 m 5 feet diameter. Explosives. Explosives are of most use to assist auger holes in hard ground, to make holes in otherwise unstable ground, such as marshes, or to loosen rock in quarries. With the advent of the swamp tractor, marsh blasting is less common, but the basic ease and effectiveness of explosives should not be overlooked where they can solve some otherwise intractable problems. Nitroglycerin, cellulose treated with acid, in glycerin, absorbed into wood dust or clay earths, as gelignite, dynamite, or plasticky is an inexpensive way to solve some earth-moving problems. Even cheaper is the mix of ammonium nitrate, fertilizer, and dizoline, known in the trade as chicken shit. Nitrates have from ancient times been gathered from manures around the soil of toilet pits, or extracted by washing and evaporation from guano. Old recipe books give dozens of reliable recipes for cheap explosives, and even custard powder, flour, or face powder will blow a room apart, as will the fumes from ether or domestic gases. Once worked as a scientific glass blower, and managed to remove all doors and windows from my room by allowing ether to evaporate from a bottle. Earlier, as a baker in my father's business, created some spectacular flashes using plain flour near open flames. Today, we must take a course to obtain a powder monkey certificate in order to set our own explosives, or we should hire skilled people. Yesterday, pre-terrorist, we simply made the stuff up and let it go, with unpredictable results and often too much effect. Hydraulic jets. There are several ways in which the quiet but powerful action of water jets assist our endeavors. Firstly, a simple jet nozzle fixed inside a pipe and connected to a garden tap may well serve to drill a water bore, a water spear, in a few minutes or hours in sands, gravels, or deep soils. Secondly, an old hose pipe fastened to a sharpened pile or post and connected to a hose will serve to sink jetty pilings in silt or sand in very little time. A jet pump, commercially available, will remove silt, sediment, mulch, and even large gravel from a dam, and deposit these behind a retaining wall as rich terrace soil, while the water flows back to the dam. Lastly, jets fired at loose sediment washes down gravels, sands, and soils for mining, as terraces, or to remove landslips from roads and fields. Quite precise control of such action is achievable. Hydraulic nozzles, drills, and jet pumps are all made by industry to serve these purposes, and also to steer deep drills in boreholes to specific locations, underground when tapping oil, thermal energy, or for venting mines and caves. Again, as with explosives, it is enough to know the range of uses, keep them in mind, and to get good advice if the need arises. Inadvertent jet drilling has a powerful pulling action, and jet pumps with their motors, rafts, or PLA horns can be dragged below water or across the ground if one is left unattended. Occasionally, a garden hose will bury itself in sandy soils in this way and so be lost. Powerful air jets now take gravels from mines in much the same way, and a whole series of turbines and powerful pistons operate from pressure applied by water, air, or oil. The science is applied hydraulics, or pneumatics. A jet plus a cutting drill will cool the area and remove waste in one operation. Finishing. Rakes and rollers are the tools for finishing excavated earth, the former to fine level, the latter to compact. Compaction is only necessary where traffic or water Retention is intended, but where it is necessary may need to be accompanied by water sprinkling in dry conditions. Care must be taken to compact only 15 to 30 cm, 6 to 12 inches, of soil thoroughly at a time. Even very heavy machines can seldom compact depths greater than 38 centimeters, 15 inches, and impact or hand compaction is effective for less than half that depth. It is necessary to strictly adhere to this careful compaction for dams and house foundations. Modern compacting machines often vibrate, using a pneumatic or mechanical eccentric weight to impact and shake soil as it is compacted. 9.9. Earth resources. Whenever earth is moved, it seldom reveals a uniform composition. In fact, most excavation reveals materials already sorted by nature and of specific use. To mix them up is to set back the clock a few thousand years, and the supervising designer or property owner will do well to follow every excavator, animal or technological, and put aside the following. Topsoil. Topsoil is the often dark, root-filled living surface of the earth. It is to be carefully stripped off, piled aside, and later returned over other material onto banks, over potty or fields, and even below water in ponds. Topsoil can be very thin and rare, and is usually no more than 6 to 18 centimeters deep. Where deeper, it can be spread on pooter soils to help them produce, or pocketed for trees in poor soil areas. Peats. Excavation in marshes, bogs, or lowlands may reveal 1 to 9 m, 3 to 30 feet, of semi-compacted fibrous plant material. Most can be stockpiled, otherwise 0.6 m, 2 feet, or so returned to the surface. As for topsoil, the peat stockpile is most valuable for mixing with sands. 247. And loams for making even more topsoil. It can also be used as a fine growing medium in nurseries, as an insulator in buildings, and only in desperation as a fuel for those who burn peat are near the base of life on Earth. The next step is into barrens and rocks. Peatlands throughout the world now urgently need preservation as threatened habitats of unique vegetation. Peat preserves timber, animals, and such unexpected treasure troves as hordes of acorns and firkins of beech butter from the forests which preceded the bogs. A whole archaeology may very well lie in peat, and the record may reveal past history. At the base of Irish bogs, the fir bog, the little people, their axes, bridges, butter, and forest life are well preserved. They and their forests were banished, as if by magic, by the Tuatha the children of Diana, who now dig the peat. Diana was displaced in turn by Mary, mother of God. But all are mixed in the peat and the tongue of Ireland. Clay. Good clay is very useful stuff. A depth of it can extend 0.3 to 6 m, 1 to 20 feet. This resource can be stockpiled, and preferably covered with plastic sheets. Both dried and baked brick can be made of it, dams and ponds sealed, and pots shaped and fired. Some types of clay make good cricket pitches, and other types make fine porcelain or special filters and insulators. Fire clay is 58 to 75% silica, 25 to 36% alumina, 0.25 to 2% iron oxide. Silica bricks 95% silica, no alumina, and 20%. Makes ovens and mortar, sharp sand, or mostly silica. Makes glass and cement, or can be mixed with peat to grow trees or other plants in nurseries. The best use. Sieved sand gives special sizes for special use as dotted grit, or polish in mortars and grinders. Gravels. Heaped up, it makes good roads, drains, and soft sunbathing patches much better than lawns. No green stains. Angular, gravel makes good concrete, and smooth, good water filters or enzyme columns. It is a mulch for trees, as is cinder and crushed pumice. 19 mm size angular gravels are the best for heat stores, where air from solar attics or glass houses is blown into a heat store wall or tank filled with such gravels. Heat stoves can be placed under floors to heat gravel beds. Shingle. Shingle is good under gravels on roads, for drains, and coarse filters. It is an excellent mulch for condensing water in deserts or dry places, a refuge for snails and decomposers, a filter bed for swimming pools au naturel, and so on. Slate. Floors, tablets, and billiard tables are of slate, as are roofs. Any rock that can be split can be utilized for walls and houses, roof areas, garden paths, and floor tiles. Boulder. Boulders can be used as a coarse mulch, wildlife refuge, and walling and windbreak material, which gains and radiates heat. Some boulders are very 248. Good as pounders, others excellent mortar and pestles. Weights, anchors, and ballast in boats. To me at least, a bulldozer or excavator is a source of information, and the making of a pond is a rare chance to explore, explain, and store useful information and material relating to the site. On a complex site, old volcano, shoreline, swamp, or desert pediment, one can confirm or deny theories on formation, geology, and geological history. Best of all, experience on many sites gives a predictive capacity on similar sites, and more confidence in finding the right sites for ponds, excavated houses, silos, or silage pits, and in finding more earth resources. All this, and just for a careful look at actual operation. It would not be uncommon for excavation to pay for itself on any one of the factors listed, and for yourself or your client to benefit long after the water storage is built, from materials put carefully aside during excavation. If you are wise, you never leave the site when earth is being moved. It is very expensive to bring machines back for fine touches, to adjust the work, or to sort out mixed materials, tracks and signs, like the snow and wind-blown sand, newly moved. Earth and puddled clays reveal to the observer a section of earth life, and makes an imprint of those secretive and nocturnal birds and mammals on site, from beetles to elephants, mice to plovers. After rain, it is a good time to take a notebook and observe the footprints, scrapes, and tracks of any site where earth was freshly moved. A list of species obtained this way adds to basic information resources and may warn of troubles in store from ground foragers. Many cryptic animals avoid traps, but can be detected by their tracks. The earth hides a great variety of life forms, from secretive larvae and worm-like legless lizards to redolent fungi revealed only on the surface by their garlic-like scent or fruiting bodies. Mice, gophers, and larger mammals leave tunnels, nests, and food stores underground, and all these and other secrets, such as the extent of root penetration and spread, can be revealed for our analysis. Shards and fossils. Under the earth, almost everywhere, lie the mute stories of prior life. These have more lessons for us than do futurologists, who alter all can only look forward by Looking back first, or they would not know which way is forward. The camps of our ancestors are revealed in soils by shells, tools, shards, ashes, bones, and can be so dated. Buried trees give growth rings to tell the story of older climate, air quality, and to accurately date their own burial. Pottery shards may encode astrochemical or technological data, and bones reveal past diseases and wars. As the Ganges River today bears its children's bodies, their clothes, adornments, and possessions to race blindly over the continental shelf to the ooze below, and as we carelessly drop broken pottery on the ground, so in the far future other people, or other minds, may want to know about us, how we lived, and references perhaps when and why we died. Today's disposal pits Bradshaw, 80, and M.J. Chadwick, The Restoration of may well become tomorrow's minds. They are Land, University of California Press, 1980. Ourselves in Past Cycles, an expression of life preserved for our education and guidance, Skiaktl, Hugo, Bioengineering for Land Reclamation and Conservation, University of Alberta Press, 1980. Swales used as Fahubab Ziong Musines. HOWN grazed by 46G60. Pond 7. Hold what? Tantep to lotus. Bamboo for trellis or craft. Swatsutsa Esrin LS. Dash wet term SWLA, TiVo. -2 windbreaks Wu, or adhere whale WWE habit areas, production in swale. 3 production swale, Frey hardy trees, Mago, olive, e.g. 4. Roge windbreak swale or interswale. 4. Ridge access road, run off TE4 and 6. And onwards and production whales. Windtend. Trees, avocado, citrus. Interswales equals useful mulch and forage crop, Dalit S, Compad acacia. Lincana, lupin, Copros Lucerne T. Ocerne. 249. E. Chapter 10. The Humid Tropics. 10.1. Introduction. The subsets of climatic zones included in this chapter specifically exclude arid tropics, which are included in Chapter 11, together with cold arid areas. As plants and techniques do not split off neatly into climatic areas, the following 3 chapters should be read in total for any one site. A subtropical site, for instance, can have quite severe frosts, cold winds, torrential summer rains, and 7 to 9 months of drought, so that it needs the strategies, earthworks, and species suited to temperate, arid, and tropical humid climatic regimes. However, it is true that soils and climatic characteristics do dictate the specific broad design responses. Some special topics of the humid tropics are those of soils, mulch sources, planning for polycultures, and appropriate house construction, each of which is given a section. In the wet tropics, heat and high rainfall would leach made mobile nutrients from soils, except for the biomass of the great variety of plants, which contain 80 to 90% of the available nutrients. Humus is an essential soil fraction, and humus creation must be given considerable emphasis as prerequisite to sustainability. Inappropriate strategies are those of bare soil cultivation, or intensive clearing and burning in short cycles, less than 8 years or so, for cropping. Appropriate 8 strategies involve complex and multi-storied plant systems designed to yield basic staples, create mulch, and preserve soil nutrients. James Fox in Harvest of the Palm, 1977, has been one of the few who have analyzed the social changes and loss of self-reliance following the abandonment of ancient and balanced palm polycultures in Indonesia. Ancient tropical civilizations have been noted for their stability, indicating that sustainable land use patterns are an essential prerequisite for social harmony. The Food and Agriculture Organization of the United 250 Nations, FAO, admits to failure in transferring Mechanized monocultural systems, barely sustainable in temperate moist areas, to fragile African or tropical soils. It is a wonder that this was tried at all in modern times. The clearing and cultivation of tropical soils has for decades proved disastrous, and most ecologists would have predicted this failure by the early 1950s. Complex perennial fodder and food systems are known to be stable, but are not as yet part of the officially funded agricultures from such sources as the World Bank. Deserts present even more fragile systems, and need greater skills to stabilize and manage. The most inappropriate advisor is an agriculturalist trained in modern techniques. What is needed is continuous local education of experienced people and a lateral transfer of their evolved skills. Emphasis in such education should range from an analysis of health and environmental problems to practical solutions, with sophisticated plant/animal/technological assemblies adapted to local food preferences, nutritional needs, and cultural requirements. Romantic literature on the easy tropical life leaves out the skin cancers, rodent ulcers, dengue fever, filaria, malaria, chronic bowel and skin disease, and the constant battle with rampant growth that is an everyday experience at latitude 0 to 25 degrees. That, and the pythons, ticks, termites, rain, mold, and lethargy caused by heat exhaustion. With the increasing loss of atmospheric ozone, it is folly for fair or red-haired Europeans to expose bare skin to the tropical sun. A cause of skin cancer in Australia and Hawley rot, a form of fungal bleaching of the skin, in Hawaii. Humid heat induces a lethargy compounded by chronic illness in many populations. Waterborne and mosquito-transmitted diseases are almost impossible to totally control, given the aerial reservoirs of water developed by palms and bromeliads. In houses, induced cross-ventilation and careful construction for mosquito control are essentials, as are plant systems. Based on a tree species polyculture, the two combine very well to reduce climatic extremes. We can largely emulate the tropical forests themselves in our garden systems, establishing a dominant series of legumes, palms and useful trees with a complex understory and ground layer of useful herbaceous and leguminous food and fodder plants, vines and epiites can complex the situation as it evolves. In the wet dry tropics, more open palm polycultures are appropriate. The excesses of heat, light, and rain are best modified by an open canopy of palm fronds and the fern-like leaves of tree legumes. 10.2. Climatic types. Based on Truartha, 1954. Wet tropics. These are the river basins and wet coasts from latitude 0-25. Major localities are the Amazon and Congo basins, Central America, Sri Lanka, Malaya, Borneo coasts, and New Guinea. This climate covers about 10% of the Earth's surface, 5% of the human population. It is heavily occupied only where terraced alkaline volcanic soils enable sustained cultivation. Java. It contains remnant tribes of hunter-gatherers, often pygmoid, in remaining forests, and is rapidly being ruined by overexploitation of forests, mining and extensive cattle rearing, mostly developed by large corporations. Hence, there is a recent tendency for catastrophic wildfires to develop in logged areas such as Borneo, and for soils to be leached to low fertility, or eroded to ferricrete or silcrete subsoils. The sun is mostly overhead, with temperature fluctuating little at about 21 to 32 degrees Celsius, 70 to 90 degrees Fahrenheit. Humidity is ABCI zones of direct sunlight. P zone. Reflected of chars melted allele. Figure 10.1. Structure of a wet tropical forest. Dense planting is possible, and beneficial near villages, species. Assemblies are simplified on the broad scale. Levels in natural forests are also indicated, after more, New Scientist, 21/8/86. 251. Constantly high, frost unknown. Rainfall is from 152 to 328 centimeters, 60 to 129 inches, with rain most days and frequent thunderstorms, 75 to 150/year, usually towards evening or late afternoon. The landscape features perennial streams, deeply weathered and rotten rock over bedrock, regolith, and rounded hills. There is rapid water runoff and evaporation, with swamps confined to coasts and lowlands. Rivers usually have floodplains and extensive alluvial plains and deltaic deposits. Access inland is often by rivers and tributaries. The vegetation is luxurious, best developed as broadleaf rainforests with lianas and epiphytes, very much mixed as to species up to 800 tree species per square kilometer. The shaded floor of the forest contains little growth and has subdued light. Mangroves are extensive on appropriate coastal and estuarine sites. Growth is rapid, uninterrupted, and continuous. Insects and birds are plentiful and varied. Most fauna is nocturnal and arboreal, and there are abundant fish and aquatic species. Ground grazers are rare and large herd species do not occur. About 85% of nutrients are held in plants or animals, so the soils themselves are infertile, especially if clear cultivated, tending to erode and leach to insoluble oxides of iron and aluminium. Only terraces, floodplains and new volcanoes keep some soil fertility replenished or held if land is cultivated. Staple cultivated foods are plantain and banana, cassava, yams, coconut, corn, taro, paddy rice, ducks, pigs, poultry, and fish. Trade and plantation crops are spices, copra, palm oil, cacao, rubber, banana, manila, hemp, tier hardwoods, balsa, tropical nuts, chicle, and drug plants. Housing is usually raised, steep-roofed, thatched, with permeable walls, and screened. Health problems relate to sewage disposal, insect vectors, and skin fungi. Asterisk hygienic faces disposal. Asterisk clean water sources. Asterisk integrated and benign insect control techniques. Asterisk gradual replacement of ground crops by trees. Asterisk preservation of natural stands of trees. Asterisk development of river versus road traffic. Asterisk evolution of natural products. Asterisk no-dig, mulch, techniques on root crops. Asterisk domestic foragers for snail and insect pests. Asterisk appropriate medicinal plants. Wet dry tropics. These adjoin the wet tropics but are poleward of them. They take up about 15% of Earth's surface from latitude 0°-25 degree, unbalanced in favor of the southern hemisphere. The Campos, Llanos, Gran Chaco areas of South America, parts of Central America, encircling the Congo Basin, and many Central Pacific islands, Hawaii, are all wet dry tropical areas, most now developed to grazing. Winter, the low sun period, is the dry time, when 252 clear skies and intense sunlight take day temperatures to 38 degrees Celsius 100 degrees Fahrenheit or more. Humidity is low, and strong. Desiccating winds may blow. Summer, the high sun period, is like the wet tropics, but episodic flooding is more common and natural erosion therefore greater. There are no frosts, and temperatures range 21 to 27 degrees Celsius, 70 to 80 degrees Fahrenheit, in the wet season, 32 to 38 degrees Celsius, 90 to 100 degrees Fahrenheit, in dry season. Rainfall is 25-152 cm, 10 to 60 inches, decreasing towards desert margins. Windward inland slopes and coastal mountains may receive excessive rain to 1016 cm, 400 inches, but rain is erratic and least predictable. Towards the desert margins, rain shadows evolve on Les Lopez or in the lee of mountains. The landscape is of intermittent streams, some wadis, and floodplains, karst, limestone, areas with sinkholes, cenotes, and absence of surface water, Yucatan, Mexico. Hills are rounded, but gully erosion can develop rapidly on slopes. Extensive inland swamps may develop in flooded areas, and lakes and rifts are common. Africa. Rivers often have dangerous ways of silt and sand due to active erosion sequences. These regions contain the vast savanna grasslands of the tropics, with thornbush and flat-topped acacia trees. Africa, evolving to steppe grassland on plateaus, with baobabs and dry deciduous trees. Grasses reach 1 to 6 m, 4 to 20 feet, in the wet season, and are often burned off. African areas contain enormous numbers of herd species, zebra, gnu, antelope, and therefore large carnivores. Arboreal species occur only within tree islands and the gallery forests of valleys. There are termites, ostrich, rhea, locust, and large numbers of reptile species and insects. Soils are generally more fertile and alkaline than the wet tropics, especially where they are less leached by rain towards the deserts. Cultivated land is still at risk from erratic rain and erosion, leaching, and wind effects. Due to overgrazing and fire, erosion may extend the desert into these areas, or into dry summer subtropics. Serious soil erosion results from short-term shifting cultivation, less than 15 years fallow period. Staples are corn, millet, wheat, beans, potatoes, cucurbits, peanuts, cattle and goats, sheep, and game products. Herding of low-yield large herds is a major erosion hazard. Plantation crops are sugar, cotton, peanuts, pineapple, sisal. Exports are cattle and sheep products, and hardwoods from gallery forests. Houses and granaries are generally mud or pisé with thatch. Design essentials are for asterisk small domestic water storage and reticulation. Asterisk hedgerow against winds. Asterisk in crop tree legumes such as acacia albida. Asterisk improved stock varieties and stock management. Asterisk natural herding system of local herd species. Asterisk mulch use of grasses. Asterisk increased tree crop of high forage value. Asterisk decreased fire frequency. Asterisk tree stands for fuel and structural timber. Asterisk no tillage, cut and mulch, grain techniques. Asterisk low bunds for water retention. Asterisk chisel plow and sod seeding techniques. Asterisk greater reliance on in-village bee crop near wells and ponds. Asterisk reclamation of eroded lands using pioneer species. Key line techniques of flood control. Asterisk soakage pits and impoundment of runoff by low bunds or swales across slopes. Registered tree forage and tall grass hand-fed to domestic stock. Asterisk the use of manures in gardens. Asterisk the development of domestic fuel wood systems near villages. Monsoon tropics. These are really a subtype of wet-dry tropics, but influenced by nearby continental land masses and oceanic winds onshore. They are confined to the Indo-Thailand region, northern Australia, East Java, Timor, southern New Guinea, and extend latitude 0 degrees to 35 degrees north in India. Despite only about 8 to 10% of the world's land surface, monsoon areas contain large human populations. Late summer heating of the continents causes onshore sea winds and, with luck, heavy rains. The dry winter season reverses winds from cool interiors to coasts, giving end cold period not in the wet dry tropics. Temperatures 13-21 degrees C 55 degree * 70 degree F. Temperatures rise, and dry hot winds develop to over 38 degrees C 100 degree F in spring, with heat increasing until the onset of the monsoon. About 60% of the rain falls in summer, but rain is erratic and varies from 102 to 1016 centimeters, 40 to 400 inches, depending on topography and distance. From the coast, floods and droughts are equally unpredictable, but common. Most activities are determined by the monsoon rain, transport, fishing. Tropical forests once clothed the hill slopes and river plains, and grasslands extended towards deserts as savanna. Population pressure, deforestation, and marginal agriculture has devastated this ecology in India. Dry deciduous broadleaves are common, teak and bamboo once extensive. Tree canopy is less dense than in wet tropics, so that dense understory is also developed. Mangroves occupy river mouths and low coasts. Large native anime are now rare in the Indian subcontinent, but reptile life is abundant, as are feral or native deer, buffalo, and primates. Monsoon Australia is better vegetated, with scattered eucalypt and acacia trees, riverine forests, and very low humans. To date, large marsupials, feral buffalo, and marsh waterfowl are abundant. Soils are lateritic, often very hard in the dry season, and of low nutrient status. Some are cracking clays. Housing is often mud pole structures, thatched, steep-roofed, with wide eaves and good drainage for wet IOC. Design essentials are similar to those of the wet-dry tropics. 10.3. Tropical soils. Special problems arise with tropical soils, in that except in areas of recent volcanism such as Indonesia, soils are old, not renewed by glaciation, and deeply leached. Most of the silica and calcium is in low supply. In clays, aluminium ions substitute for some silica ions, giving soil particles a net negative charge, especially in the oxidic kaolinitic soils, common in weathered volcanics. Only kaolin clays and oxides of iron aluminium remain. In these soils, the charge, or cation exchange capacity, CEC, of the soils is affected by pH. Once cleared, the humic particles leach out to about 30% of prior levels, and infertility appears in such crops as banana and sugarcane. There are a few ways to restore the soil's ability to hold nutrients. Wayne Ralph, Managing Some Tropical Soils in Rural Research No. 117, pp. 15 to 16. Asterisk restore humus with green crop, and especially perennials such as luerat and tree late times generally. Any cultivation loses humus as carbon dioxide, so try to grow plants with intercrop. Asterisk now, add small quantities of superphosphate at frequent intervals so that plants can take it up before leaching. If possible, add fine crushed basalt, a scatter of cement powder, and use shredded bamboo or cane mulches for silica and calcium. Increase pH with lime after trees and green crop are growing well. Asterisk whatever is added or available as fertilizer, give as a light spread all year at 6-week intervals, until plants are well grown. If at all possible, substitute perennial for annual crop, and never practice frequent cultivation. Basalt, cement powder, coral, and bamboo mulch supply essential nutrients and increase swap pH, hence increase the negative charge on soil particles and their ability to hold calcium, sodium, phosphates against leaching. Soil charge copyright plus equals yen equals ACIP. Figure 10,2. Tropical clays. Gallium exchange capacity CEG and Volbods and sale. Change with pH as diagrammed. If alkaline. On coral cays, the calcium-rich sands bind to phosphate to form insoluble calcium triphosphate, so that a sort of cement, platin or calc-reedy, forms. This may be naturally evolved from the guano of seabirds, but superphosphate rapidly forms the platin by its greater solubility. In calcium-rich tropical soils, fine rock phosphate yields more slowly and is therefore more likely to provide long-term benefits. A return of crop waste as mulch is also essential, which can reduce pH. In coral sands, pH 8 to 9, to a level nearer to pH 6.5 or 7, which is suitable for gardens. In fresh foliatic areas, or areas with volcanic dust deposits, soils are sufficiently rich to sustain intensive agriculture without such aids, but constant cropping will exhaust even these soils. There are many excellent tropical soils such as the alkaline volcanic soils of Indonesia, which support rich terrace and palm polyculture systems, and many tropical high island soils where dolomite tops, or forms a mosaic with recent volcanics. Apart from testing for minor elements, the addition of mulch manure mix creates excellent gardens on such soils, and plants show only minor nitrogen deficiencies. These deficiencies can be eliminated by legume intercrop and manures. In the long term we must rely on tree and ground legumes to keep up soil health in the tropics. Destructive approaches, now very well demonstrated. Combine forest clearing, bare soil cropping, and careless water runoff management to make desolate, baked clays, brick-like and hostile, out of one's rich tropical forests. We have, as yet, no categories of crimes against nature, but these will prove, in the future, to be some of the worst. Deep granitic sands. In soils over-rotted granites, such as are found on the high islands of the Indian Ocean, the Deccan in India, and where granites are left as inselbergs, domed hills. A peculiar problem arises in that open, coarse, granitic sands, often very deep, will not retain mulch beyond 1 growing season. There are 2 approaches to these. Free draining and low nutrient soils. Broad scale. Palms, Albizia species, Inga species, Acacia species, a general. Planting of adapted leguminous trees, and other native vegetation will establish a light canopy of leaves if small amounts of nutrient are added at regular intervals. Palms planted in mulch-filled pits will then establish a high crown cover, and the detritus from legumes can be used to establish more valuable fruit trees, always retaining a complete roll web of legumes. Palm trunks are ideal trellis for vanilla and passion fruit crop. Niches and clefts in the granite mass itself will hold pockets of soil and mulch for valuable trees, and vines will establish there to cover the granite slabs, which maintain heat and ripen crop effectively. It is the mycelial web of the pioneer legume foots which enables us to maintain the benefit of applied nutrients, to reduce water use, and to establish fruiting trees, mango, cashew, pomegranate, persimmon, citrus, tamarind, lychee, custard apple, avocado, in such sparse and drought-prone soils. Drainage is, of course, excellent, and deep-rooting trees thrive. Palms suited to these sites are date, coconut, dum, and Borassus palms. Gardens. It is effective to excavate long trenches in the loose sand, 1 to 2 m wide, 1 to 1.5 m deep, to lay in a sheet plastic base, upturned at one end only, or to line the trench thickly with cardboard, paper, carpet, and leaf, and then to backfill with sandy loam. The deep sealed layer holds water and leached mulch, and household waste. Water can be let into these trenches to provide root water and nutrients. Otherwise, we can build log boxes above ground level, carpet the box base with plastic or thick paper. SPM. Cement. EN. 10.3. Broad scale tree crop in loose granitic sands. 254. And fill with humus sand mixes for green crop and vegetables, top mulching as needed. Large domestic water tanks, good ponds, solid granite dams, and underground plastic lined cisterns backfilled with sand will hold water. Soil life in the tropics and subtropics. Termites, ants, and some worms are the obvious soil mesofauna of many arid and humid subtropical areas. Both ants and termites are very active in the transport of rotted rock and subsoil to the surface, in opening up galleries for the infiltration of water, and in the breakdown of woody and leafy plant material. Some species create large mounds, others build underground compost heaps for fungal culture, and all are active burrows and builders. Termites may have a decisive role in the dynamic and delicate balance between the erosion of surface soil and the replacement of the soil by subsoil and rotted rock particles. They certainly have an important role in plant succession and distribution in savanna areas, or where termite and ant mounds are the only well-drained or elevated sites in a landscape subject to floods, or where impermeable clays underlie thin peats, usually with acid anaerobic soils. In these situations the spoil heaps present an ideal site for pioneer vegetation or adapted crop planting. Harris, 1971, records that both the leafcutter and in South America and termite mounds in Uganda assist forests spread or establish islands of taller vegetation in grasslands on their mounds or colonies. Have also observed this in the granite country in Hyderabad, India, and on acid peatlands in Tasmania. Such mounds protect soils from fire, waterlogging, and poor aeration. In humid areas, some such sequence as tall grasses, Painazetum, Irogrostis, are followed by shrubs such as castor oil bean, prosopis, and thorny legumes. Finally, an understory and forest may develop from larger trees, such as tamarind, vitex, sapium, or palms dominant. Thus, we can start this process or a modest version of it by seeding into termite or ant mounds using similar species. Even low ant heaps may present a site for ground cover pioneers in grasslands. Harris records crops such as sisal, cotton, and tobacco deliberately cultivated on large mounds in grasslands. Palms and coffee can have much of their outer bark removed by termites without suffering loss of production. Termites may greatly assist the primary breakdown of logs, coarse stems, and hard leaf material used as mulch in plantations of coffee, tea, or bananas. It is a matter of specifying, by observation and local report, which useful crops or trees are left alone on mounds, which are attacked but remain productive, and which actually benefit by association with a local termite or ant species. Planting an ant or termite mounds is a particular example of niche gardening, widely applicable to the tropics. Have successfully germinated daikon radish in ant heaps in grasslands as part of a changeover to crop production. Ant and termite mounds present a rich deposit of calcium and potash, better aeration of soil, and a faster infiltration of water to release minerals from such rocks as granites, which noticeably rot or erode faster when buried in a free infiltration soil environment. Sources of humus for tropical soils. As humus in the soil provides a good CEC, we must look to the provision of such humus as a priority. Some sources are logs and branches of trees. These are sometimes rotted in wet terraces or piled up as rough mulch around new tree plantings. Palm wastes are often plentiful. Detritus from stands of bamboo, pines, casuar rinds. Aquatic weed mats and emergent water weeds. Crop wastes and manures, household wastes. Hedgerow, forage, and specially grown mulch. Plants. Green mulch and ground cover. Logs and branches, rough mulch. The rapid breakdown of wood under the combined influence of rain, heat, termites, and fungi means that we can lever whole logs together, or in line cross-slope to act as planting sites. This technique is most useful on bare clay soils, eroded areas, and isolated atolls, using the trunks of old palm trees. In Hawaii, a traditional strategy is to rot the logs of Fujiire tenri. Gardening in coarse and sands. Grey water seepage pipes along plastic-lined trenches made raised mush gardens in coarse granitic sands. The kukui tree, Alurites mollicensis in the shallow water of taro terraces. As logs rot, an edible fungi appears which is taken off as crop. The remaining log is then crushed and spread in the taro terrace. Leaves and branches of kukui and other forest trees were gathered. The same food pose, terrace mulch. Marjorie Spears, in Queensland, Australia, has successfully built temporary rough wood terraces across a deforested slope using rejected jogs, and created a complex and rich garden based on this strategy and green legume mulch. Logs are available from palms, although fast-growing acacia species can be previously close planted for this purpose. Figure 10.5. Detritus. Several plant species, most palms, bamboo thickets, caswaring, and many acacia species, provide silica-rich mulch, a 5 dew grain and nut husks and residues from Copto operations. This can be applied as shredded or chopped mulch to crop or to the base of newly planted trees. The silica is released for growth and has the secondary effect in alkaline island soils of reducing pH from 8.5 to 0.6.5 in my trials on coral islands. Of particular value are the fronds and spades of palms, shredded or whole, and the stems and spades of bamboo. Both have essential structural uses, and larger stands can be used to produce mulch. E.j. Floating aquatics, including the water fern Azala. Several species, the water lettuce, pistia, water hyacinth, eternia, and alga, mats or fern fronds, plus reeds and rushes gathered from ditches, are excellent crop mulch. Azofla has largely replaced kukui, ulrites, as a taro mulch in Hawaii. Pistia has been successfully used in Attica, and water hyacinth in many areas. Azala and algae such as Adabacnatone species of which nest in the gladina sacs in Azala, provide nitrogen. In the dry wet tropics, shallow flood water buns collect or produce these plants, which can be gathered as rolls of dry material when the water dries out in the winter period, thus providing garden mulch in abundance from temporarily impounded water. John Selman of Cooktown, Australia, has used algal rolls in this way for his garden plants. Crop wastes and manures. The husks of corn, kitchen wastes, including bones, and human and animal manures are invaluable trepical garden mulches and nutrients, and most need only burial near tree roots or in growing mounds for safe disposal. Cardboard and newspaper, where available, are valuable grass-suppressing weed mulches, and a cover of gut husks completes the job. In the Seychelles, cinnamon leaves and branches from pollard stumps are considered an excellent mulch for vegetable crop, and the bark is a valuable spice. Hedgerow and mulch plants. All hedgerow, hibiscus, cassidrina, bandagrass, palms, leguminous trees such as gliricidia, acacia, and prosapis are almost continual mulch sources. The legumes provide in crop shelter, see later section on avenue cropping. Lower garden windtake, especially lemongrass, Symphopogon citratus, and comfort, Symphytum officinale, are as useful in preventing kikuyu grass intrusion as they are for repetitive cutting. For mulch in the vegetable garden, many people now use both these species as a combined kikuyu barrier and mulch crop. Figure 10.6. Figure 10.5. Log barriers on slopes, Marjorie spears. Logs cross-slope hold mulch until tree lines establish, logs rot quickly but mulch is renewed annually. Tribanana clumps. 256. In and around end trees, soft herbaceous plants, such as nasturtium, comfort, marigolds, tobacco plants, and the tops of mature taro plants and other Araceae not only suppress grass, but provide a constant source of mulch. Even more valuable are such soft legumes as Hispania, vetch, hypha clover, cowpea, lablab, bean, soybean, desmodium, ceritro, and centrosema. These can be slashed or, in wet dry tropics, interplanted with grains to give a nitrogenous ground cover, aiding in the suppression of grasses. Lablab dies down just before grains ripen in the winter dry season. Thus, a combination of growing and gathering mulch enables us to create a rich humus for gardens over clays or sands, in loose volcanic cinder, on oil lava, and in loose coral atoll sands. Each of these situations can successfully produce mulch. Some difficult mulch such as hibiscus, lantana, and weeds which tend to resp out from cuttings or seed if mulched. Several grasses and hedge species can be rooted to gardens via poultry or cattle pens, where seeds are removed and foliage eaten. They can also be shredded for anaerobic digestion in biogas plants, bagged in large plastic bales exposed to the sun, where they cook to a wheat-free silage, or simply bundled and immersed to rot in covered water pits. In fact, some such rerouting is ideal for the primary processing of plant wastes that promise to infest gardens if untreated. Pigs eliminate or eat the nut grasses, rhizomes, bulbs, and sedges that resp out from compost. All else failing, even a plastic sheet mulch has excellent effects on row crop, preventing rain splash and nutrient leaching, and at the same time condensing groundwater at night. It does not, however, add to the humus content of soils, nor to the cation capacity of soil structure, and may even release unwanted chemicals to the soil. The value of surface mulch in weed suppression is a major factor in lowering work. For this reason, any mulch should be thickly applied 20 to 25 centimeters, 8 to 20. Table 70.1. Crop yields under selected mulches. Mulches maize, cowpea, soybean, cassava. Rice husks 7, 4.40.8, 26.3. Penicillium 33,642, 14.2. Straw. Elephant grass 3.30.91.3, 16.6. Millet straw 3.62.41, 15.5. Panicum. Legume waste 4.31.0, 14, 16.5. Sawdust 37,608, 1.9, 20.5. Bare ground 3.00606, 16.4. Heavy yields are emphasized after B&O kickbone arlal, residue mulches and agriculture. Inches, deep when first establishing home gardens. Later mulch can be derived from green herbage and borders or windbreaks. B&O kickbone arlal in residue mulches and agrisilviculture, International Conference on Ecological Agriculture, Montreal, 1978, in mapping strategies to cope with increasing jan pressures, found that no tillage systems maintained or gained yields for maize in Nigeria, and increased yields from mulched crop for cowpea, soybean, and cassava. I have selected out some natural mulches from the more extensive original table given. Mulch trials are compared with bare ground, on the last line of table 10.1. Maize had a marked positive response to legume straws or water plant, pistia, mulch, while the legumes themselves responded well to grass and sawdust mulch, and cassava to both legume and grain husk wastes. Kikuyu, mun, swulst, scent planted, feces luti, lemongrass. Figure 10.6. Weed barrier. Grasses are kept at bay by barrier plantings. Mulched grasses can be planted out day if paper or cardboard is used over undug grasses. Mulch scent planted same daw, obi kikuyu. Herbs, vegetables, ginger. Forbid trees. Root crops mers. 257. Although plastic mulch has a good effect on all crops, it does not add humus to soils, and is therefore not as appropriate to a remote village situation where soils must be built up from wastes and from mulch. However, every type of organic mulch increases yields, and we should therefore use all available materials for soil restitution. Mulch provision is the cornerstone of tropical home gardens, and green mulch and tree legumes the essential accompaniment of main crops and tree crops. Special mulches may be used in tropical areas, grown to provide N.P.F. kgoms, comfort, pultania, and to increase or decrease pH. Pine and legume mulch may benefit the growth of bromeliads, pH 4 to 5, buckwheat, and nut husks serve to raise the pH of garden soils, as do many bark mulches. For fire control, too, it pays to rake under bamboo and clump canes, and reroot the leaf mulch through animal bedding or poultry straw yards. Branches of legumes and forage trees may also be used in the same way, on their path to the garden. In the rampant grasslands that replace fallen forests, there is little else we can do than to strip mow and mulch while trees re-establish. The timing of slashing is important, as seed-free mulch, called second cut grass, is best for placing around valuable crop seed head. Mulch should not be placed in gardens or areas where it might be a nuisance. All species of weeds and grasses give weed-free mulch when not in seed. Many useful tree species provide leaf mulch, and so are excellent also for interplanting with crop, for example tamarisk. In dry areas, cassowarin in sand, and legumes in all. There is absolutely no excuse for burning any organic wastes in the tropics, as even large logs quickly rot under the onslaught of fungi, termites, and beetle larvae. At the same time, logs provide cross-slope barriers against monsoon erosion until new trees take hold. Coconut husks have a variety of uses, not the least of which is as mulch for a valued crop such as vanilla orchids. Their one drawback is that they hold small sections of water which will breed mosquitoes, but on many islands they will also be available, with palm fronds, to shred to a first-class mulch of high potash value, to burn and steam to activated, filter, charcoal, or to be used as a solid fuel. Shredded bark and broken shells are ideal mulches for ginger, turmeric, and vines. I have not found any crop or tree suited to the specific locality that does not grow, produce, and thrive in mulch, nor any widespread pest that grossly affects a total polyculture yield. Ginger, taro, beans, bananas, palms, fruit trees, flowers, yams, sweet potato, melons, etc. have been trialed in thick mulches of straw, fronds, nut husks, cardboard, and sawdust. A thick mulch almost totally eradicates kikuyu grass and other persistent grasses. In the field situation, extensive mulching is often impractical, particularly if it is carted in from off the site. However, a pioneer crop of quick-growing tree acacias, bananas, legumes such as lab, deep-rooting comfort, and a grove of bamboo and palms will provide continuous mulch for gardens and main crops, fruit trees, and valued plants. Growing in exhausted or poor tropical soils is possible, but the early work of rehabilitation takes hard work, seed, essential fertilizer resources, and a strategy. Figure 10.7. Mulching gardens. Held by a log edge, coconut husks and coarse fronds or grasses provide mulch for home gardens. Gray water irrigation is ideal. Coconut husks A and P front. 258. Of starting small and expanding the system at the periphery. Dense planting of nucleus areas plus mulch is a key strategy. 10.4. Earth shaping in the tropics. On level ground or gentle slopes, 2 to 8 degrees, in the wet dry tropics, a series of large contour banks or swales have an excellent sail preservation effect. Coupled with the gradual development of a terrace, the retention of wet season water, and mulch providing hedgerow, this ensures a stable situation between the main hedges. Mulch hedgerow and borders can be developed in crop, or the terraces can be flooded seasonally for irrigated. 10.8. Guy Mary had sites, less than 4 degrees, a series of raised mounds or ridges can operate to drain crops in very wet areas, or to impound water for absorption in drier areas. Pits can also be used only where rainfall is less than 76 centimeters, 30 inches, or where soil drainage is good. Thus, cassava, yam, and cucurbits are mounted in areas where drainage is a problem and rainfall intense, and pitted in dry areas or savanna dry seasons. Pits retain mulch and moisture, as they do in desert areas. Almost every slope benefits from earth shaping for soil conservation. Handmade slope terraces need to be narrower, to 3.5 to 6.5 m 12-15 feet, than machine-made systems. Garden terraces on very steep humid slopes must be kept narrow, and in sets of 6 to 8 downslope, otherwise instability may result. Borders can be kept vegetated with trees. Figure 10.11. Classical wet rice and taro terrace has water continuously let into the top terrace of the series, and each has a drain and sump to regulate water level. Fish. Figure 10.9. Mounds, ridges, pits. Mounds increase yields of yams, ridges ot cassava and sweet potato. Pits store taro, arrowroot, and mulch grasses. Terraces need such detailed earthworks. Figure 10.8. Broad contour banks evolving to terraces show erosion of crop soils built up behind tree banks to form stable contour terraces. Trees are permanent stabilizers. EYSY == may be grown in the deeps of such terraces. Figure ARGF. 10.12. Banks and funds, being of teeth of ranks, and in stable clay or clay loam soils, terraces not only step funds made for tree crop hold and infiltrate water, but permit mulch application * slope faces and walls with minimal leaching losses. Where no streams exist to registered on trellis out from bunds. Feed the terrace system. Dry terrace holds the soil * in and around ditches and drains against erosion in cropped areas. Lacking streams, A * on steep, unterraced slopes. Deep mulch keeps terrace soils moist. Where a stream, registered the flat area of the terrace itself, or part of a stream, can be led to upper terraces. Wet crops such as rice, taro, watercress, kangkong, and water eye. Chestnuts, Indian or Chinese, can be cultivated in * millet, summer or dry periods. Water level controlled potting. This is the rich wet * dryland rice, spring summer. Terrace culture of Asia and Oceania. * barley, wheat, rye, winter and cool periods, spring. Essentials are, about 1/2 to 1/3 of the total copyright wheat varieties, brassicas, fava beans. Terrace area should be devoted to mulch tree crop amaranth, summer grains, spring greens. Providing fodder for livestock or direct leaf and branch * quinoa, summer. Mulch to terraces. Ideally, the upper 1/3 of hills, * grape / mustard, winter sits and oilseed. The very steep slopes of 30 degrees or greater, terrace registered lentils, intercrop, and nitrogen fixing. Side borders, and the outer faces and crowns of bunds _ legumes. IA. Walls, should be planted to productive and mulch * grams and pulses, intercrop and nitrogen fixing. Producing tree and ground crop. This not only adds to the terrace stability, many of which have existed in _ fodders, Production for up to 5,000 years. Euro.G the wet terrace call. Tag assist. Banda grass. Comfort. Lucana. Crop. Tours of the Ifugeo people of the Philippines but will waste and straw. Also provide a local mineral mulch crop for terrace. Cultures. Included in such mulches are the crop waste garden terraces near homes. Underscore of the preceding crop. Asterisk banana, papaya, melons, chilies, peppers, cucumber. Herbaceous fruits $mulch trees on Iberase face. PUCHCR or year 10.10. Comfort Pliquons, terrace system. Small garden terraces. With 1:2.5 banks, pits dug to absorb rain, can be fully planted to vegetable and herbaceous perennial crop. Figure 10.11. Sets of narrow terraces on steep slopes. A series should be finite to 6 to 4 and 1 glacé, forested above and below, and to the sides, for stability, path slope alternately to spill. Excess runoff, and are mulched, twice annually path much is lifted to uphill terrace beds. Poo out on a mulch of the clippings weeps. Has RSUCCESSCUNE used by Michel and Jupe Vanneton. Near Nimbin, Isai, Rollin. Very separate slopes, 735 degrees. 260. Rhubards, maize, beans, sugarcane, cultivated green crop. Brassica, edible chrysanthemum, edible hibiscus, rosella. Horseradish tree, moringa, coconut, mango. Asterisk chayote, cucurbits, beans, passion fruit, kiwi fruit. Asterisk bamboo on borders provide tree flies material, as do rot-resistant timbers. Mulch crop and fodders above to the borders. Asterisk tree legumes, bannock perizitai, lemon. Grass, vetiver grass, comfort, bamboo, and palm fronds. Alfred species, Crinton and Burnett SPP. Asterisk contour strips of vetiver grass, lemongrass, banna. Grass with legumes not only replace contour ridges, but trap soil particles, and is a cheap way to terrace. Even on steep slopes. These strips provide mulch for trees and intercrop, figure 10,13. E-borders, added uphill, C-story, forest crop. Planted and selected for mulch value and fodder, or asterisk animal sheds, ducks, pigeon, poultry, pigs, bees. Overtop terraces, manure on a washdown system. Asterisk in crop mulches such as beans, azala, clovers. Asterisk staggered, short sets of terraces for steep slopes and high rainfall, compact with more continuous and longer series for winter dry irrigated terrace. Asterisk deep areas in terraces for fish/crayfish/shellfish. Refuges. Asterisk vines over all or part of the terrace to aid such crops as taro. Asterisk bunds planted in clover, beans, comfort, lemongrass, fruit crop. Asterisk splash stones or splash plates for falling water. Methods of draining terrace. Asterisk border drains in terrace to keep soil dry for mid-season crop. 10.5. House design. Optimum comfort levels for people are at dry bulb. Temperatures of 20% C, 68 degrees Fahrenheit, in still air, winter, and 25 degrees Celsius 77 degrees Fahrenheit in summer, subject also to individual preference. Above relative humidity levels of 40%, we effectively add 1 degree Celsius to dry bulb temperature for every 4% increase in humidity. As average summer humidity in wet dry tropics commonly exceeds 50%, and long periods of humidity of 70% or so are experienced, there are times when sensible temperature exceeds 30 degrees Celsius, 86 degrees Fahrenheit, and heat stress results. In homes, a useful indicator is a wet bulb thermometer, where the mercury bulb is kept damp by cotton withdrawing from a beaker of water. Below 18 degrees Celsius 65 degrees Fahrenheit wet bulb temperature, we can remain fairly comfortable. Factors that accentuate heat are nearby radiant surfaces and lack of air movement. For a nearby radiant heat source, wall or pavement, that exceeds 38 degrees Celsius, 100 degrees Fahrenheit, we can add 1 degree Celsius per degree radiated to the air temperature, and conversely, we can subtract 1 degree Celsius for any airflow above 1 m/second. Evaporative cooling in dry air greatly reduces heat. But as the high humidity periods of tropics do enable us to cool by sweating, we must therefore use every strategy available to dehumidify air, mainly by cooling, to cast shade, to develop cool surfaces, and above all to induce cold air currents in houses, over shading trees, attached shade house, white exterior and interior surfaces, and clear path breezeways are essential design strategies both in equatorial and subtropical climates. In many continental subtropical locations, we are faced with dual problems of quite intense winter cold, with some frosts, and rare snows, and very humid and hot summers. Thus, the sort of house we need to build has several unusual characteristics, and needs perhaps more careful planning than either equatorial houses, where reducing heat is the only problem, or temperate and boreal housing, where providing heat is the only problem. Figure 19,12. Water continuously fed to terraces. Stone are needed. Deep border ditches hold fish or shell fish, vine crop and bun crop assist yields or provide mulch. 261. Bithwim. AIV. AEN. IBSF. WIME. FM. SSFAMS. Venvergrass. VETEVAGIA2IZANOIPS. Lemongrass, Syngopiogo and Citratus. Figure 10.13. Vetiver or lemongrass strips. Provide cheap erosion control on contour or bund stabilization, both. These grasses clump readily, have few seeds, provide mulch, and hold soil movement. TION. Total improvement. A system with CH per please. Is times the sorghum. With 4 CE the QD. Equals 6x increase in TET. Efficiency for semi-arid areas. 262. The subtropical house needs to both heat and cool. For heating, it needs to have an insulated slab floor or trompe wall, and for the cooling system it needs induced or forced cross ventilation from a cool or shaded area to an updraft area. The secondary effects of high humidity range from the merely annoying, salt will not pour, to far more serious effects, clothes, food, film, and books mildew. Thus, we face two sorts of problems in house construction. Asterisk human comfort. Asterisk safe storages, for these we need both cool and warm storages, but both need to be dry. Human comfort is greatly aided by these factors. Asterisk shade, light and heat are both excluded as incoming radiation in shade. Shade is particularly critical on massive walls or over water tanks close to homes. Asterisk transpiration, plants can assist cooling by transpiring. Partial shade helps this factor in understory species except in extremely wet conditions. Asterisk cool bodies, large heat reservoirs used as water tanks and relatively cool blocks of shaded stone, concrete, and mud brick absorb heat from the air and from warm bodies. Conversely, hot radiant bodies adversely affect us. Asterisk air flows, even low air flows from shaded areas, greatly aid both transpiration and evaporative cooling. To create such air lows we need to develop both relatively hotter and colder air sources and to provide a type A terrace. Figure 10.14. Variations on terrace culture. Wet larais, potty, fish crop, shade house or grow tunnel, ridge crop. G. Peat. Fine terrace. BS. SE. U. Itres B0. Sphere. Asterisk. BIL. TET. IOE. LNT. TP. AES. SERAT. I. AET. F. APSA. AO. S007 equals F. A4. GF. A. Facet terrace. Alternate dryland and WEL, potty, crop suit summer wet subtropics. Figure 10.15. Terrace culture. The sloping side bank here is shown planted to ideal mulch. Trees, cut. Of coppice show enrich terrace crop production. Drain pipes are adjustable to dry out terraces. 263. Cross-flow airway. Even a fan, simply stirring the air, semi-detached kitchen in the tropics. Commonly, these aids in human comfort are reached by a vine-covered shade area, are asterisk removing heat sources, all massive themselves shaded by palms or trees, and have wide cook stoves and hot water systems are best placed on eaves and ceiling vents for hot air escape. Figure 10.16 dBl. Gross ventilation for houses. Vars corn san rahau rato me sepa and CPL alas AR. Enter. OE. A WR yin YJYYF. Y. Cree air fill ABI. Figure 10.17 asterisk trademark MB Dodges. Cool air from shade house and buried F pipe. SE. Paleotesi. AQSX05 MTUM and 20 MNGOU and NWS equals. Intake to dehumidify and cool equatorial air, with a solar chimney to a draw air through the house. Compenia TIO and DNs OE. 264. Heat can be used via metal roof areas, hot water storages, and attached glass houses or solar chimneys to yent hot air and create updraft, which in turn provides a heat engine to draw in cool air. The essentials of good cross ventilation are that the flowing air has a simple pathway to follow, no unnecessary comers to turn, and that large vents are used to allow a good volume of air through workrooms and storage areas. Figure 10.16. Probably the best cooling systems in tropical houses are those which use a hot roof or metal chimney to draw in cold air from earth-cooled underground tunnels or pipes. As this cool air is dense, it will naturally flow downhill or sink to lower levels. This cool air can be drawn into houses via a positive exhaust system, or actively fanned into rooms. To cool a pipe and lead off the heat continuously, we need to construct a trench 1 m deep and 15 to 20 m long. Cut in the earth, drain off the condensed water, ideally making it set draining to a lower slope, and provide this trench or pipe with a sloping floor. The intake end can be box screened to keep out mice, and shaded by plants. Outlets can be floor grills or a loop cup board opening to the pipe or pipes in the trench. Figure 10.17. Natural cross ventilation can occur if a well-sealed room has a roof vent or chimney to create an updraft. Some forms of air scoop may help this process. The cold tunnel solution is very effective, and can be used together with evaporative cooling in desert house. But it is also expensive, and difficult to fit to an existing house. For this reason, many homes can be sufficiently cooled by the use of vertical shutters acting as air scoops, a satisfactory solution on subtropical trade wind coasts. Or a shade house can be added to the poleward side of a house and cross-ventilated to a well-vented greenhouse on the sun side of the building. Basic essentials of the equatorial house. Some essentials of truly tropical housing: no cold season, are side choice. Asterisk orientation is to prevailing winds, not to the sun. Cooling is by cross-ventilation. Asterisk shaded valley sites greatly aid cooling and shelter. Asterisk induced ventilation is essential, achieved by siting in palm groves or overshaded by trees, which should be permeable to wind at ground, house, level. Palms and trees can be pruned up the trunk. Asterisk site sheltered from hurricanes, tsunami, and volcanism, sited on stable soils that resist mud flow in heavy rains. Asterisk walls white or reflective, overshaded by wide eaves and palms or trees. Asterisk heat sources such as stoves and hot water systems detached from the main structure, e.g. outdoor kitchens. Asterisk we material light, even permeable to wind. Woven matting and mosquito screens. Asterisk mass, if any, internal to rooms, smooth and white painted. The whole house can be of light. See nutrition on the outer walls. Asterisk vertical loops and window shutters aid in heat losing globe. Figure 10.18. Cool storage strategies. A cold air tunnel can open first into a pantry area, or a half-buried cool store for root and fruit crop. Cross ventilation. Registered in hurricane areas, a strong central core or refuge may be needed, or an earth bank shelter raised to protect the house. Cellars should be entered above ground due to flooding danger in hurricanes, or well. Asterisk very strong cross bracing, deep ground anchors, and strap timbers may be necessary if powerful winds are known to the area. Large bamboo groves placed to the windward will bend to the wind without breaking, protecting the house. Where thatch or tile is impractical, use a vented sheet metal roof, in this case a thin, 12 mm board. Telling is necessary, and soffit lining can be of able netting or screen to allow an airflow to the roof space and vents to the exterior via high roof vents. 10.6. The tropical home garden. Seasons. The wet season is the hungry gap, where plants are growing, but too young to harvest. Early in this season the soil is soft enough to plant and establish trees, but plants must be well timed as the dry season is long-lasting. Planting too late is to risk drought. Before ripening of the crop, vegetable crop is started at either end of the wet season. Water storages, Chapter 7, are essential, no matter how modest, for garden, tree, crop, and diversity in yield. Molds, mildews, and root fungi are encouraged by humidity, and it is best to use resistant plant varieties or rootstocks. Species: mango, papaya, sapote, banana, limes, coconut, cashew, macadamia nut, breadfruit, mound planted avocado and pineapple, durian, and so on are the garden and orchard framework, as are any productive palm crops. Large legumes such as inca, gliricidia, lucina, cajanus, and so on are essential interplants. In the vegetable garden, yam and sweet potato yield better than, or in place of, potato. Adapted small fruits and tomatoes of wilt-resistant strains grow well. Amaranth is a good green and grain crop. Lima, velvet, and dolichos beans trellis on tree legumes. Forage and ground legumes provide green mulch and help suppress grasses, as do comfort and lemongrass. Chilies, peppers, and the range of tropical vegetables are preferred to temperate species. Bamboos, balsa, teak, palms, and mahogany provide structural and craft materials. Rattans can be encouraged along waterways and in mangrove edges. Oil palm, jelly palm, bactras, morantia, salic palm and doom palm provide trusses of useful frizzets. Pests, large insect pests, locust, cicadas, sucking bugs are plentiful. Guinea fowl or chickens on tange are some defense. Native rodents and pigs can be damaging, and pythons rather than foxes take poultry. Termites and ants largely replace worms in soil building, and buildings must be constructed to resist them. Geckos in houses eat many insect pests, as do wall spiders. AE. WATE of F. Pain 10.19 rips equals grain storage system. With its lid sealed with mud or tar, and with an air dock for carbon dioxide escape, a nearby ferment provides oli which kills pests. Stores radon phones to allow chicken control of termites. RNA. Me ESSSRW. Pick Ajax. PE seal of gum muse, QET, UPOUGI. Shade Myo. All. To range N. Conti RO. Ds. Low EY. Pi. BST PI E. Equals a // OSNet. 266. Domestic animals, pigeons and bees are most easily protected from predators by elevation on pole structures, or over shallow ponds. Guinea fowl, franco, lin, pheasant, and bantams provide essential foraging and insect control services. The guinea pig aids small tree establishment as they chip the base of young grasses, and small pigs of Taiwanese strains provide orchard fruit garden scavenging duties. Waterfowl and aquatic species add yields to water storages and assist in grass control. Hurricane damage can be limited by raising large earth banks, selecting valley garden sites, screening plantings with bamboo groves, establishing a general tree canopy through garden and plantation, or a combination of these strategies. Oversized swales aid wet season water runoff control and diversion to storage. Specialist crop. There is a wide range of specialist crop potential, from rubber, hevia, betel, nut, chamogra oil, and chicle to essential oils and medicinals. Many are suited to primary processing in remote locations, or conversion to commercial quality end products. The high value of processed product enables smallholders or cooperatives to pool research and processing facilities, and to select high-yielding varieties. Interplant, as well as the essential legumes, A. Cedar of Banksia, Casuarina, Gigas vermicalis bora, and Pultinia with their mycelial associates will fix phosphate and return it via leaf mold. Several plants pump sugars or carbohydrates into soils, while leaf-sucking insects and scale insects exude sugars. Figure 10.20. Anchored. NIMIME. BAT EIHSNM. PO. ES. A. ET. Earth-sheltered hurricane houses. Based on Japanese typhoon-proof coastal housing, bamboo groves provide a flexible wind barrier. Earth mounds, houses. WEL traced and CESCEPRA. 267. Figure 10.21. Equatorial house. Based in the Fijian Beret. Earth-sheltered and well-fastened. Traditionally by complex rope cross-binding, this house is ideal for hurricane areas, cool living, strength, cheapness, and uses only local feel. SRES. Set to it. Plan we. Of whale /res. Strong. Set founds tons. A per Ufic. Ud mass. Is I loss. Overage. Drains. Foot 36 vo. File LEC. Figure 10.22. Hurricane garden. Sunken between earth berms or in natural sheltered valleys, palm and bamboo to seaward. Heavy emphasis on root crop for emergency food, fast regrowth. House well braced and anchored, low profile. 268. From stems. Dilute molasses or cane and sorghum sugar. Juices and stems also activate soil fauna. Marigolds. Neem tree leaves or berries, and pyrethrum daisy. Control soil pests and provide insecticides or water. Insect control. The neem tree is often planted to overhang ponds, so that the berries that drop control waterflies and mosquitoes. Establish tough grasses of the savannas resist gardens, and need to be mulched or overshaded with tree canopies. Essentials are asterisk to mount or raise garden beds for good drainage in the wet season. Asterisk to use mulch and mulch tree species to create topsoil for gardens. Where logs exist, they make ideal garden bed edges to hold mulch and soil. Gardens have been devised for many tropical areas, may containing the following. Asterisk designed for full nutrition for an average family. Water conservation and safe water disposal. Hygiene, a necessity. Species poem to suit local cultural preferences. Asterisk sufficiently varied to survive reasonable climatic change, or seasonal irregularity. Asterisk protein sources, livestock, their forages, or grain/legume replacements for meats. Asterisk water routes and use. Asterisk basic foods or staples. Asterisk fresh vegetable and fruit for vitamins, minerals. Varied uses. Asterisk some fuels, medicinals, flowers. The elements in figure 10.23 are those that make up the house structure itself, and those that make up the garden, hedgerow, livestock, and path access stroke. Tours. The best way to use the section is to read it through very carefully, study the plans and diagrams, and then improve it, or better it to fit to a specific site. The house room size and number is adjusted to family size, but is basically a simple, easily heated and cooled structure, preferably on slab or raised pise floor, and preferably edge insulated. The induced cross ventilation acts to cool and heat as per figure 10.16. In addition, vertical sashes or shutters to each room help to scoop air in. In hot periods, the main living area is outside rear, or under a similar porch trellis to the front if the people prefer to be seen from the road, as is the case in most close-knit societies. The side trellises are seen in figure 10.17. Materials can be local, as can any insulation. Glass is needed, as are some pipes or drains of stone. And a tank. The garden. How the garden works, see figure 10.23. First, it accepts all water and wastes of use. Only plastic and glass or metal are not used, although some cans may be buried for slow zinc and iron release. Second, it provides most mulch and a lot of fodder or forage. which when bulked out by house scraps should feed rabbits, guinea pigs, some poultry, and even fatten a small pig. Next, it is very accessible and well designed. On a need to visit and tend basis. It is also very natural in appearance and function. If no septic tank is present, a dry toilet will do, and the manure can be put under trees, in pits. Even toilet paper can be built into the hedges. Nicotiana is great, as is Lucana. Accessories. Hot water for showers can be achieved by a hot water collector or at least a coil of black pipe on a roof or bare area. With a couple of oil lamps or a photovoltaic array. A solar oven on casters, an efficient cooker, and a small solar food dryer, life should be fairly cheap and healthy. Adventure can be sought in teaching neighbors how to do it, writing novels, or joining an adventure camp group or even a permaculture group. They behave very diversely. Gungam is mandala. In Taiwan and the Philippines, small intensively planted home gardens are planned to feed a family of 5 all year. One have added to these designs my own permaculture lease path layouts to give a very concise and effective model of sustenance garden design for tropical and subtropical regions. These can also be adapted to temperate regions using suitable species. The overall pattern can be altered to fit almost every side form, but is presented here as a flat side pattern. Although the building of such a garden is fast and simple, its design is sophisticated. The whole design owes much to the work of the East-West Institute in Hawaii and the Samika Gardens of the Philippines, but the layout is purely permaculture. Have named it Gungam as mandala, after one of our Karnataka, India, permaculture design graduates. Steps in the process are: 1. At the center of a 100 square meter, 1075 square foot, or larger area, describe a circle 2 m, 6 feet, across, and excavate the topsoil, or subsoil, to a dish shape, ridged on the perimeter, and about 0.6 to 1 m, 2 to 3 feet, deep from hollow to rim. This is a banana/sweet potato/papaya circle garden, as per figure 10.26.1. The whole circle is then covered with wet paper or wet cardboard, banana leaves, or any mulch material, and the hollow is filled, or overfilled as a dome, with rough mulch of short logs, coarse twigs, hay, rice husks, and sawdust or indeed any humus-creating materials. A little scatter of manure, ash, lime, dolomite, or fertilizer can be added. If stones are available, bank them to the outside of the rim. The rim is then planted to 4 to 5 papaya, a tall variety, 4 or so bananas, dwarf types, and 8 to 10 sweet potato. If available, yams or taro can be placed inside the rim. Later, beans can be planted to climb the papaya and banana stalks. In the banana circle, we can place a grid. 269. ABT. F. AOLE at VE3. I. HS. HQ. BLE. M equals. I equals asterisk pike. ID. SE3GS. G4 \E. Pound bet AEOL. SAEEE. NGIOA or SVIA. Airs E senior. C. AXBA AEF4. VN. STPSA. What and SE hates. Serie Iather. Figure 10.23. Elements of a total design for a garden. Based on a Brazilian design by Margaret Kennedy and the writer. Climatically appropriate house of local brick and tiles amortizes in 4 to 7 years if a garden is developed. All water is caught or directed to gardens. High, an entry. In the subtropics this is a glass house, fitted with a wide ceiling vent and drawing cold air in from H6 the State House. Note the straight-through airway via living area, H2, and winter. Kitchen, H10. H3, 4, 11, bedrooms and study library if needed or possible, all. Open off or into the central kitchen, hid, hang axis, Hertz. HS, the bathroom oilet. From here, shower water goes to the wet area of garden, A, or to mulch forage crop, E, toilet and sink water. Art AC hand basin water goes to 8, banana circles. The shade house, which can extend around 3 sides of the IOE St. Urtine trees, or their trunks, in IL, minor treadleys resting against it, and a crop below. High, is the peri-paved area of the summer kiln, AHD the outdoor cooking stove and bulk cooking stove, the ashes of which go to A, C, and the garden. H and, mudroom/pantry off the kitchen, with outside basin/sink door. Primary vegetable processing. Table scraps go 19 livestock or below mulch in boxes, B series, of the garden, sweepings to mulch. T is the tank, catching root water. There is a sichel tank, IINE. Animal shed. The tank can also be sent filled from a reticulated water system, on a flow valve. All tank overflow goes first to A, the wet garden bed, which is in part under the house trellis, in part in the open. There is a path, PF, around the whole house and to the outdoor kitchen, animal house, etc. The garden has the following main elements. A is a wet food patch with earth bank edge, detail figure 10.24. This receives clean water and grows wet crop, at point 9. Laro, rice, kangkong, watercress, Chinese water chestnut, etc. The bank is planted to dry staple foods, at point 9. Yam, sweet potato, cassava, etc. Which benefits somewhat from the wastewater. Some of this crop is under partial shade, which Terra appreciates, as do some over subaquatics. B are banana certs, see figure 10.26. They can also be papaya circles or mixed papaya/banana/pigeon pea/tomato yam circles, of any such combination. They are watered from the hand basin and kitchen sink and mulched inside from the hedge. E. C is the dirty water patch, figure 10.25. It contains no direct food plants and aory crag, only vigorous, damp tolerant, manure-tolerant green forage crop, sentachi, comfort, batina grass. More. 040 degree are avenue crops of maize, or side main crop of value. 2 layouts, spiral and zigzag, are shown, detail figure 10.27. They consist of silly mulched and stable intercrop systems, such as maize, beans, yan beans, cassava/beans, or melon/beans. Plants of Leucina, Gliricidia, Sechania, or some such productive chigendalk sticks from these go to the fire, ash returns. Clippings from E or exotic mulch, paper, carpet. On these beds, leaf-trimmed hedge of forage mulch species, and 35.2 windbreak and a sometime food source. Just. Dense weed barrier, W. In 2 places this hedge is pens, yen and 2 yen. Where there are spots it means PS. NISES. Ha. Of simple, edible shul, solid bamboos. 7 E pay E partly for mulch. Fe. AFT or showy flowers, if the culture. A few basic medicinals, pleasant scents, a fibra. Plant or two, to help the trellis, a few ornamental food plants, cacti. Sonnet, and se saley weed sod plans mosca are here. Piv agb den beds, pidgey. To either side of the use fr lage fame, and more to the rear if. Mecticus me in pith ece greens, are here. The nearest bed to the kitchen has the usual bulk culna but. Some of these are also on the small spiral herb bed, figure 4.34. Beside HB, the outdoor stove, and a few wet area herbs are in pots. Under the trellis in the A pond, mint, some rare dry area herbs may be at or near the front door, F. The two trees near M8 are lemon or light and an allspice or caper. Tree, shrubs, really. They placed near the house as they are the most used trees in the system. The rest of THAG beds are Carololi plant seasonal vegetal. Crop. They are mulched from the hedge and the pit. Some food. Scraps, ashes, mulch, and shredded paper or plant waste are dug into them in little pits. Of 5 are their own crop waste and the cuttings from the windbreak plants, W. They are always in action, full of plants. Water is bucket or reticulated from a main system. Shower or bath whaler can also be used, if run along a length of low pressure Leahy pipe. This a fuckfocus style grain plot, mostly for people and partly for poultry. TL has a low surround of dry tolerant mulch such as Wobut is also mulched from the hedgie and the palm. K. K is a circle or clump of 6 to 12 pames, of 1 to 4 species depending on site, tastes, availability, and needs. They ideally would be 2 to 3. Coconuts, 2 OL. Palms, 2 dates, and a sugar pame, but may be simpler. The inside circle is malted with fell chopped fronds, their husks and wastes, ashes, and broken hedge material or mulch brought in from other sources. In this deep mulch, a yam or vine will grow in the wet season. Every dense black spot is a tree trunk. These are carefully selected trees, and their crown spread is indicated. They can overshade the house roll, and may even be placed inside the house trellis, with holes in the roof to allow the trunk hole. These few trellis trees have light crown and slash or troots that fall or that can be brought down BAOIS at the roof. They are intended to shade the roof area and can be tough. Spreading legumes, prosopy is good, yielding a food crop for livestock, or they can be palms, or a thin foliage tree. Other trees are producing staple fruits, a few avocado, on mounds. 7 high-end and I'm across in WEL roses, RAS, 2 few knollies, and an oil palm. They have soft ground cover below, nasturtium, sodal, legumes, comfort, and this is sometimes slashed as mulch for the tree, sometimes fed to livestock. The little hashed areas are the roots of rabbit hutches and chicken roasts or pigeon lofts, quail houses, or guinea pig rest areas, depending on the culture and preferences. A lot of the hedge, E, the wet muisset, G, the tray hen bear, and the spare corners are devoted to plants chosen just for the animals. Each lit roof catches some whaler and leads it to a small tank of the garden or bath. Yen-2, these are 2 fenced areas. They are changed over to suit the animals, and while one is rested, it can be cropped if space allows. Both are well-shaded animal runs. The fence can be of woven barn palm rib, band of grass, stalks, or of wire netting. Both areas are timed if sour. The house trees areas are very carefully fitted up with vine crop space to let some light through, 30% LS vine. Basic vines such as chayote, kiwi frol, beans, cucurbits, and grapes are carefully chosen. For the house treadleys, which can extend 1.5 m above the whole roll area if the roof is sound and solid. 1 or 2 non-bearing vines can, in fact, be let rampage over the roof with great benefit to the cooling of the house. Knolls, however, the type of goiters needed in this case to mulch the roof runoff, figure 7.21 and 7.22. On the sides of this trellis, more ephemeral bean and cucurbit crop can be grown on leaning trellis of bamboo, or separate bamboo trellis can divide the G beds. There is no vertical limel to some vine crop, and if water permits, every palm in the K clump can eventually carry a high vine, granadilta, grape, or kiwi fruit. A 5 can any large leguminous tree. Otape, kiwi fruit is 100 dense. Linder the tree flees a few shade tolerant. Plants will grow, coffee, taro, AFL, or platform of wood over the mulch, and this then becomes an outside shower or wash up area. To a circular sunken path 0.6 to 1 m, 2 to 3 feet wide is covered with sawdust or gravel around the central circle garden, and off it, 5 to 6 keyholes or indentations are made. The system now looks like figure 1 0.26.2. 3 around each keyhole a bed 1.5 to 2 m, 5 to 6 feet wide. Is first edge banked with soil 100 to 200 centimeters, 4 to 8 inches high to prevent water runoff, and the beds are then papered and mulched. As for the banana circle, the whole garden now looks like figure 1 0.26.3 in plan. The thick lines represent low earth ridges. Thus, we have 6 major keyhole beds, each of which is separated from the next by a thin strip of lemongrass, Sympopogon citratus, or vetiver grass, vetiveria, zizanioides. Just outside the periphery ridge, strips of lemongrass, comfort, and arrowroot, Canaidalus, form a kikuyu grass barrier, and behind that, a taller border of cassava slash banana slash papaya slash pigeon pea slash lucina slash crotalaria forms a hedge or windbreak. All these borders give mulch, forage, barrier effects, or food. The whole mandala is fenced or has a spiny woven hedge boundary for cattle exclusion, if necessary. The mandala has now been earth-shaped and mulched to prevent water runoff and to conserve moisture. We now proceed to plant, using buckets of good soil to place the following zones of plants. A. On the track edge border of the central path and keyholes, within stoop reach of the path, plant those frequently plucked or everyday greens of high value. Here, the end selection criterion is that all the plant, or most of it, is picked for much of the year. These are the pathside greens. They include all the chive and shallot species, plenty of parsley, coriander, thyme, and sage, celery, broccoli, edible chrysanthemum, chard, and any such long-bearing or perennial greens, e.g. various perennial spinaches. This is therefore a narrow border to the inner side of the keyhole beds. Planted in the rich soils there. Be behind or outside the pathside plants, we plant a 1 m, 3 foot, wide strip of species which are frequently picked over a short to long season, e.g. tomatoes, eggplants, bell peppers and chilies, bush or staked, beans and peas, kale, corn, okra, and so on. These are the narrow bed plants, all within reach of a path or keyhole. As yet, we do not need to step on any beds to harvest. See just out of reach, on the outer borders of the Keyhole beds, we place most long-term root crop. Potatoes, sweet potatoes, carrots, or any crop we cut and remove, cauliflower, head lettuce, and cabbage. Thus, for this crop we step, once, on the bed, to harvest and replant, following root crop with fava, beans or dal, dried beans or lentils. All beds are replanted as they are harvested, and a top mulch of straw, sawdust, bark, dry manure, or chips is added annually. Rabbits, guinea pig, chickens, or small livestock are fed from weeds, waste vegetables, household scraps, and forage greens from the border. Hedge, comfort, cassava, leucaena, or lemongrass, vetiver grass, lemongrass, etc. are cut 3 to 5 times annually for mulch. The roots of vetiver grass prevent rodent burrowing from outside the system, as do the root masses of euphorbia species. All trees, shrubs, and tubers are planted before papering and mulching, then about 30 centimeters, 1 foot, of trodden down and wetted mulch is added. Tray. Seedlings 8 to 10 centimeters, 3-4 inches, high, and large seeds, such as peas or beans, are each planted in a hole, burrowed in this mulch, with a good double handful of soil to each hole. Small seeds, lettuce, carrot, are tiered thickly on lenses of soil 50 centimeters, 1.5 feet, across and 5 to 8 centimeters, 2 to 3 inches, thick, placed and firmed on top of the trodden mulch, followed by dusting over 1/2 inch, thick layer of fine soil. All seed can be pre-soaked. The whole bed needs a good soak with a sprinkler at each stage. If no weed seeds are included in the mulch, the beds are weed-free. It takes 9 to 15 months to build up worms and a good soil. Any surplus compostables can be pushed under the top mulch layer. A larger system, designed for a community kitchen at a rural center in Karnataka state, India, uses a core assembly of 4 to 5 banana circles and has 8 to 12 keyhole beds. In this case, a keyhole accesses the banana circles. Figure 10.26.4. Any one of these banana circles can contain a small. Figure 10.24. Detail, wet food patch. Roll and tank overflow plus gray water can irrigate a wetland mulch. Garden of semi-aquatic species, banks except dryland species. MIT. YSI. So. Peepfok FSH. AMTERSVRP's water. 272. Pond for frogs and water convolvulus, or taro, we can plant alubina or palms for high shade and mulch, at the junctions of the keyhole beds. The hedge surround eventually provides the annual mulch, figure 10.26.5. This garden is intensively planted, has very little path per bed area, is easy to build and maintain, provides everyday greens, minerals, vitamins, allows no water runoff, and can be built on airy substrate, rock, concrete, roof areas. Rainwater harvest, eventual self-mulching, various weed and animal barriers. Small livestock fodder. Overhead shade, non-dig gardening, least path. Access, direct wastewater disposal, and a pleasing design. Avenue cropping. The system described here is adapted from Ray Wijeward, 1981, Conservation Farming, IITA Sri Lanka Program, Dharmapala Colombo 7, Sri Lanka. It is a deliberate fuel wood / mulch / soil lime improvement crop integration of great use in the tropics, but adaptable to any climate, with good species. The essentials are simple enough. Correct spacing to shade the ground fully but to allow cropping between the tree legumes. Asterisk lopping to leave stems 0.5 to 1.0 m above ground. A suitable tree legume is Tagasis or Leucaena. Asterisk sowing of crop just before rain or irrigation, to beat the growth of weeds. Asterisk possible 2-crop sequence, with mulch also turned from crop wastes. A very similar system is used in Africa with Lyricia, and more recently in New Zealand with Tagasis. As the green crop, a parallel system, regular or irregular in ground plan, is successful in establishing small trees, which otherwise perish from frost or in open grass competition. At least 2 problems arise in sustained coppicing of legume trees. Firstly, such coppice should be confined to warm wet periods, allowing mature leaf to carry over into dry, cool, or frosty periods. Secondly, constant coppice weakens trees over 5 to 8 years, and replanting is necessary. Very few legume trees will sustain constant coppicing, and other strategies are called for. Perennial, thin-crowned leguminous trees can be spaced throughout the orchard and garden, or fast-growing, and short-lived legumes can be allowed to grow and die, or can be ring-barked or felled on a 2 to 5 year cycle. However, with permanent high legume cover, mulch can be obtained all year from a variety of non-legume hedge and understory. Such species as Nicotiana, Echium fastuosum, lantana, cinnamon, even clumps of daisies, wild ginger, lemongrass, vetiver grass, painazetum, and crop wastes from maize, cispania, and soft ground legumes or comfort provide constant mulch under high legume cover, so that the coppicing of susceptible legumes themselves is reduced or eliminated. In any evolved system, avenue cropping or mulch provision can be sustained by a carefully planned system of mixed non-coppiced tall legumes giving a seasonal leaf drop, erythrina, tipwana tipu, and a row series of non-legume store ground mulch. Barrier plants. There are several reasons to erect barriers of plant. 5. Asterisk is a block around the annual garden to resist invasive grasses, such as kikuyu and buffalo grass, knotweeds, etc. As a corral for animals, or to keep grazing animals out of a compound, or to guide animals to a gate or commissary scent. Figure 10.25. Detail, dirty water patch. Sewage fed to a mulched 5x8 m stone e-pill allows a surround of useful species. Mulch can be grown in the pit. Corada. Feasley. Lu. 273. Gor Sangam was 9 BAAO. NE, ACB. I bananify Savell with shower wash art fitted. B Sajuated, Vice JWSKS, OB gravel path. GC keyhole paths as B above. D keyhole heads at path side plus knock out bed plants 01 vis right plants. ET wind, animal baby hedge. Sequence 0-9, IME outer, Vedavia. Lungri, Combine, Ababak tall of hedge pose, Papaya, Vitalabi R. QCI pigeon P odd banana. DT and Gafkan ES Avi Lakakna OB palms fob shade in head visions. 2F4. Figure 10.26. Gun and Bimas Manola. An ideal lease path, 0 runoff, accessible tail for tropical home gardens. Figure 10.26.4 shows how this mandala can be scaled up for group gardens at schools, villages, etc. Gangamia is an Indian permaculture stunt. NEAE. At IESLEW. Figure 1. Figure Z. Of Nulave. The keyhole paths. 8. Mulch OB Avenue equals banana circle. 275. Corral. Asterisk against hot, dry, or salt-bearing winds, on seacoasts, cliffs, or exposed sites. Asterisk is contoured strips to disperse overland water flow, to catch silt, and to prevent erosion of soils. Garden barriers. Around annual, mulched gardens laboriously freed of weeds, a band of grass barrier plants prevents weed reinvasion. There are 4 to 5 forms of plants which are effective, and all of them can be used if space permits. Asterisk a deep-rooted broadleaf, e.g. comfort. Asterisk a clump grass which does not seed down or is not browsed, e.g. lemongrass, vetiver grass. Asterisk a carpeting plant such as sweet potato, nas. Tertium, or impatiens. A dense low shrub, oncopa, corpusma, echium. Asterisk a bulb such as canna, agapanthus. In total, the same plants can form a fire barrier. Provide ample mulch for the garden, and if initially cared for, establish in one season. When first placed, they need to be mulched, manured, and watered. Animal barriers. Corrals or cattle goat sheep barriers can be strengthened with 1 or 2 strands of barbed wire, but should have the potential to resist on their own. Thus, they involve thorny or distasteful shrubs. These can either be planted as a hedge, or as a coppice crop, which is cut and built into a thorn fence, boma. The latter enables more flexibility in changing the arrangement of compounds, while the former is less trouble. Species ideal for such bomas are Lycium faro, Sisimum, Acacia tortilis, Oncopa spinosa, and Euphorbia tyricoli. Of these, only Lycium and Oncopa may not need ape. Z. Figure 10.27. Avenue cropping. Coppicing legumes, Leucaena, Cassia, Acacia, Gliricidia, etc., cut. Annually provide nitrogen and mulch for intercrops such as maize. Equals I. Sweet potato, ginger, pineapple, crop wastes are returned to field. Firewood is a byproduct. 276. 1 Principles and Design. 2 PT Augusta. SA, Australia. At first, acid rains from cars and power stations supply sulfur and nitrogen to forests and fields. This fertilizer, in the long term, becomes a fatal pollutant to life systems. The first signs of collapse are plagues AF. Pests like the ant moth. Asterisk caterpillar which infests stress trees. Principle of disorder number 1. 1 Maui, Hawaii. Lower slope clearing for cattle like the cloud base near and on Molokai. This loss of cloud cover reduce precipitation and lead to the desertification of the verdant offshore island of Kaho'ola'i. Now unoccupied, desolate, and used for a bombing range by the U.S. Air Force. Our ability to change the face of the earth increases at too faster rate than our ability to foresee the consequences of that change. Birch's principle number 5. Underscore. 3 Canterbury. Plains, New Zealand. This apparently ordered landscape TS maintained only by excessive work and at real energy cost. Such systems are disordered and represent chaos in lead systems and produce too variety of pollutants in air and water. Principle of order number 2. 4. Over Montana, USA. Great energy spent on center pivot irrigation can in 3 to 4 years produce desert by evaporation effects, water run OW harvesting AMD. Perennial plant systems could lead to harmony in this desert landscape. Principle of stress and harmony. Me 5, Wilton, NH. A USA. Careful site observation. All natural processes. And here the author assesses a woodlands on Samuel Recaiman's farm in early fee spring for forages. Microsites, SNDW melt. Effects, wildlife refuges. And lil leader distribution. Leading to appropriate design strategies. Methods of design number 2. Copyright, observation. 6 Wamikata, Central Australia. Following observation of runoff into Zary's rock can be used to direct water to one useful tree. Such strategies arise from observation of rain effects and tree distribution around Inselbigs. Methods of design no 3 deductions from nature. 9 Stanley, TAS, Australia. The double spiral of seed in a sunflower head, counts of seed reveal. 2 Pattern. 7 Buffalo, WY. USA. This section of a cottonwood limb cut by a chainsaw resembles the general model. The summation series or Fibonacci numbers along each spiral band. 11 Stanley, TAS, Australia. A spiral of spirals of spirals. This range of orders of similar forms is basic to fractals. It can be seen in many phenomena here. A. Romanesque broccoli. An aberrant chugaro erupts into an overbeck copyright jet, and the stem reveals copyright increasingly turbulent growth. 8 Stanley, TAS, Australia. This section of a tamarillo also resembles the general model. Tucson, AZ, USA. I. Yen. 12 Vernabella, SA, Australia. P. Jajantara women transfer traditional patterns to new materials, here. Using a batik, wax dye, process to print fabrics. Older patterns were made in sand. 3 Pattern. 1314. Vic, Australia. A sea snail egg seen from its underside. Conical form, crenellations, and estuary reveals the nature of flow here, a Von Karman trail. And spiral slots all ensure excellent stability in flow and self-induced flushing due to differing flow velocity near the sand surface. 15. Another Von Karman trail in a lava flow. 16 Deception Pass, WA, USA. The tidal flow in the narrows between Whidbey and Orcas Islands shows another Von Karman rail. 17. The unfolding of agape leaves reveals the imprint of other leaves. Von Karman trails show very similar increasing, or decreasing, magnitudes of flow. 18 and 19. Boar Farm. 2 Kent, UK. And a flow form system. The Beard. Photos show water switching. Plus naturally into alternate basins. Excellent for water aeration in a situation where volume is fairly trademark constant. 4 Tropics. Developing a food system. 20 Hawaii, the Big Island, Hawaii. Fresh lava flow has been crushed and leveled by tractor. Spot mulched with compost and macadamia nut husks, and irrigated. C21 for growth in 1 year. Steve Skipper inspecting. USDA trial. A. I7E. 3E and EY. Algae RETEEC 22 Molokai, Hawaii, LAT 28 degrees, subtropical. Chicken tractor system. Developed by Dan O'Gorsick. Foreground is 6 weeks of vegetable growth following the clearing of the chicken tractor, 5 pence in 0.5. Ha. Dano and his wife, and members of The Busby family stand at the front edge of a papaya system which is 2.5 years old. Chickens, Australorps, are moved from pen to pen. Over the year to clear weeds and grasses, they get most of their food from fallen papaya, seed, insects, and greens. Income from their eggs and papaya at the OO Cooperative plus home garden largely. Support the Gorsic. Emily. 24 Maui, Hawaii. Kikuyu grass. Here, people have planted tagetes, marigold, around their avocado tree to kill and form a barrier to the grasses. 21, Hawaii, the Big Island, Hawaii. Growth of trees in 1 year on a lava site. More extensive mulch. Enables interplant. Numbers 20 and 21 reveal that mulch plus water can establish valuable trees on apparently hostile sites. Here mango, citrus, macadamia, guava. Traditional Hawaiian garden VDS. Combines banana, papaya, smiley face, beauty, chili, and taro. Pigs fed. Fram surplus, chickens at end. Range below system. Developed by IMU and Rachel, Rahila, Naki. Together with fish and home garden, this is a self-reliant and commercial system. Equals F. 25 Kaiwaka, and S. Shea. New Zealand, fees. Instant garden or gauges. About 18 months previously, B3. This was pasture. K. Baxter first set up a small nursery, then set out, at one time, a windbreak of eucalypt and blackwood, acacia, melanoxylon, and an interplant of nasturtium. Comfort, sweet potato, SS. Ground covers, banana, cheese. Tag assist, taro, under story, and a scatter of biome. Citrus, apple, peach, etc. S5 and fruit crop. Grasses. Suppressed and the system co-evolves. Mulch from comfort, tag assist is thrown around fruit trees. 5. Getting rid of weeds, grasses, rampant species. See also play 22 small livestock. A sea of Kikuyu lawn is held at bay by a low barrier of canna, lemon, grass, and comfort. Part of the lawn, number 27, has been converted to a no-dig garden by Jack and Sandy Lewin. 28 Kualapu, Molokai, Hawaii. Electric fencing restrains pigs which root out and eat Kikuyu and grasses, leaving prosope trees unaffected. This can now be planted. And the pigs moved on. 100 pigs into each pens will tractor 40 ha in 2 months. Hawaiian homelands area. 30 Molokai, Hawaii. Chickens clear all grasses and weeds for gardens. Papaya, and arranged on the greens outside. Fence, papaya provides most of food. Equals 27 Kula, Maui, Hawaii. The reverse side of number 20 SIXS barrier planting is an instant garden of mulch over newspaper and cardboard which, laid directly on the Kikuyu lawn, obliterates that grass. The garden was built as a class exercise at a permaculture design course based on field observations of Kikuyu behavior. 29 Mullumbimby, NSW, Australia. David McGrath has grenaded an area of Pantano with Choco Sikiamatul, which has killed out, by shade the Lonatana, and covered his truck. This patch yields $120/week in fruits. Choco is easily removed by chickens or pigs, and the area can be blurred to orchard or crop. 6 tropics. Beaches, islands, and windbreaks. Sir Evo. Apte. 31 Oahu, Hawaii. 32 Maui, Hawaii. Profile of a stable sand beach with beach convolvulus, and casuarina. One stable coast eroding due to beach vegetation destruction. This shore can withstand severe storms. Recreation can destroy coasts, destabilize snowfields, and erode dunes, sand buggies. CSEAA. AI. 33 Nataba, Flul. 33 Molokai, Hawaii. A hurricane has almost cut this island in half, following deforestation of at the Molokai Plant Research Center. Tropical windbreak trials indicate the shortine, a fringe of mangroves, a hitopora, is restabilizing the importance of windbreaks in reducing stresses on plants and sea edges. On low coral islands and shores, the removal of coastal animals, especially on islands with salt-laden winds and consistent vegetation, can destroy the island quickly in cyclones, monsoons, and trades. 36 Kitwan, Nepal. Traditional low EU. Forbia hedge provides windbreak, a habitat for spiders, a section of bamboo, and demarcates a cattle lingway from mustard crop, Ifu. Forbia antiquorum is often so used, and e-bound. Tyricoli in Botswana, all need goggles when cuttings are taken to prevent eye injury from the milky sap. 35 Molokai, Hawaii. A live set, cuttings, hedge of erythrina, willy, and banda grass. Painazetum, shelters crop against coastal winds. The grass is cut for mulch, and can later be removed as the erythrina bushes out. Casuarina, lucina, or grevillea is often used as permanent hedgerow. 7 tropics. Pattern systems. E. 37 Garanda, Queensland, Australia. Some years of work by Marjorie Spear have evolved a very productive garden. Ever 2.3 ha, sited on the edge of a coastal lacing cliff. Night condensation of mist is heavy. Marjorie has stacked the garden with acacia, coconut, citrus, ferns, flowers, and mixed fruits to produce maximum yield in least space, with minimum grass or weed maintenance. Systems of this maturity demand management more than development work. Only access tracks are in grass. Real. 39 Kualapu, Molokai, Hawaii. Chuck Busby has developed mulch circle gardens, some with trellis fitted to form nuclei in exhausted pineapple farm soils. Mulching and watering and compact shelter is of banda grass. Note: rye yams and beans can use banda grass for support or tray. 47 Nimbin, NSW, Australia. Michelle and Jude Fanton use lemongrass planted on contour to hold steep slope soils, provide mulch, and create upslope planting sites for electreats. Lemongrass is also used in beverages and cooking. Vetiver grass is used in this way in Africa whenever stability is needed on slopes. Euphorbia trochale in deserts. 38 Nataba, Fiji. Clump coconuts, hair, 8 together, yield as well as spaced coconut. 32 412 M, fee up mere ground, a able spot mulch serving all trees, assist harvesting, and concentrate watering. Several plant species, e.g. banana, macadamia, scent and be clumped in this way, maximizing space for intercrop. 42 Kitwan, Nepal. Uma and MC Pereira have developed a more structured stacked system than in number 37, with pineapple and ginger main crop, edged with fucuna and lychee trees. Looking to provide fodder, fire U-pod, nitrogen in soils, and mulch. This system too needs minimal maintenance, and is no tillage, unirrigated, but sustains Yo, provides surplus firewood, mulch, and supports 3 to 5 adults on A. Dollar. Tropics. Irrigation and weed control. 43 Malanda, Queensland, Australia. Bob Kingwell has devised a simple manifold to lead water in 3 directions from a head drain. Pipes are plugged or open to allow flow in channels, using simple concrete plugs with rubber O-rings. 44. As for number 43, here Bob has fitted a head drain with cross stops to allow water to back up and flood the field to the right. Again simple. Pipes are used, carefully labelled. OO. AA equals_equals. At IEE1AO. 45 guinea pig shelter. 46. 3-4 guinea pigs manure, and keep kikuyu from choking, young lychee in lieu of guinea pigs, desmodium. Restrains kikuyu grass. This uses trees, they forage below the canopy, and are fed food pellets. Owls and more water than the guinea pig solution but does not need food. Pythons eat excess populations. Pellets. OE. GS. 7 equals. 5A equals E. 7 SSFI, RE. 2 OE equals Y. 47. Flood irrigation of papaya on slide ridges also waters. Green mulch. Desmodium carpets the papaya. Mounds, and comfort provides a mulch interplant. 9 drylands. 48 Kumba, NSW, Australia 49. Wilmington, SA, Australia. Desertification due to overgrazing. Collapse of soils and forests is goals reduce ground cover and make regeneration of trees. Evident impossible, the area needs swales, long equals rotational grazing, intensive. Cut forage for milk goats, in swales, a scene that could be of any semi-art area. 50 Las Palmas. Canary Eye Sounds. A tethered milk goat, fed on cut hay and cactus. Creates to a well-manured niche and bare granite rock. Alter this, an almond, fig, or chestnut tree is planted, oats regenerate. For hay. In this way, extensive orchards are developed in eroded granite country. See. Number 51. 51. As for number 50. A general view of an almond orchard developed in granite using goat and donkey manures. Small hayfields lie below this slope. Cattle or goat pens can be used in this way in any arid area. 53 Pyramid. Lake, NV, USA. OE. Gerard and Gus Fay. James of the Pyramidine. Lake Paiute tribe copyright. Examine Indian rice. Grass reseeded in sands. The seed is acid. Treated, buried 0.3 m, 4. And the glums flame 5. FORAC 4. Cooking. Onyopsis is a staple of the Shoshone. In this region, NA. Good perennial range. Forage for cold deserts. FP. It spaces itself to about 52 Wiluna, SA, Australia. 0.6 m between. Caves part excavated by Wallaroo, a rock kangaroo, offer shelter copyright bunches. Below a scarp edge, such shade sites determine the number and type of wild eid, idachi, lizards, Wallaroo pigeon, able to occupy and breed in Drans. Author takes refuge from the Sui. 10 drylands. 94 Port Lincoln, SA, Australia. Sand dune on hard pavement absorbs water and grows larger trees. The range is in fair condition. Sessile trees prevent sand erosion or trap sand on dune crests and sides. Flinders, SA. Asterisk Australia. Percent berry pills gathers. 4 sheets of guano from below tree roosts. Me beside a dryland. M dam pigeons and parrots visit for water and enrich area with guano below roost trees. 98 Alice Springs, Central Australia. Gabions rock-filled wire basket structures stabilize a floodway near Alice Springs, reducing flood flow and silt burden in the stream. 95 Poverty Flat, Sejuna, SA, Australia. Raised beds, sunken paths, perforated pipe irrigation, mulch, sulfur, and bentonite combine to produce a rich organic garden on an eroded sandy soil site. Water 1,100 ppm salt. Aboriginal students taught by Peter Bennett produce excellent crops in desperate soil conditions. 97 near Adnatata, SA, Australia. Hard bank, on skyline, constricts flood water to create a scour hole in river sand beds. Such effects can be created. 99 Charakat, Nepal. Gabions stabilize the steep hillside gully on the road to Charakat. A. Swiss design. 11 drylands. Housing. 60 Las Palmas. Canary, slants. A rocky arroyo, wadi. Canyon, gully, floods. Periodically bringing down large boulders. See. Number 61. 61 Las Palmas, Canary Islands. An arroyo IG part blocked by concrete stone band floor on right, and bled. A by at course trash screen to tunnels, galeria, and cave storages. Linked to irrigation systems at lower levels. 62 Kuniba, SA. Australia. Aboriginal gardeners dig an absorption trench from a kitchen sink outlet, in brick hard ground. Trench is plastic lined, manured, revigiled, and planted. See number 63. 63 Kuniba, SA, Australia. A few months growth in grey water produces abundant vegetable food, establishes fruit trees, cools area, and utilizes mulrents. Previously lost to a waste lagoon. 64 Lake Winnemucca, NV, USA. 65 Saro, Botswana. Flessional boulder benches on the shoreline provide a natural swale, setting out swales in thoracation to infiltrate overland flow for vines. System and infiltration, determining vegetation, range, distribution, and valuable hires. Sorghum and melon crop can be interplanted in Giver deserts, reg, can be swaled in this way for range species, thorn forest. See number 66 FSIG for swale growth in similar salt bush and useful crop. Rainfall conditions. 1 brown triangle. Periodic table key. The major elements of which soil is composed. 2 elements occurring in minute quantities in plants and marine and freshwater algae. 3 green triangle major nutrients in plant tissues and soils. 4 trace elements necessary to metabolic functions in plants. 5 catalytic elements involved in metabolic function and hydrocarbon processing. 6 blue triangle major elements necessary to metabolic function in animals. 7 trace elements necessary to metabolic function in animals. 8 elements critical or limiting to phytoplankton, aquatic organisms. 9 orange triangle poisons, radioactive isotopes taken up by plants and animals. Example. IRN 222, 1131, CS 187, TH 232, U 235, PU 239. 10 poisons, metabolic poisons, elements or their compounds dangerous to life forms. 11 elements specifically concentrated by bacterial action, root. Associates of plants, anaerobic bacteria or thiobacilli. 12 diamond states light blue, gas at room temperatures. Dark blue, liquid at room temperatures. 13 name elements name. 14 number elements number. XS. I. M on lanthanum. Borders. LACAE. Silicon. OS. ES. RI. AE. 6 RN. 14 swales. Maya. 66 Kuniba, SA, Australia. 67 Pumpinville, NSW, Australia. A swale under construction using a side casting grader in the dryland swale under construction. Of central southern Australia. Swale in number 67.6. Months later with watermelon, sorghum, and semcorn, cucurbits on the equals. Bank, and taro in the base. 69 Village Homes, Davis, CA, USA. Michael Corbett, designer/developer. New swale area being planted. 70 Village Homes, Davis, CA, USA. Another swale, heavily shaded by trees which are nourished by the swale soakage. Andrew Jeeves surveys the lush vegetation growing in one what would otherwise be a desert. /top. 71 Village Homes, Davis, CA, USA. A gravel-based swale collects water from a suburban road. Because of extensive swaling, Village Home sits on its own deepening soil stored water reservoir in a surrounding desert. Equals 15 drylands. We 72 Kenyon Deshay, USA. We so Easy's cluster like swallows nest in a notch at the scarp base of E. Cooper. Navajo fields and cottonwoods occupy the canyon floor. I 74 Kuniba, SA, Australia. Dust storms in settlement carry infectious diseases, bacteria, atsectolitis, and cause about 40% of sinus of asthma problems, and sear throats. Face broad NS streets need paving or realignment. Myriads of zigzagging houses are dust-fouled by winds. A GI. B underscore. Asterisk. Equals. 76 Detail of number 75. Detail of grasses in pits. Building. 73 Tafra Alta, Canary Islands. The facade of cave houses is all that reveals the dwelling, excavated in soft tufa, volcanic ash. The rooms need good ventilation to reduce radon levels. 75 Alice Springs, Central Australia. Extensive disc pitting per 600 square km has reduced dust storms around the town. 77 near Aspen, Co., USA. Traditional earth-up barn in high cold desert at Ford's winter hay. Searage and shelter for livestock, such barns are insulated by snow. 16 drylands. Building and settlements. AJE. 79 is for number 78. 78 Fresno, CA, USA. Underground orchards, hand-dug caves open out to shaded pits underscore looking up from underground, the sky is covered by oranges, roots. In. Containing fig, grape, citrus, and pomegranate. This house covers 2.8 pits are cool, easily mulched. The ground surface can be hot and was hand-dug by M. Forestieri. Funnel shaped to catch water and directed to plant containers. Lea. 80 Greenock, SA, Australia. Traditional buried dairy shed keeps milk and food cool. Vine, earth, or early experimental version of the Windstar Foundation's biodome. Tree shade assists cooling, uses solar electricity, heating ponds, domed greenhouse to grow. Tender crop year-round in high, 7,500 ASL, cold, dryland where the growing season averages 60 days. Frogs and finches help with pest control in greenhouse. 7 I/Opia and hydroponic vegetables are grown in the ponds. TS equals LEEELBALA equals IEOEOTEE. Yes. 82 Village Homes, Davis, CA, USA. 83 Roof of house in number 82. Ice plants and herbs provide active earth-sheltered house with solar hot water, turf roof, and slab floor, cooling by transpiration and shade. Provides good comfort control in the house. 17 drylands. 84 Las Palmas, Canary Islands. Puncha provides fruit, tuna, vegetable food, cattle forage, hedge, and is here hosting the conchyneal scale, used locally for food dyes. P.S. 66 Las Palmas, Canary Islands. Apple and pear crop is sustained by a deep, 0.3 m, mulch of an iron dot. Jeep cinder, technique using volcanic cinder to produce fruit, potato. OTing crop in an area receiving mainly night fog and condensation. Mr. 88 Las Palmas, Canary Islands. Many desert acacia sop provide abundant poultry seed, a 5-du lycium, SPP and solanum SPP, here. Kali provides abundant fruit and seed. Sutabta for chicken forage, many woolly solanum sop provide dryland fruits or pot herbs. 85 St. Teresa Mission, Central Australia. House veranda is screened with bryonia, a cucurbit, labab bean, and tomato vines. Such screens cool west and sunward walls, and are sustained by waste wash water and grey whaler. AE. 87 St. Teresa Mission, Central Australia. Gija, Acacia compagii, creates a desert mound. Orneca about 1.5 m high and 12 m acmes. Many sessile or weeping trees in deserts will cause dust accretion in this way. Acacia SPP in the rayon do the same, providing deep absorbent soils and mulch for vines, other trees, and burrowing animats. B9. Tucson, A. 7, USA. A spiny Deetleo hedge guards an Oodam, Papago, garden. This species is cultivable for fencing, can be measle to grow if irrigated, and is widely used as to reinforcement or base for mud wall construction. I. Is a useful crop in itself for desert structures. 18 drylands. Salting. A registered RE. 90 Bodlington area, WA, Australia. Deforestation, grazing, and wheat cultivation have produced widespread salting, here visible as collapsed soil at seepage lines. The i.e. barley greas, Hortum maritimum, is also indicative of soil collapse. Cone TEE equals S. Re H7. Key. 35. FPF. 92 Quay rating, WA, Australia. A farmer develops interceptor banks to run surface water and through flow off fields to a natural valley, thus isolating soil blocks for rain leaching and preventing a cascade effect downhill of salty overland flow or through flow. 94 Birmala, WA, Australia. An interceptor has prevented soil collapse by flooding, node rushes on upslope side, thus protecting crop below the bank. Spike rush. Juncus is another indicator of imminent soil collapse, surface flooding, and anaerobic soils. Subsoils are dry, cemented, or subject to groundwater rising. An interceptor BA. NKS. OEAE. OE. Underscore AE. Underscore IJ. 91 near Quay rating, WA, Australia. A closer look at a once forested marsh in wheatlands, now a salt pan. 93 Quay rating, WA, Australia. A classic interceptor bank, ending on the streamline as marked by the distant trees. A bulldozer has rammed subsoil on the downhill wall of the bank. Depth equals 1.5 m, width 4 m, spacing not more than 100 m. Apart, or, on slopes, 1 m vertical separation. Soil pit below this bank. Shows no through flow, no rising salted groundwater. 95 Birmala, WA, Australia. A series of interceptor banks in wheat fields isolate soil blocks from overland flow and salting effects. 19 Cool temperate. Establishing systems. 96 and 97. Collingwood River, New Zealand. Rampant gorse covers 280 ha, limes are rolled down or slashed, and eucalypt, pines, and acacia are planted by Dick Nichols. Zone 1 degree. Is fully cut and planted to pioneer iris. Tamarillo cuttings can be planted directly into the slash. 99 Nelson, New Zealand. Dick Roberts uses gorse aid rough mulch to protect fruit and forage. Trees and steep sheep. Pasture, reduction of a weed species protects the succeeding crop. Tree. Crops will shade out. Gorse age ethically planted 28. In numbers 96 to 98. $3. As for numbers 96 and 97. S5 ER 2 to 3 years, the remaining gorse is slashed, and mature rainforest species self-seed into the SC floor. After 5 to 6 years the gorse has rotted, and rainforest establishes under acacia, which, at Thomas Feld, native birds carry in rainforest seed. 100. Kajika Jadera. Central Australia. Fallen trees, here near a desert insulben, provide protection from feral animals for young moss. Fian for Andrew to establish a food tree in the branches. 101 Mahalapi, Botswana. Fierce thorny mulch from acacia tortilis protects new trees from intense browsing pressure in compounds, here planted by Dorothy Endaba. 20 Cool temperate. 102 Tug, New Zealand. Avocado in hard frost. Area thriving in a clump of tagassist. Kikuyu is slashed to provide additional mulch at Jim and Miriam Tyler's farm. The tagassist yield up to 7 m of mulch. Trimmings per annum. AI. 104 Banks Peninsula, New Zealand. 1 m in row, 2 m between rows. Tagassist provide summer forage from coppice and short period browsing by sheep. Grasses thrive between rows. DSIR trials by Doug Davies. Tess. 106 Stanley, TAS, Australia. Tomatoes in a keyhole bed sheltered by windbreak of sunroot. Jerusalem artichoke, in old tires on a cold and wind-swept side. High FFI TIC. EY RERI Yule. Mid Al. CSC. Pia. Asterisk. Of. 103 Canterbury Plain, New Zealand. Tagassist drilled with turnip for future sheep forage, seedling trees. Established through turnip, brassica, crop at Matthew Carpenter's property. I. Sil. OORF underscore mat equals 5 SA4. OE patient asterisk EAEOOA GAS. 105 Banks Peninsula, New Zealand. Pampas grass is both fast shelter for lambing ewes, and a preferred forage for most livestock, propagated by divisions. Combines well with tagassist strips. 107 Stanley, TAS, Australia. A herb spiral in the form of a ziggurat provides ample culinary herbs. At the kitchen door, drainage and aspect suits most cool area species of herbs. Spiral 2 m across, 1 m high. 21 Cool temperate. FBS Slack Forest, West Germany. J. EA SoCal integration of foam and winter dant, mature. Pine orchard. Even the bees are housed in this radiant inn. Turn note earth ramp to upper floor of barn to assist hay. SE. Copyright 109, near Grist Church, New Zealand. Willow coppet crop, here. Intended for basketry, can also be used for medicinals, forage. Stickwood for radiant mass, heaters, active. Charcoal filters, artists. Charcoal, and 50 on. Willow water, fresh. Chip soaked if water. Provides gibberellic acid for promoting root growth. In the striking of cuttings. 110 near Chase Church, New Zealand. The Willow coppice field is for 109. 111 Perth, TAS. Australia. Here, willows are pollard for propagation. Cuttings at a nursery. 192, Nelson, New FC. Zealand. Matsudinga Willow Pro. Vide strict windbreak for 3 Kaidire Yule vine crop on the plains near Nelson. The strict form allows minimal space loss on the ground and needs little maintenance to control shape. 22 Cool temperate. Small livestock. 113 Forest, TAS, Australia. A rabbit cage tractor cleans clover and grasses from mounted strawberry crop at Michael Manjabilaki's farm. Rabbits are part of the yield of the wheat system and provide manures for the strawberries. 115 Lake Chelan, Okanagan, USA. Chickens tractor grasses for small fruit, background crop, weed. Small fruits over the autumn period, and provide manure. At Michael Pilarski's, Friends of the Trees Coordinator, Farm. 116 Aspen, Co., USA. I. 114 Stanley, TAS, Australia. Lycium ferocissima hedge carries vines of hops, banana, passion fruit, and shelters main crop potatoes. Its berries are loved by poultry and being a sharp thorny shrub, used to keep out lions in Africa, provides ideal shelter. C equals F. C equals plus equals equals EI. R. Chicken heated greenhouse and solar heated seedling cloche. Enable early planting in short season high mountain areas. 117 Wilton, NH, USA. Reed turkey forage below autumn olive. Pass AE, Elinus umbellata, with abundant berries. And autumn olive are important tree forage. Legumes of cool and cold climates. 23 Cool temperate. 118 Calder, TAS. Australia. Jim Bassett confines. His rampant thorny. Blackberry, 35 Keglayer. Ugid, in a strait jacket. Of old oil. Drums which also makes for easier harvesting. 720 Clealum, WA, USA. Pigs in fir forests maintain high production of berry fruits, fungi. EEC's all an important crop to the Salish Indians. Here, filberts. Pemsiadavi, black raspberry, huckleberry, wild strawberry thrive. 722 Tumbarumba, NSW, Australia. At Drews and Jason Alexandra reduce fuels in a gene pane. Sipo chips are mulched, composted, and fermented to methane. Mecha 6. Removal of forest fuel reduces the fire risk and enriches. EEZOIKU. Burns which impoverish soils and often lead to wild. 119 Kiwa, Vic. Australia. Jeff Wallace I. Observed the tree seed. Apple and blackberries on and. His. Farm, his cattle. Demolish the black. Berries to get to the. Apples. He now plants. Apples in the brambles. Part of a natural guild in. England, they prosper in. Their protected hole. Fruit, and soon the SAE% E. Brambles are trodden SY. Down by cattle eager for. Sweet apples. 121 Whidbey Island, WA, USA. Stumps of firs grow many deny species, and slabs from fir stumps. And logs generate berry clumps on lawns or in cleanings, a 5 do fallen. Fir logs. Birds bring seed and manure to stumps and they establish. Protected from deer browsing. 123, Evergreen College. WA, USA. Close raises early tomatoes in leaf mulch, sides are hinged to allow. Late spring growth of crop, Rooney missing in action sleigh. 24, Urban. 124 The Bronx, New York. USA. The green gorillas transform. Vacant land in urban wastelands. 2. Productive, beautiful, and recreational usages. As city farms. 126 GLIE Farm, South Bronx. New York, USA. This urban farm provides 8% of New York's herbs. And provides employment for many people in an area of urban decay. FONEL. AFAE equals F. ISE, LN. 128 Black Forest area, South. Germany. West or sun-facing walls in cities and towns provide radiant E4. Marginal crop here in espaliered pier grows well and softens the wave of an urban barn. We can therefore regard most urban buildings as additional agricultura, spaces are trellis systems over alleys, shopping complexes, upbuilding walls, etc. OOAE. 125 West Germany. The productive sugar gardens adjoin almost every settlement and provide food and much needed recreation. In cities, people are permitted to spend weekends on these many farms. One example of greening the cities. PEDEL #*ZALE. 2. 127 The Bronx, New York, USA. The only example of productive use of New York's food waste is this small composting business operated by the Bronx Frontier Group. Small mountains of compost are sold off-site to create meadows over rubble-filled wastelands. 129 Louisville, KT, USA. Project Warm volunteers retrofit and insulate old Fox flums by the thousand. This sharply reduces energy costs and deaths from the cold. The cost amortizes into winters. Only minimal funds are directed to such sound expenditures in Western society. JT is always cheaper to conserve rather than generate energy. Such projects make many dangerous or dirty power generating systems obsolete, e.g. nuclear power, trimming. All of these protect diversion banks and compounds from grazing animals. Euphorbia takes root from cuttings in even arid conditions, and acacia. 40 leaves is ideal for cut and build fences. When cutting euphorbia, be sure to protect the eyes with goggles, and keep the skin covered if allergic to the milky sap. Primary tall windbreak of Araucaria, cupressus, casuarina, pinus, hardy phoenix palms, and even mangroves may be needed in frontline locations. Followed in the loo with such hardy quickset species as Euphorbia tyrwelli, Copros morpens, Echium fastuosum, and so on. It is always best to find local plant species that do well in the district. Erosion control. Contours at 10 m on medium slopes, 2 to 7, and at 5 m on steep slopes can be planted out with root sets of canna, vetiver grass, lemongrass, or pampas grass. These are set out at 0.3 to 0.6 m spacing and form an broken hedge, or a crown on earth walls or dam banks at spillways, figure 10.13. They both disperse water and create SJLT traps. Behind such self-perpetuating walls, soil is deeper and trees can be planted or crops grown. The system is cheap, effective, and provides mulch. Some of the yuccas, agaves, and aloes may provide the same structural effect in desert areas. 10.7. Integrated land management. The Maori Maori or Hawaiian Ohana were geomorphic and sociological units in which land and people were integrated for sustenance. They may have evolved out of early errors of overclearing, excessive burning, and the extinction of useful animals before reaching equilibrium. We can only hope that the modern world also has time to take stock and come FO if senses, but that will rely on determined change by many thousands of us within society. Presuming a hill-to-shore profile, often a volcanic cone profile, figure 10.28, the stable tropical landscape may require some or all of these features. Asterisk protected skyline and hill forests. These not only protect soils and waters, but both mine and release plant nutrients from the upper, sometimes steep, slopes. They can be used as limited forage source and mulch provision, but should have ironclad protection. Their clearing brings compound catastrophes ranging from landslide to loss of nutrient in water and crop, desertification, and consequent severe social disruption. At the base of these forests, as the slope eases to 15 degrees or less, water can be diverted or harvested to replenish groundwater and irrigate terraces and crop. Asterisk mid-slope or key point. A diversion of stream water here will lead water out to ridges for terrace crop and village use, thus, cropping commences below this critical point. Human occupation and complex cultivated forests and gardens can now be established. Downslope. The stable plateau, the hill rising above the valley, and bench sites above the reach of flood and sheltered from hurricane and tsunami are prime cluster settlement, village, sites, with some scattered housing. Higher on ridges and the forest edge. Asterisk low slopes, 2°-15 degree slope, are well suited to earth shaping as terrace and potty, with limited grazing and innovative forestry. These are the sustainable agricultural areas, where attention to subcontoured agriculture, windbreak, and access will help direct runoff and water to crop. Asterisk coastal flats and valley floors. Rich and often deep humus soils can accumulate on valley floors. Gray water and processed manures from settlement and livestock add to fertility, where extensive aquacultures or rich forest/orchard crop can be developed. Shorelines are preserved for 100 minutes, 330 feet, or So inland for essential windbreak, shore stability, and cloud generation over land, selected quiet harbors and refuges except fishing settlements based on sea resources. Shores with 15 to 20-year tsunami history need sacrificial palm/caswarana barriers to reduce storm damage ashore. There may be lightly built and temporary shore housing, which is used only when working the coast, with more substantial homes and sheltered gardens safely inland or behind earth embankments. If shallows or a coral-based lagoon/reef system stretches offshore, the following categories of use also apply. Asterisk lagoon and estuary sea impound. Manse. Ancient and yet innovative sea walls, usually of semi-permeable coral blocks with entries, flood tide gates, and a series of inner pens, are an excellent use of the shallows. Restricted mangrove plantations help stabilize the banks and provide sea mulch while catching any silt that washes down from above. These warm water lagoons are rich in algae and are good sites for cultivated seaweed. They also impound and fatten mullet and mangrove fish, oysters and eels, shellfish and prawns. In the sea lagoons, mobile phosphates are fixed in plants and mud in a few days, and are then available for growth. Such rich estuaries are invaluable. As managed maricultures. Asterisk marine constructs. Artificial reef systems of tires, on sand, coral blocks, and boxes of palm trunks greatly enlarge the habitat for sedentary fish and lobsters. Within a year, these constructs are consolidated or cemented by corals. Weak electrodes on metal mesh creates an artificial but permanent coral line deposit more rapidly. In extensive sandy shallows, log barriers full of sand and stabilized with mangroves provide shore barriers, lagoon walls, and edge in the sea. It is as well to have an integrated concept of appropriate land use in mind for both broad policy. 277. Figure 10.28. Ohana System, Hawaii. 1 radial valley of a volcanic island. A. Taboo forest of upper slopes. B. Stream diversion to ridge or high terraces. Main village, copyright. Caroticial forests of Gale Te Nodity Hurricanes. D. Reef fish ponds to retain leached nutrients, growing mullet and shellfish. E. Reed. Modified with coral blacks to shelter crayfish, fish. 278. Planning and future land redistribution. There are slow moves in present government circles to institute some sanity into life and landscape, as, like agriculture, government must change towards an environmentally 10.8 elements of a village complex. In the humid tropics, based on traditional and modern villages, a complex can be built from the following checklist. A well-arranged array of housing, often grouped around a compound. Asterisk the compound has processing and storage areas, threshing floors, dancing areas, meeting house, cooperative or retail store, bulk fuel depots, firewood, and mulch depots. Asterisk a well, piped water, tanks, or dam must be sited and integrated for clean water, depends on local skills, resources, water available, and site characteristics. Asterisk a plant nursery to serve gardens and forest. Asterisk at each house, 0.25 to 1.0 hive home garden and orchard, based on self-reliance. At borders of gardens, ranges for domestic species, e.g. chickens, guinea pigs, ducks, rabbits, small pigs, pigeons. These are a manure resource for the home. Asterisk in areas of plentiful water, fish ponds over which some animals are housed. Asterisk sector or zone of fuelwood plantation, potentially integrated with windbreak. Asterisk a strong yard and sheds for cattle and pigs at a commercial level. Registered a careful zonation of tree polyculture as per figure 10.29. Asterisk special facilities such as a log trimming or boat building area, fish net drying racks, canoe or small boat landing, wharf, freezer, solar pond installation, power house, large community drying shed, craft work areas, and vehicle or draft animal park area. 10.9. Evolving a polyculture. If, as is often the case, we start to evolve a permaculture on grasslands or compacted soils, then the very first step is to thoroughly plan the site and rip, swale, pit, or dam every area to be planted, thus ensuring maximum wet season soil water storage to carry over to dry periods. This process should commence at the highest point of the property and around the house or village site. On these loosened soils and in mulched swales, a mix of tree legumes, fruits, bananas, papayas, arrowroot, canna, cassava, sweet potato, and comfort can be planted. There should be one such plant every 1 to 1.5 m. With acacia at 3x 3m spacing, banana at 2x 2m, fruits 5x 8m, palms 10x 10m, and the smaller species as gap fillers. As well, all larger planting holes should be seeded with nasturtium, dolichos, hypha clover, broad bean, fava, buckwheat, umbellifery, dill, fennel, lupin, vetch, hairy or woolly, dung peas, chilies, pigeon pea, or any useful non-grass mix available and suitable to climate and landscape. The end aim is to completely carpet and overshade the ground in the first 18 to 20 months of growth. Ideally, dense plantings of this type should be grass or hay mulched, using monsoon grasses, swamp grasses, and later the tops of arrowroot, comfort, banana, acacia, and green crop. Later still, shade-loving species such as coffee and dry taro can be placed in any T.S. Gary for access, openings for annual crop, bee plants. On the edges, flowers and fire-resistant wet ground covers such as comfort, trata scantia, impatiens, and succulents can be placed as time goes on, while the fruit trees are kept free of grass and mulched by cutting out crowded acacia and banana as mulch. It is far better to occupy a quarter hectare thoroughly than to scatter trees over 2 ha as production is higher and maintenance less, moisture is conserved, and frost excluded. As for species richness, or species per hectare, this can be very complex and dense near the village or home, and simplify to well-tested species of high yields. As distance from the home increases, any trellis crop should be first placed to shade the home, livestock, or to make fences, and only later placed on acacia or other legumes as they age. The number of productive, managed, and effectively harvested species in a polyculture is decided by a complex of these factors. 1. The number of people responsible for managing 1 or 2 of these crops or animal species, labor. 2. The proximity of the complex to village or settlement, zoning. 3. The relative cost-benefit balance on increasing inputs to optimum levels, fiscal economics. 4. The need for effective plant guilds, harmonious ecological assemblies. 5. The method of marketing and processing, whether these can cope with complex product. 6. The total area which is controlled, larger areas demand increasing simplicity, at a cost to factor 4. Above. 7. The maturity or stage of evolution of the plant. Systems more regular product. In practice, the gardens, walls, roof areas, trellis, systems, and compounds of villages are the most complex and rich areas of cultivated species. We can manage and find uses for some 200 to 400 species in such situations, of which the following usage classes are dominant. Some very useful species fall into 3 or more. 279. Of these classes, while a complex polyculture of many hundreds of species delights both the naturalist and, in food plants. Asterisk basic food species 7 to 90 the householder or villager, and the benefits to. Asterisk mulch and fodder provision 10 to 30 settlements are numerous, it becomes difficult to con. Asterisk medicinals and biocides 20 to 50 draw an extensive rich polyculture and collectives. Asterisk structural and craft 5 to 20 are very complex polycultures work best at small scale. Asterisk culinary herbs are, and with close attention from people. The depopulated. Asterisk beverages and export specialties 10 to 15 to humanist, and now almost deserted wasteland. Of. Asterisk fuel wood and coppice 12 to 30 modern agriculture is unable to cope with any but the. Asterisk special uses, sacred uses 8 to 15 most basic and simple intercrop systems, thus. Total cultivated species 155 to 280 sacrificing yield, quality, stability, and inevitably. SPE thus, if 1 the $ICS of such, equals us, if we analyze all our economics of SUG. Poppis and Borzini systems, there will be an optimum number of species. Cheater. Ye. XS figure 10.29. Nigerian polyculture for humid tropics. Cassava, street, 0 runoff, contour L data from Ibo end. Includes pig or gold pen and forage crops appropriate ridges for Lao. ESCMEM. 280. Figure 10.30. Earthworks for polyculture on A2. Ha. Subtropical site, slopes about 7 asterisk. Heavy emphasis on diverse water crop, fire control, swales, potty crop, dense fuel and food forestry. Arrows indicate complex water paths. Through the system. Slope is to the sun side. IPS, LTC, A. MIC-ATAMIA, low GUAT Sud. Y2UPOTE, CBTRUS. Renan MPAS. IB. I. All flat botine P. Y10C cent FHI. 1. ST. CWH. OA. 281. For broad scale cash yields. If we analyze for total nutrition and total yield, ignoring the dollar returns, A. Different and richer species assembly will be indicated. While the fiscal return peaks at about 6 to 8 species in a system, the nutritional total yield system peaks at 50 to 100 species, well distributed over all seasons. These 2 factors, extensive intensive, fiscal nutritional, must be defined by ourselves for our needs, and will have a profound effect on design. What we may arrive at is a sensible zonation of species richness close in, and a concentration on less species of high value as we extend the system. It is in the garden, however, that we may learn the value of such successful extension, without sacrificing large amounts of energy and capital. Thus, our gardens are trial areas for the outer zones. Planning the whole site. Even in established polycultures, particularly in plantations, it is good to resurvey the site with special attention to asterisk main access and harvesting ways. Asterisk earth shaping for rainwater harvest and specific crop. Asterisk sufficiency of mulch. Asterisk best water and irrigation strategies. Asterisk better village planning. Asterisk improved or more sophisticated site processing for market. These are the main factors that can reduce work or increase yields and commercial values. There is great benefit in testing new legumes, tree varieties, and earth shaping systems for optimum yields, and in assessing labor, work, social, and market factors for future development. On a new site, the same considerations hold, but the establishment of windbreaks and any earth shaping is a priority, preceding planting. There are also essential soil tests for plant nutrients and trace elements, as it is a modest amount of these that give early vigor and early yields. Intercrop selection is also a priority, sometimes used to shelter a more delicate crop, but also as mulch and nurse crop for nitrogen fixation and for wind, salt, or sun damage reduction. Steps in total planning are roughly in priority. 1. Assess market, future, prices, potential for processing to higher value, labor, shares, legal systems, social necessities and local self-reliance needs. 2. Analyze and get advice on soils and necessary nutrients. 3. Plan ground layout and windbreak, access, and water, detailing can follow later. 4. Plan and carry out essential earthworks. 5. Establish nursery and use selected varietal forms for new or replacement crop. 6. Commence broad-scale placements with or after windbreak and nurse crop. 7. Continue by constant assessment, consultation, feedback and innovative trials. Fill niches as they evolve. 282. Pest and disease management. Here, consider only the species we can add to the polyculture to assist in the regulation of problem species, plant and animal. Some powerful biocides that are found in plants are harmless or short-term and are totally biodegradable, natural substances. Classic insecticides are those derived from Chrysanthemum spp, Derex spp, Rhodnon, and the neem tree, Melia or Azadiracta. A few of these plants in home gardens and small clumps in crop give a ready source of insect control, or control of invertebrates, nuisance fish, and amphibia in water. Both neem and Derex control aquatic organisms. Most insecticidal plants are lethal to aquatic species. Broad-scale mosquito control, applied from the air or as ground mists, can combine fats or oils, e.g. lecithin, a poison, neem oil, and an infective agent, Bacillus thuringiensis. All of these are potentially assisted in pest control by small fish and such insect predators as netonectids, back swimmers, in open water systems. Ground foragers, chickens, pigs, cattle, large tortoises, eat fallen fruit and larval insect infestations. While leaf foragers, birds, frogs, attend to infestations. In the canopy, a 5 do a variety of small skink lizards. Some lizards, Tiliqua, forage for snails and slugs at ground level, as do ducks. Pasture grubs are eagerly sought out by a variety of birds and small mammalian and marsupial insectivores. Tropical land crabs seek larval insects in mulch and provide useful food themselves. Even the problem of kikuyu grass is eased by domestic guinea pigs on range. In small houses, these free trees from grass competition and provide manures. Neem tree leaves and oil deter pests in stored foods and have been so used for centuries in India. I'm sure little research will indicate plants, invertebrates, vertebrates and common harmless substances of great Use in the tropics. Believe that there is no pest prob. Lem will not yield to our applied common sense and an integrated natural approach. In any tropical tree crop monoculture, soil fungi and nematodes may become persistent pests. Marigolds. Tigetes often serve to reduce or eliminate nematodes. And Crofolaria as a leguminous green crop traps them in its root mycelia, so both these plants need consideration. Where nematodes are a problem. Mulch and green manures, soil humus, often buffer the effects of these. And fungal pests, hosting fungal predators. Palm groves provide sheltered and shaded aspects for both intercrop and livestock. Chickens, for control. Ling pests such as rhinoceros beetle larvae, guinea pigs. Geese and land tortoises, to reduce grass competition. Pythons, for rat and mouse control. Owls, the best rodent predator. Bees for pollination, and all species for their monoreal value and other possible beneficial additions to the palm/crop/interplant complex, give complex yields as a byproduct. Pigs are ideal scavengers in tree crops below palms and fruit. Chickens and ducks are especially valuable in weed control in pineapple, ginger, and taro, and will control comfort and trade scantia if needed. The latter plants also control grasses if planted as part of a weed barrier. Perhaps the main function of animal species in the tropics is to recycle plant wastes and to help control the rampant growth of ground cover. The usual domestic species, often penned, are pigs, chickens, geese, guinea pigs, rabbits, pigeons, and milking goats. Cattle, or buffalo, horses and bullocks or oxen perform draft animal functions. Moreover, useful endemic animal species, and especially island species of restricted natural range, need to be more widely examined for their particular uses, and selected for their functions in a wider set of trials out of their normal range. In the established tropical system, geese control pond edge grasses, and wallaby or small grazers keep forest clearings and paths open. Both are encouraged by feeding out bran or pollard in the areas to be clipped. Where no foxes or pythons threaten poultry, flocks of guinea fowl and hens, ducks, and bantams perform invaluable pest control and monoreal/scavenging roles. Where predators are a problem, special housing or pigeons in safe elevated roosts may be the only way to keep fowl. The effects of electric fences in tropical areas, if not within forest edges, are often nullified by the rank growth of coarse grasses, and become an opera tip for repelling python, pig, bandicoots, and foxes. For this reason, fence lines must be planted with a dense perennial ground carpet of low herbaceous plants to exclude grasses, or overshaded by tree canopies. 10.10. Themes on a coconut or palm-dominant polyculture. There are many considerations to bring to the planting of a coconut or palm-dominant polyculture. They can dealt with in the following themes. Asterisk structure and zoning. Species selection. Asterisk patterning. Asterisk economics. Asterisk reworking old plantations. Asterisk the effects of plantation monoculture. Structure. Any humid tropical polyculture that duplicates or imitates the normal structure of a tropical forest is likely to succeed. The structure of the system refers to the final cross-sectional appearance of any polyculture. Near large markets, or mass transport systems, it is quite feasible to introduce large tree species into the palm system, and to use the fruits and nuts as a supplementary market crop. Around villages, a far more complex and species-rich approach is needed, with fuel, fodder, structural materials, and basic foods, oils, and medicinals in a complex intercrop. Remote from settlement or market, some livestock ranging pigs, cattle, can be contemplated, with the intercrop selected to assist animals on range over dry periods, as ground forage, or as for drop from fodder trees such as figs, breadfruit, papaya, or Inga italis. Proximity to village or settlement decides species complexity and, by implication, structure, in that labor-intensive systems are best placed close to the village. Zoning out, we might place asterisk productive trees in palms, total species, 6 to 12. Figure 10.31.a. Asterisk palms within crop and avenue cropping between palms, total species, 30 to 35, figure 10.31.b. Asterisk animal forage and free range in palms, total species, 8 to 20, figure 10.31.c. Asterisk village garden and trellis, root crop, greens, total species, 100 to 150, figure 10.31.d. Asterisk fuelwood in dwarf palm, total species, 3 to 4. Figure 10.31.e. Asterisk forest and tree reserves. It is in and around the village that small livestock, fungi culture, potty crop, and terrace is appropriate. Criteria for species selection. For any one-sided selection of species that go with a palm polyculture has to be made. Some criteria are: in village, a mosaic of the full range of food, craft, and medicinals is needed. Special intensive crops such as fungi, potty, and even algae can be planned. Experimental plots can be located here. In palms, species are selected according to a general zoning/use plan. It is helpful if asterisk species are suited to soils. A mosaic approach is indicated based on soil drainage and nutrient status. If the site is complex, then so should be the main crop. Asterisk species are locally acceptable, or are very similar to local types. New introductions need trials and instruction as to processing. Asterisk species chosen have a wide potential for processing. Coconuts have hundreds of known products or uses. This gives market flexibility. Asterisk species do not become rampant unless they are controlled by livestock or cultivation. Asterisk there is good information, some varietal types, and assured yield or low management input for the species used. Asterisk species are compatible, such as those listed herein. Asterisk species serve a present and future essential use, as thatch, fuels, oils, dry stored food. For coconuts, and many other species, guava, yam, taro, banana, papaya, there are dozens of varieties, developed for quite specific sites, soils, microclimates, or uses. There are coconut palms ideally suited to oil production, while others produce very fine quality copper for temple use, and others are ideal for shredded coconut, coconut milk, fresh nut markets, and so on. There are dwarf, medium height and tall varieties. 283. Kissing face, Pepeta ift Rioi. HFRA melina. Tie idle bn. I2SMTHT. CETI, TT. LLY. Cattle forage. INGH, banana, papaya, muciavio, CWXO, yaminga, prosopi leucaen gliricidia, herbal layout. Figure 10.31 comfort, legumes, graces, scent FORBS. AE structural variation IW palm polyculture. Cattle forage. D. Grassland evolution. E. Fuelwood plus palms. And can. A. Palm strip layout. B. Palm row crop. C. Palm pig forage or be zoned around a village. 284. The former are ideal for village surrounds, especially in windy areas, where there are dozens of deaths each year from falling coconuts. Dwarf varieties, Philip, Pine, Samoan, are easily accessible, have large nuts, good eating characteristics, and will not damage people or buildings if the nuts fall. Pest resistance and soil type must also influence cultivar selection. In older plantation areas, selected and well tested, local species will be available. For areas with no plantation history, it is perhaps wise to build up a small arboretum of many varieties and select a range of cultivars suited to the end product aims. In every country, the cooperation of local agricultural authorities and their assistance with varietal selection will be needed once a nursery is established, either as large containers or open bed planting, later as field plantings where rainfall permits. The side planting can go forward, but every plantation needs a mulched, shaded nursery, no matter how modest. Shade is most cheaply provided by light foliage legumes at wide spacing, e.g. acacia, albizia variety. As almost all coconuts must be seed grown, we can expect a variation in all crop characteristics, subject to later selection, culling, and new selections for site. Even if we grow from root tips in tissue culture, meristem and single cell mutations are very high. In seed grown crop, we might expect about 1 in 20 trees to show some very different characteristics, and of these, perhaps 1/3 will be favorable for site, giving a limited set of new characteristics for selection. Thus, it is unlikely that seed grown or culture grown palm plantation will demonstrate a very uniform genetic resource, and this will later lead us to cull and select options in management. This indicates a need for initial overplanting to allow for a 24% cull within the first 7 years, when we can make a fair estimate of vigor, nut production, bearing, and pest resistance, and another 1% cull in years 7 to 14, when the tree is mature. Final culling, 14 to 60 years, should be in the nature of a replant and renewal process. Culling and replanting in palm crop can be a continuous process, so that plantation vigor and overall design is updated. Species suited to co-processing in special plantation intended for, e.g., ethanol or biogas fuel production, the same ferment and distillation equipment will serve a complex of crops that can form a special use polyculture. In aleohol-oriented, fuel, palm crop, interplant of cane sugar, century plant, agave, beet, or sorghum. Sugar may add to total sugar crop and suit the processing or distillation unit, while oil palms may be interplanted with mustards, sunflower, rapeseed, etc. to take advantage of oil press equipment and to increase honey production for bees, which themselves increase oilseed crop. Similarly, wetlands suit many swamp palms, Nipa. 285. Morandia, taro, rice, and azalea fern or blue-green algae complexes, where the fern acts as nitrogenous mulch and the palms as deep nutrient pumps for the potty crops. Thus, special site conditions, investment in processing equipment, or special end use may dictate special plant assemblies in the site mosaic patterning of palm polycultures. Pattern and water runoff. Many sites on clays and clay loam soils benefit from earth sculpturing for runoff absorption. On extensive sites, and on clays over limestone or dolomite, absorption swales may be the only practical broad-scale irrigation method. In fact, any leveling or terracing of land helps water infiltration. Palms and Figure 10.32. Appropriate village zonation. A. Livestock. B. Pain polyculture. C. Forage for larger animals. D. Potty crop. E. Header dam and aquacultures. F. Commercial crops in palm. G1 G3. Reduction in species and increase in wild gathering. Feewoods and hardy trees. Figure 10.33. Land patterning for maximum water absorption. Crossio hollows to hold mulch and runoff flow should precede palm and tree planting. Broad swales also provide access at harvest. Urns of SGN. Eating too much Jake Syriac apes, and of coconuts. Figures 10.34.ac illustrate some. GF the possible plantation layouts. While A and B are MVLC arises from several independent S have made on densely planted coconut. SIXS appreciate groundwater reserves. A hillside pattern as per figure 10.33 suits clump. Eightings of palms. Swales are illustrated and D in chapter 9. 10 to 12 coconuts planted in a circle, and each only a few feet apart, do in fact quickly adopt a divergent growth habit, something like that in figure 10.35. Not only do nut counts compare favorably with trees planted on a square grid pattern, and nuts drop cleanly to the ground, but a third, probably more important factor emerges, to do with mulching. Coconuts in plantation mulched with their own fronds and husks show better growth and bearing, but in normal plantation, husks are left at one tree in 10 to 30, because FAE7 FIMTMNS POLU/Y plus equals asterisk C A BAL asterisk Ox miterate double fours KL Original Soyadzine Boch base loust KRA registered 86 10.34 WSON of linear and clump layouts SC of intercrop yields IOLC I1 to 12 clump palm layout low, more, and earlier crop yields. Plan shows how various palm percent interop ONBLE clump planting of palm layouts frees up ground space, enables easier access, easier mulching and irrigation. 287. The labor of first gathering and then distributing the mulch is too great. However, with the circle clumps, it is easy to both gather and husk the coconuts in one place, and thus mulch the base of all trees, conserving water and returning tolerance to every tree. A little care in turning husks face down prevents mosquito breeding in these mulch heaps. Any other nutrient, manure, blood, and bone, is equally easily applied to clumps. Clumps also form more suitable trellis for vanilla, black pepper, and other vine crop, are very economical for watering, and give a large area of growth free, although lightly shaded. The wide spacing of circles enables replanting to take place in discrete sets of 10 to 12 palms without gross linear disturbance to the system as a whole. Although originally saw such clumping as a convenient way to apply mulch, it later became clear that broad areas of clear ground for grazing and intercrop are also available. Such patterning frees up to 60% of The ground area, as against 30% for linear planting. Clump planting is ideal for runoff harvesting of water. In circular swales, figure 10.33, or in coconut circle. It's FS for the spacing of palms in lines, a very good rule. Is to space at twice the frond length for that side plus 2 feet. This allows full crown development without abrasion damage to the fronds from wind sway. Intercrop spacing is as usual, cacao 2x3m, banana 3x3m, cassava 1x1m, velvet beans 0.5x0.5m, maize 1x 0.5m in rows, citrus 9x9m and so on. Local agricultural people can advise, coconuts on new sites are normally 6x6m. Mulch for busy. Sensible roading or grassed access ways are necessary for gathering or handling heavy crop, and some provision for these must be made even where horses or donkeys with panniers are used. More importantly, a careful assessment of mulch sources is essential. Wherever mulch-loving crop, avocado, banana, or short-term crop, dryland taro, ginger, yams, are planned, a layout such as figure 10.36 ensures mulch sources for the system itself and for short-term crop. Natural fall from palm fronds and husk or nutshell will line mulch about 1 in 8 to 12 rows of palms with about 2 m wide x 0.5 m high mulch beds. In clumps, 10 to 12 palms will provide about 0.5 m. 4/we. V. Figure 10.35. Palms planted in clumps. Palms, bananas, macadamia outs, and many other useful species yield well in clump plantings, freeing space for intercrop and concentrating mulch and irrigation nests. Figure 10.36. Layout of plantation for mulch. Palm fronds, nut husks, hedge foliage, and intercrop leaf all suffice to heavily mulch every 4-5 th strip each year for high yield annual crop. 288. Deep of mulch for the inner circle of mulch. This is easier to gather and keep in place in windy areas. The addition of bananas, especially with avocado, has become standard in many plantations, as the banana plants at harvest, with root mass, provide about 25 T/hive organic matter, a key resource for a healthy fruit. And palm crop, Penn, J. New Scientist, May 20, 85. Small tree legumes, cassia, calandra, lucina, also help. Bananas in legume crop may be regarded as pioneer mulch in grassland reclamation. The layout in figure 10.36. Asterisk reduces the labor of harvest by providing regular access. Asterisk provides sources of mulch for short-term crop. Asterisk enables mulch accumulation by long-term crop as interplant. Earth shaping for intercrop. Earth shaping is worthwhile for several reasons, not only to assist water infiltration and runoff, but to give a free root run, to retain mulch in wind, to effect better drainage in over wet areas, and to provide microclimate benefits with respect to wind shelter and ground warmth. Briefly, earth mounting for root crop and cucurbits is beneficial in humid tropics, and earth trenching is best in dry tropics. Earth working is discussed in chapter 9, but some relevant data is given here. Ridges of 0.5x1m increase yields in cassava, sweet potato, and yam crop. Mulch and green crop can be grown between the ridges. Pineapple and ginger also prefer ridges in wet areas. In figure 10.37, Lucina intercrop for mulch is on mounds, while maize and green mulch, beans, occupy hollows ridges. Permit deep mulching for low crops such as pineapple. The mulch being applied between RIDG mounds and volcano-shaped mounds with hollow centers or good cucurbit sites if enriched with manures, a stone or two helps heat the earth to germination temperature for cucurbit and melon crop. Furrows assist mulch retention for ginger and pineapple in dry areas. They are best covered with mulch and will carry subsurface water seepage lines. Basins, even shallow basins, aid dryland taro and banana, or patches of Chinese water chestnut. Soil is more easily saturated, and deep mulch assists this process. Boxes of palm trunks are ideal mulch holders for yams, banana, and vanilla orchid, vines generally, and borders of beds in home gardens. Such log boxes can be 1 to 3 logs high, and greatly assist weeding if mulch filled. 2. Plantation can be cropped with short-term grains for a season or two, but by years 2 to 4, the palm fronds of linear plantings, not so much of clumps. Cosmac. Figure 10.37. Mticas, mounds, furgoes, boxes. Appropriate earth shaping specific to crop type or soil, drainage, precedes all planting operations and increases yields. B equals 289. Figure 10.38. Palm intercrop. A wide variety of crop and accessory earth, or trellis, structures can be integrated with palms after years 4 to 7, JTRG Schultz. Sectional evaluation. Anical damage and obscure the ground. After years 4 to 4. A stem forms, and from 6 to 14 years, complex perennial. Intercrop, not short-term grains, can be placed in linear systems. In clump systems, the early ground effect is less marked. Economics. Nair, 1975, gives convincing economic analyses for coconut, showing a 50% increase in yield for irrigation alone and a trebling of the yield for complex intercrop of 2 or more species, effectively doubling the cash return to the grower on the same area. Cost of irrigation and intercrop, plant or animal, never exceed returns if care is taken to select beneficial plant and animal species for available soil, water supply, and climate. Often, the cheapest irrigation system is to pattern the ground to hold wet season runoff for tree crop use in dry seasons. On Nair's analysis, where unit equals 4 rupees, the net income from coconut was as table 10.2, adding 3 species and increasing net yield by 3 to 9 times increases costs by 3.1 times. This is a clear implication for small holders that much less area, polycultured, would give as much return, 3 to 8 times, 4 for less expense, as X. Hence is also a function of expanded area under crop. Irrigation of any sort is obviously a key factor. There would be a point, however, where more species added, even if very carefully selected, would push labor, harvest, and control costs past sensible limits, as per the schematic in figure 10.40, so it is also clear that a complex polyculture must be managed by many more people if expanded to a wider scale. Reworking old plantations. People who inherit or buy old stands of coconut or other palm crop need to undertake clearing and figure 10.39. Yields over time. Beyond 7 years, intercrop adds to yields. Constant replanting of selected nuts is preferred to 50-year replacement as shown here. J6RG. Schultz. Fa. 3 Peaks FS. G. E. Repla 40 year Gao Furland hashtag O year at Fowley. /T/TTT. EO3 BOOFOAE FAAC. 291. Replanting programs for renewal if the stands are 60 plus years of age. This is an ideal time to reassess the potential for intercrop, to assess local processing potential, and to use the trunks, fronds, sugars, and palm heart products of the overmature palms for mulch, food, and structural material. If hurricanes have stripped the old crop, it is also timely to assess the placement of windbreak for future plantation, and to place casuarina, acacia, albizia, bamboo, or tough Prosope species to afford greater shelter and to fix nutrient in the crop, or to provide forage for grazers, such as pigs, cattle, tortoise, or game birds, turkey. Fees. The clearing of old trees should be carefully planned to give a maximum return and to correct placements in older plantations, as it may take 8 to 15 years to rework a neglected old plantation. The process can be staged and tuned as trial systems. In many areas, the old palms are tapped for sugar before removal, and the palm hearts eaten or sold as millionaire salad. Although palms planted specifically as young heart crop have a very good yield, can be close planted, and are a crop in themselves. Good managers may be about the business of replacing, replanting, or regrouping plantation at a rate of 4% or so per annum, giving it slow but constant renewal and culling as needed. The new trees also give an opportunity for field testing selections from the nursery beds. It is generally agreed that coconut is overmature in 40 to 80 years, when nut yield falls from optimum 45 per tree or so to 15 or less. Excellent trees bear 60 to 100 nuts per year. Uses of palm trunks. The trunks of coconut are a good resource. Not only do they provide an excellent building material, but stacked in open box fashion, they make baskets to hold mulch on land for the growing of yams and vines. Figure 10.42. In the shallows of tropical seas or lagoons, they form a frame for coral to cement together, sheltering crayfish, crabs, and fish. The trunks hold silt and sand in reclaiming new lagoon areas, or in creating stable planting ledges in hurricane garden hollows, cut into coral sands on the sides of it, or plastic-lined surface ponds on islands, or as an aid in retaining bank stability and plant establishment on slopes. Palm trunks can also be used to create planting benches on pits on coral islands. Pit base, taro, mint, parsley, kangkong. Sides, cassava, papaya, yam, banana, spoil, sweet potato, mulched. Figure 10.41. The effects of plantation monoculture. Plantation crop in the tropics may bring with it all the evils of monoculture, and especially those of poisonous sprays, which not only affect the workers themselves, but infect all streams and eventually town water. These sprays drift over adjacent properties, making livestock unsaleable, and poison the landscape generally. S. low I3AE2B. Years. Figure 10.40. Schematic of a palm polyculture. Nut yields. Slow decline after year 15 requires that selected planting of 1/20th of area is a continuous management process which yields logs, mulch, and variable age across stand. I equals we. Figure 10.41. Planting benches and pits on coral islands. Grow pits 1 to 2 m deep and 8 to 12 m wide are ideal in coral sands. Lower levels are close to permanent water table, which reduces pH to 7 to 75. 292. Plantations almost invariably erode the landscape, pollute rivers, estuaries, and corals with silt and sprays, and exhaust soils. They scent release power and corrupt local politics, often funding repressive politicians. Their products are of low nutrition, and contain high levels of residual chemicals. Perhaps worst of all, plantations almost always displace local self-reliant tro, and replace it with company store dependency. Cures are available. Firstly, plantations can be yuckily managed by worker cooperatives, as in some Sri Lankan tea plots. Here, at least, the workers have a say in and profit from their labor. This does not necessarily alter many of the ecological factors, how QBER. Secondly, plantations need not exist, as the same area of crop can be produced by smallholders and processed centrally. This is a further improvement, as quality can be rewarded and good ecology instituted. Such an approach needs shared research, market, and processing systems. Thirdly, meat plantation itself can adopt to reformatory good ecological management through the use of polyculture systems, soil building, organic fertilizers, and biological control of pests. The common work approach, where workers lease secondary or tertiary crop in, around, and under the main crop, or lease rights to the processing of the main crop residues. Modern analyses, computer modeling of intercrop, show that intercrop and polyculture raise employment and income, and plantation itself should be designed ethically to allow intercropping throughout the life of the palm. It is quite feasible for people to extend specific, successful crop mixes from their home gardens to more extensive situations, thus giving a surplus for trade. Money is then gained as a result of extending a stable and tested polyculture rather than by imposing a figure 18.42. Mulch boxes made of palm trunks. Palm or oak surrounded areas filled with mulch are ideal for vanilla beans, cucurbits in sandy or alkaline soils, aso on a larger scale. For potato, tomato. Table 10.2. Economics of palm and intercrop, after. Nair. Plantings net expenses. Unit/ha. Coconut only, under 1,600. Rainfall. Coconut only 1,512 817. Irrigated. Coconut and cacao 3,122 1,300. Coconut, cacao, black 3,882 1,880. Pepper and pineapple. Monoculture on an unsympathetic and fragile landscape. No landscape or soil can maintain long continued monoculture production of crop, as even tree crop is susceptible to disease in this situation. The approach of extending small and successful trials is basic to success. Broad-scale trials have unstable effects, social and ecological, from the beginning, and success is rarely achieved as a result of such an approach. However, it must also be recognized that complex small systems may work well simply because they are close by, and many such systems cannot be scaled up to large acreage as a totality. Size itself creates new factors of cost, control, market, and labor requirements. Plantation and monocrop have the undeniable advantages of ease of harvest and predictability, neither of which are necessarily the best criteria for human-centered benefits. Malnutrition and low socio-economic Status are common factors in the human populations of the wet tropics, and criteria such as full nutrition and enhanced self-reliance are where we should be concentrating for the tropics. 10.11. Pioneering. If we are going to pioneer in the tropics, the only ethical conditions in which we would contemplate such a process is to rehabilitate 1. Grasslands developed by burning/grazing sequences and monsoon grasslands. 2. Semi-forested clearings and old monoculture plantations of scent.g sugarcane, banana, pine, eucalypt, pineapple. We will suppose some weed invasion by lantana, tobacco bush, vines, or shrubs. 3. Logged and burnt forest with reject logs, branches, stumps, and weedy regrowth. These are some typical conditions. The end results we would envisage would range from terrace culture and water absorption systems, extensive aquaculture or substantial dams, polycultural forests. 293. Managed forestry or rehabilitative forestry for perpetual yields. Or, more probably, we would PN for all of these appropriate combinations for site. Tropical grasslands. The management of deforested grassland areas is the main problem of the wet dry, soil erosion, rank grasses in the wet, and inflammable or low nutrition. Feed and drought result from burning and overgrazing. Once deforested, the pastures are open to summer winds, and the nutrient cycle of tree/grass/browsing is broken. Fire, often out of control, only accelerates the process. Although there are very few trees which can survive in tropical grasslands, it is essential to re-establish tree legumes. Some vigorous grassland cover crop legumes, Desmodium, Ceratro, will help reduce the grasses and eventually lay down a mulch. Under trees, a short stem Desmodium will defeat the grasses, but it is then essential to be able to supply dry season water, as the legume also competes with the young trees for moisture. Some fast-growing leguminous trees, Albizia, Acacia, Inca, Lucana, will quickly establish and can be grown in the shelter of bandagrass or elephant grass, Painazetum. If these grow vigorously, they also provide green mulch. Heavy cattle browsing is a major cause of pasture deterioration and soil loss. Their extensive grazing is probably the most common destructive use of tropical lands. The first step is therefore to relieve the land of the weight of too many cattle. No ration, nor the globe, can support destructive grazing agriculture on the agribusiness/cowboy/pyromaniac model so general in tropical countries, in America, and wherever cheap beef is produced. The long-term cost makes such systems uneconomic in any terms. A positive approach is to re-establish either a multi-species system ecology, trees and a variety of browsers, or to intensify cattle rearing. Cliff Adam, Chief Research Officer at Grand Anse, Mahat, in the Seychelles has grown Painazetum atropoprium, 7 parts, plus Lucina leucocephala the Mimosin type available in Australia 1 part, and may add the Bocking strain of comfort. This pasture, cut and fed to cows, supports 7 milk cows to the acre. All manure and washings from stable/dairy are returned to the irrigated field. Imported artificial manures have been reduced to 1/10, and he hopes to further reduce this import by building soil. Meanwhile, in the same climate in Australia, 1 cow per square mile is enough to lay waste land. A friend who bought a degraded cattle property north of the Daintree River, Queensland, Australia, gathers a load of coconut from the beaches, and, traveling the ridges of old fields just before the wet season, throws dozens of coconuts at intervals into the streamlines and gullies. About 4% take root and grow into sheltered and pioneering palms. Not far south of there, another innovator rolls down the monsoon grasses as they begin to die off in the dry season, and broadcasts tall stalk rye and field legumes, faba, dolichos, vigna, into the thick resulting mulch. Enough moisture persists over the dry winter season to grow these crops. After harvest, the monsoon grasses regrow for next year's rye crop. This clever use of seasons and growth is possible for the establishment of many species, some of which become permanent and grass-defeating pioneers for later evolutions. Consolidation of the area for regenerative forestry, however, proceeds more surely as a scattered set of pioneer tree and herbaceous machli, that is, the steady establishment of clump pioneer trees in open grassland. This is a natural process which duplicates the seeding of grasslands by fruit pigeons. Figure 10.43. Planting in grasslands. Adons, 2.x2m, planting on nucithi of legumes, palms, shrubs. 294. Ground covers, and bulbs plug stone or stick mulch quickly shades wool grasses and produces a closed canopy, Jurg Schultz. Figure 10.44. Early pioneer copse in grasslands. NSE nucleus mulch planting joins up to create self-generati. Iovesis in grasslands within 10 pairs to 295. And fructivorous birds. In steep moist valleys, there is good reason to plant patches of bamboo and rattan palm for later wild harvest, large nut trees of heavy water demand. Macadamia, coconut, pecan, wind-sensitive large fruits, avocado, and a selection of high-value timber trees, rosewood, teak, cedar, tropical conifers, balsa, mahogany. On more gentle and accessible slopes, a mixture of productive tree and palm crop can be planted in the shelter of pioneers, and on ridges a protective windbreak of hardy palms, casuarina, and wind-fast legumes. Excellent nuclei clumps in grassland are built up from a close planted 1 to 2 m spacing mixture of acacia, Mearnsii, a melanoxylon, Inca, Gliricidia, Nicotiana, Casuarina, Vigna, Tagetes, comfort, a box or two of nasturtium, box, soil, and all, a few handfuls of fertilizer, and a visit to slash grass and tall weeds. Occasionally, any stones, logs, cardboard, or old carpets help if laid in the clump. Natural aids are stumps, plant in these, and large rocks keep them central to clump. Plant around boxes, logs, or log piles, pocket soil and plant in the logs, or even old buildings and rock walls. It is within and around these pioneer nuclei that we can commence afforestation or productive tree crop, using our nuclei as mulch sources. A general note on the legumes. Most legumes, and other genera of plants such as alder and casuarina have mycelial root associates which fix atmospheric nitrogen. As these organisms, and the roots to which they attach, are in a constant process of death and replacement over a growing season, much of the nitrogen is also released for use by other plant species. Clover and tree legumes perform the same benefit for pastures. Such trees as the rain tree, Samania salmon, can preserve green grass below even in dry seasons. The amount of nitrogen fixed has usually been estimated at 75 to 100 kilograms of nitrogen/ha/year, but efficient legumes such as lucerne, alfalfa, may provide 250 to 500 kilograms of nitrogen/ha/year, and tree legumes such as albizia as much in quite poor sandy soils. Iski, D. 1982, Economic Botany 36, 1. Every part of such legumes as lucina, acacia, albizia, gliricidia and tephrosia may contain high nitrogen levels. One can actually smell the ammonia from the trees in rain or when the roots are crushed. Thus, cut green material from such trees, green mulch, lightly turned into crop, water mulched, or even as interplant, supplies much of the nitrogen for crops. It is necessary to make sure the trees are inoculated as seed with the correct root associates, in the nursery or in the field. Most agricultural departments can supply a list of strains of inoculants, or the inoculum itself. Many firms supply inoculum for legume and other species, or soil from nodulating trees can be washed in around newly planted trees, or mixed with 296. The nitrogen is distributed around root zones as for figure 10.46. Some shrubs and trees lay down about a 9-year supply, and if cut or ring-barked, the slow decay of the roots gives up nitrogen for 6 years or so. Nitrogen, if supplied artificially, quickly leaches in warm rains, so legumes, with their slow nitrogen release, are of critical importance in any tropical crop situation. The management of leguminous tree crop must be carefully assessed for local conditions. Some considerations are spacing, with shrubs and small trees, 0.5 m apart, is the best for foliage production, and trimming. Height of from 0.5 L5 m is recommended. Season, only in frost-free tropics can we trim all year, 4 to 5 cuts, wherever cold is a seasonal problem. 2 months of growth must be allowed to harden the plant before winter, or it will weaken as the shoots are cold-killed. Trees in drought can be part-trimmed. Asterisk forage, there is some danger that young coppice shoots will have higher levels of metabolic poisons than 2 to 3-year-old shoots, and if stock do not thrive, this factor should be assessed. Asterisk shelter, trees can be more widely spaced for root nitrogen, seed production, e.g. for poultry and bees, and for in-crop shelter, as flowering and seed production is better at 2 to 20 m spacing, depending on tree size. A full canopy may be needed to reduce or eliminate frost. Asterisk replacement, although many trees will coppice for 4 to 30 years, any sign of loss of vigor should indicate the need to replant. Replant for small shrubs may be necessary every 2 to 3 years, while some shrubs and ground covers are annuals or become annuals in cold season areas. To assess total nitrogen yield, we must assess soil nitrogen from mycelia, say 200 kg/ha/year, and leaf and /nitrogen/ha. In such crops as tephrosia, yielding 135 t/ha in 4 cuts, leaf nitrogen should be about 20-30 kg/t, or 1,000-1,500 kg/ha/year, which is some factors higher than the root nitrogen yield. This is the whole rationale for avenue cropping and legume mulch. Phosphate and potash levels in green mulch are also satisfactory for crop production. Pioneering in secondary forest growth. And lantana. Lantana is analogous to the rampancy of gorse and blackberry in cooler areas, and the essential process remains the same. Asterisk roll down, crush, or cut out contour strips. Asterisk plant advanced, vigorous mixes of acacia, eucalyptus, vines such as chayote, ground legumes, and local pioneer species. Manure each plant and mark small plants so they can be easily seen. Asterisk / every few weeks in the wet season until the trees are above the lantana canopy, and free any new natural tree seedling that comes up. Figure 10.45. Components of the tropical forest tree. Polyculture. Palms, lianas, vines. Crown bearers to the outside and stem bearers. Inside clumps, fungi and shade species below. A elevation. Yerkschultz. Components of the tropical forest tree. Polyculture. B-plan. Yerkschultz. 3 klp. 297. Asterisk do final / at or about 18 months, and then cut or roll adjacent strips to extend the system. Asterisk use early pioneers, e.g. acacia, as mulch for selected high-value species as previously planned. The shading dash out of lantana takes from 2 to 6 years, and only remnant and weak shoots remain under productive forest. In all extensive hill areas of gorse or lantana, benches or roads cut on contour every 250 to 100 m is a great aid to regenerative forest processes and subsequent harvesting or slashing of new plantation. These can be kept mowed and cleared, and eventually stabilize as trees grow. Road borders can be of dense, evergreen, wide-crowned trees for track shading and stability. Such deep shade also keeps fences clear of grasses and weed crop. Pioneering on difficult terrain. On man-made and natural landslide or volcanic areas of the tropics, it is first necessary to pocket the area with soil mulch mixtures. Nut husks from coconut and macadamia are excellent to establish any pioneer species. Thereafter, species such as Inca idalis, Lucanilococephala, various acacias, A. Mernzii, Scalzia pedunculata, Prosope pallida, and light legumes, Delichas, Desmodium, will prepare the area for palms, cacti, figs, and the more useful fruit trees, by providing shelter and mulch for subsequent plantings. It is better to plant small assemblies than to space out a lot of species on their own. It is better to plant small assemblies than to space out a lot of species on their own. A heavy spike roller crushes nuea lava, an Hawaiian term for lava which is softish, not far removed from pumice. Crushed lava is both accessible and easily rotted to soils. Soil pockets can be provided with trace elements, boron, manganese, zinc, copper, molybdenum, if not analyzed as present in any specific location. Near the sea and on islands, the night air condenses on the sea-facing side of the stones, which have a richer moss algae-like flora than the inland side, and pockets of vegetation act in a similar manner to condense sea vapors for their use. Thus, islands and sea coasts will have dry and wet sides suited to different plant species. In such conditions, a ragged or spiky forest canopy, where palms and tall pines or fruit trees lift above the general canopy layer, will ensure more condensation from sea air than will a level and relatively closed canopy. The saturated winds that sweep off tropic seas carry a heavy moisture load which is available as dew on grasslands, but is much more effectively trapped on the myriad leaf surfaces of an uneven canopy of trees. Hence, the forested slopes of sea-facing mountains in Tropic trade wind areas. Even small garden tree patches. Rain softly on clear nights when a sea wind is blowing, and let down drips in a steady stream to swell. Dried out leaves and to channel down leaf midribs to 298. The fibrous trunks of palms and tree ferns. Once plants are cleared, the effective precipitation falls, rivers cease to flow, and the land becomes truly dry. Savanna forestry. Wherever overgrazing plus fire or cut and burn. Forestry has ruined native forests, in particular towards the wet dry tropics, closed grassland species of fire-prone and tough grasslands develop, closing out the tree seed bed and preventing good management practices. Further burning or cultivation may result in a depauperate grassland of low stock carrying capacity over the dry period, and patches of bare and eroded soils, low in nutrient states and at times acidic, pH 4.4,5, may develop. Bladdy grass, Umbrotta cylindrica, and other tropical forage grasses are stubborn, tough, and almost impenetrable barriers to gardeners and stock, although they provide good mulch. Given rains of 60 to 150 centimeters, a set of rough pioneer legumes are available for the rehabilitation of hosted sites, including mine spoils and road embankments. Providing enough seed can be obtained, direct seeding in scratch holes or chiseled strips will result in the fast establishment of some, or all, of the species listed below, to which can be added Leucaena and Albizia species. Tropical grasses, sod, or mown 5 to 6 times annually, make good mulch for trees and gardens. When using legumes, leaf drop and nodulation will re-establish soil fertility. The canopies of acacia, auriculaformis or a mangium will shade out and kill the grasses, so that fire intensity is reduced or eventually eliminated. Using these pioneer legumes as nurse crop, firewood, pulp timber, mulch, and honey sources. High-value timber such as rosewood, mahogany, and ebony can be introduced in lines or clearings in the first crop, and the gradation made to either high-value forestry or to sensible strip cultivation on a sustainable. Figure 10.46. Zones of nitrogen intensity around a tree legume. Nitrogen will diffuse from the soil for up to G years after a tree is cut down, so the effects last long after the life of the tree. Intensity of nitrogen concentration falls in the outer root zones. Equals. If Leucaena, Samania, Prosope, and Inga are planted, a long-term forage system will evolve, providing replanting or rest periods are given for seedlings to re-establish. The only thing preventing or delaying savanna forestry is a lack of tree nurseries and seed sources of appropriate species, and this too presents an opportunity for a pioneering enterprise in the humid tropics. A very good selection of potential species can be found in the National Academy of Sciences publication referenced at the end of this chapter. Species such as Plerocarpus indicus or P. erinaceus can be first seed planted in a nursery stand, then coppiced for 2 minutes quickset planting in boreholes in the field. Some species can be set out at 10 centimeters diameter, and make good timber trees. Pioneer and grass excluding species. Firewoods. Acacia auriculaformis is an important pioneer for exhausted savanna and tropical soils, where over a very wide range of soils and sites it can defeat bladdy grass, Janeparita cylindrica, restore fertility, provide firewood, and act as a tree nurse crop. It reduces fire and provides good paper pulp. It coppices and self-seeds and is widely used in tropics as a shade and street tree. A mangium has similar characteristics but is straight-stemmed and therefore better suited to forestry. Sesbania grandiflora is a fast tropical pioneer, can be coppiced, and is a good forage tree, an excellent green manure in rice, and reinvigorates worn-out land. Exceptional nodulation. Grows to 10 m and provides good firewood. Wide soil tolerance, extensively used for eroded hillsides. Young leaves, pods, and flowers. Used for human food, 36% crude protein. Seeds are 40% protein. Used as light shade crop, vine support. Good in crop. Frost and wind tender, life about 20 years. All food from this tree should be cooked. X. Why fast growing? Calliandra colodersis. A stickwood coppicing species, which defeats grasses and provides abundant firewood. Repairs exhausted soils and restores fertility. Dalbergia sisu is salt and frost tolerant, fast growing, and defeats grasses. It tolerates a wide range of soil types and can be quickset from large cuttings. India. Enterolobium cyclocarpum is a durable timber tree with large pods, defeats grasses. Central America. Mimosa scabrella of Brazil is a subtropical pioneer. Provides good humus and a living fence. Samania salmon, rain tree, is a very fast-growing large tree of the tropics and subtropics, with sugary pods. Grass grows well below. Wood is valuable, durable. 10.12. Animal tractor systems. Following are 2 examples of animal tractor systems, either of which can be used to prepare soils and remove grasses or persistent weeds for evolution to garden and tree crop. Chicken tractor. Confined chicken flocks will remove all green ground, cover and surface bulbils, depending on how many are confined on how big an area, thus killing out or summing such plants as oxalis, nutgrass, kikuyu, onion, wheat, and pastured species of convolvulus. Dano Gorsic, on a 0.5 ha farm on Molokai Isle, Hawaii, has planned and executed a successful chicken tractor/garden system on a stony hillside site. The process is to fence 5 to 6 plots and rotate a 4 chicken flock on these plots over a period of 18 months. As each forest area is scratched bare, it is limed, raked, and sowed immediately to vegetable crop, typically brassica, beans, peas, amaranth, cucurbits, radish, root. AE chickens are moved to plot 2, and in about 6 to 5 weeks vegetables are in full production on plot 1. As Dano also needs a cash crop, he has interplanted young papaya in plot 1 amongst the vegetables. These grow strongly and succeed the vegetable layer, giving high shade, and, from the waste fruit, chicken forage in later rotations. Thus the tractor system proceeds, with chickens. A Eurosi. Figure 10.47. Savanna forestry. A high-value advanced seedlings planted in riplands. BD chiseled. Area sown to desmodium or lablab ground cover. C acacia strips. Sown in kaisati ground. E selected large figs, albizia, inca, set out. Equals G. In Q-God soils around hollows, F look and bean crop drilled in. Chiseled area. G quickset coppice forests of Bauhinia, Phoracarpus. Some in deep holes. 299. Pioneering the weeds and vegetables and papaya. Succeeding them. In about 18 months to 2 years, a more perennial system succeeds a weed layer. Eggs, chickens, vegetables, and papaya are at modest commercial level, and both milk goats and chickens are let out onto the paths to eat greens when the pens are bare. I have now seen numerous chicken tractors, all different, some with passion fruit fence/trellis crop, some just as vegetable gardens, and some for small fruit or herbaceous orchard. All are remarkable for lack of weeds and high production. In the more mature cycles, buckwheat, comfort, millet, sunflower, and sorghum can be sown in the pens a few weeks before the chickens are returned, providing greens and grains. Even rocky or rough country is so prepared for crop by chickens, the main cost being secure pen fencing. Strong fences also support vine crop, and a few larger legume trees provide high shade, tipu and a tipu. Larger albizia, for pens and crops, where chickens are to be the main crop, chicken. Forage plants replace vegetables and some fruit crop, and the system then provides all food near the house. A few small top-netted and secure rearing pens allow broody hens to replace the chickens called normal. Weeds such as oxalis, cleavers, dandelion, onion weed, nettle, and nutgrass are excellent chicken fodders, as are any of the solanum family, huckleberry, black nightshade, pepino, kangaroo apple, tomato, huskberry, sodom apple, etc. Pig tractor. The pig tractor follows the same technique but is more suited to 1-40 HA properties. Larger shrub weeds, lantana, gorse, blackberry, or deep-rooted weeds, convolvulus, rhizomatous grasses, comfort, call-for-a pig tractor. The density of pigs per pen should be at the proportion of 50/HA for full clearance of weeds. In practice, 0.5 to 2 hop plots are fenced, most economically, using permanent electric fencing, which is much cheaper than chicken mesh fencing. Once each pen is bare, 6 to 10 weeks, and rough plowed by rooting pigs, it is easy to plant lucerne, comfort sets, sunroot, jerusa, lem artichoke, sweet potato, inca trees, papaya, banana, and similar crops for pig forages, and to keep up this rotation until the pigs return to the pen. On a large scale, 20 to 40 ha, the pig tractor system can pioneer high-quality milk cow pasture of chicory, dandelion, comfort, dock, and clover, and cows follow along 2 to 3 months behind the pig tractor. A continuous rotation is set up, and excess milk product, whey, skim milk, fed to the pigs as accessory food. Piglets ranging over such pasture rarely show iron anemia deficiency, parasite cycles are broken, and the soil constantly improves in humus. Such large animals as pigs and cows need fenced tree strips, tree guards, and border hedgerow to supply tree forage crop. Obviously, these intensive animal tractor systems can be a phase followed by tree crop, an accessory to tree. 300. C-top, or a permanent feature of the mixed farm, or used seasonally to remove crop wastes and fallen fruits. Chickens, I feel, should be a permanent forage system in all mixed orchards. 10.13. Grasslands and range management. In view of the prevalence of livestock enterprises in the tropics, some guides to management are required for milk and beef or sheep production. The following management strategies can be implemented. Send to add a tone of forage species to grass lands. These can be grass legumes or trees, the latter providing foliage, food sugars, seed carbohydrates, or fruits. Asterisk environmental changes, particularly in terms of water storage and soil structure, irrigation, windbreak and shelter, key fertilizer or trace elements, can be added, and plant species can be maintained by slashing or light cultivation of pasture. Asterisk conservation of forage by rotational or periodic rests from grazing, by using hays and silages, by supplying protein or urea supplements and molasses in drought, and by keeping stocking rates below the worst case conditions. Asterisk stock management, especially by well plant buying and selling to keep numbers in tune with seasons and longer term fluctuations, for example, timing calving or buying in animals in spring or early summer, and selling them or dry cows in autumn. To lessen winter feed demand. At the extreme, stock can be penned and fed harvested fodders. A sequence of species or a species polyculture can be planted to take best advantages of FO. A mixture of legumes with a selected grass species, plus some storable forage is ideal for the tropics. Most grazing systems can extend under palms, between large tree crops, or a five complex with belts of forage tree legumes yielding fodder, fruit, pods, or large seed for food concentrates. Each soil type, location, rainfall area, slope type, and main crop needs assessment and planning. The leaf swords valued by graziers may also suit green crop cover for orchardists where regular ing for easy fruit harvest is practiced, or sporadic grazing. In these cases it is essential that the orchard crop is well established using manures before twining legumes are planted. Soils under pastures are of excellent structure, and erosion is effectively stopped. Elephant or banded grass, Painazedum purpureum, is best on deep alluvial or coarse flats above 110 centimeters. Alluvium, or 90 centimeters, coastal, rainfall. It reaches 2.5-4.5 m high, but can be grazed to 1 m or cut to 15 centimeters for forage and mulch. It needs a vigorous legume, e.g. Leucaena and turplant, or forage legumes such as calopogon, centrosema, glycine, in high rainfall tropics. If a cool season is expected, autumn cutting should be later so that cool season regrowth is obtained. Banana grass can be set out as windbreak by burying hard slim pieces of 4 to 5 nodes horizontally at 8 to 10 m depth in summer. Furrows should be manured and kept free of weeds until the stems shoot strongly. Permanent plots can be established, well suited to feeding selected stall-fed dairy cattle. Accessory plots of bean trees, coconut, banana, etc. for diet variation, and palms for bedding, are ideal. Banded grass can carry 7 milk cow/hive cut and hand-fed with leucaena and sugar pods. Tropical pasture grass species. Guinea grass, Panicum maximum, this is a bunch grass. For warm areas of more than 90 to 300 centimeters rain, it is drought resistant but yields best in humid areas. Frost sensitive, shade tolerant, and suits thin crown tree crop, often yields well under trees. Valuable in that growth is maintained in cloudy summer-autumn regimes. Grazed down to 15 to 20 centimeters combines well with twining legumes which climb on stiff stems. Suits rotational grazing, 12 to 18 fields, interspersed trees and tree fruit forages. Drilled to 6 millimeters. To establish a first choice for subtropic and tropic. Painazedum clandestinum. Cold tolerant. And grown from cool to tropical areas. Valuable for cooler uplands, thinner soils, and for good autumn growth of nitrogen fixing trees, acacia, leucaena. Prosope, albizia, are established. Prefers light soils, red loams, and can be sown as runners or seed. Excellent for water spillways and erosion control. Few legumes tolerate the tight sward, so that trees for nitrogen are essential. Desmodium, glycine, and white clover. Sod-drilled in autumn cut areas can be tried. Mockra grass, Panicum coloratum. Bunch end. Spreading types for 40 to 90 centimeters rainfall. Tolerates alluvial fans, floodplains, black clay soils, red earths, and even semi-cake salted soils. Needs a year after seeding to establish, so suits rotational systems. Lucerne interplant. Can succeed in irrigated areas. Drilled at 1.3 centimeters, 2 to 3 kg/hog or planted from rooted cuttings. Valuable for winter green feed, drought resistance. Suits long rotation grazing in open savanna of acacia, sugar pod trees. On black clay soils, purple pigeon grass, Citeria porphyrantha, may germinate better than Mockra. Para grass, Brachyarea mutica. For warm areas of low frost intensity, valuable for swampy soils and at soaks. Dams, water holes. Provides good soil structure due to fibrous shallow roots. Can be grown with the forage. Legume phasy bean, green leaf Desmodium, Centrosoma. Puro. Ideal as a fenced out reserve food for drought. To finish off animals for sale in poor seasons. Planted from cuttings at 2x2m or seeded if seed is available. Do not plant where clogging of channels can be a problem or where other crops are to be grown. Can reach 4m in one summer. Sorghums, sorghum almum, silk sorghum, and Sudan grass, S. hulipans, are annual, biennial, or persistent. From seed, and are of most use as broadcast sown. Pioneers in/mulch at 50 to 90 centimeters rainfall. They can be used as pioneers with the perennials, as mulch in orchard strips, as emergency dry season fodder, and as a garden mulch source. Easily grazed out, the sorghums provide bird seed, forage, and help control weeds. They are of particular use in early establishment and can be surface sown. Establishing perennial grass swards on weedy or eroded areas is a 1 to 3 year process. The best way to proceed is choose a land-forming system such as swaling, interception banks, or pitting. Try to establish some dams for irrigation above good soil types. Sow a pioneer grass such as molasses grass, sorghum almum, or silk sorghum mixed with sawdust into slashed weeds, or drill selected grass and legumes. Burn molasses grass, or drill selected perennials, and broadcast sorghum almum. Concurrently with earth forming, plant a mixture of leguminous trees along swales, through the area to be grossed at 30 to 100 meter strip spacing. Allow 2 to 3 years to grow with light grazing to year 3. Commence managed rotational grazing, and drill or broadcast forage legumes into established grasses. About 15 to 18 fields are necessary for rotation. On irrigated areas, some strip grazing is possible. Use electric fences. On rocky knolls, leguminous tree pioneers followed by kikuyu sward may succeed. Early furrows of banana grass provide erosion and wind control at 30 m spacing until tree legumes establish. At every stage, soil analysis and minimal mineral fertilizer amendments may be necessary, and with intensive grazing, sulfur and potash dressings are desirable. Tropical forages and green crop. Desmanthus virgatus is a shrub to 3m resembling lichen and tolerant of heavy cutting and browsing in the savanna tropics. It is vigorous and seeds are prolific, thus should be on range, not in field crop. 7 to 70 t/ha/year. Desmodium discolor is a browse shrub to 3m, yields some 30 t/ha/year green fodder and is sown prior to rain as strips in rangeland. Also compatible with maize. D. disperchum. Perennial to 2m. Good on acid soils, 2 to 7 t/ha/year. D. gyroides. Shrub to 4m tolerates wet sites in tropics. Can be cut for forage, stems brittle. D. nicaragans. Excelient forage, wide soil range in tropics. Pioneer plant in grassland, for cut forage. Tag assist, Chemositis hispamensis. Tolerant and hardy to tropics, GU areas, widely used in New Zealand in dry areas for cut forage, pioneer, mulch, and nurse crop. T. Gledatia triacanthus. Selected trees. Bear heavy loads of pods in dry subtropics, frost hardy. 301. Thornless forms exist. Deep soil moisture is required in the dry season, but the tree is soil tolerant and wind hardy. Best trees are thornless, high sugar types. Kiwi, Prosope pallida. Staple pod forage on dry savanna sites in subtropics, dense wood, excellent. Firewood and termite resistant posts. 20% thornless. Trees on Hawaii. Non-invasive. The pasture legumes or forage legumes. Calipo, Calipogonium mucunoides. A short-lived twining perennial used mainly as a pioneer of burnt or weed areas to smother weeds before permanent systems are established. It is suited only to low frost coastal areas of high rainfall, above 125 centimeters, and is moderately shade tolerant. It reseeds, but shades out or can be grazed or cut out. High seedling vigor. Centrosema pubescens. A twining perennial. Used in both pastures and grain crops. Prefers more than 125 centimeters rain, warm climate between the tropics. Excellent cut forage and soil builder, tolerant of wide soil range, acid soils, short flooding, some frost. Ideal for Guinea grass permanent pastures, Banna, Pangola, and Para grasses. Climbs to 14m, so is not suited to short perennial crops, bushes, small trees. Can be broadcast in burns or slash areas, or drilled. Seed may need hot water treatment, inoculation. Persists well undergrazing. Kenya white clover, Trifolium semipilosum. Persists well in short grass pastures, dairy strip grazing, more than 100 centimeters rainfall or irrigated. Flowers autumn and spring. Needs good seed bed, scarification, inoculation. Haifa white clover, Trifolium species. Strain adapted to summer heat, subtropics, persists well, reseeds after drought. Good interplant together with woolly vetch. Greenleaf Desmodium, Desmodium intortium. Vigorous trailing eel used as understory in tall orchards, after establishment, affected by frost, needs more than 100 centimeters rain, but valuable for soil building in sandy soils, for early spring and autumn growth. Tolerant of poor soils, and stands some water logging. Needs rotational grazing. Seeds need inoculant. Companion legume is glycine for wind control. Silverleaf Desmodium, D. Wasinatum. Trailing Vigorous perennial for mulch in established orchards. Rocky sites, pastures, wet, not boggy, areas and acid soils. Pod sticky, and some people get skin rashes if it is used in gardens. Macrotylome axillary was Dolichos axillaris. Twining perennial, forming a dense sward. Needs more than 100 cm rain in light frost areas. Valuable in shallow, rich soils, tolerates some dry periods. Establishes readily. Lab purpureus was Dolichos lab. Vigorous annual or short-lived perennial useful for soil building and weed control. Grown as a forage and mulch legume wherever cowpeas succeed. Will stand. Sporadic grazing, kept in rotation or strip grazing. Good silage, compost, mulch, pioneer crop. Tolerates acid soil, rough seed bed. Broadcast at 20 kg/ha, drill. 302. At 6 to 10 kilograms. Inoculation assists establishment. A good screen plant on trellis for watered dryland gardens. Pods and beans edible. Glycine, Neonotonia whitei was Gilsine whitei, G. Java and ICA. Slender, twining perennial with deep roots. Cycles phosphates from deep soil layers. Resists drought well, but affected by frosts. Useful in cool subtropics and tropics. Good winter growth in pastures. Main growth in summer. Often fenced out in late summer or early autumn as a winter reserve. Rainfall. Ideal at 80 to 180 centimeters. Does best on well-drained deep red soils, but also yellow clays, black cracking soils, areas not subject to waterlogging. Needs rotational grazing. Rested in late spring. Good silage, with molasses. Mulch, fertility restoration of soils. Good seedbed and inoculation desirable. Lucerne, Medicago sativa. Grown from cool temperate to tropics, usually as a pure sward cut to baled hay, but also in well-managed pasture under rotation, allowing a year or so of light grazing. Grows from 55 centimeters and up rainfall, as it is deep-rooted. Combines well with macrocari, sorghum. Regular resting is essential to persistence, and in pasture needs reseeding every 4 to 8 years. Cut for hay just before flowering. Reseeded in cut sward by chisel seeding. Inoculation essential, and lime pelleting also essential. In acid soils. 6-14 kg/ha sown, lighter on rain-fed areas, heavier if irrigated. Silage with molasses now. Popular, hay expensive, and in high demand. Garden plots used for mulch, rabbit feed, seeds for sprouting. Macroptylium lathyroides was phaseolus. Lathyroides. Self-regenerating annual, long erect. Twining stems. Needs more than 75 centimeters rain, heavy soils. Can be sown with paragrass in swampy areas. Also with glycine. Ceritro, Macroptylium atropurpureum, perennial. Legume, creeps, good root system. Warm areas of 75 centimeters or more rain, ideally 90 to 110 centimeters for soil tolerant. Excellent contribution of nitrogen to grasses, e.g. Rhodes grass. Ideal for rotational grazing, readily established, resistant to nematodes. The basis of many excellent pastures. Puaria phaseoloides. Pioneer green and cover crop, perennial climber. Very vigorous as a smothering summer mat. Used in wet tropics. Palatable, good seedling vigor, can be broadcast. Can be kept in pastures if rotational grazing practiced, but also suits green manuring, orchards, garden mulch crop. Stylus amskianensis. Perennial pasture. Legume of warm areas, 90 to 100 centimeters rain. Good pioneer of poor acid soils, poor drainage, sands, rocky soils. Hillsides. Combined with low grasses, signal grass. Pangola, sensitive to copper and phosphate deficiencies. Excellent mulch in tree systems in such soils, can be cut to silage. Surface planted, wide range of inoculants. Many varieties. Suited to specific sites and climates. Some shrubby types are an excellent Saba interplant, or also suit banana/papai once plants. Of fruits are established, as a mulch, often kept as a feed for dry season, suits fenced off reserves, Sika. Variety, shades out in dense plantation but maybe. Ideal establishment mulch. Cowpea, Vigna sinensis. A preferred annual cover. Crop and soil improver. Also with sorghum, maize. Millet as a hay or mulch in established orchards. Lupin, West Australian varieties of seed lupins. Tent cover crop and seed in acid sandy or good. Inoculated, can be broadcast or sod seeded. Good. Winter green crop, annual, in vines, bush fruit crop. Mung beans, Vigna radiata was phaseolus orlis. Vigorous garden green crop, forage annual, hay or grain crop. Suits gardens and low crop systems. Annual. Note, serious attempts to establish green crop and productive perennial pasture should be prefaced by research into species. An excellent place to start is Humphreys, L.R. A Guide to Better Pastures for the Tropics and Subtropics, Wright Stevenson and Co. Pub. Australia P/L, P.O. Box 113 Ermington, NSW 2115. Rows of tropical hedgerow and windbreak. Evolution from Painazedum hedge to a permanent palm casuarina legume windbreak over 2 to 5 years. Quickset. Erythrina assist in early establishment estrogen set in soil. 10.14. Humid tropical coast. Stabilization N. Shelter belt. If we presume a fairly delicate sandy coastline, then we need to build a complex stable assembly from the wave break to 10 to 20 m inland. The natural profile of undisturbed beach vegetation is that of a convex profile into the wind, and these uncut shores are very stable. Tropical hedgerow and windbreak. Deliberately mixed hedgerow is a preoccupation, skill, and literature of the temperate zones, as these were the first to suffer enclosures of common lands, but the rape of the tropics has now proceeded so far and fast that pioneer hedgerow is a priority theme for tropical coasts and hill country. Due to ideal growing conditions in the climate, if not the soil, hedgerows quickly establish. A classical hedgerow for the tropics is given below. Well-tried procedures are as follows: cultivate, manure, and place strip line along a hedgerow side, and set out, concurrently, a row of tall grasses or clump bamboo, Painazedum as usual. Quickset cuttings of Erythrina fusca or jatroph. Seedlings of Leucana or acacia. Occasional palms as seedlings, preferably those with spiny trunks or midribs. The results can be as in figure 10.48. This is for field conditions. When first setting small orchard crops such as citrus or avocado, both wind tender, first cast up an earth-rich system and plant Painazetum hedges every 30 m, 100 feet, crosswind and, if possible, cross slope. This may result in a series of parallel lines, if wind and slope coincide, or a diamond pattern, wind at an angle to slope, or a series of squares, wind and slope at right angles. Pay particular attention to the top of ridges in wind-prone areas. As the young orchard grows, the Painazetum at 30 m shelters it. Every second row of Painazetum can be combined with Lucina, and every third and every ridge row with acacia and palms. The evolutions follow. Later, the inner rows can be removed as mulch, complicating the HE row. Tomato trellis can be placed on Luena and passion fruit on most trees. Mango itself is a good windbreak. Eugenia can replace some Levcina, and we are on the way to a mixed hedgerow for wildlife, domestic forage, and food in the tropics. Would never neglect a clump. Bamboo as a source of structural field material and effective windbreak. The cross-slope ridges early established become long-term soil and water traps, and accumulate mulch for later evolutions. These are a feature of the tropical crops material center on Molokai, and there one can see their uses and long-term evolution under cultivation into terraces of undoubted stability, as in Figure 10.8. Roads should be provided with concrete or 303 stone fill at X, the downhill side of the mounds. Permanent roads can be made after the faces are formed. 10.15. Low island and coral cay strategies. All coral sand cays and many low atolls lie within 28 degrees AF the equator, as do coral reef areas and sandy alkaline coasts. As many peoples live on atolls, very careful design approaches are needed to avoid the known risks of hurricane erosion and damage to plantations and coasts. Asterisk water table, water lens, pollution, and asterisk poor nutrition due to a limited diet, usually high in carbohydrate and oxalic acids. Additional design input is needed. Asterisk to extend vegetable and fruit crop. Asterisk to extend water storage and to conserve water. Asterisk in conserving natural vegetation and unique birds, reptiles, and lagoon or reef fauna. Asterisk to use shallow marine waters for aquaculture and pond fish, and asterisk in developing energy resources locally. On atolls, we can expect soil pH values of from 8.0-9,5, sand abrasion, and basic mineral deficiency, especially iron, zinc, molybdenum, boron, in soils and plants. Elemental sulfur, iron sulfates, and humus added to garden soils and planting holes lower the pH. Humus sources are palm fronds, coconut husks, tree trunks, and leaf litter from such pioneer species as Casuarina equisetifolia, sea grape, Coccolobus unifer. Coastal shrubs, Cibola, Tournefortia, Pemphies, and Barringtonia trees, all yield abundant. We also can expect a thin coral-lined sand over a hard pan of caliche or calcrete. Calcrete is worsened by the application of superphosphate, usually the guano from seabirds provide sufficient phosphates if colonies of terns, gulls, boobies, frigate birds, and shearwaters are protected or encouraged. Failing this, domestic pigeon, quail, pheasant, geese, ducks, and chickens can be kept as such predators as feral cats and foxes are usually absent. Preventing water lens pollution. The sole natural sources of water on low islands are those biological storages such as we find in baobabs and coconuts. About 12 coconut trees provide for a person's drinking water for the year, and that water trapped in the sand below the caliche, floating on the seawater. The water lens of figure 10.49. As rain falls on the islands, it quickly absorbs in surface soils and leaks through the caliche to the water lens, which itself leaks slowly to sea between or below tide levels. As the beach berm is 2 to 4 m above sea level, and the inner atoll about 2 to 3 m, the delicacy of the situation in the event of water pollution is obvious. For this reason, settlement, toilet areas, processing, livestock, and even gardens should be kept to the periphery of the island, and the interior devoted to dense natural stands of food and native trees, kept free of pesticides or industrial pollutants and fuels. It is obvious that a polluting source at the center of the island can affect the whole water lens, all plants, and all people. By what methods can we increase the supply of potable water? First, by using runoff water to house tanks, the latter above or below ground and made of a reinforced cement coral sand mix, which is widely used in construction on all but remote atolls. Secondly, and of most importance to plants, by using deep mulches, and by growing ever-abundant coconut, banana, arrowroot, papaya, legumes, and like plants to provide leaf and trunk materials for gardens and other tree crop. Lastly, and often successfully, we can try leaf ferment seals, glaze, of gently sloped coral pits, where a 20 cm deep mash or shredded mass of banana, papaya, and other soft green leaf is applied to the base and sides of the area, covered with plastic until fermenting, sometimes only 4 to 5 days, and then pumped full of water from the fresh water lens. Figure 10.49. Water lens on an atoll. Fresh water lens loading of the sea below the sands. Real care must be taken on atolls not FO exhaust or pollute the AEPTIF. These 4,409 IU. Us. 7.19. Made carefully, such surface ponds will also take roof runoff. Success follows careful trials at small scale to get the system working, then scaling up to significant ponds for ducks and garden water, water leaf crop, and animal drinking water. As such ponds are often a source of cross-infection in children, it is sensible to swim in the lagoon, and to drink tank water. Seawater serves also for many toilet uses. Planting trees on coral cays. To plant trees, we need to clear off a patch of topsoil and break open the caliche, making a pit about 40 x 40 EMS and 60 to 80 centimeters deep. In this pit we make a humus pile of domestic and plant wastes, plus some sulfur and the mineral trace elements, and plant a coconut or other seedling tree. The tree roots spread out above the caliche layer, and feeder roots go below the caliche to the water lens, which is usually 0.75 to 1.0 m down, and 1.0-2.0 m deep. As a saturated sand layer, trees are thus well anchored and easily obtain water. To plant gardens, we have 2 or 3 possibilities. The first, and best, is to open a pit garden of about 8 m, 15 m, and slope for stability to about 2 m deep, thus often damp or wet on the base. Figure 10,50. The sloped sides are stabilized as steps with coconut logs or caliche, and the spoil banked around the rim. Mulch is thickly applied to the base and behind the stepped terraces, and when this is rotted, a range of plants are grown from base to crown. Some such sequence as follows is appropriate. 1 base, damp, mulch, watercress, parsley, chives, brassica, taro, kangkong, salad greens generally. 2 first tiers, 18 to 25 centimeters above base, tomatoes, taro, sweet com, beans, peas, taller crop. 3 second tiers, 25 to 60 centimeters above base. Banana and papaya, sweet potato, cassava, all provide mulch. 4 third, or highest, tiers, cassava, sweet potato, banana, dry tolerant vegetable crop, and mulch. Trees such as labiena, gliricidia, tipuana tipu, moringa, alifer, and local tree and shrub legumes to provide leaf mulch and partial shade, palms for front mulch and high shade, vines to climb on these, passion fruit. 4 winged bean. Secondly, under some light palm legume canopies. Boxes of palm logs will hold thick mulch and house hold waste for surface gardens. These can be planted as beds of potato, yam, sweet potato, and normal veg. Table crop. The thicker the mulch, the less watering needed. Thus, log boxes, pits, thick mulch, and high shade canopy are the essentials for good atoll gardens. Staples are coconut, root crop, fruits, and normal salad. Vegetables plus fish and shellfish from the lagoons or coasts. Figure 10.50. Pit planting on atolls. See Figure 10.41. Shows hard planting of calc-reedy layer, species selected for water. Allergy plus. Sub-SUUATI. Of 305. Avoiding and reducing hurricane damage. Access to atolls is traditionally by boats in reef gaps and today by light planes. When blowing a gap for a reef entry, or clearing a landing strip for a plane, great care must be taken not to open a wave or wind gap to gales, or any atoll can literally wash away. Thus, reef entries are cut on the slant through the reef at the east or west quarters. Winds blow southeast to northwest south of the equator, northeast to southwest north or the equator. In fact, reef gaps should be in the most sheltered sector of the reef in any winds, and also just wide enough, 6 to 10 m, to admit a vessel or barge. Airstrips are also aligned about 20 degrees off prevailing winds, and both ends and sides should be of tall palms and trees, especially those borders on the coast, so that light planes drop in, using their rudders to straighten up below tree crown level. Airstrips carelessly made have destroyed whole islands when hurricane winds have cut them in two following the line of the airstrip. For the same reasons, the sandy coasts of all atolls and cays need a sequence of perennial shelter belt to hold the shoreline against hurricanes. This starts on the beach as convolvulus, /pompon pescapre, and beach pea. Rise on the beach berm to a dense shrubbery of vines, Tournefortia, cibola, and in sheltered bays mangroves, and is backed by a 5 to 6 tree deep layer of coconut palm, casuarina, coxifero, Barringtonia, and other hardy beech trees. Figure 10.51. It is behind this dense front line. Windbreak that we side houses, gardens, and productive trees, which will produce in shelter but not as exposed systems. Extending diet. People who live on small islands, and indeed small traditional villages generally, may exist eating a very few starchy root foods plus banana, with fish for protein. It is quite probable that mineral deficiencies and IOW vitamin high carbohydrate diets can impair health. Thus, a well-mulched pit garden, and a well-selected introduction of tree fruits, guava, citrus, generally, vine fruits, and a polyculture of minor fruits and nuts, greatly extends and buffers the diet. The addition of, in particular, zinc and iron to mulched soils, and periodic tests of leaf content of such minerals, serves to eliminate problems due to restricted diets and highly alkaline soils. Even on high islands, soils can be devoid of, or have, very limited mineral rocks, and soils may need trace elements. Almost every island group has unique plant and animal species, some of great value directly, others of value in that they exist and demonstrate new forms and behaviors. Such groups as land crabs, derived from ghost crabs, shore crabs, and hermit crabs, do special work as mulch shredders, scavengers, larval insect eaters, and may form a valued food resource. Giant tortoises are also excellent scavengers of fallen fruits, and keep grasses below palms neatly trimmed, while putting on a considerable annual growth. Marine iguanas, giant lizards, the Komodo dragon, flightless or specialized birds, and rare plant and animal survivors of older land masses are not only common, but usual on islands. All need careful preservation and assessment for their special values, and many provide useful functions in polycultures. At low tide, even the usual tides of about 1 m variation, atolls may almost double their dry area. It is thus possible to modify lagoon and reef for better. A. Beach convolvulus. 8 cibola. C. Tournefortia. D. Barringtonia. E. Sea grape, cocopa. F. Date or coconut palm, casuarina behind. Beach berm, this profile T.S. stable. 306. Conservation and feeding of economically useful fish, shellfish, and marine plants such as mangroves, or to consolidate and protect shorelines with coral block breakwaters. There are many such marine impound ments throughout the Polynesian world, and new matin breeding techniques are bringing into cultivation such species as trachis, turtles, many inshore, mullet, milkfish, and edible seaweeds. Because of the frequent internal, atoll, or external annular reef, lagoons in or around low islands, designers and residents have extensive quiet waters in which to trial a wide variety of productive mari cultures, shelters for fish, breeding places, and under $A constructs generally. The daily flux of tides through reef outlets brings a regular fish movement, well known to indigenous peoples. Island energy resources. Islands in oceanic energy flows behave very much like bluff bodies in streams. Tide, waves generated by winds, and the water crashing over low reef areas and flowing out of constricted reef inlets present. G00D opportunities for energy generation locally. Reliable biogas technology is now widely used in Asia, and the less reliable wind electric systems can also be used for energiation. Solid fuels from coconut husks, fast-grown copicing legumes, fronds of palms, and casuarina stands are always available on well-planned islands. Climates are usually mild, and the main fuel needs for cooking can be much reduced by a vegetable fruit garden development. One area all atolls and islands can develop is that of tide flow turbines. These can be propellers or egg beater catenary curve vertical axis turbines. Coral and cement provide strong anchors for such turbines at reef outlets. Both tidal and ocean current flow provides dense energy power at 1 kW/square meter/second of flow, so that a few such turbines at selected high flow sites can provide either electrical or pneumatic power for island workshops and lights. The above outline should assist island design, but one factor that we cannot design for is that of rising sea levels. Many of today's atolls will simply be topped or washed away by a very modest rise in sea levels, which is expected to occur over the next decades. For these sites, early evacuation is the best action. 10.16. Choose adapted high-value foods for intensive mulched home gardens. Allow 30 to 90 species in Zone 1, but concentrate on 7 to 20 high-value crops in Zone 2. Avoid bare soil systems in all areas. Design a careful plant/animal assembly related to culture, market, processing, available labor, and value to village. Design houses and villages for low-energy climate control. 10.17. References. Davies, J.L.N.M., A.J. Williams, Landform Evolution. In Australucid, Australian National University Press. Canberra, 1978. Etherington, Dan M. and K. Karanaya B. and Eco. Nomic analysis of some options for intercropping under coconut in Sri Lanka, Sri Lanka Journal of Agrarian Studies 2. Uses mulbud, a multi-period bud getting program for the economic assessment of the intercrops in perennial crop. Fox, James, Harvest of the Palm, Harvard University Press, 1977. Harris, W. Victor, Termites, Their Recognition and Control. Longman, London, 1971. Martin, Frank, and Ruth Robert, Edible Leaves of the Tropics, Mayuguas Institute of Tropical Agriculture. Puerto Rico, 1975. Nair, Pkret. Alia, Beneficial Effects of Crop. Combination of Coconut and Cocoa, Indian Journal of Agricultural Science 45, 4, 1975. National Academy of Sciences, Tropical Legumes. Resources for the Future, Washington, D.C., 1979. Nelliot, E.B.F. Alia, Multi-Story, A New Dimension in Multiple Cropping for Coconut Plantations, World. Crops 26, Note/December, 1974. Ralph, Wayne, Managing Some Tropical Soils, Rural. Research No. 1I7. True Artha, 5. T. An Introduction to Climate. McGraw-Hill, Inc., NY, 1954. C. For Modified. Köppen Climatic Classifications. Designer's Checklist. Maximize tree crop, herbaceous perennials, banana, papaya, arrowroot, taro, and plant a multi-tier system. Integrating windbreak, forest, orchard, understory, and ground cover. Complete earth shaping before setting out plant systems. Acknowledgements. Many friends have helped with information and trials in tropical areas. Would like to acknowledge data from Bud Driver, Marjorie Spears, John Selman, Michelle Fanton, Chuck Busby, Sandy Lewin, Cliff Adam, Imu, Anne Helanaki, Richard Waller, Dan Ogorsic, Bob Kingswell, and Walter Jenny. 307. Chapter 11. Dryland Strategies. The dunes, like harmonic chords, multiply and repeat the notes of the rustling, shifting sands. You now hear what sounds like the sonorous music of distant drums roll after roll. Quilichi, 1969, on the Tobal, or Music of the Dunes. 11.1. Introduction. The development of conservative strategies for the preservation of dryland species, and for the responsible human use and management of arid lands is probably the world's most pressing problem in landscape management. Only sporadic world attention is given to famine or drought in arid areas, with such sudden emergencies consuming great quantities of resources and finance, much of which is wasted in it. Problems of aridity, salted soils, and long-term drought can always be expected where we venture into desert borders with pastoralism and cropping. 4. Added to the natural background fluctuations of rainfall due to Earth and Moon orbits and solar radiation variance, we as exfoliators add deforestation, soil erosion, and the consequent salting of waters and soils. All desert areas are extending, many dryland areas are being created, and antecedent plant and animal species are thereby brought to extinction. A great many arid area species are not so much dry adapted as drought evading. Plants dry off, cease growth, or exist only as seeds and tubers in drought. Many trees are dry deciduous, evading the worst effects of drought in a leafless state, but truly drought adapted plant species also exist, and use max insulation, reduced transpiration, and large water storage organs to withstand droughts. Animals. 308. Estivate, migrate to humid areas, or take refuge near oases and wetter areas. Many animals get sufficient water by eating succulent vegetation, by browsing at night to take advantage of condensation, or by predation on insects and other species of animals. Almost all small animals burrow by day to escape soil temperature fluctuations, often to 1 or 2 m deep. Some termite colonies develop deep galleries, to 40 m, to mine water, and also arrange air conditioning by adapted permeable surface nest structures. Increasing desertification of agricultural lands has focused world attention on salt and drought tolerant plant species of potential use. Gary Nabham, in Annals of Earth TV, 1, 1986, has totaled 450 edible plant species. For the Sonoran and Great Basin deserts of the North American interior, 20% of the total species. The semi-arid or transitional areas are particularly species-rich, thus desertification is taking a rapid toll on potential useful plant diversity. Of the 936 woody plants in the West Australian wheat belt, 45% are at risk. Large reserves are urgently needed. The present reserves in arid lands are entirely inadequate to conserve even a usual proportion of the genetic variation. Nabham, 5. Cold high mountain deserts like the Gobi have some 60 flowering plants, and 360 species of birds, Geo 7/4. 1986, while large areas of the arid Sahara have 6 to 8 plant species in total, and recent deserts such as the there are some 15 to 18 species. Most of the world arid species lie in the Kalahari, Sonoran, and Australian deserts. Arid lands are areas where direct evaporation exceeds rainfall, and where annual precipitation averages fall below 50 centimeters, and as low as ICM, some times only as due. Although the greater part of these areas are hot desert, there are substantial montane, hot cold deserts, and very cold desert areas near the North and South Polar regions. Typically, an extensive hot desert area consists of a savanna edge towards more humid monsoon areas, a Mediterranean climate edge, extensive scattered shrub forb associations, forbs, are any non-grass or herbaceous plants, dunes on Harder pavement areas, and almost bare pavements of harder rocks with faceted pebbles, give or plain or reg. Underscore where overgrazing has not been the dominant feature of land use, a desert may present an eye level appearance of a low-crowned forest with shrub understory, and some areas may be as rich or richer in plant species than a more humid forest environment. In detail, however, there will usually be larger or smaller areas of bare soil between all major plant clumps or species. Closer inspection may reveal a fungal algal lichen, cryptogam, crust on the bare areas, more or less intact depending on the frequency of hoofed animals. This cryptogamic crust is a critical and delicate feature preventing wind erosion. Its preservation is essential for soil stability. Some features of the deserts are asterisk plants produce copious seed with long viability. Seed is often wind dispersed. Asterisk termites and ants are more effective than worms as soil aerators and decomposers. Asterisk rain may fall in mosaic patterns, so that vegetation also a varied mosaic of fire and rain, and ephemeral plants at different response stages from growth to decay are evident. New generations of shrubs may experience favorable seedling conditions as rarely as every 7 to 20 years. This then becomes the period of recruitment of new forests or shrublands. Asterisk much of the water runoff system may end not in tivers but in inland salt pans or basins, Enderhike drainage, from which all water eventually evaporates. Asterisk normal erosion is by wind, but rare cloudbursts shape the main erosion features and move vast quantities of loose material from the hills in turbulent stream flow. Wind transports materials locally in dust storms. Asterisk animals burrow, seek shade, or are nocturnal in order to conserve water. Many are highly adapted for water conservation. Asterisk plant associations may be very varied in response to changes in long-term aspects such as slope, soil depth, salinity, browsing intensity, pH, and rock type. Semi-arid areas have steppe, scrub, and low forest vegetation. Arid is steppe and scattered chow shrubs. And true desert has little but oases and ephemeral vegetation appearing after the rare rains. Deserts have a rainfall classification of asterisk hyperarid, 0 to 2 centimeters annual average, e.g. Atacama. Namib Desert, Central Sahara. Asterisk extremely dry, 2 to 5 centimeters annual average. Asterisk arid, 5 to 15 centimeters annual average, e.g. Mojave. Sonora, Sahara margins. Asterisk semi-arid, 15 to 20 centimeters, maximum 40 centimeters, much of the Australian deserts, Asian deserts, Kalahari. Above 40 centimeters, and to 75 or 100 centimeters rainfall we have potentially dry savanna forests, and it is up to this latter level that we will be dealing with in this chapter. Rainfall is not dependable in arid areas, with a normal 30% variation, and a potential 90% variation in any one year. Potential evaporation can range from values of 700 m/year in hyperarid areas to 100 centimeters in steppe. We can also regard the polar ice caps as hyperarid for precipitation, but evaporation levels are very low. Wind removal of snow places evaporation. Both the very cold and hyperarid hot deserts have one thing in humidify and preserve a great range of organic and fabricated substances, which presents a management problem when dealing with pollution, as breakdown of most organic substances can be very slow in the absence of water. A paradox in almost all large desert or arid areas is the existence of two types of more humid environments, exotic rivers which flow in from better watered or forested regions, and oases. There is a third, invisible water resource, that of aquifers. Underground waters. All must be used with great caution, as water in all of these resources can be locally exhausted, and aquifers can be depleted over vast areas by modest use, as they have been in the USA. This misuse can cause widespread subsidence, collapse of the aquifer, and a permanent disappearance of those oases which were in depressions fed by the aquifer. Instead of concentrating on exotic water in deserts, we should attempt to increase the input of water into the aquifers, soils, and streams, and to rehumidify the desert air by planting trees and protecting existing vegetation. It is the presence of trees and shrubs, transpiring rather than evaporating water, that keep the desert salts from evaporating at soil level. Once evaporation alone operates, capillary action quickly brings subsurface salts to the surface as magnesium, sodium, calcium, and potassium compounds, chlorides, sulfates, carbonates, and we can no longer establish vegetative cover. When we talk of arid lands, we should also remember equatorial low islands, unstabilist sand dunes in midsummer even in cool climates, and whole periods of relative drought even in more humid areas, including the dry winters in many subtropical areas. That is why it is important to specify pioneering and drought-hardy plants for many situations, and why any strategy to get water into soil and keep it there is worthwhile. There are large areas of Mediterranean climate on desert borders which are arid if they have deep sands and poor water retention. A profound question to ask about deserts concerns our basic usage. Livestock herding has been traditional and devastating. Australians, Peruvians, and Africans, Arabs, and Tibetans have all used arid areas for herding. Aboriginal Australians managed better by harvesting the natural abundance of deserts, so that the artificial stress of herds was not superimposed on the natural stresses of dry seasons. We should rethink our strategies of desert use, and the way we occupy arid lands. It is possible to establish a carefully developed core settlement to set out hardy plants for many kilometers along favorable areas or corridors, and to take advantage of the rare rains to establish a wide biological resource for dry years. It is 309. Not possible to count on permanent cropping or herding in regions that experience one good year in every 4 to 9 years. As for desert revegetation, by far the most effective and cheapest strategy is to exclude animals from headwater areas, when after a few years thousands of young plants may establish. Desert borders are now used for a seasonally and uncertain production of wheat, barley, millets, and sorghums. About 1 year in 4 produces a reasonable crop, but severe wind erosion and dust storms make this a precarious use of such delicate soils. Herding and extensive livestock systems also occupy great areas of the deserts, with seasonal or nomadic herding in North Africa and Southwest Asia. If we look at actual income versus land use, the central desert of Australia allots some 73% of the area to pastoralism, and only 27% to aboriginal reserves and conservation areas. However, income is 15% from pastoralism, 76% from tourism, and 7 to 8% from mining. In small areas, even the mining is a tourist industry, where it concentrates on precious stones, and aboriginal art is a large part of the tourist interest. Pastoralism and mining are publicly subsidized, and has a grossly unwarranted system of direct and indirect supports, producing a largely surplus product for the world market. No wonder pastoralists must maintain a powerful lobby in the halls of government. People rarely want to live in the desert. It is an expensive place to maintain a high standard of comfort, in modern terms. But they love to visit, and to see wildlife, genuine tribal art, and the landscape itself. To people, the land is life itself. They are a part of the whole, and their art reflects this. Deserts are inspirational for designers. Not only do the hills reveal patterns, rock types, and processes of erosion, but as the light changes from early dawn to late evening, new insights arise from the shadowed and light areas. What is often unclear on the ground becomes part of a whole pattern if seen from hills or the air. When we understand these many patterns, the distribution of materials and organisms makes sense, and we are able to creatively inhabit the landscape. It is little wonder that desert peoples, in the great silences, beauty, and vastness of nature, arrive at profound mystical pattern concepts. Only the confined oasis or town dweller concentrates on the of finance, commerce, and conduct. In the open, survival demands sensitive reaction to environmental imperatives. 11.2. Precipitation. Rain occurs in deserts as a lesser part of the normal cyclonic, convectional, or orographic rains occurring elsewhere. Both warm, unstable tropical air masses and cold westerly rain may be entrained into air cell circulation over deserts, but there is a significant proportion of convectional rain due to local heating. 310. Over sands, rocks, and bare soils. Only in some deserts does rain fall fairly reliably in a seasonal distribution. In areas affected by monsoon borders or westerly coastal belts, elsewhere, rain is episodic and averages are meaningless in that many years may pass at any one place without rain. There are the natural deserts, the Namibian coastal areas and the Atacama, where offshore winds and cold sea currents ensure that rain is rare or virtually absent. Such areas are treeless, and depend on fogs and dew alone for plant growth. As dew may be critical to plant survival, dew traps of stone, scattered shrubs, or even vertical metal screens to 1m high are strategies to catch moisture. Moroccan foresters are contemplating such metal screens to condense dew and to thereby establish shrubs, which in turn will become moisture condensers. Opportunistic responses to precipitation. A rainstorm 8 to 12 millimeters produces runoff sufficient to start headwater stream flow, and only the occasional downpour of torrential convectional rain, or the heavy rains of monsoons and trade winds over headwater streams remote from the desert produce river flow down the braided or sandy water networks that thread through the desert. For tribes people and the mobile fauna of the desert, distant rain is the trigger that sets off a whole sequence of migration and perhaps a subsequent intensive breeding program. Just as we can write a dissertation on the phrase Om Mani Padme /Nam 50, we can write essays on such simple concept words as walkabout for Central Australian tribes, rather than being an arbitrary, willful, or unpredictable movement that the calendar-regulated Europeans see it to be. Walkabout translates as something like, our scouts saw thunderstorms to the far north. If we go now we can arrive in time to harvest some of the birds, animals, art plants that will respond to rain, and to follow the water to the waterholes that will fill with fresh water and give us fish, turtle, and frogs. For a few months, we must go now, in time to celebrate the cycle of plenty that comes from the rain. Thus we can see such movements as being sensible, and appropriate to an environment which presents rare opportunities to harvest the varied resources provided by rain, to visit newly regenerated country, and to lighten the burden of resource pressure on favored home areas, so that they can regenerate as reserves for hard times. The response of the desert to rain is truly remarkable. Ephemeral plants carpet the ground, and flowers and seed are produced in abundance. Buried tubers throw out great patches of melon, bean, and yam vines. Shrubs or trees may produce numerous seedlings in areas where few young trees existed, in the streams and OP peak. Peak amplitude 7. Co. Stall whirlwind B. Locomechian altirum yen pa. Equals. A. BA act 2 plus. T. Mania AECT na IG sun air went OE. So. CBUMVLE Nickbees. Cumulus. CUEUUP cap. A. Figure 11.1. Some climatic factors in drylands. Sea dust storms, raised by fierce downdrafts before convectional. A daily temperature range typical of hot deserts. Soil temperature storms are often followed by rain, pitting of soils, see figure 11.15. It may lack bearing, and exceed, has extremes. Convectional aeroolumes prevents dust lit in winds. Usually occur at about 1 to 3 p.m., and die out at dusk. Zero dryland flood sequences are moderated by retardation basins. And B rainfall, here in South Australia, may never exceed potential. The form of the catchment, most runoff, 35%, occurs in headwaters. Evaporation, hence the importance of infiltrating runoff into solis. Much less in mainstreams, 0 to 5%, unless in widespread rains. Pools, frogs, and fish appear from mud-packed retreats, or invade from the rare permanent pools. Fish may breed and grow in a few months, and seabirds migrate inland and nest to take advantage of this. Flocks of pelicans, flamingos, herons, terns, gulls, waders, and ducks occupy the waters, and for a few months life is. Antelope, kangaroo, and the desert quail, pigeon, finches, and parrots flock to waterholes and spread their ranges over new forage areas, and animal numbers build rapidly. The longer-term collapse of this explosion of life is slower but usually inevitable. Some new tree generations may have established, but the waters turn salty, dry up, and life scatters, dies, or returns to rest in mud and sand. Seeds are blown and buried, and the desert waits again. Birds disperse, as do the migratory animals, and the desert fringes experience a sudden eruption of migrating species. The party is over. It is part of our strategy to capture some of the estimated 88% of water that either evaporates or rushes unused across the land at these times, and to safely store it below ground for a prolongation of the growth period, and a rehumidification of the desert air itself by a transposition from trees and shrubs. In natural conditions, as little as 0.8% of total rainfall infiltrates to recharge desert aquifers. 11.3. Temperature. The air temperature, up to 60 m height, over deserts, approximates the daily pattern given in figure 11.1. Have not given the 6 a.m. temperatures, which can range from 8 to 30 degrees Celsius, but show a general least graph, which holds true for most cases, and indicates a rise of about 10 degrees Celsius to 25 degrees Celsius over the day, with a peak from 12 to 3 p.m. Soil temperatures follow this general curve, but peak about an hour earlier. The soil is also colder just before dawn, at about 5 to 6 a.m., and the effect of temperature falls off as we go deeper in the soil. There is little effect of daily changes at 30 centimeters, 12 inches, depth, and the peak surface temperature reduces about 2 degrees Celsius for every 5 cm depth, or 13 degrees Celsius in 30 centimeters, so that soils at 30 centimeters deep may have fairly constant daily temperatures, some 5 degrees Celsius, or 50 higher than the lowest surface temperature, and 15 degrees Celsius or so lower than the highest surface temperature. Another way to look at this is that soil evens out the heating that affects air for a considerable distance above the ground. Both air and soil follow a slower cycle of annual range depending on latitude and radiation received in season. This affects soils to about 2 m depth, with about 5 degrees Celsius annual fluctuation at this depth, or about the same fluctuation that we experience in underground houses and cellars. Soils also can gain and hold much higher levels of heat than air, and 5 centimeters depth, in favorable sun. 312. Slopes and in poorly conducting soils, about 60 to 70 degrees Celsius, can be reached at peak. While this effect is good for solar hot water collectors, it is lethal for young plants. Surface air temperatures frequently reach 30 degrees Celsius in deserts, and there are isolated records of 52 degrees Celsius 125 degrees Fahrenheit. Layers of superheated air just above the soil may become unstable and form rapid convectional currents, especially on sun-facing slopes. Cumuliform clouds can arise from this effect as thermals or strong updrafts, or as clear air turbulence in very hot dry periods. In order to escape the extreme surface soil heat, desert animals commonly burrow to below 30 centimeters in depth, or in some cases seek out high refuges in low shrubs or on stumps or posts in hot weather. The other way that animals escape soil and air heat extremes is to seek shade, become nocturnal, and to develop efficient cooling strategies and water economy. In larger species, shade may be the limiting factor in survival, e.g. the amount of cave shelters in the desert may limit the numbers of large desert marsupials. Consequently, deserts have a far greater proportion of their fauna as subterranean and nocturnal species. Soil humidity also rises steeply, especially in dune sands. Give her an average 4% of water in the top 1 meter, we can reach 10 to 20% water content at 2 to 6 meters, and at 20 to 60 m, there may be quite saturated soils. For both plants and animals, it is preferable to draw from these deeper, cooler, and more humid layers of soil. 114. Soils. We normally expect to find dominantly alkaline soils in the waterways of deserts, with areas of surface salts and carbonates. It is in these alkaline areas that we usually locate our settlements to take advantage of water runoff. pH levels of 8.5 and 9.0 are not atypical, and drying water holes can reach pH values of 10 to 11. Soils may have high nutrient potential if pH is adjusted and if water for irrigation is available. Acidic sandy soils form around areas of deeply weathered granites, and may dominate large areas of these landscapes. High and low pH areas have, as a consequence, low available mineral trace elements, and in high pH, zinc, iron, copper, and manganese deficiencies are common. Indicated in crops and fruit trees by such factors, in citrus, as interveinal color loss and leaf thinning, with tip curl in severe cases. Manganese zinc deficiency causes more severe leaf yellowing, and is often associated with manganese deficiency. Copper deficiency causes giant leaves, gum pockets in citrus branches, and multiple budding or trunking in trees or citrus. Foliar sprays, elemental sulfur, and oxides or sulfates of the deficient elements can be used. Special problems may be caused by non-wetting sands. A fungus is responsible, and high salt levels in water or soils, bentonite or humus will ameliorate the non-wetting problem, as do swales and raised beds with high edges to prevent water runoff. Salt problems can sometimes be solved by flushing beds with fresh water, but if the water source is itself salty, salinity needs the combined solutions of humus production, perhaps a ponding period of water with algae production and water crop, ionic or distillation treatments, and a choice of salt-tolerant crop. Free draining sands can be irrigated with salt levels in water much higher than will be tolerated as spray irrigation by plants, to 1,500 ppm. Despite all these problems, we can usually establish home gardens and adapted tree crop systems, and many selected areas, especially near scarps, rivers, hills, or ranges, will grow excellent fruit, vegetable, and tree crop with appropriate water runoff harvesting. Perhaps the most important thing to remember about any activity in desert is that the natural systems are fragile. Good management and constant appraisal is essential. Small systems may be called for, especially where runoff is harvested. Natural yields should be carefully assessed, and broad-scale or grand trials avoided until the capacity of the total system, especially of water resources, is assessed. Excessive mineral content in soil or water can also be toxic, both to plants and anime, and in particular bore waters must be tested for fluorine, sodium, and radioactives. Nitrates are to be rigorously tested where children are consuming water and garden leaf products, and nitrate fertilizers are used at minimal levels, or not at all in the absence of mulch or high organic soil content, 20% or more humus. Aluminium, boron, sodium, and manganese can be in oversupply at very low or high pH values, and only humus can buffer the uptake of these excess minerals. Aluminium in acid soil solutions damages roots, and high levels of manganese causes stunting and yellowing in plants. 0.5 ppm copper, or 10 ppm lead or zinc can stop root growth completely. Bradshaw and Chadwick, 1980. A complex soil nutrient, essential to all plants for growth and enzymes, is phosphorus. It readily becomes insoluble in acid soils, combining there with iron or aluminium. In calcareous soils it forms insoluble calcium compounds. In arid areas, phosphates can be deficient except in humus, in forests, and in the silt of ponds. Manure from seed-eating birds has high phosphate levels. Correct inoculation of introduced plant species with phosphate mobilizing mycorrhiza may be essential to their growth. Acacias, eucalypts, legumes generally, pines, casuarinas, and even garden crops can benefit from the root associates that enable their roots to accumulate phosphorus from the surrounding soil. Phosphates must always be applied in small quantities, close to the crop. Trace elements, zinc, copper, can be applied to soil. As sulfates, and 7 kg/Hi of both zinc and sulfates added to alkaline South Australian soils. Enables pasture growth, and the carrying capacity of sheep, to increase by a factor of 40 times. 50 cents/Hi of molybdenum in more acid soils enables clover production. However, it is also possible to add micronutrients as foliar sprays, to infuse them into irrigation water at root level, to include them in slow release pellets at root level, or to mix them in bulk. Soil amendments such as dolomite. Oversupply of these same nutrients will result in toxicity and health problems. No amount of guesswork can supplant careful and skilled soil analyses. Plant tissue from healthy garden plants should analyze about as in table 11.1. Mineral solubility and pH. Soil amelioration. A general solubility diagram is given below for soil minerals. This is, in fact, a measure of the availability of specific minerals to plants. Important soil constituents: iron, cadmium, silica, show a range of solubilities with pH as follows. Asterisk iron, very soluble at pH 3 to 3.5 as limonite, yellow, FeO, and at pH 7 to 8 as iron oxide, FeO, which reddens alkaline deserts. Asterisk aluminium, very soluble at pH 4-4.5 and pH 9.5 to 10 as alloy, relatively insoluble over normal garden ranges. Asterisk silica, slightly but increasingly soluble over pH 0 to 8, but then rapidly becoming more soluble up to pH 10 as SiO. Iron and manganese, ferromagnesium minerals, are closely associated in soils, and show the same spectrum of deficiency with pH. We can often therefore ameliorate soils at the higher pH levels with the addition of simple sulfur, and restore iron, magnesium, and phosphate levels to plants if these are locked up, and test as being present. We seldom garden at pH +4, but if we do, we will need a fairly massive calcium input as crushed or burnt lime, or crushed shells, to increase the availability of nutrients. In the deserts, the soluble aluminium and silica may be evaporated to the clay minerals allied to a light or montmorillonite soils. With all minerals, higher temperatures in water greatly increase solubility. Aluminium ores are usually formed at the lower pH values, and hydrated to give site or bauxitic ores. The carbonic acid naturally present in rain, and very much increased in rainwater as it infiltrates soils, removes potash from orthoclase in granites. In the plagioclase of white granites, calcium and sodium bicarbonates are similarly formed, or potassium and magnesium carbonates from biotite rocks, biotite, dacite. Fertilizers in arid areas. Fertilizers, apart from humus and limited animal manures, should be used sparingly. Excessive green growth can subject trees, in particular, to drought stress. May suggest a novel method of burying 2 plastic bags in the planting hole for valuable trees, provided. 313. $. Chlorine. Manganese FF. Boron. 104 10 to 4 103 10 to 2 10 colon 1 10 400%. 0.11 102 103 104 105 108 equals ppm. SIBO TTTTTTTT. Arbun. Table 14.1. Oxygen typical concentrations of mineral nutrient elements in hydrogen plants, and concentrations in Y solution for satisfactory potassium growth in sand culture. Adu Bradshaw and calcium CEA, 1980, plants and magnesium. Phosphorus F. Sulfur. Copper 0.01. IJIJLJ. 0.05. Satisfactory concentrations. In sand culture solution, ppm. Figure 11.2. Desert valley profile in fold mountains. A hard lateritic or ironstone cap in plateaus, skeletal soils, long-lived, hardy, woody plants. Below scree slopes, bunch grasses, hardy plants, some forage trees. Torrent is good, coarse sediments, mammal and reptile shelters. Arose. CG. Cutwasholing. Sandy clays, fast runoff, will grow trees if swales are introduced. Sandy are infiltration and flood out areas. Trees can be as scattered. 314. With pinholes. These contain 0.5 kilograms of phosphate and slow release pelleted fertilizer. These last the life of the tree. Mag. DH. The potential for horticulture in Central Australia, XRO horticultural science. Gardeners generally have had good results from shredded bark, manure, and leaf nutrients as mulch. With compost below this, and some sulfur additive, pH is high. Others have developed pit composting with continuous mulch layers above. An excellent system. Where salt in water is not a major problem is to combine a permanent compost pit with drip irrigation from a small sprinkler, or a smaller humus pit with a jar for watering. Figure 11,69. In dunes, phosphate, ammonia, or guano, and zinc give good results for trees. Ammonium sulfate is also used. Sewage waters have everywhere given good results with fuel wood trees. Salt content must be checked for, as water gains in salts 300 ppm on its way through towns. Sewage lagoon walls are excellent tree sites, as are raised islands in the lagoons. Shallows. Grow lotus and water lily. One feature of such lagoons is the large number of trees that are bird carried, as it is of water holes generally. Many seeds are defecated or dead near water. Most people do not add potash, as these salts, and sodium, chlorine, carbonates, calcium, boron, and magnesium may be plentiful in many arid soils, but the best advice is to get thorough analyses of both soils and leaf before and after growing. The effects of poisons in deserts. All persistent biocides should be sensibly banned from drylands, as it is the missing aquatic plants that break these down most effectively. Herbicides used on lawns will seep slowly to sandy watercourses and down them 4 miles, travel up and down on groundwater, and kill thousands of plants over time. Water movement in soils is slow, and deep sands do little to offset poisons. Thus, natural remedies are a high priority for deserts and all fragile ecosystems. We should outthink, not poison out, any species that promise to trouble us, as most weeds provide biomass or mulch. California is in very deep trouble with its ground water supplies after a 40-year chemical orgy, and many Californians die of these poisons in their water. The few nearby swamps and lagoons are being wiped out, as are the trees near Alice Springs, Australia, where lawns are developed along with their poisons. The position of settlement, and the disposal of sewage must be carefully assessed in arid lands, including arid islands. In Israel, New Scientist, October 13, 1977, sewage and agricultural pollution rises through the sands in summer, and nitrates can be included in or water pump for domestic use. Winter rains again carry pollutants down, and they must then be kept clear of the water pump to reservoirs. As many desert waters already have high levels of dissolved salts, any additional stress from nitrates may cause kidney malfunction. Some 47% of Aboriginal outstation people using bore water do in fact suffer kidney damage, consequent high blood pressure, and excessive intercellular water, a form of dropsy. It is easy enough. FGH. Savannah, thick grasses, alder rains, stick nest rats and mound-building birds. River deposition of silts, many burrowing reptiles and small mammals, large trees will eat mows, figs, casuarina, river trees. Cottonwoods in North America, redgerns in Australia. F. Sandy riverbed or wad, a fringe of dense large trees and vines of raised G-resistant rocky offs, can be springs, adapted FOS, hardy trees. H. Dry rocky hills, scattered shrubs and grasses after rain. 315. To go wrong in desert, and to put whole populations at risk, water in particular must be subject to frequent analysis for pollution and salts, and deep bore or well waters rigorously tested for excessive mineral and tachyoactive pollutants. 11.5. Landscape features in deserts. Occupied and fire-managed arid lands present a total mosaic of vegetation, with very different changes obvious to the traveler. To read such a landscape mosaic, a designer needs to note asterisk process, whether wind, water, or infiltration is active locally. Asterisk rock and soil type, these decide local response to process and produce characteristic landforms. Asterisk aspect, even slight shading by hills changes opportunities and promotes growth. Asterisk fire frequency, and the time since the last fire. Asterisk the date of the last heavy rain, more than 12 millimeters, which may have been the trigger for a specific age group of plants, recruitment of species. In drylands, erosion landforms are both more significant, conspicuous, and more numerous in type than in humid areas. Extensive deserts may show ranges of mountains with complex long valleys and sheer-sided gorges draining these, isolated or grouped. Granitic domes, inselbergs, rise steeply out of the desert plain, and the complex scarp and pediment landscapes of fault lines, mesas, and wadis. Box canyons are also features of the desert. Badlands of complex, eroded, softer sediments may develop on unconsolidated areas, and sharp-sided and much-branched gulches, gullies, develop on steep slopes. Series of folds give a basin and range topography over most desert borders near mountains, and are a feature of the Great Basin deserts of North America. True desert has a broad primary landscape pavement classification of erg, sandy desert, hamada, rock and boulder pavement, and reg, gravel surfaces. Of these, erg is further broken down into each types and formations, some of which may lie over the reg or hamada base. Reg is generally taken to be an area from which sand and silt has been removed. Erg is composed of sand plain as near level sand sheets over various substrates, also called sand fields, and dunes of several types. In total, desert landscapes are angular and actively eroding. Humid areas, and especially those clothed with grasslands and forests, have softer and more rounded cut lines, with rare cliff faces at recent fault lines or shorelines. Figure 11.2. The lower slopes, basins, and plaias, pans, of overgrazed and eroded drylands need attention, as do the dry riverbeds and aquifers that lie below the 316 surface sediments. For this reason, and because a very scattered literature exists on desert strategies with respect to specific landform types, have tried to assemble here a set of strategies suited to specific sites and ion forms. Figure 11.3. Scarps and wadis. Wherever periods of uplift, or scarps of faults fracture, desert peneplains, long cliff lines, some running many tens of kilometers, stand above the lower erosion surface, while these uplift scarps are iso-visible in humid lands. In deserts they remain less softened, and develop characteristic profiles. These profiles, angular and essentially simple, will quickly emerge from the rounded hills of faulted humid areas once the vegetation is cleared and desertification sets in, as it has emerged in country cleared of trees and eroded in the 1920s in South Australia. The process develops as per figure 11.4. In true deserts, the profile is typically as per figure 11.5, scarp section above and wadi plan below. Usually, the scarp face is fairly straight or only gently curved, and the wadis are at near right angles to the scarp face. Within the wadi side, valleys leave again at near right angles to the main valley. The pattern is that of parallel fault, weakness and compensating joints in the rock. Complex box canyons, wadis ending in cliffs, mesas, isolated pieces of the main scarp, and buttes, cut off. Scarp sections, make various scarp dash lines. Scarps are capped, the upper erosion surface, with durable ironstones, hard sandstones bands, ferricrete, or silcrete, crustal material. Cliffs and scarp faces are generally of softer, sometimes bauxitic, aluminium oxide, material, and the lower erosion surface is covered with silts and sands washed out of the wadis and later distributed by winds. When it rains, the hard rock surface of the upper scarp surface sheds most of the water, which follows gentle valleys behind the scarp and falls as sudden water falls over the cliff ends of the wadis. Just before it does so, however, turbulence may scour out deep holes in the upper surface. Figure 11.6. Water may rush in torrents through the system for 3 to 4 days after rain, and the volume discharged largely depends on the catchment area. A curtain of water, or tills, may fall along the whole scarp. There is usually a downslope just before the cliff, but this is a much more ephemeral flow. Nevertheless, over time, this curtain of water or cliff-base seepage may partly undercut the soft scarp, and figure 11.5 shows one of these scarp-base caves in the profile. Like the cliff itself, the notch at the base can be very large, tall enough to take a 6-story house, or very small, just large enough to give shade to a kangaroo or a sheep. Notches in the cliff face may be occupied by pigeons, owls, swallows and swifts, rodents, reptiles, and insects or their larval forms. Shade, like water, is a critical resource in the desert. The wadi profile, or fair approximation of it, is also 1x on Ruhr's. When positive. Figure 11.3. Total desert strategies. A1. River headwaters, most runoff and best area to create swale for oases, deflation hollows, provide nuclei for settlement and dune Forests and general vegetation downstream, stabilization. 2 inselbigs, scarps, and folds give many sites for communal collection. TB coat Benlerspirpi led man der Sagbataye Tinbia. Some dams, foothills flood retardation and tourists. Scatter of pollated seed on the desert awaits rains. 3 upwind, pelleted seed, salt pitting, dune stabilization protects 6. Factors affecting desert stabilization, investment and political. Downwind areas, pollocs have the greatest influence on these. 317. Wikumi, forested AR deforested. Figure 11.4. Development of a desert scarp profile. An old fault or fold strata buried in the humid landscape can develop a copyright heads and cliff develops. 3 scree slope develops at cliff base. Desert scarp profile in as little as 50 years following deforestation. 4. Angular profile of desert scarp emerges. Overgrazing, or erosion. 1 humid 5-degree profile of landscape. 2. Upper. Uriaso and superface. Equals. Sequence 1 underscore. Plan. S water. Flow. Figure 11.5. Scarp and wadi drainage. Section. Water from the scarp backslope falls over valley jats to wadi moors. Settlement often locales on wadi pediments out of flood reach, or in. 318. Found in incised sandstone valleys in semi-arid older landscapes, where rivers have cut down as the land rises. In these cases there is a valley floor, often with a fiber remaining, and the cliff is not a simple scarp but more often a set of complex smaller scarps and caves in bedded sandstones or mudstones, as per figure 11.7. Caves still occur, large or small, at the base of a cliff, or figure 11.6. Scour holes. Dust before plunging over wadi walls, streams often scour out water holes. Some of these can be enlarged into cisterns, all are import to wildlife, especially birds. Old sand-filled holes can be rock-rimmed for tree planting sites. In the cliff face itself, side valleys may resemble box canyons, but are less regular than those of fault scarps. And waterfalls may be a series of cascades. After heavy rain in deserts, water pours off the cliffs and rushes as mixed mud siltstone torrents down the wadis. At times, the flood can be devastating, and has caused many fatalities in unwary campers, or has carried away badly sited villages and houses. The ironclad rules are to keep houses and roads well above the valley floors, to cut them into the pediment of the scarp itself, or to site houses in the base caves of the cliffs, and start on the top erosion surface to harvest and divert water. Up top, we can erect stone and center it. Dams across the generally gentle valleys of the upper plateau. These will hold clean water, and can be fitted with plugs or base pipes to let the flood water through more gently. Next, we can cut gutters across the scarp top above useful caves, and prevent too much water splashing over to our cave house sites. We can also clear silt from, deepen, and seal the scour holes in the upper surface, and use these as tank storages. Some of these can lie inside dam whales as deep spots. We can also cut gutters away from the main valley head and spill all, or a larger proportion of, the water to the side valleys, again lessening the torrent in any one place. Once our high dam fills, however, we may still receive torrents over the headwater cliffs, and the only way we can further moderate the erosive effect of these is to make concrete or stone cut chutes leading into excavated pools at the cliff base. All wells, pools, and dams will gather silt, however, and will need periodic cleaning. Dams can be cleaned by leaving base pipes open in alternative flows. Cliff pools self-clean by turbulence. There is little hope of growing any but the very hardiest trees on the upper surface, except in crevices or deliberately constructed rock-walled containers. It is on the wadi floor that we find deep sands, gravels, and caves as some JS0ILS, and sands, root plains, CCO stel, DYAges, IODABA, as ODAEA. Figure 11.7. Sandstone valley scarps and caves. Sandstones in semi-arid areas give a succession of scarps, caves, ledges, and a deep sand floodplain. These are mere complex sites than true desert scarps, and are open to invalid design, wet. 4. Are common on lower ledges. Such profiles can arise in more humid landscapes of massive sandstones. 319. Silts, and from there, they spill out for a few kilometers. Hectare, 20 ha, of runoff surface, are reserved as onto the lower erosion surface catchment. From the moment it begins to rain until in the wadi, therefore, we need to erect strong rock. Fields are soaked. The systems around Petra need cloths, walls across the floor, and jet silt. Fields build up behind. Attention. In this area of the Negev, some rains fail them. 4 minor wadis, the whole width may be reliably in winter every year dammed, and spillways cut in the pediment rock. In the ideal is to let a minimum of water escape as wide wadis, a centra channel, can be left open and run off, and to absorb as much fresh rain water as we fields built to the sides, fed by side valleys. Once the cannon fields or silt beds with FOT of people or a few flood spreads out on the lower plain. However, we can hold all water from even heavy rains. Form very broad wadis of earth and stone and sock iron, although the outer fields may seldom flood. In Nimel, the fields so contained, these banks are best stabilized. Tains. As an ideal, we try to absorb about 0.5 to 1 m of with unpalatable shrubs, 1 sto each field. This gives us enough to grow the most extensive wadi development study to crop of grains, or to keep palms and fruits alive. The date is the ancient Nabatean systems of the Negev. Upper T-swars can be released soon after torrents. Desert, Michael, Ibnari and D. Kohler, 1956, ancient seas, and top up the system. These OT the desert, scientific, American 194, 4, 39 to 45, even without all this work, a few people can live in these have been in part restored, but there are also wadi and established productive tree crop by seeking thousands of hectares of fields still abandoned. shaded sites and deep natural silts. We can erect the Nabatean systems. Hold 80 to 90% of runoff behind. Windmill over. At well or bore. Close to the scarp. Arid. Ox in the wadis. And these are spread to lower dikes. Pump fresh water up to tanks or rock cisterns on to the plains. The water is spread by highly condented up Penn's plain. From there, it will ran by gravity flow. Fcod and soak regimes to orchards. For every irrigated houses at the cliff base, where they are shast safe. Figure 11.8. Scarp and wadi. Elevation. Features of wadi settlement. 2 with the ant. Tip stretch. Water to high. Settlement, I passe. Chan nets. Fields, and ventral spill channel. Are systems above. THA settlement. IEAE. 320. From flood, and can be in part excavated into the cliff base. Figures 11.8 and 11.9. Fortunately, most peneplain crusts are formed over softer rock, so that the cutting of channels and gutters is fairly simple. There is usually a plentiful supply of rock for field walls on the pediment slope, and it is simple enough to dig a house notch if none exists. It is even easier to dig small animal shelters and pigeon nest sites. And these also form a food source. Fencing, too, is minimal in that box canyons can contain many hectares. Most are bounded by steep cliffs, and have only a single entry, so that both human settlements and animal compounds are easily defended or protected from feral animals or predators. I believe that with modern machines, fencing, windmills, and solar panels or photovoltaics we could creatively occupy many wadi systems, on a modest scale, that are now just grazed or neglected, and plant a desert forestry system. Large trees already grow in most wadis, shaded and protected by the cliffs and immune from sand blast. By restricting hoofed animals, many more trees would grow. Overgrazing is the most obvious plague of arid lands. There is a wealth of detailed work that can be. Figure 11.9. Scarp and wadi plan. Hind/flu. Plan of some settlement modifiers 10 desert scarp landscape. The dams on the upper surface act as retardation basins for heavy rains. Infiltration to trees and crops during rain episodes. Done in the complex wadi systems, with many special niches utilized, and a rich flora and fauna, in most deserts, to be preserved and encouraged. Just by increasing shade, crevices, and ramp access water cisterns we can stabilize and support a great many more desert quail and pigeon. Where grazing animals, camel, goats, have been removed or controlled, as in parts of South Australia, a dense calitrized pine forest has regenerated, and palm forests can be established. Residuals, domes, and inselbigs. Compared with wadi and scarp, these are simple systems indeed. Great domes such as Uluru, Ayers Rock, in Australia, and many similar massifs of granitic or metamorphosed sandstones rarely develop deep caves, but do have some rock shelter, rarely have pronounced valley entries, and usually dip steeply into loose sandy soils around the base. Inselbigs are, however, very solid runoff areas, some of many tens of hectares. Large trees and good humus soils will develop at the base of cliffs on the shade side, and if we allow 1 acre of field to 20 ha of rock runoff, we can lead base floods via fluming to such fields, and grow both crops and fruit trees, or palms. A few shallow mulch-filled valleys exist on these massifs, and the soil in them is mainly humus. They can support trees, yams, and other vegetation. Figure 11.10. Occasionally steep and shaded clefts present sites for rock dams, but for the main, partly sealed tanks and soil infiltration must suffice. The larger systems, 100 ha or more, have often been occupied in historical times by careful and conservative peoples, usually as base camps for long-range foraging after rains. Each one has a special charm, and very sensitive and restricted occupancy is called for developing and protecting natural resources rather than attempting extensive systems. Very small rock slabs, 1 to 10 ha, present a useful area for a gutter and tank system, a hectare or 2 of trees, and a wayside house. Some of these have been guttered using rock walls, slab on edge, or concreted drains to serve the needs of a house or of steam trains for water in remote locations. Many would support a wildlife ramp tank for desert birds and small mammals. Figure 11.11. Fold mountains. These are the most extensive features in many deserts, and have characteristics combining those of inselbigs and scarps, but are generally far more complex than either synclines. Downflexed sediments may erode to great canoe shapes, with a few river gorges cutting their way out. Anticlines may form great whalebacks, but in the long run a river will form on their spines and again produce a long valley in the hills. Figures 11.12 and 11.13, faced on each side by cliffs or rock dome. SGR. Figure 11.10. Rock dome water LED to vegetation. A concrete or stone gutters on bare domes lead runoff to walled fields, the latter about 1/20th are of the dome. 8 simple concrete or rock slab gutters gather water from rock dunes, or inselbigs for infiltration to fields, or storage in cisterns. These small tanks have access ramps for pigeon, quail, small mammals, and slash or frogs. Thatch retards evaporation and excludes large animals. 322. Figure 11.17. Inselbigs. These massive domes of granite o metamorphic sandstones are the separated by priel and sewers. While run not JS assured suitsake. Lost common dryland hill landscape, they at times occur in series require cautious use of water. ELEBATIONL. ITIOEP. Equals. Asterisk. Law PR7. 5. Figure 11.12. Desert mountain profile, folds. Series of folds form successions of desert basins. It is the anticlines that most commonly erode to form valleys. Synclines are less easily eroded. Eventually, typical basin and range series evolve from folded series. See also figure 11.19. 323. Steep tilted sediments. In many places, a dam at the exit of a river from these ranges has resulted in a large ovoid freshwater lake in the interior of the ranges, but the permanence of this water depends on the proportion of runoff area to storage area. This must be 20-31 in deserts, thus modest and deep storages are more likely to hold water all year than large shallow storages. Such dams need careful hydrological assessment and engineering. However, the opportunity to create successful freshwater dams is greater in fold mountains than in other desert landforms. Wherever massive ranges back The fold mountains, as in Colorado, Nevada, and near Mt. Ararat in Turkey, foothill dams will hold water. A combination of snow melt and rain runoff. Settlements and roads need to be well off any flood path should they burst. As few settlements exist in deserts, this is an open option, whereas large dams in well-settled areas tend to be built above the existing valley settlements, with frequently disastrous consequences in war or earthquake. A great many more modest dams are available in fold systems. They range from narrow rock-walled exit valleys to foothill dams where exit waters are led to diversion dams. Some complex freshwater dam systems can be led off low-slope wadi-like streams as they flow to the plains. A vigorous day hunting around village sites usually reveals many possible storages, wherever the ranges are sufficiently large to shed volumes of water. These are almost always a few permanent rock holes and streams, as it is a characteristic of fold systems that they occur in large series and have correspondingly large catchments. All fold mountains of sedimentary or metamorphic rock show more or less marked palisades of harder rock series, and these usually run along the slopes like so. Many subcontours. Wherever vegetation exists, it is far taller, greener, and denser on the upslope side of such palisades, because it is there that runoff is slowed down and forced to infiltrate. These palisades are not as effective as swales, but they help. Some are wide-spaced, fairly well on contour, project well above the surface, and develop striking tree lines. Most are more subtle. See Figure 11.13. Fold mountains. A folds created by continental drift often form inside coastal ranges. B valleys form in weak anticline rock. C basin and range landscapes. Parallel series of polycer rock form on steep inner slopes. MP fold 324. Figure 11.14. Headwater stream diversion. Fast streams from fold mountains can be bled off to dams or limonia beds, tree lines. This fresh water, in dams or swales, is used to aid Gear 1.27.8, using rock or concrete walls, silt traps, reed filter desert forestry, or is infiltrated to soil storages. 325. Wherever series of these palisades are a feature, a horizontal bore will often enough tap sweet water trapped in the rock strata. Unlike quinats, figure 11.37. Such water can be sealed off and used only as needed. AHD can be regulated to that amount taken into the aquifer. A shallow, fast dry stream system usually out of the upper foothill regions of folds, often of stream sequences only 4 to 15 m wide and with banks 0.5 to 2 m high. The bed is usually rock-filled, and detritus along the banks shows the extent of flood levels. As in wadis, the flood periods, when they occur, are violent and sudden. The boulders attest to this. Along with the smashed lower branches of large trees, we cannot effectively dam these violent flows, or we would fill that dam with boulder and silt in a few rains. But what we can do is to bleed off the torrent and divert it to a more peaceful contour flow, and thence to a dam. If we lead this flow along an oversized, wide, and shallow contour trench, silt fails out in the trench before ever reaching the dam, and the trench itself presents a planting site and a silt trap that is easily cleaned out. Whereas a dam is difficult to desilt, figure 11.14. Dune country. Sands occur on pavements, or as dune fields, sand seas. Depending on the wind intensity, duration, streamlines, and velocity, and the supply of sand downwind, dunes can take up any of a number of characteristic forms, chiefly those of transverse and regular ridges. Oblique dunes, longitudinal dunes aligned with the wind, barcons or crescents, horns, downwind, and sand seas of curiously wave-like, rough sea forms, with lobed advance edges. Dunes on pavement, isolated dunes, can be planted after rains with a fast-growing grain or oat crop, sorghum, millet, some desert legumes such as moth, bean, or yam beans, and a set of hardy acacia seedlings can be put in place, preferably with a mixed fertilizer. If all goes well, the grains flower and the straw lasts for 2 or more years. The moth beans leave seed, and the small acacias grow to effect permanent stabilization. Species such as Acacia victoriae give copious leaf mulch, and desert yam bean pits can be placed in later years using this leaf mulch. The whole process depends on a good rain, pest and browser control before sowing, and some minimal protection after sowing. A few larger quickset trees, tamarisk, may succeed if they are deeply set in or near the dune base. Extensive dune systems need a very different approach, although even here, pelleted seed can be broadcast from the air to await rain. Many such pellets will be buried by sand, and if a heavy rain occurs, some will grow. Pelleting is a relatively simple matter of mixing seed, mud, fertilizer, some insect repellent, neutralized copper sulfate with lime, neem tree leaf powder, magnesite, in a stiffish mass, passing it through a mincer with the blades removed, and then on to a vibrating tray with a slight slope on which dry powder or dusts are shaken. The extruded rolls of pelleted seed become round pellets on the shaker tray, and can be spread out to dry. Pelleted seed is not eaten by birds or insects. One pit in section with LFES of sand, seed fed user leaf. Figure 11.15. Machine blades for pitting. Trail discs cut to pill the sandy desert swat situation, stop dust storms, provide good seed sites for pioneer trees and grasses, or pelleted seed. Discs can have 1/4, 1/2, or 4 or there. Perimeter removed. Is creole no or not. Wherever rain flows or falls occasionally over bare sandy ground, pitting is an excellent device. Here, a set of large discs with 1/4 section cut off or a small disc fixed to a wheel, figure 11.15, is drawn across country, and seed and fertilizer spread soon after. Seed, fertilizer, and sand blow into the pits, and these respond very well to subsequent rain. Many hectares of these pits have grown well near Alice Springs in Central Australia. Severe dune blowouts on coasts need more intensive treatment, with hand planting of quickset tasses such as Ammophila species, pelleted moth bean seed, and brush fences in 7 m squares to effect early stabilization. Such fences are built from stakes 2 m long, driven 1 m deep, and with numerous bushy weaves between. Pits of seed and Acacia victoriae may succeed after rain. We can look on dunes and dune fields as large water tanks. In deep sands, the surface to a few meters may have only 4% water, but as we dig deeper, at about 6 m, we find damp sands, and at 40 m saturated sands. Some dune fields, with humus and dust particles, will support quite dense vegetation, 50% cover, while others are almost sterile and lack basic plant nutrients. Any traveler in vegetated deserts will notice that the Largest trees, sometimes the only trees, stand in the dune ridges. This is apparent with dunes on harder pavement, or dunes on clay and a strong base pavement, but it is also true of coastal dune hollows and deflation hollows in sands. Dunes represent a reservoir of fresh water, much as the coral sands of an atoll hold rain which floats on the salt water, so dunes present a very large surface area of sand grains for water to adhere to, and rapid infiltration of rain is possible. Figures 11.16 and 11.17. At the edge of large dune complexes, it is usual to see water rushes and sedges at the base seepage, and even shallow lagoons which are as much dune-fed as dune-dammed. It follows that dune on pavement or salted ground is the best site for permanent plantings. The problems are how to establish those trees, and to stabilize the dune. Figure 11.17. Chevron bank in dune swales. Sidecast banks haul flood flow down dune swales, hatched areas will. Pros trees, parented. Glue 90/F68 swale 90, chosen must have a slope. Downhill. Dunes, large trees, fresh water lens. Stabilization by brush fences bring bark on dunes to a halt. Drift then creates an oval dune with infiltrates water and will. Adapted vegetation. Some sessile trees greatly aid this process. Acacia. Mesquite. 327. In China, where they take trees seriously, rice straw mats are used as fencing or surface stabilizers, and advanced trees in baskets are planted, basket and all, in the matting shelter. These pioneers give shelter and mulch for later forestry and crop. Once stabilized, dunes must be protected from recreation, devastation, vehicles, heavy browsing, badly aligned roads, and sand mining to windward. There is no doubt that sawdust and any such mulch in hollows is very beneficial. Mill wastes, bark, sawdust have helped establish an acacia safari forest in coastal dunes in Tasmania, but unless there are such wastes locally available, other strategies must be undertaken. All plants in dunes benefit from nitrogenous fertilizer, phosphate, and trace elements, as old dunes are usually deficient in plant nutrients. Dune stabilization. Apart from the stabilization of sand and silt surfaces by pebbles and vegetation, any cementing system will help. Water creates bonds between particles that call for much higher wind speeds to move the sand, as does salt, especially where dew is present, as salt is. Figure 11.18. Dune stabilization strategies. Stationary dunes provide a water lens at 2 to 3 m depth to line trees, if oval profile. Moderately fertilized. As a traveling bark on stabilizes, it assumes an silkreth, forcrete, T, WA, AEW, backslash, WSIC, YN, NA, V, ER. Hills FOT books equals Latin S tans PU sample LA LLS. Well Salt Lakes. Plains Cow ERK Pret Hills before I is. 4s. Figure 11.19. Basin and range topography. A classical profile in Fold Mountain series. Water conservation begins. Complex foothills provide many sites for water storages and on foothill slopes and forests are generated downhill, swales, limonia, see figure 11.278. 328. Hygroscopic or water ing, or we can use tars, oils. Moisture loss. There is less, at 1.8 to 3.0% less than the Payz touch as latex, lichens, bacteria, fungi, and alga. Of hardy ARNT. Annex are precursors to the planting. Mats form naturally, as do salt crusts. Thus, no dunes. Of hardy perennials, adapted to dune conditions, form in some deserts, where salt crusts, or minute plants, as lethal soil temperatures, are rarely formed. Below, cement the surface of the ground. These, often delicate, 5 m in dunes. It follows that a careful placement of desert crusts are critical to stability. And when cooled, trees in holes this deep or deeper, stabilized from animals, fast vehicles, or, worst of all, agriculture IG, collapse by woven hasker or at cardboard. Kalfar, with brought into deserts. Wind erosion may quickly follow. Prevent the new seedling being cooked until JT can. Stabilization in urgent cases can be affected by cast its own shade, praying tar oils, laying down pebble beds, or building any fertilizer should likewise be thinly placed at this. Brush fences 0,9-1 m high in parallel, rows 7 m apart. INE, as the rapid infiltration of water in rains can take across the main wind direction. These fences must have it down below root reach after the and equals AIA. Riomi underscore equals LEUY lost Jave and asterisk CLP Baines asterisk pies. Kuarsari A. Figure 11.29. Revegetation of scalds. Fatidni 8 side cast up hit. 8 infiltration and vegetative cover, as of speckled banks. Can be made J banks level out, new banks and abide plantings to establish. Circular Aeon AEMS. On large clay pans, total revegetation may. In. For a T. Rog by. Sway. PIBEFU. Section throw. Kernan. BRCSIO and gully. Sure. Figure 11.21. Strategies for healing active gully erosion. Small gullies can be filled, fenced, and planted. Large kitties need water upside walls, gabins, on gully floor, fencing, and tree planting. Multiple strategies, including diversion of headwaters, swales, to hold spreader banks spread headwaters gently downstream. 330. 6 strategies as vegetation stabilization do not apply to hyperarid zones, where only fences and add surfaces can operate to hold sands from roads. Dements, which would be rare in such signs and basins. Flat areas or near circular depressions are called the large-scale tectonic basins. Next in order, Rissoan's large deflection, wind, hollows, and eelar depressions with flat floors are called pans. Some of these are clay-based evaporation areas and are salad clay pans, others are salt-based and are called salt pans. Clays can be treated with gypsum to freeze their capacity to infiltrate water, or with etium carbonate or bentonite to seal them where they aid to be used to store water. Natural montmorillonite or TE clay swell and form impermeable surfaces after a or period of rain, and this may greatly impede. Some small depressions, gilguys, form as a result of swelling and shrinking of plastic clays. These are killer in outline and are useful water capture systems. Here erosion has left them as hollow sand-filled. Y cease to function. RB is in the great tectonic depressions that solve lakes. D dune seas, dras, form smaller depressions. Her runoff and develop typical base materials of spended silts or salts carried by the water and left on pans when the water evaporates. A typical desert profile is given in figure 11.19. Underscore soils in older deserts usually show some yellow or reddish color from a complex of iron oxides, but areas may vary in composition from free sands to heavy, compacted, or cracking clays, which becomes noda. Underscore flexly sticky if wet, preventing all vehicle movement. Clays are most typical of flats and evaporation pans, and the softer clay loams typical of dune swales and foothills. Scalds. A scald is the name given to a bare clay pan or where a duplex soil, originally light sandy loams over a sharply defined transition area with deep clay below, that's lost its upper soil layer. Clays remaining are often solanelic, with a high content of sodium ions. As a result, the clays tend to melt when first wetted in rain, effectively sealing the surface of the clay base and preventing infiltration. The wet crust so formed on the surface is almost imbly. The same effect is used to seal clays deliberately for use in leading runoff water to tanks. Scalds are not hollows, but have a flow into and out of the area, as opposed to clay pans. However, if a bank is graded up to 10 to 15 centimeters high, with the cut on the lower side, water will back up a considerable distance. Let this distance be 1/3 of the total area to be treated, allowing 2/3 of bare soil as runoff. Seed pre-sown on this surface will germinate, the low bank will eventually melt flat, and the next 1/3 can be treated as a successional strategy. Figure 11.20. Over 2 to 3 years a complete vegetative cover can be re-established. If banks are made too high or too solid, the plants will drown. Spiral earth casting and ridges sown at their apex are also successfully used to seed CLA. Revegetation of scalds is important, because in Australia at least, plague locusts lay their eggs and hatch most successfully in the narrow shaded edges of the scalds. Most scalds are produced by overgrazing, so that the desert grazier inflicts plague on whole regions. Clay pans. Unlike sealds, clay pans rarely overflow, but receive silty waters from clay soils, and after they cool for a while, clay settles out and water evaporates. In the wet phase, tall cane grass, Irrigrostis australasica, can grow. Duck and waterfowl nest, and as the swamps dry out, marsupials and rodents take refuge. These swamp areas were frequently burnt by aborigines in autumn, or as the cane grass dried out, but regenerated in wet periods. Non-saline eroded clay pans have also been revegetated by pitting, by building flood retention banks, and by checkerboard ridging. A low bank of 0.5 to 1 m is sufficient to support adapted trees in salt pan areas. The trees then assist desalination. Plowed or ripped clay allows faster water infiltration, and vegetation keeps the initial crevices open if dry leaf mulch species are avoided, and herbaceous or needle leaf groups substituted. Salt pans and salt lakes. These can hold many meters of water in floods. When this water evaporates, great depths of salt may accumulate, sometimes with a thin clay top. Vegetation of salt-tolerant plants occurs only on the margins. Salt enters the freshwater zone in sandy deserts and atolls from these sources. Asterisk salt is washed down by infiltration of water through saline surface sands. Asterisk salt diffuses up from deep, heavily salted waters, usually saltier than the sea. Copyright salt advex in rains from the sea or salt pans after rain. This effect is most pronounced if fresh water has been overdrawn from the ground. Asterisk salt is drawn up and in by forceful pumping locally, and then pollutes surface soils. Gilguys. Gilguys are puff and hollow areas formed by patches of clay 3 to 5 m across, which expand into 6 to 20 cm deep. Hollows on a swell shrink regime. The hollows occur in solanetic clay soils which shed their water into the hollows. The hollows can link up in chains or patterns. 331. Weirs to cage. Ripplins divert water from gully erosion. A. Ripplins from gully live at 1:200 or less to ridges divert sheet flow away equals. From gullies, as do swales, trees stabilize gully sides. See also figure 11.21. OOSWAHSTENEFILTLE. Wire cages form a weirs. A series of weirs and gabions. C. Gully erosion fences or weirs need splash aprons, and need to be +2. Keyed into gully sides, toe fences, 0.5 to 1.0 m, are more likely to 9.7. Survive foods. 332. WEL. The whole area is rich in plant species. Imicenius overgrazed, the gilguys become lead, the solanetic clays wash away, and a series base sounds evolve. The area loses most of its called flatouts, or run-ons. These are the ever-teeming flattish floors of valleys as they leave the hills. Streams are only 2 to 8 centimeters deep and 20 m or more wide, braided, and stable. Water absorbs over a wide area of such plains. Overgrazed, the streams commonly first erode some deeper channels, then become steep gullies. At this stage, diversion of water from gully heads, water spreading from large canals, and larger gullies planted behind stone walls or gabion barricades once the feed water has been diverted or spread. Figure 11.21. Evaluation is neonchili x malian hashtag. Asterisk relieving the causes, usually those of overuse and lack of water control, and asterisk preventing further cutback of the gullies. Fragile soils, loose shaly ground, and recent sediments exposed to sudden overland flows may gully in a few downpours. In deserts, this most frequently occurs where foothill floodplains are overgrazed, where rabbits tunnel into loose subsoils, where vehicles or cattle create downhill tracks, or where badly built roads direct sheet flow to culverts that concentrate flow. Such areas need fencing out, light or no stocking of animals, pest control, and above all, spreader banks for the water. In the valleys above the gullies, stream flow can be diverted to flood spreader channels, and a series of rip lines drawn downhill from the gully bank towards the ridges, sloping at 1:1000 or so. Figure 11.22. Small gullies can be bulldozed full, or interceptor drains made across them to cut off flow. Large gullies can also be filled or dammed if soils are suitable, but extensive gully badlands are too expensive to treat in this way, and we may need to fall back to creating small silt dams in the valley floors themselves. As with many dryland techniques, gully retention banks need to be small, frequent, and well made to effectively spread flow and create absorbent flats where water trapped in silts create beneficial growing media. In many areas, once gullying has developed, there is no alternative to allowing water to flow in the gully systems and to create fields there. A series of weirs 0.5 m high trap sediment so that tree establishment can stabilize the runoff. Weirs can be made from a series of well-braced wire mesh fences, or low stone bunds across gully floors, or stone-filled wire baskets, gabions, placed to spread the flow of floodwater. Figure 22.23. If the weirs are higher than 0.5 m, it is necessary to provide a splash apron at the foot of the weir where plunge pools form. However, if interceptor banks can be made above the gully head and water diverted, then the lower volume of flow permits weirs of 1,0-1.5 m high without scour damage. All weirs are started at the gully outlet and built in sequence upstream. Where no local supply of boulder is available, the lower height of weirs are built of wire mesh only. Where there are plentiful stones, stone seepage weirs are very satisfactory and form roads across the gullies. Weirs must always extend up the gully sides, well above any flood level. Stone weirs are more easily maintained and restored than wire fences, and more permanent. All weirs need vetiver grass or some such tough plant barrier to hold erosion. At projects such as that at Asomata, Cape Verde, in the Sahel, International Agricultural Development Jan/Feb. 1985, terrace building and check dams built of stone-filled wire mesh gabions in the stream beds have effectively checked and stabilized soil erosion. Both help to absorb runoff water. A change from sugarcane cropping to tree and vegetable culture also assists soil conservation and aids local nutrition in this area of high unemployment. Some 2,000 ha have been reclaimed in 2 target valleys. Pigeon Pea, Cajun has supplied food and ground cover, and cooperatives have to and market food, with credit provided for crop production. Wells and galleries dug to tap groundwater. IOY. A. If uses. K20M. Figure 11.24. Gibber Desert in windrows. Stony Desert windrows, side cast downhill are excellent tree sites. Associated swale infiltrates runoff on contour. Cautious trials should precede broad-scale windrows as trees are need to prevent DIST. O senior. And have served to establish tree and vegetable crops. The silt brought down by erosion has built terraces 6 to 8 m deep and about 200 m wide across eroded valleys, and copious spillways let floods flow over. A change from G0 ATS and sheep to rabbits and pigs have helped replace animals that overgraze the hills to those supported by domestic wastes. In all, the project has integrated several important biosocial strategies to make modest improvements to a degraded area. Asterisk government aid is available as revolving loans to plant new crops and to buy an alternative livestock, replacing erosive species. Community involvement is assured by the employment and education of unemployed people towards projects that relieve their poverty. Meaningful local work. Asterisk education is integrated with development. Asterisk export crop is being replaced with local nutritional food crop and tree crop. Asterisk pioneer legumes have helped improve soil and halt erosion while providing forage and food locally. Stony, Gibber, desert. Vast areas of desert may develop a stone layer over fairly well-structured soils, the stones being once part of a soil matrix, but now revealed after centuries of wind erosion. Old stony deserts have wind-faceted stones, whose facets reveal the direction and intensity of local sandstorms, or the salutation of sand grains in wind. Wherever a road grader passes across this country, a windrow of stones results. Large sturdy side rakes are now developed which will also windrow stones in fields or on Gibber. It is these windrows that present a great opportunity to soak in runoff and to start tree lines across slope every 10 to 20 m. The bare area between windrows not only gives greater runoff, but provides a seedbed for smaller shrubs, legumes, and forbs. Insects, reptiles, and birds leave manures and there remains in the windrows of stones. Water is impeded and largely absorbed below the stone piles, and dew forms in aerated heaps. If practical, ripping the pavement below or between windrows helps root penetration, and a touch of fertilizer greatly aids growth. Swales can be made just upslope of windrows. Figure 11.24. Some natural stone windrows evolve below cliff shorelines on receding lakes. Below the stones the soil is cool, moist, and obviously well structured due to insect occupancy. Many tree species appreciate these conditions. Reg, Gibber Desert, is stabilized only by the layer of stones. Active dunes can also be stabilized by laying pebble beds over them. Thus, if there is any disturbance of the stone layer, erosion can recommence, so that windrowing stones for annual cropping is certain to increase erosion. However, windrowing in stages to plant trees at 10 to 30 m intervals, in stages, because we need to assess the possibility that we would be able to grow trees there, will reduce erosion and also trap dust from outside the area, or bring sand to rest. Like a great many desert techniques, a limited trial is needed before broad-scale windrow systems evolve. It is thought that the Nabateans made windrows on steep slopes in order to increase runoff, and to lead water by hill base channels to fields, but good absorption does occur in figure 11.25. Ditch and bank landscape in plains. Circular side cast pans of 30 m or less diameter prevent all runoff and will grow forage species in perimeter swales, ideally, smaller, 20 m or less. Pans may become partly overshaded by trees. Pelleted seed in ditches helps revegetation. Figure 11.26. Yeoman's shallow swales. Very low, 1 to 1.5 m, banks on flat deserts hold back runoff water for up to 6 kilometers, bled off to fields, and infiltrated. This water is useful for opportunistic crop, sunflower, millet. 334. Trees of Aziapsuas. Vines of Percatwhes. Agua Xcopiphase. Palmcitus. 45 Omoes terry. /0097 capacity after rains WF. This is meta. Sol. Wood hypehoves. Te fupase. Figure 11.27. Swale construction. A sways by rodicides provide tree water and shade at 2 to 3 rains 8. Limbonia. The Auroridaris at Comp and foothill sites. Wales hic. Infiltrate. This can be used to cool urban streets. Many swales infiltrate a copyright 1 to 1.5 m of water, which overflows via talc-based spillway. Forests. Water in from 2 to 48 hours and provide ample tree irrigation at early or citrus groves, olives, palms, can establish in the base of limonia. Establishment. 335. Windrows over clay or clay loam soils in gentle slopes. Lower foothills and plains. Even flat land has some slope, not detectable by the eye, but revealed by rains and sheet flows of water. These extensive plains, often browsed to near extinction, can be regenerated or seeded by simple circle swales. preferably made by tractor and tilt blade, or a road grader, especially where a few salt bush, blue bush, acacias, or shrubs remain. One simply drives a grate circle around them, casting earth out to make a ditch. And bank landscape, figure 11.25. Such circles can be 30 to 100 m across. This too has succeeded in re-establishing poor range, as seeds, leaf mulch, dry manure, and water all gather in the ditch. Where no mother plants exist, seed and fertilizer can first be broadcast to await wind and rain. A series of such conjoined circles totally prevents runoff and trap seed and dust. Equally well, graded contours will back up and absorb water for a relatively great distance. Have worked on plains with falls of 10 m/km, and here a 30 cm contour wall will hold water up for a few kilometers in heavy rain. Seed can be sown as soon as the ground is firm, or pelleted seed spread beforehand. A scale larger than these shallow swales is a 1 to 2 m bank thrown up by repeated side casts, used by PA yeomans in semi-desert, figure 11.26. These back up water for miles, especially if the banks are sited to run from hill to hill on a pass between low ranges. The water can be left to soak in, or spilled under slide gate. Control into yet smaller wall fields to grow a crop of sunflower, millet, beans, or short-term crop. Trees and shrubs will often establish well on these bunds. Such systems suit fairly permeable soils, but can develop as salt flats in areas where clay soils and salty surface water is used. Crops can be sown as such lakes or pools dry up, in sequences following the receding waters. 11.6. Harvesting of water. In arid lands, water is the dominant theme for designers in arid landscapes. The quantity of fresh water, less than 700 ppm salt, is the final arbiter of successful settlement and sustainable agriculture. To obtain fresh water, we must intercept it before it washes salt from soils, mixes with deeper saline groundwaters, or runs off roof areas and rocks. To open this section, have chosen to start with tanks and proceed to broad-scale techniques on specific landforms and for specific slopes. Regarding water catchment, our aims can be summarized as follows. Asterisk to store fresh water for cooking and drinking. Asterisk to divert cheap flow and wastewater to gardens. Asterisk to infiltrate water into soils, and to produce plant growth on that site, and asterisk to give rainwater runoff time to soak into the landscape where we live. The conservation of rainwater. Here, we have two basic strategies to apply: the fitting of tanks, cisterns, or sealed wells to take house roof water, and the provision of very large public sealed and roof reservoirs to hold water runoff from public buildings, paved areas, and roads. Many dryland. Flan BIUW/ figure 11.28. Bare rock slab with gutter to storage. A roof cistern stores rock slab water for houses or wildlife. Some towns create an ironclad area by roofing or concreting of hill slopes. Settlements in Australia have public cisterns. These are at EED for domestic or agricultural water, depending on the quality of runoff. Underscore the cheapest water storages for trees are in able earth swales, of any shape, alongside the roads, which are essentially large compacted collection areas. For swale is a dead level hollow built on contour, though the base need not be level, which create temporary pools. Swales are ribbed, gravelled, sanded, planted at the base to assist rapid water infiltration. Must be large enough to take all tank or storage, rillo, pavement runoff, and additional harvested, empty diverted overland water flow from the environs outside the settlement itself. In short, they may need a capacity of 200% of village runoff, which then infiltrates locally as soil water storage to 3 to 5 m down in the earth. Village Homes, Davis CA, USA, is fully swaled, and grows its trees on water so harvested, planted in or beside the swales themselves. After a few rains, ample sill water is available for tree growth. In Mexico swales, apart from the greatly reduced cost of eliminating stormwater drains, gutters, and curbing, swales will grow the very trees needed to shade the pavements, courtyards, and parking or market areas that they serve. Swales also provide dirt spoil to raise road beds, sand for construction, and topsoil, loam, and clay for gardens. There are two approaches to the problem of water conservation in homes and buildings. The first, a regular feature of life in arid area towns, is to allow a strict household ration of water per person. This is achieved by using the simple strategy of fitting float valves to all home roof tanks of fixed dimension and pumping them full only once a week. The second is to strictly meter use, more generally pipe flow. Figure 11.29. Large tanks forming foundations. Uphill barns will fill large cellar storage tanks from root catchment for it provide flow to house and gardens. Acceptable approach, and put a sliding increase scale on excess use. Waste and costs much more than conservation. Meanwhile, inside and outside the house, the most water can be saved by using the least possible in gardens, especially by planting shrubberies instead of lawns, and using subsurface trickle irrigation, mulch, and shade. This can save about 50% total water use. Saving water by less use, especially on toilet flushing. If hand basin and raised floor shower water is fed to a low head, low flush cistern with overflow bypass, then 40% of the remaining 50% of water use is saved. Further, bath water diverted to a pre-soaked trough for clothes, and laundry water to the garden makes good use of this wastewater. Water-saving shower heads and timer taps stop us streaming in the shower and save 14 to 20% of water so used. Whenever kitchen sink water is used, it too can be diverted to the garden and used productively. Every family roof should catch its own drinking water in tanks of from 20,000 to 50,000, 5,000 to 12,000 gallons, depending on family size and regularity of general supply. In a few sensible towns in Australia, all roof areas are run by public pipeways to large storage tanks, and all road runoff to reservoirs to be used on public gardens. Other settlements run all road water to swales where trees and fruit crop are growing. Much simpler but still quite hygienic systems use rope and pulley showers, basins for hands and laundry, often under a lean-to, and earth closet toilets. They've spent most of my life using such systems in bush camps and in pre-war houses. They work well and save a great deal of water, usually a fraction of that caught on roof areas and stored in house tanks. Only 1 centimeter of rain produces 1,000 for a roof of 100 square meters, or 100,000 I/hive sealed runoff. Domestic tanks are built at about 20,000 to 1 to 100,000 1. For small settlements, any multiple of these tanks can swales for roof drip. Small stone-filled domestic swales provide a shaded soil water source for vine trellis. 337. General summary of water strategies for deserts, appropriate usages and sites. IJ. A. Apps last siege. EAS alba P year alg. 218 /8 /5 /A 3/6 8 3 5 8 E 8 5 A. OETSO/EOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLOLO 3. Shaded rocky valleys. Go systems *ELEF. 5. Wadis and wider valleys donkas, degree. 6. Floodouts. Asterisk. 7. Low foot hillsides, 48 degrees, B degree shelled ES, heat. 8. Plains. H. 9. Floodplains. 10. Dune scent. 11. Pans EJ asterisk LE. 12. Large valleys ELE. 13. Steep slopes, 8 to 15 degrees. East degree. 14. In towns and settlements. Oduls. $E build up concrete, using a central vertical pivot and sliding form in which to pour the concrete. It is easy enough to scale up or down from these figures when estimating tank or swale capacity needed for dwellings. Even in very low rainfalls of 10 centimeters or so, large rock or roof runoff surface will supply all the drinking water that we have tanks to store it in. Because of the costs of building cisterns, we can seldom afford to store all the rain it is possible to catch. Roads are commonly sealed and otherwise packed by traffic, and in desert downpours collect large expanses of water. In other areas, we can seal hill slopes above villages with concrete, wax, bitumen, or plastic, and use the area as a roof. But the cheapest roof is to locate near a bare rock slab in granite, or a natural sealed cap on hills, around which we run a gutter, rock cut or cemented, to storage cisterns or tanks. Tanks, versus dams, can stand on or above the soil surface, and are fully sealed and usually roofed. Large tanks have a roof which is itself a catchment to the tank. Sometimes a tank is excavated and sealed with a tough plastic or rubber membrane. Sites are usually chosen above houses or settlements, and an accessory windmill in foothill settlements, or a solar-powered pump, is used to fifth clean groundwater from wells to tanks in any period of higher demand. On very flat plains, the tanks are raised on a stand, and the windmill lifts to the tank for house and stock water, a very reliable and widely used system even in towns. Some figures, as an aid to storage planning for arid areas, is shown in table NI. Large garages, factories, recreation halls, and shops provide ample roof area for catchment in most communities, and are so used in arid areas. The tanks themselves can be earth sheltered, partly or fully buried, covered with vines, or they can stand in shaded courtyards, sited uphill from houses. Large ground tanks can form the foundations of barns or garages, and the space between such tanks a cool store for root and fruit crop. Figure 11.29. All the more wonder, therefore, that, apart from in Australia, tanks are a rare event in settlement, and clean rainwater is let run to waste. There is seldom enough storage for all our roof water in tanks, so we can then run the overflow to swales in the garden. Such swales can be simple channels, or, in deep sands, long plastic-lined and sand-filled swales, from which we can pump water, and on or beside which we can grow plants. This surplus garden water can be augmented by shower water from the house. Neat swales for roof drip are made from rock shingle, filled hollows or channels with vertical concrete edges, but unsealed below to allow infiltration. Figure 11.30. There are some myths surrounding the storage of water in tanks. 1. It is stagnant water. Untrue. It tastes fresh for years and remains clear and clean. 2. It breeds mosquitoes. Not true of covered tanks. Mosquitoes can be totally excluded in open tanks. Mosquito-eating fish can be stocked. 3. Jr. Contains dust, etc. from the roof. True, for this settles as a biological sediment and keeps the water clear. Generations of healthy Australians have been reared on tank water, myself included, and have escaped cholera, bladder cancer, from asbestos pipes, heart attacks from acid water, and the 46 plus additives now used in reticulated water. Get a tank and survive. Tanks can be brick-lined, domed, and rendered in sandy soils. Build of stack sack, plastic tubes of 1:9 cement sand, bricked and soaked in water, in plastic-lined holes. Build of cement plaster on a wire netting base, excavated in rock, or poured of concrete in mobile steel forms on site or at the factory. They are also made of, or lined with, galvanized steel, fiberglass, plastic, or it is beneficial to place limestone, dolomite, or marble, gravel, or mollusk shells, in a bag in every tank to offset acidity, to fix metallic salts, and to harden the water, as it is healthier to drink alkaline or neutral water. Less heart attacks, less metals in the diet. The fitting of tanks in arid areas should be integral to every building. At the least, every home can drink its own tank water, and at most a large house roof will grow a home garden, an orchard on wastewater and overflow water harvesting on open sites for tanks or cisterns. Wherever good clays are found, we can make earth tanks in the ground. The essentials are that asterisk tanks should be deep and narrow, asterisk they should intercept the runoff area, and asterisk they should ideally be roofed to prevent evaporation. By instituting a system of cisterns, tanks, and swales, any desert settlement, wherever average rainfall exceeds 30 centimeters, can create for itself a reserve of soil and roof water that is, in effect, an oasis. The proportion of water supplied to swales by local runoff and from more widespread interceptor banks harvesting the overland flow of surrounding areas. Therefore, as rainfall decreases, more extensive harvest of landscape runoff must be made once rainfall declines below 30 centimeters, and must be directed to village swales to support large trees. Both for domestic and livestock use, a variety of deliberately sealed or compacted runoff surfaces have been constructed in Australia and elsewhere. Some of these are at ground level, and range from bitumen sealed and fenced areas to road catchment of 300 m long by 10 m wide, rounded and graded surfaces. Side slopes are at a ratio of 120, drains at 1:100-1:200. The earth can be stabilized by gums, a light cement mix, or simply well compacted clay soils. Figure 11.31. Other approaches are the sheet metal roofing areas of up to 600 square meters at ground level, feeding to 100,000 I tanks. Slopes covered with roof metal can be steeper than those of earth. It can, of course, be 339. Pediment. 01 AIEQ. Q. Underscore. Runoff agriculture. In udouts or sitpans in basins, a schematic of Papago Indian. Oadham, brush-walled fields. If arroyos spread sand over clays, the fields are excellent growing situations. Strategies apply to Botswana. Southern Africa, Australian deserts. 340. Iokari. GGAE =. Tile, /isoa. Underscore. Clay. J-silt. CLL Act. 4P. Trap. SREARBOE compact qua. SITTRAF. IL. Y-4. E. Figure 11.32 repeat. Clay catchment sloping to cistern. Elevation. OE. Clay soils can be excavated to run water FO a central roof cistern for animals drowning. Stock or garden use. Screens are necessary allinearies to prevent small. 341. Advantageous to actually use galvanized sheet iron to cover extensive roof areas for hay and implement storage, or even for lease, as many warehouses near towns, many such roofs on factories and warehouses lie unharvested in settlements. In clay soils, square or circular spread banks sloping to a central cistern are also made, the topsoil first removed and the excavated central material rolled down to create a water runoff area. Ramp access, base drains, or pumps can be used to access water. Figures 11.32 and 11.33. Water spreading. The fate of rainwater in a thinly vegetated or over grazed desert area is usually that of most of the water running off over the land. So little is absorbed, less than 12% in bare hill country, that even modest rains will create sudden and turbulent flood flow in previously dry streams. Large boulders will be swept down to steep-sided wadis, and enormous quantities of silt, sand, dry leaf and stick material, dry manures, seed capsules, desert snails, and other debris are washed off the hill surfaces and carried out onto the plains. Very little soil water is retained. As the waters spread out over the plains, they increase in salinity, becoming rapidly more saline the further they travel. In a few days or weeks, the headwater rains reach the salt pans, and there they may pool for months or years, until they evaporate to salt-encrusted flats. In total, little but ephemeral plant growth results. If we are to creatively use this rare water resource, we must halt and divert the flows, and make places for water to soak into the soils while it is still fresh enough to be of use to plants. Once fresh water is infiltrated, it forms at soil reserve or aquifer that travels very slowly underground to the riverbeds and salt pans, effectively desalting the shallow water reserves, even though below this fresh aquifer flows very salty deep leads. Figure 11.34. Trees and tree lines, swales, deep-tipped contours, silt dams, and lines of stones or palisades of natural rock all help to haul runoff and let it infiltrate into the soil. Trees in particular help recycle the water through growth and transpiration, keeping the deeper salty water below root level. When we cut, burn, and graze off the desert trees, we effectively reduce infiltration and the deep leads rise to the surface due to flooding and bare soil evaporation. The forests of Ethiopia have been devastated by grazing and the development of export crop. The rainfall has likewise been reduced, and salted lands increased. If we put as much effort into forest rehabilitation as we put into lawns, or as much capital as we put into war, then we could rehabilitate the earth. China and Taiwan have proved this to be feasible on the broad scale. As we cut forests everywhere, aridity and fires, salt, and sterility will increase. South Australia, with an impoverished 3% of her original tree cover left, has banned all new forest clearing, although many farmers cleared as much as they could just before the legislation was enacted. This is not enough. Any sensible government would allow agriculture, as perhaps 20 to 30% of the total land area. We rely on forests and lakes to support even this area of crop and grazing. It's time for farmers to also become foresters, and so prevent future disasters. A general profile of water depth and quality from intake to salt pan decides the strategies of settlement, water systems, water quality, water disposal, and placements. Hence, design. Figure 11.34 gives the general pattern on hill country. The second determinant is frost level and aspect. Rain in the desert, falling as 25 om or so per day for lie degree. SLP. Absorption wells. In NTMI. Figure 11.33. Strategies in headwaters. IF. To foothill CIME and IAO and DYMS. 342. 2 to 3 days, as it does, is likely to produce severe local flooding, and this too must be kept well in mind when AAA are located or built. This flash flood factor be critical when settlements are built in wadis, on the upstream side of restricted gaps in hills, or in hollows near dry water courses. If we are to stare or use the intense, sudden, and infrequent falls in deserts, we need oversized channels, drains, infiltration, and diversion systems to cope with such high intensity storms. F in Australia, 88% of rainfall runs off or is evaporated from land and water surfaces. Other hot deserts would have similar losses, with only 12% of rainfall available to plants. Normal estimates are of 12% water runoff for forested areas, 20% for non-forested areas with sandy or friable soils, and up to 80% for the rare, concreted, compacted, or clay-sealed bare sites. These few figures enable us to make educated guesses as to the volume of runoff water, and hence the capacity needed in channels or flood bypasses in any arid area, or to estimate flood levels in valleys. Some precipitation intensity figures, mm/24 hours, are listed in Table 11.3. Given such daily rainfall intensities, what are the typical proportions, percentages, of runoff we can from various substrates? It is the percentage of runoff that will decide the proportion of storages needed in arid areas, as soil or swale storage pits. Damies, or cisterns, we presume a rainy period. At 10 mm/day. See Table 11.4, the data refers to arid lands. As well as surface conditions, other factors affect water runoff. Some important determinants are catchment size. Small catchments discharge a greater peak flood flow than large catchments. Foothill areas will peak to floods more rapidly than plains. Stream gradient. Steep streams discharge more rapidly than downstream areas of gentle gradient. And this is related to the factor above, as the smaller headwater streams are, in fact, usually steeper than the larger streams in the plains, which are often sand clogged and have wide floodplains. Size of storm. Large storms may totally wet a small catchment, causing local floods, whereas the same storm will have little downstream effect. It is common in deserts or arid areas to see a flood disappear a few kilometers from the headwaters, except in the case of very widespread rains. Storages and retardation basins, dams, retention or interception banks, swales, natural swamps, and created swamps all reduce or delay flood peak. Local soil absorption is much more efficient in small streams of high density, but large catchments have greater dampening capacity for floods, providing such retardation areas are for such purposes as flood control. Many of these areas are drained, filled, or built upon catchment form the normal dendritic tree like drainage patterns of rivers, where branches join at small angles, are subject to faster flooding, greater streamlining than fold mountain or fault area grid catchments with their abrupt turns, constricted valleys, and relatively long runs of middle order streams. Drainage density, the actual length of stream per square kilometer. Very dense streamlines remove water very efficiently and create higher and faster flood peaks. Sheet flow across the flat interflows or off slopes in low density areas regards flood waters, as does the braided and broad streams of flat desert areas. Vegetation. Runoff increases as vegetation is cleared. The less ground interception, humus storage, and ground interference encountered by rain, the more water runs off. If tussock grass replaces shrubs on dry. Figure 11.34. Salt in landscape water. Water from wadis rapidly pick up salt, so that wells and windmills should be located close to hills in the loose sediments of alluvial fans. Fresh water. SUT at TO2A. 343. Wabble 11.3. Precipitation intensity. mm/day. Examples and phenomena. Alta. Runoff from various substrates. Percent runoff substrates. 0 to 10 light dews, 0.8, light rains in semi-arid areas, 4, prairie rains. 6, the smallest rills commence. Flow at 6 to 10 millimeters. 11 to 20 all-day drizzle. 12, sheet erosion. Can occur at 13, gully erosion can develop at 15. Diversion drains in first and second order streams will flow. Typical of rains of humid coasts, warm frontal air masses. Typical AF monsoon cloud streets. On coasts, or light rain all day in western maritime climates, and periods of convectional rain in descents. 21 to 50. 51 to 100 the condensation drip ram. Onshore fogs, 60 millimeters, tropical. Rains exceed 100 millimeters once a year. 100-200 plus heavy rain all day, and exceeded once a year on monsoon coasts. Trade wind coasts. Exceeded once per century in temperate maritime areas. 0 coarse sands, active dunes, fixed dunes and dune seas. 5 forested, 10 wooded and grassed areas, tussock, grassland. 15 cultivated, sands and sandy loams. 20 approximate average figure for semi-arid and arid areas. 25 ungrazed steppe of mixed shrubs, forbs, grasses. 30 equals drained and cultivated clays and clay loams. 40 steppe and shrubland grazed by hoofed animals. 50, 0 equals undrained clays, clay pans urban. Toad areas. 60 skeletal soils and scattered vegetation. Compacted soils, solanatic soils. Non-wetting, extensive paved areas, full whaler storages. Rangelands, runoff decreases. However, it rises rapidly, as perennial prairie or tussock grass is in turn replaced by burnt ground or grazed out areas where only ephemerals or annual grasses can flourish. Burning of clump grasses, therefore, has a sudden effect in increasing water runoff. Season. Runoff has its most disastrous and erosive effects after long dry summers, broad-scale fires, extensive autumn or spring cultivation, and in fact, subsequent to a period of stress on the landscape that reduces vegetative cover. It is at these periods that thunderstorms create gullies, flood thin soils, and cause the soil collapse that can create salted soils. Artificially sealed areas. Roads, parking areas, house roofs, bare rock, concreted open drains, and compacted areas of settlements produce flash floods in nearby streams. The area of these total runoff systems in catchment must be calculated if effective. Flood retardation systems are planned. Soil and rock type in catchment. Rapid rainfall infiltration occurs only in coarse or open sands, sandy loams, krasnozims, deep, well-structured soils, and soils with 15 to 20% or more humus content. Non-wetting sands, sealed clay soils, compacted soils, and sheet rock or massive rock domes all shed water. 344. Typically, areas of each type need to be mapped or noted in the catchment under study. Gravels and boulder banks, shattered rock ridges, unconsolidated pediment wastes, limestone outcrops, and eroded fold crests all act as intake areas for aquifers. These will remain open and reduce runoff unless, as can happen in deserts, fine-blown dusts and sands bury the crevices and boulders, or wash down into rock crevices to seal the aquifer intakes. Once this occurs, springs will cease to flow and overland water flow will increase. Time. Whether as a result of well-dispersed and low-intensity rains, 1 to 2 centimeters per day, or of impeding surface factors such as tussock, litter, pebble, or artificial pitting and contour banking, water will soak into soils without runoff over periods of from 30 minutes in sands, and from 3-4 days in clay fraction soils. Thus, we need larger artificial storage capacity in clay areas, or we risk drowning plants in hollows over the period of infiltration. Most plants can withstand 2 to 3 days of flooding. Ideally, best plant growth results from 0.5 to 1.2 m of Saturated soil and infiltration rates of this depth should be timed in a pit, first wetted, then filled to test infiltration time, so that this depth of soil is wetted in less than 48 hours. Given this data, the width and depth of total interception by swales or banks can be calculated, and retardation basins built to reduce water loss, increase vegetation, and control ONI. These artificial intakes are now necessary over very large acres of overgrazed and eroded country. Water viscosity. Water density is little affected by temperature, while temperature has significant effects on water viscosity, hence on streamline shear or friction. Daytime rains on warm surfaces run off faster than night rains, or rain in cool night periods. As many deserts encounter rain in summer, monsoon regimes, floods peak earlier in these regions than they do in winter rain areas. Both the velocity of flow, the main erosive factor, and turbulence are accentuated by warmth and lower viscosity. Viscous water may cause local water level rise in low order streams at night, and support heavier floating loads of detritus. In many areas, local long-term stream gauging will not exist. The best guide to past flooding levels is therefore careful observation, based on damage to trees, old detritus levels, flood detritus caught up in trees, local knowledge, and a sensible assessment of the catchment area, its type, and rainfall data from similar regions. Any designer can, by reference to rain days, catchment area, and a set of the foregoing factors, make an estimate of the potential for runoff as overland flow in a specific locality. Thus an estimate of the potential storages needed can also be made, so that loss of water offsite is eliminated or reduced. Runoff in deserts, depending on the permeability of the surface, ranges from 5 to 80% of rainfall. Averages may be foul, but in flash floods, not uncommon in the total precipitation, higher percentages are obtained. Have seen diversion channels in stable non-wetting dunes flowing as small streams in 1 centimeter of rain, and these filling large storages in a day. We can accept about 20% as an average of runoff, but in practice it is safer to allow a 20 ha runoff area to 1 hectare of crop, or cultivated vegetation, to ensure sufficient soakage for long-term growth. Only in areas of reliable rains can we reduce this ratio to 15:1, catchment area to field area, or productive crop. Halting and absorbing water runoff. The halting and absorption of runoff has two main aims: to convert water from a destructive erosion force into quieter life creative energy, to develop forests, and to recharge groundwater so that fresh water sheets develop above the deeper saltwater leads of the desert, and trees can benefit. However, we should always do our sums and keep good records, for if we withdraw fresh water from the groundwater storage faster than we can recharge it, we are only temporary inhabitants of the desert. Thus our uses must be frugal, needful, and devoted primarily to establishing deep-rooted and drought-resistant trees, not to supply wasteful lawns, flush toilets, and leaking pipes. Wherever we establish a surface intake from runoff steams, we may risk silt clogging. If we design a broad intake with trees on the outer banks, we can use this silt and any cover crop we sow on it as a rich side dressing to trees. For a check on silt depth, it may be wise to place permanent steel picks with clear graduations in swales, and to sow and grade off at any time that more than 20 centimeters of silt is deposited. If only hand labor JS available, such silt removal requires swales not exceeding 4 to 5 m wide, but with a tractor and blade, or road grader, swales can be 5 to 18 m wide. Infiltration can be aided by ripping the swale base, and using gypsum in clay soils. Should low slope soils themselves be subject to steady erosion, swale banks can be exaggerated in this way to form eventual terraces, with trees now on the outer terrace slopes. Such evolutions occur where the slopes are sandy, or where cultivation takes place on the slopes between swales. As terraces, with treed edges, the slopes stabilize, and silt removal is a less pressing necessity. Such terraces are not a continuous series, but spaced downhill at intervals of 20 times their width. By a succession of such strategies, large and small desert groundwaters can be compelled to sustain a recharge. It is quite possible to create springs and to maintain low stream flow if a succession of 5 to 7 swales are made to behave effectively on runoff slopes. Such effects occur naturally where once full lakes such as Pyramid Lake Nevada receded in a stepped succession, leaving 1 m deep and 3 to 6 m wide bands of beach boulders across the slopes, and so halting nin off below these bands but above the present lake. Evil, freshwater springs occur. Bleed-off systems for turbulent and silt-laden streams can tax our ingenuity. In every case, a restricted water exit should open into a much wider drain, the silt trap, which later leads into a broad reed bed, from which fairly clear water can be led to a dam or swale, sited well away from the streamline itself, and not above a valley settlement area, figure 11.14. While dams store water for village use, swales from these systems can be a few kilometers long. They can reach to the next fast stream, and can therefore grow extensive forest lines with no more trouble than an occasional silt clearing and a few hours with a road grader. Seasonal silt clearing in the silt trap may be necessary until trees are well established. If heavy machinery and very large stones are available, sent more substantial dam can be built, allowed to silt up, and a water channel cut from the level area just before the dam. The aim, however, is clear. It is to lead runoff on contour to absorption or soil storages before it flows out to the salt flats and is made useless. For minor flows, a simple swale suffices to direct and absorb sheet waters. Even dam spillways in deserts can be led from the rear of the dam into long swales before being spilled into minor streams. We can hold thousands of times more. 345. A ripple of step cascades we abynu as aid seasoning glavation and sit beps hebel by widening of shallow watese coves cromwells with of withdut fo and ste low flow c convergeni underscore curts to r and increases load cz diver lees screens may figure 11.35 designs for SOR equals t /ser op res bank and pepesit silt copyright and floodplain be of concrete, rock wall, or floodplain, trees, i.e., willow aporlar. Ting preferred solids. Rivers, canals, floodplains, and diversion drains can be sculpted to houses. Silt be needed in most deserts. See figure 11.40. Deposit a variety of loads where these are useful. Near gardens of for details of feed plea fences. 346. Sold by Webs MT Me. MR 3 feet. A. Underscore. AEE. First. Water OT. A. Mat. FICAN CTT. And CI. TT. Aquifer intake areas. A-fold sediments may create a series of aquifers above impermeable. Pumping. Layers. Slint bores can tap some OTVs at head by gravity flow. Seabore wells. Be a manifold of 50 mm pipe and filters is ideal for shallow sand. EA may draw sol whale or table up to pollute surlace. 347. Water inside the earth than we can in small dams, and with a greater beneficial effect on trees. 2 dams of modest size near a village gives a clean water source for houses and a welcome swimming area. These functions need to be clearly separated, even if the latter is also for garden use. Israeli runoff traps, lima neem. In gently sloping uplands with well-developed valley. Runoff in rainy periods, and where lowest soils enable deep infiltration, Israel has developed what are essentially dry dams of from 0.1 to 0.5 ha, the bottom graded flat, and the dry walls little consolidated. The banks themselves are 1 to 2 m high and 2 to 5 m wide. It can be beneficial to support the inside base of the bank with stone sills at the ends of the walls will spill water at a depth of 40 to 60 centimeters, when it can flow to the next. Lima neem. Trees are established in these impoundments. The runoff area is from 30 to 500 times that of the catchment. The more gently water can be let in, by low slope diversion drains or as sheet flow, the less silting and sill erosion occurs, but trees will grow well if the soil is kept open by tillage, or compaction by livestock is prevented. Catch crop is possible in wet years. From Wilson, G. in Landscape Australia, August 1980. Aquifer intake areas. Only in hill country, and then for the most part on ridges, plateaus, and detritus slopes do we find open subsurface channels for the deep infiltration of water, as loose gravel ridges, shattered or soluble rocks, cappings of loose dune sands, or heavily forested ridges and high slopes of porous materials such as limestone, free draining soils, or fissured rock, figure 11.36. From the intakes, water will enter the soil and rock strata, and travel for many meters or kilometers to springs, rivers, or artesian basins. If water from these latter sources is to be utilized, care and maintenance of the primary intake is essential. Satellite telemetry reveals the patterns of flow in underground streams. Most follow the dip of sediments and the general slope of the land, but aquifers can, unlike streams, flow uphill, and they can also produce a head of water, usually from 0.5 to 7 m, in bore pipes or piezometers. Pressure meters. On flatter land, large areas of sand act as burst aquifers above less permeable desert pavement or clay soils. Water from these seeps out of a dune base, and can be used locally for trees. Water is found from about 2 m deep in dune sands as moist sands. The intake areas can become ineffective by deposit of volcanic ash or mud, by fine dust from desert dust storms, or by sand and dust blown uphill from cultivated and overgrazed areas. Except for volcanism, such effects can be minimized by stabilizing the landscape, by windbreaks, and by protected reserves. In all cases, deforestation of slopes and ridges reduces the effectiveness of intakes. We can assist aquifer intake by planting trees on ridges and slopes, building deep interceptor drains on contour near ridge tops and on plateaus, ripping rock pavement or capstone areas to allow water penetration, leading surface drains to wells cut in shattered rock, and creating banks of loose surface boulder, or opening pits and swales in gravels. 7. Trees, in the long term, keep such systems open to infiltration and reduce or eliminate dust from loess and sand deposits from surrounding areas. By a combination of all the foregoing factors, intelligent preparations can be made to utilize this fresh. A. Figure 11.37. Quinats. Deserts, they have the disadvantage of being non-sloppable, but are in ancient galleries or quinats run for thousands of kilometers in many wide use in 5. W. Asia. Air from these tunnels is vented to cool houses. Detail gives gallery construction in sediments. 348. Here where JT does occur, quinats have been used. PTHE Middle East for centuries to tap aquifers. Figure. When areas were forested, ungrazed, uncultivated. SD lacked the hard pavements of roads and settle. Little runoff occurred and through flow in soils. PT streams flowing. Desertified areas lack these ticks, and we need to intercede in the hydrological cycle to store, infiltrate, and convert ater to vegetative growth, in short, to create soil. Number 5 to assist forest regeneration. Infiltration of water and the time taken to infiltrate 25 mm of rain, in hours. 11-7 mm/HBr minimum in sands and dust, Lois. J. Copyright 41 mm/HR minimum in clay loam 6 to 20 hours. _*1 mm/HR in alkaline swelling clays 24 hours. This has quite a few implications for us, for if we can spread neutral or acidic sands about 0.5 m deep or moreover alkaline clay pans, then we have an excellent surface to first infiltrate and then hold rain, and consequently a good garden or tree site, on which we can store up to 1 m of water for long periods. This effect occurs naturally at the discharge end of some gullies, or another way to achieve this is to open deep swales in alkaline soils in front of sands and gravels on the move, and let them fill. In many areas, people have, with great dabur, buried layers of clay, plastic, thick colloidal, green matter, clay, and tar or latex under the deep sands of their gardens. On the broad scale, drainage slits are left every 100 to 200 m in these systems. It is obvious that we need to hold water for a day or more for it to soak into soils. Slope stabilization for infiltration. Spinifex or porcupine-type grasses help to stabilize slopes and increase infiltration, forming cross-slope sand dams as they age. The normally circular tussock form breaks open to create an open crescent, its horns uphill. Detritus forms deeper sandy rubble banks behind these lunulate clumps, effectively creating a swale. Burning destroys this effect and allows sudden slope erosion to occur. However, we can create such infiltration aids as swales, wadi dams, lavelle gardens, and soakage pits. Of these, the swale is most easily created on a large scale, but wadi dams may also work well for local food forests. Neither are a trouble if some basic machinery is available. In cold deserts, tussock grasses and mosses perform the same function for unstable rock slopes and soil flows, and cross-slope vetiver grass lines on contour greatly assist water infiltration and slope stability. Flood water harvesting. Aboriginal Australians, Stevenson, 1978, made Earthwall floodwater dams to increase pamukam grass and their seed, as did the Papago and neighboring groups in the Sonora regions of the USA, Nabham. 1979. The latter groups worked on river floodplains and deltaic deposits at the mouth of wadis. Nabham notes the interesting fact that although summer storms bring 40 to 60% of water, they add only 15% of the runoff to mainstream reservoirs. Most of the runoff is localized in intermittent streams and is only available for local headwater agriculture. About cm of rain is needed to give useful runoff over a catchment area of 15 to 27 times the area of fields. Hardy crops such as sorghum are produced with runoff only 4 times that of the field. Along the Colorado River, floodplain fields were also constructed for major floods. Techniques cover temporary basins, irrigation canals, and field boundaries of stone and earth reinforced with posts, brush, and vegetation. Planted and wild or weed species are grown together as a crop complex over 4 ha or less per field. The system is part of that illustrated in figure 11.40 and needs minimal. As headwater streams coalesce and enter broad valley systems flowing out of the ranges, broad braided rivers, dry most of the year, break out across country, dropping silt as they do so, and leaving lines of organic mulch at their high water level. This mixture of seed, manure, twigs, mollusks, and debris is excellent garden material and can be trapped using a sequence of stout scoop fences, figure 11.40, for use in gardens. Where the land flooded is flattish, a gridiron of low banks keeps the floodwater and silt settled and absorbed. Such grids need banks only 0.5 to 1 m high, and those are best stabilized by stone on the upstream side, tussock grasses or tough low shrubs, live set sticks and brush, or can be made of heavy rock walls from the main riverbed. Such systems in Papago Indian areas maintain high levels of the major plant nutrients and were the basis of the rich Nilotic agriculture. When and as the river floods, fields of millet, sorghum, and legumes can be broadcast sown into the wet silt and later headed as stored crop. Further away from the main stream, broader deep dikes will hold waters in narrower and deeper channels for tree crops, and the trees should overshade the deep absorption swale so developed. Braided streams. A close study of braiding patterns in streams and in the associated green areas of vegetation, showing up as darker areas on a black and white photo, reveals that there is an inverse relationship between the land areas, wetted or saturated, and the channel width. Small, multiple streams produce much larger wetted areas than simple main channels, figure 11.38a. This suggests an as yet untried strategy where in dry 349 periods, we can build concreted, deeply bedded deflections in main channels, and set these out to split the flood flow as often as we have space to create small channels, and there is ample space in most arid flatland floodplains. In effect, we are trying to widen and slow the floodwaters, and wet as much alluvium as possible. As such floods more frequently arise from headwater runoff, not local rain, it is in our interest to spread and harvest such water before it is lost to salt pans in the desert, figure 11.38b. Methods of achieving multiple stream braiding would be best modeled in experimental sand channel flows, but the ground effects on vegetative growth are evident in many arid areas, when the wetted areas support strong tree growth. The process of braiding depends on the shallow water flow over extensive deep sand sheets. Braiding does not occur underwater. Each braid form is initially a diamond, rather, a rough diamond, with plunge pools at each corner, caused by the confluence of side streams. Ideally, the unit forms are as in figure 11.39. A. We 1 and H. Atsatia. Sputting Bafir. Figure 11.98. F. A braided stream. A natural braid occurs in sand beds at the center of floodplains. B. Notched weirs. Can spread flood braiding across a full floodplain. Hatched areas show absorption areas where trees and shrubs will grow. See detail. See details of braid patterns in sand. Notched weir to initiate braiding in sandy rivers. Section. Elevation of no TTEPW. Spank of knots T. Rulu. Figure 11.39. Notched weir, elevation. GC. And vegetation. 350. TS low how conditions, only the channel flow. RSTSTS, and sheet flow across the interflow is absent. S at what initiates the pattern is not clear, although Euler flow patterns arise from scattered pebbles or bells in sand. However, believe that we could spread headwaters more fully across plains, initiate a finer ash of the pattern, and spread and absorb water. Objectively, if we erected a level, notched wall across the hided area, the notches are in effect the imitation JR holes. Within 10 to 50 kilometers of ranges there may be a few perma and desert lagoons. They are often of great beauty, full of crustaceans, fish, mollusks, and water plants such as lotus, kangkong, water chestnut, and submerged weed. Birds and mammals visit by day and night. How do these lagoons form? In every case, they arise from a strong natural ridge, often unnoticed by visitors, that approaches the river from one or both banks, thus constricting the flood flow and forcing an increase in velocity and a powerful hydraulic digging action. These days, it is simple enough to replace or construct such ridges using a combination of rock cement walls and a bulldozed bank, stronger and deeper near the riverbed itself. The ponds remain full in drought only because the deep sands of the river contain millions of liters of slow seepage, which we can also increase by installing sand dams higher up in the system. Nevertheless, we whale Esponet feet ever. Figure 11.40. Scour hole lagoon, mulch fence. Solid or strong fences on floodplains create self-scouring holes, silt, and mulch traps. Swales and fields hold floodwater for slow infiltration to crops and border trees in backwater areas of silt deposition. L. Sectonal. Elevation 4%. F. Cop T. Seves. 351. Should not create these open water systems too frequently unless we have made silt dams of up to 9 or 10 times the capacity of each pool, as open water will evaporate over time. The profile of such natural scour beds is as in figure 11.40. Sandy river beds. Wherever deep sands fill rivers, palms and lime trees will stand in small embayments off the river, where flow damage to their trunks is less likely. A good guide is to observe how native trees survive, and where the largest trees grow, that is, if cattle have not killed out the range. It is very noticeable that desert river banks in hills will often have quite separate species of trees on either bank. This may be true of all rivers eroding country areas. One species needs the slip-off or silty slope, the other thrives on the harder country rock of the erosion bank. Almost all the burrowing animals use the silted or a lip-off slope of the river. Figure 11.41. Very long spreader banks. Spreaders take concentrated flow and the waters harmlessly. Downhill. In important areas, a solid core can be added insurance. LEME Suncrete core. Even flow across the hill across wall eventually blocks the ends the bank to prevent discharge. _____ FON I. Equals. Syllable. A. Concrete. Wo. CR. A. AE. Foot. Dash. Equals. IUI. Z. PASERT. Equals YA. RSS 4. EY. Legumes. AI. E. RSSLE equals. APAS. Brava. Fa. 5 dash underscore at ARE. E. Flow. Pence protections. Figure 11.42. Grass spillways with steering banks. Below 4 spreader hang 2 well dash east and fence I can lead. Water safely downslope, side or steering banks prevent sideways. 352. In sands. And light soils. Equals cutting a quarter section. Slice off a set of disc blades. Asterisk pits are made, with a quarter of their length. As at breaks. As discs are drawn along, we get a series of mini swales. And these two are staggered, like O swales. A great advantage is that such short pits or furrows need not be strictly on contour, 50 that they can be drawn by eye. No one pit is so large as to spill too much and cause stream flow. Seed can be added to pits, broadcast, or blown in from residual vegetation. The method is fast, effective, and can be completed on broad scale. Grasses, shrubs, trees, and forbs can be seeded. These pits effectively become small swales for an area of bare soil. Over many acres, they have enormous storage capacity. They would usually be spaced at 0.5-0.75 m apart, and be from 10 to 15 m long, and 0.3 m deep at the most. Here, soil is ideally sidecast downhill or downwind, but this is not a critical factor. On near flat sites, this form of disking acts as surface wrong-heading, and eliminates or greatly decreases dust storms, as S00 and as it is made. There are many forms of pitting machines, but they can also be hand-dug. Pelleted desert shrub seed plus a light fertilizer dressing creates the condition for soil stability around settlements. Gordon, 1975, working in semi-arid hills, records average annual runoff of 20%, with up to 80% in eroded and compacted soils for individual rivers. He recommends, for slopes in excess of 2%, a series of contour furrows or mini swales at 2 m intervals, with only every 20 to 30 contours actually surveyed. The swales are broken to allow flooding through to the next series. Vegetation. The furrows remains green in drought. The soil chosen for these systems must have the capacity to absorb the moisture, which means soils primarily of sand. The scale and area treated can be as large as is required at the 2 to 4 m spacing. Spilling water downslope in fragile suns. Steep-sided gullies often result from road culverts, animal tracks out of wadis, or water discharged from diversion drains after fields are flooded. There are only a few safe ways to spill downslope. In deserts, these are very long spreader banks. Figure 11 to 41. Maintained and inspected in rain. Asterisk gross spillways with steering banks. Figure 11.42. These take a few years to evolve. Downslope sealed spillways or pipes with e-plash poles leading to a swale, one of the above, or a dam. Figure 11.43. U-shaped channels filled with older, smaller rock, then gravels, so that water is forced to follow malleable sidle paths. These, in fact, imitate in their structure the rock sorting of dryland breccia slopes below Clitus. Elibito. Figure 11.43. Sealed spillways to splash pools. Quaddy heads or your water must be spilled to streams, cone reeded, or stone spillways and splash pools. Quiet and erosive effects. FD4. EA. Seal of SP. TE splash food. Sand dams and clear water reservoirs. Washes in gently rolling foothills carry broad flood water surges. It is very advantageous to dam these so that water backs up 10 to 20 times the dam width. The wall must be keyed in for 46 minutes to the side banks, or water will scour around the ends. Before this is built, it is necessary to cut a series of 2 m deep bays into the upstream banks, and to have several loads of coarse stone to place against the upstream side of the wall itself. This will form a drain to a clear water dam, which itself should be less than a ninth of the total area backed up by the wall. Figure 11.44. How it functions is fairly simple. The first floods rush down and over the wall. Silt and coarse sands fall out, and in a few rains fill up the storage. The shingle or rocks on the inside of the wall act as a filtered seepage to the clear water dam. The dam itself also leaks water through the riverbed it is intended to, and some it e a ria lep lep e a said tros 6s2 spill ua. Figure 11.44. Clear water dam. A wall, silt float above this whale is planted 00 trees and opportunistic crop. Downstream seepage creates forests below wall. A sail downhill spillway from dams must be carefully constructed. Oversized. U-shaped, otherwise gully erosion occurs. ERHAEE. CEEEA. Ray. J. Wadi wall SEC ton NA. Sir. Bounty ILLSP Ulway section L. 354. PS through to the downstream forest. The base. RT also fill with sand and make a flat filed silt bed on the edges of which we plant large trees, pecan, palm, avocado, mango. E make up the upstream forest. Such trees can also ID the Clearwater Dam, the Dam Forest, and the Barrier Dam is sand-filled, several deep. At subaquatics will grow there, e.g. asparagus, iti palms, Chinese water chestnut, swamp, yeah, etc. Full, the rubble and sand act as a buried T-spar which keeps the dam full, I know of one. M that dropped only cm in level over a 7-year. HT, and also as a deep reserve of moist sand 4. Equals the downstream forest may extend 1 to 2 kilometers in the ends of the river, for a wall only 50 m wide. Re 800s or thousands of such sites a few. Trace from foothills in deserts, and this simple but sophisticated system creates oases where there were before. The figure shows a dam built by railway. Sejoneer at Adelaide, South Australia, in the 1920s. And still functioning well in the 1980s. Below roost trees around such dams, the guano from ERT birds may be gathered as sheets of phosphate. Laser, and these are of great value in establishing May or rock windrow trees, as a dilute solution or Ikes with 30 to 40 parts of damp sand. On the silt dam. Grow very well as the first swampy condition. Fecities, and a good crop of legumes and melons can be planted at that time. A few such dams support a strong village population, and will keep scour holes downstream recharged with water for swimming holes. Underscore all clear water dams should be 5 to 9 m deep and of reduced surface area, rather than shallow and wide. Dams. Barrier dams across streams in wooded and stable hills. Sent and be expected to have a long life of 100 to 300 years or more, before silt and humus fill the catchment, and even before then a well-designed dam can be silt flushed from the base. But barrier dams in arid areas must be planned from the outset to fill to the brim with silt and rubble in the first few years. The water they hold will be stored in sands and rubble. Thus, clear water dams in deserts should be built well away from such valley sites, and the turbulent flow from wadis or foothill sandbed and boulder streams must be bled off into almost level channels fitted with sand traps, and only after that to atom. This dam should not itself be sited so that fast water can run into it over loose surface material. T should be fenced, and the margins planted to rushes and shrubs. Figure 11.45. Some helpful factors for an effective sand dam can be checked before construction begins. Ideally, the rubble and silt in the dry creek bed should be very open and permeable, of stones, pebbles, and coarse sands. This will almost certainly mean that the dam is near the foothills or in a valley close to the headwater rocks. Secondly, the floor of the dam is ideally clay or massive rock, and hence leak-proof. However, even if neither of these factors are ideal, sand dams will still be good growing sites, as we will be slowing down flood water on a long and level site. An extensive silt dam of 9 to 12 m in height is always built in 1.5 to 2 m stages, and the wall raised as the earlier stages silt up. Behind each wall, gabions allow water to filter down to a base pipe, which can be led to settlement. The whole area of such catchment needs to be protected from sprays, fertilizers, and browsing animals to protect health in settlements. Rock holes and nimbus. Rock basins, often filled with water, arise from a series of origins. Some are rock scouring in stream flow, corrosion, on stream beds, asterisk freeze thaw and with dry swelling and shrinking, plus rock mineral hydration. Registered salt eroded ponds in rock, 45 near the sea. There are many ways to assist water conservation in rock holes, e.g. asterisk fill hole with pebbles to lower evaporation. Some water is lost. Registered thatch or cover hole. Asterisk build gutters to hole. Asterisk erect a metal mesh fence to direct to condensation to hole. Asterisk deepen hole, and plaster it with cement if it leaks. Evaporation and evapotranspiration. As we have defined the climatic scope of this chapter, open pan evaporation, pans of water exposed to air, will always exceed or equal precipitation over the year. In fact, almost all of the subhumid to arid areas tested have a potential evaporation well above that of actual rainfall. This means that for most of the year, there is no longer any free water to evaporate except for the water in dams or other open water storages. A typical grain crop such as millet needs 50 cm underscore of water to mature. It is unlikely to obtain enough water unless water storage from runoff is available, or unless runoff has been infiltrated into the soil. Direct evaporation in still air, the oasis effect, will exceed potentially 100 centimeters per year in most arid areas. But a far more severe effect is that of hot wind evaporation, the clothesline effect, which in unsheltered fields most affects the field edge and increases transpiration 10%-30% over the background. Effects. Chang, 1968, records that winds blowing from arid to humid areas may affect crops or trees for 400 minutes before acquiring a non-evaporated water moisture load. In effect, a 400 m wide evaporation border of trees may be needed between the desert and productive croplands. There is no doubt that a windbreak of trees uses less water than that removed by the hot winds. 355. Overcrop, so that throughout croplands, scattered trees and crosswind tree breaks are essential. Needless to say, such trees should be selected to be both dry adapted and of benefit to the crop. Acacias, such as A. albida and Prosopis species, are some of those commonly used to protect and benefit crops in arid areas. Evaporation from open pans of water outside the crop of tree shelter can be 16 millimeters per day, while 300 m into the crop, only 5 millimeters per day is lost. In this case, the crop itself acts as windbreak, with a consequent gain in yield due to fast evaporation. Whatever we can do to prevent the drying effects of hot desert winds will be worthwhile, so that although we will always be left with an oasis effect, we need not suffer extra loss of water. For restricted areas of crop, narrow canals, or home gardens, we can screen out winds and shade the area either with shade cloth to 50% or more shade. Vine crop, the canopy of palms and Umbralia acacias. These strategies plus ground mulch drastically reduce the water loss to evaporation from open storages and crop species. Conservation of water in transit. The transmission of water, as with any fluid or gas, needs great care. More water can be lost in canals, especially in loose soils or shattered rock, than is lost in use. Even open concrete channels can lose great quantities of water to air. There is really no substitute for long runs of pipe, and in small systems, extruded PVC, flexible or rigid, pipe is most effective. Runs of 100 m or more can be made in one length. There are now long rolls of collapsible pipe for surface use. which can be unrolled as needed. There is one other way to store water from opportunistic runoff, and that is in tough plastic or neoprene bags. These can, uke swales, operate from fixed diameter pipe inlets, much as the feeder drains operate from a head drain. The swale in this case is provided with a rolled container, which fills and unrolls as water fills if and forms a sausage along the swale. Precisely the same technique can be used to capture fresh water flowing into salt lakes, so that the freshwater sausage floats and is available as unmixed water on demand. This can be a much bulkier article with greater depth/width ratio, as there is no Pargier. PSRN, figure 11.45. Clear wetter OAM bled off sand trap. A weir and drill allows water from a minor stream to be diverted to a clear water dam, or long swale, via silt trap. 8. Ori rivers in folds may develop very different tree species. On each hank, the river is eroding on one side, depositing silt on the other. Trees should be selected for side preference. Tile head pressure on an immersed bag. In #lay, or as a series in swales, such bags would need a protection from large animals, but would be evaporation-free storage, preferably above to reflect light, and trellis or 1C to further reduce light and heat. Bags in OT water can be towed to other locations, or pipelines. D across jakes to fill storage bags near villages. There are these basic approaches to reducing in water storages in deserts. _* underground and in-earth storage. _ copyright surface treatment of dams, and registered storage configurations. Any reduction in total evaporation of water is of in areas where this factor may teach 160 centimeters in .a. Faint-fall of 30 centimeters water is an expensive resource in any situation, and more so in deserts. Several cultures in deserts, Peru, Iran, Afghanistan, Canary Islands, have avoided gross evaporation loss by conveying water to desert farms via many kilometers of underground galleries, the qanats of Iran, and by storing the water in clay or cement-sealed caves. This is irritatingly an effective strategy, only superseded in modern times by the development of extruded and leak-proof pipes and concrete tanks, by bears in headwater aquifers, and by the well and windmill systems widely used in Australia. Water absorbed as rapidly as possible into soil is also safely out of the sun's rays, but to be efficiently stored, it is necessary to ensure that just enough water to soak the soil is admitted to swales or fields, that excess does not in fact escape to the groundwater at depth. A loose cover or mulch should be kept on the soil to prevent excess evaporation, and a crop established to use the water effectively. A 10 to 15 centimeter surface layer of loose gravel or volcanic cinder is widely used in the Canary Islands for crop and trees. Coarse mulch has the same shading and insulating effect. Impermeable clays or rock lies at 2 m or so, trees can retrieve all water so stored, and desert trees penetrate to 30 m in free soils. In view of the evaporative effect of winds, any exclusion of wind from dams greatly reduces surface loss. The exclusion can be by tree windbreak, artificial mesh windbreak, or even by building trellis or shade structure over small dams, as Australian Aborigines would do with Nabas, open rock pools. Nabas. Area of greatest. Dina T.S. Abuladin Rtowiji. Pelgab in the S/LT. 357. Up to a few meters across would be completely covered with a wooden frame covered with thick spinifex, thus providing both shade and wind protection. Covered tanks are likewise protected from wind losses, although vapor pressure can cause some loss in unshaded tanks. Roofed earth tanks are still widely used in Australia. For more extensive water systems, strategies have ranged from floating rafts of wax, tough more permanent and effective strategy used in South Africa, where hexagonal floats of white surface light concrete, a slurry of cement, sand, fine gravel and polystyrene beads, are floated out until the entire catchment surface is covered. This is very effective where water is rare or expensive. Larger and lighter rafts could be made of sealed pipe floats and thin panels, but the concrete is durable and simple. Blocks are tar sealed below, and their specific gravity is 0.8, so that they float deep enough to resist wave effect. Comers are rounded to allow air to the water. Structure of dams. There are effective approaches to the structural effectiveness of dams. The first is to make the dam itself as a deep conical section, so that as the level falls, surface area is also rapidly reduced, as the square of the radius. Much of the same effect is achieved in V-shaped valley storages. Secondly, deep and shaded valley sites are far better protected from sun and wind than shallow valleys, and, if choice is possible, a shaded east-west valley is best. Thirdly, a simple strategy of creating a series of 3 to 5 storages, each able to be drained by gravity flow to the next lower dam, is very effective, far more so than a single storage of the same surface area. The system needs active management so that the use sequences from the top down. The top dam is drained into the others just when they can take any residual water. As each is emptied, evaporative surface reduces by 1/3, 1/4, 1/5, and so on. Obviously, the shorter the series, the better the result. It is better to create 2 series of 3 dams rather than 1 series of 6 dams. Like much else in the desert, the scale of operations decides efficiency, and in this case smaller is more efficient. Figure 11.46. Despite all the potential problems with salted soils and water, there are many sites in desert or dryland foothills where freshwater springs and groundwater, less than 200 ppm salt, are available, where shaded valleys can be safely dammed, and where soils are open and free draining. Endless problems and expense are avoided if such sites are carefully identified and selected wherever local long-term food provision is of an overriding concern. Many ideal sites lie in the inner valleys of spaced fold mountains, where deep sands over clay hold many millions of liters of fresh water run off from the hills, and all that is needed is a reliable windmill or solar pump to raise this water to a mesa or nearby hill. As frost rarely exceeds the 12 to 20 m level in warm deserts, a raised tank will irrigate subtropical crop on the upper hill slopes, and deciduous plants needing a chill factor are planted on the lower slopes. This situation is common in hill country with restricted cold uplands. If all surplus runoff is used in wet years to set out forest trees held in nurseries, such situations quickly become not only sustainable but self-reliant and far less subject to serious drought effect. It is all a matter of careful site choice, responsible behavior, and modest scale. Figure 11.46. 3 dams in series reduce evaporation. Evaporation loss can be as little as 40% of a single dam of the same capacity. All desert dams are ideally conical in section. Surface Te Vilum patio. Increases YD drop in PAM. PEP therefore evaporation. Increases, A equals a proportion. A volume. As Pinini GGTE net. PAM in series to CSS. Surpace ABSATE volume ratio. 11.7. The desert house. Like the subtropical house, desert housing needs the twin qualities of summer cooling and winter, or night. 1. Many features of desert houses resemble those of both subtropical and cool temperate housing. Traditional systems are often very sophisticated. The older houses of Iran, Afghanistan, and Rajasthan were all well designed for climate. Some features are asterisk cool courtyards in building interiors, narrow and tall to preserve shade. Evaporation strategies from water in tunnels, on glazed pots, tanks, fountains, bark mulch, and coke or Hessian wicks for water evaporation. Asterisk narrow east-west streets maximized, broad north-south streets minimized. Asterisk use of white painted massive walls, often of mud, as cool surfaces. Asterisk small windows or stone grills, most light is in direct from the inner courtyards. Asterisk towers, vanes, and air scoops for ventilation sys. Thames. Asterisk cooking outdoors under shade trellis. Asterisk earth sheltered or underground housing of various registered vines on walls, over roof areas, gardens, shore houses. Asterisk roof area creatively used for drying crops, wash in clothes, pigeon lofts. Houses can be constructed so that they assist other houses. The colony of swallows' nests appearance of many settlements in arid areas is not a coincidence, as the strategy has independently arisen in Asia, India, the Middle East, in the Mediterranean, and in the Americas. Close clustered dwellings, with the eyeing axis of their streets east-west and common or close-spaced walls ensures that neither wind or heat can easily penetrate the fabric of the settlement. If all these dwellings are sun-facing and of more than one story in height, cool air in shaded narrow wells is always available in courtyards and streets, and vents at roof level will draw cool air the rooms of the dwellings. The bottom floors and flat roof areas are used for living, and the upper floors or roof areas for bedrooms. However, where cultures are accustomed to more space and privacy, a line of bungalows or cabins on an east-west axis, and with dense strips of vegetation too, the shade side can achieve much the same result, providing the side itself is correctly landscaped. Village homes, in Davis, CA, USA, is an ideal mode for such design. Thus, for this first factor we can set an ideal of asterisk dense housing, closely placed side by side along an east-west alignment. Few, if any, north-south cross streets are aligned to hot winds. Narrow streets, preferably overshaded by trees or 2 to 3 story buildings. Asterisk multiple stories are appropriate in restricted sites, such as wadi banks, niches at the base of cliffs, and figure 11.47. Isolated and multiple story housing. Warrow streets and courtyards can cool multi-story buildings. Shade houses are necessary on isolated dwellings. Tree shade reduces ground heat in all situations. 359. Small valley sites. Single-story housing is appropriate on more open sites, but if then needs dense vegetation or trellis on the shade side, figure 1147. Any settlement planning broad paved, bituminous boulevards and parking areas will incur areas of uncontrollable local heat. Roads and car parks, or hard paving, must be shaded and therefore narrow. In Davis, California, at least 60% of such areas must be shaded by law. Shading of lanes or streets by trellis and lattice is a very pleasant and practical way to create cool refuges in desert towns. The painting of roof areas, or the top surfaces of lattice white reflects heat back to the air above the settlement. The white canvas covered markets of Istanbul are a model of good design for commercial areas. Site conditions. No house or village site needs more careful selection than that of desert lands. Of the range and basin topography, only 15% is hill country, and of that only 5 to 10% is foothill or wadi side with adequate in-off. In both hot and cold desert, flat sites can be very cold at night. A thermal belt does exist, usually some 10 to 20 m above the peneplain, with the frost line sharply defined. Wadis are excellent sites in very hot deserts, and narrow east-west wadis are particularly well shaded. But in fold mountains low foothills a runoff area or spring is needed. The main consideration is the potential for water harvest and storage on or near the house site, excluding the deep ground waters, equable climate, and if possible a variety of aspects and soils. Deserts are the ideal sites for underground, earth, sheltered, or cave housing. Arid areas also suit flat parapet roof areas, extensive trellis, and the integration of house, water, and a vine crop. Below ground, dugout houses are cold, clean, and need low maintenance. They also suit casual extension and present excellent sculptural potential. Underground and earth sheltered, due mainly to Australia's preoccupation with opal mining, large bore, to 80 centimeters, drills, vacuum earth removal, and easy drilling by machinery is now available. For cave construction, at least, it is at Cooper PD in South Australia. Even where these aids are unobtainable, there remains the wheelbarrow, pick, arid, shovel. In the latter case, side choice is much enhanced if the proposed dugout site is in soft rock capped with kale reedy or a hard and impermeable layer at the roof level. Mud for bricks, pise, or bulldozed earth wall shelter is usually available, and quite ordinary access will plain. Soft rock walls in caves, vents, cisterns, toilets, cellars, G-places, cupboards, niches, beds, and tables can be excavated in carefully planned caves. Chimneys or vents are drilled. 360. Cisterns are rendered. Cisterns can be opened from the upper surface and deliver water at head to the lower cave. Toilets, in Kubi PD, are a vertical drill hole, 20 to 30 m deep, sited a few feet from the door, low flush. Toilet systems can feed into them, and they are then vented to air. Or they can be dry pits with compost, downdraft, and solar chimneys. In either case, they last for years, but are best occasionally pumped out for establishment of trees around the site. Where water is sufficient, low flush toilets are led to soakage beds. Where large trees rapidly transpire the water and convert nutrients, large shallow leach fields with thick top mulch are also officially permissible in arid Australia, figure 11.48. I think there is nothing so peaceful as a cool desert cave with a domed ceiling, the rock trimmed nicely flat, and a sense of safety and silence. For those with deep-seated ambitions, Fresnel lenses, and surface Mirrors, with reflector mirrors and light guides will illuminate tunnels and rooms for kilometers deep. Arid. Camera obscuri or lenses will throw scenes of the outer world on walls, where the outside world can be admired but the heat avoided. Of all desert houses, those who live there prefer caves. One of the more extraordinary underground homes was cut and planted at Fresno, California, under a calc-reedy ceiling by a miner, M. Forestieri. His underground house covered some 2.8 ha, and included bathrooms, fish ponds, and a large citrus garden, of which the only sign on the surface was the top of the citrus trees, figure 11,49. In the Canary Islands, houses are seen where only the facade stands out, the rest is hidden underground. Even the facade is shaded by grape trellis, as are many of the roof areas of houses in the region. In both ancient and modern times, caves and underground houses were the preferred dwellings in deserts. Their practicality depends on the location, having softish rock, or a softer strata below a calc-reedy or fairy-crete ceiling. Cave houses, figure 11 to 50, can be totally below ground, with skylights or more, commonly built with one wall facing the open, shaded side of a hill. Sunrooms can be built out J in front of the underground rooms, or front rooms built on ASA facade. Figure 11.48. Large shallow leach fields. Of small dams, spillways can be very long shallow swales. This area absorbs surplus runoff and infiltrates the water FO soil. At Cooper PD and in the Canary Islands, Decorah, tip facades may be built at a bench cut entry, where occasional rains are expected. Sections of the hill slope above the cave can be sealed with concrete as a roof or water runoff area for water cisterns. This also prevents water seepage entry into the cave and strengthens the strata above the rooms. In Cooper PD, machinery is used to prepare the site. First, a cliff face some 3 to 6 m high is cut into the selected hillside of soft stone, using a bulldozer. Large bore drills, 1 to 1.5 m in diameter, such as the Caldwell are used to cut corridors, rooms, and storage caves to approximate size, and to sink deep wells for toilets or water cisterns. These or smaller diameter drills cut vents, light shafts, or skylights at strategic places to light the inner rooms. Rooms are then hand trimmed, smooth with an axe, floor sealed with level concrete, and below these the essential electrical conduits and plumbing are laid before pouring the floors. Large blowers, like vacuum pumps, are used to remove spoil as the drills cut the shafts. The newly trimmed rooms are left to dry out for a few months before bondcrete registered or a polyvinyl acetate sealer is sprayed on the stone to prevent dust. Caves built in this way are dust-free, silent, and easy to maintain. It is essential to ensure good venting, particularly in volcanic sediments or rhyolite rock where radon gas may accumulate in unvented rooms. Capped surface vents or solar chimneys of metal, painted black, ensure positive venting of household heat, steam, or cooking gases. Storage areas built as furniture in surface homes are cut into walls in underground dwellings. In 1985, such houses, even when sealed and tiled, cost about 50% of surface dwellings. Comfort levels are easily maintained for both cold nights and hot days. In many Mediterranean countries, trellised entries and bright facades satisfy the aesthetic needs of occupants, and the walls themselves are often of veined, colorful, or patterned stone. Such houses were built long before bulldozers or drills by hewing the rock and removing spoil with wheelbarrows, and miners traditionally built them as dwellings in deserts. Temperatures in such houses fluctuate about 5 degrees Celsius, and are fairly constant at about 25 degrees Celsius in the central deserts of Australia. In North Africa, large pits, 20 x 20 m, are cut into the ground, and caves built off them. These courtyard pits, with rooms off them into the soft rock, are cool and protected environments. Good gutters are needed to lead water around the pits, and the walls can be trellised, as can the top opening of the pit. Water cisterns can be cut into the floor of the pit or into the upper surface. The courtyards so formed are drained by a cave exit to a cliff face, and so cliff sites are often selected. The ultimate refuge in hot deserts are underground, mud-walled, earth-roofed, and shaded houses, well secured against the multitudinous flies and mosquitoes of the desert, and fronting onto a shaded vine arbor, with their rear walls cut into the pediment as caves. Caves, single entrance shelters, are widely used in deserts as livestock pens, winter, in East Turkey, grain stores, and general storage rooms. They can be built to be hot or cold, as follows. Figure 11.49. Forestier house, Fresno, California. Complex underground housing, only crowns of citrus trees show on surface, cafiche form ceiling in upper rooms. House can be endlessly extended, and is very comfortable in desert climate. Good venting for the removal of naturally occurring radon gas is essential. 361. Asterisk hot caves, a bubble of hot still air gathers in the cave during the day. Dry heat storage suits dried fruits, and mummifies wood and paper. The essential here is that the entry is overhanging to trap hot upslope air. The cave walls are an effective heat store. Such caves may be unhealthy for living, due to lack of adequate ventilation, but make excellent grain and livestock storages in winter. The cave itself has to be built upslope from the entry in order to hold the hot air. Figure 11.51.a. Asterisk cold caves, these are excellent root storage areas, and also general storage areas for books, films, machine parts, and foodstuffs. The essentials are that the entry lies in a dip on a hillside, permitting cold night air to pool in the downsloping cave. A sill to the entry is essential where rains can affect drainage. Figure 11.51.b. Most dwelling caves have level floors and entries, but within these complexes, both hot and cold storages can be built. Many countries have instances of ideal rock, tough, loess, or bauxitic rock containing complexes of dwellings and storage caves. China, Iran, Turkey, Australia, North Africa, and the Canary Islands all have. Figure 11.50. Cave houses, Cooper PD, Australia. A. Vents and light shafts enable good ventilation. Temperature varies 5°C annually. Abu. Comfort level. Shade house. Many examples of very successful and long occupied dugouts of various degrees of luxury and complexity. Deep cave complexes are now illuminated using surface Fresnel lenses, mirrors, and light guides of solid plastic. Earth sheltered housing, where soils or stone will not support caves. Surface housing of concrete walls and roofing, with earth banks built up to the eaves, and if required, over the roof, effectively duplicates cave conditions, without the risk of soil collapse or water seepage. Where stable clay fraction soils are available, a bulldozer can quickly Consolidated turkey's nest dam above ground, and when this is formed and roofed, it too is a_cool house. For deserts, allowing a variety of treatments on the inner walls, and safe from even severe surface flooding. Figure 11.52. Intermediates between excavated and surface housing are found in the compact, not sheltered, Pueblo housing of the Great Basin Desert, USA, and Anglica sites in China and North Africa. Large. Suin KKM. Lounge. 362. At the base of scarps or cliffs are built in mud brick to provide cool and secure storehouses. EJ dwellings, safe from flooding, rain, and sun. Even when abandoned, these pueblos last for hundreds of years in good condition. Surface housing. The desert is also subjected to surface excavated or hill stepped houses compacted by bulldozer, figure 1153. This beats mud brick, and may last for millennia. Thick mud walls can be built out from half caves, or in very hard country, surface housing can be built. Surface housing is more practical where flooding may occur in thunderstorms, and where sediments are unstable or figure 17.51. Caves with cool or warm air supply. A cold seepage caves trap night air from hollows, they need a sill to divert water. Hot caves trap uphill air by day and are used to wow. IB7 equals E. Earth. Vitri. Figure 11.52. Earth sheltered, surface, houses. Behave well in desert climates and are not subject to flooding, vines can shade sunward whales. AO, CUNE counters trisses equals heka, ASIUB. Clay bune. Bune comes crosses AUD falls off a low rope hill. LGTT shell. 4 Rungstod. 62 SE Riovo Bune. Cove dune forms, and uses of sand. All sands infiltrate. 364. Wind. Low flow of plup/wind high lu. Of FLD slash. Over, sand. Over N. 42 to 34. Radon rich, granites and volcanics. The ultimate cooling device for a surface house, or its pantry and living area, is an earth tunnel. This must be a minimum of 1 m deep and 20 m long, and ideally slopes downhill, the air intake upslope. In the tunnel, large unglazed pots, pans of wet coke, or curtains of coarse fiberglass weave can be drip fed to provide evaporative cooling. Even beds of coarse bark, kept damp, does the job. Cool humid air continually falls through these tunnels to the hot rooms, figure 11.54. In swampy areas, such tunnels can be mounted above the surface soil. Most housing in deserts has been built as surface dwellings. Only a relatively restricted set of sites suits underground housing, unless these are made at considerable expense for water sealing, excavation and drainage. Thus, the essentials of having efficient housing in desert climates is a critical design strategy. We understandably expect heat to be a major problem. There are at least these ways to provide a cool air source for day use. Asterisk internal courtyards, preferably latticed or shaded overhead, and even more effective if they are 2 or more stories high and naturally shaded by the building. Asterisk extensive fully enclosed vine arbors with mulched floors and trickle irrigated. These suit single-story dwellings, although very small. Courtyards with shade can also be fitted in single-story houses. Arbors need to be about 30% of the total floor area to provide cool air, and hanging ferns or houseplants aid in cooling, as does a water tank. Asterisk tunnels, opened as ditches 20 m, 60 feet long, and 1 m deep, and with large pipes, half-round coverts, or evaporative cooling materials provided in their air flow. Asterisk downdrafts, sails, slats, or wind scoops. On roof areas, either fixed or self-steering to force a downflow of the constant or prevailing winds. At their outlets in rooms, these downdraft inlets can be fitted with damp hessian, burlap, coke evaporation beds, or unglazed pots full of water. These add considerable cooling capacity to the air, and humidify the air indoors. Induced cross-ventilation, this is masked easily achieved by fitting a black painted sheet metal solar chimney to open from ceilings or roof ridges. As these heat up, they effectively draw air into the rooms from any of the above cool air sources, and create a cool airflow in living areas. No desert house should be planned or built without its integral trellis and garden systems, as these may not only save most or all climatic energy use, e.g. air conditioning, but provide food and shelter. The attached shade house, in particular, must be planned as integral to house design, and in fact as the summer living area. For this reason, the winter or indoor kitchen must open onto the shade house, the summer kitchen. As well as these cooling devices, heat sources are needed for the frequently cold winters and cold cloud-less nights. Depending on latitude, windows allowing sun to strike an edge insulated concrete slab will provide all the heat needed. With the advent of rigid foam insulation, trenches cut at or below the foundations, to 0.5 or 1 m deep, effectively insulates the whole of the floor/earth mass under the house. It is the simple strategy that can buffer both heat and cold extremes, without the need of firewood for heating. We have also used plastic bags of straw or sawdust for this ground insulation in Nepal, where such slabs have not been built in the original dwelling. A thick vertical wall of mud brick standing 0.5 m inside a room, and faced with a glass window, will act as a heater long after dark, the Trombe wall effect. Finally, in very cool deserts, an attached glass house will act both to heat the interior in cold periods, and to vent hot air for cross-ventilation on hot days. At high latitudes, 30°-60° north or south, extensive glazing needed, and a courtyard with a glazed roof is an excellent refuge from cold. In lower latitudes, 0°-30°, about 20 to 25% of the sun-facing wall will need glazing to provide sufficient heat onto cement slabs or Trombe walls. A sun-side glass house has 3 potential uses in figure 11.53. Hill-stepped houses compacted by bulldozer. 366. Tokriado winter. Heat source. Equals to draw cold air into the house during the summer. Equals to start spring plants early in the year, to ripen late autumn plants, and to grow greens in winter. Asterisk to dry surplus fruits and vegetables in an enclosed area, unavailable to insect pests, as these are also the basic functions of the green house in cooler climates. Then it is clear that such structures operate effectively over broad landscape and climatic ranges. For both heat and cold, massive walls, edge insulated floors, effective draft proofing, insulated ceilings or roof areas, if necessary trellised, or carpeted, with thick vines, and efficient eros ventilation, are all essential strategies to moderate the extremes of daily extremes. ESs themselves can be very compact, especially where shaded outdoor trellis areas are extensive. 'Tis an excellent design feature to place the winter kitchen indoors, but to also have it open to a screened-in summer kitchen part roofed under a thickly trellised area where occupants can spend most of the day out of quite small in cross-section. Solar chimneys or attached greenhouses on the sunward side of dwellings create a cross draft sufficiently strong to blow out a candle. Thus, if a fully enclosed and totally vined shade house is constructed on the shade side of the house, a continuous cool and humid air crossflow results, providing the cool air can enter the living areas by a fairly direct route, and that some water is available to supply the vines with evaporative cooling. Figure 10.17. Commonly, air can be cooled to 10 to 15 degrees Celsius below ambient temperature by this combination of shade, vines, and induced airflow. The same crossflow from earth tunnels also supplies unlimited cool air. It is a simple matter to close the house at night or on cold days and to retain glass house heat inside. Such designs save up to 80% of fuel energy, a particularly important factor for low-income groups, where energy cart be 30 to 40% of total household expenditure. As glass and trellis are durable, and as costs amortize in 1 to 3 years, it makes sense to make these beneficial retrofits to uncomfortable houses. That we see modern houses built without such aids is a witness to stupidity, waste, and poor design. The results are to be seen in deforestation and reliance on fossil fuels, with continuing pollution. More serious results are the ill strains on poor or low-income families, the ill effects of smoky fires and illnesses due to cold and tiredness after cold nights. Roof and parapet furniture. Wherever rainfall is light, flat parapet concreted roof areas are preferred. These roof flats have a wide variety of uses for grain drying, wasn houses, pigeon lofts, and trellised over recreation areas. In the severe winters of the area, make their haystacks on the roof, in part to protect the hay from goats, but effectively providing a winter's warmth of thick insulation plus compost heat which radiates from the ceiling to the rooms below. Features commonly built into tapered roof. Anal trellis roof areas are pigeon lofts for eggs, squabs, manure, laundry troughs and drying lines, header tanks for 1 to 2 weeks water supply, fitted with float valves, wind towers with scoops, slats, jottis, sails, or aerofoils to catch local winds, evening rest areas for outdoor passive recreation. Figure 11.54. Goal air tunnel. Unglazed pot of water at outlet. Length 20 m, depth 1. Slopes down to house, CAS. Shaded intake, moist coke, or cinder bed. This tunnel provides cool Uniardo tiny desert. HISA, food storages. Hospitals. ATT. 367. Hammocks. Grain drying flats, drying racks, bulk food stores, or bins. Winter hay storage. In cold climates, heat or partial composting is radiated and conducted to the ceiling of rooms below. The essentials of a desert house. No west windows. West wall painted white and fully shaded, vine screened, evergreen trees to the west. Cold air tunnel or cold air source as a fully closed, bark mulch shade house. Positive hot air exhaust as a solar chimney or small attached glass house to the sun side. Unimpeded through ventilation for cool air. Either very thick, white, fully shaded walls, cool deserts and cool nights, or very light, screened, or matted walls, hot days and nights. Evaporative cooling surfaces in a through draft, as unglazed pottery, coke mounds, ferns in bark, thick vines, or wet hessian, burlap, screens. Cool cellars for storages, or deep cool internal courtyards with vines and ferns. Ceilings insulated, thick vine mass over roof area. Placement of vegetation around dryland houses. It is the low westerly sun that adds most heat to buildings. For that reason, no windows are placed in west walls where they incur direct heat gain. Permanent screens of evergreen trees, thick-leaved vines, or turf banks are placed to the west of the house. $0 is to shade and shelter the west wall. The shade side of the house is where enclosed trellis is built. The east side can be part shaded by deciduous trees or vines, and can have small windows. Glazing is most useful on the sun side where 100% in cold areas to 25% in warm areas of the wall can be glass. The house itself needs to be elongated east-west, so that sun in winter can reach all room floors. It is the heat width on the sun side that permits the winter sun to enter the rooms, and the summer sun to miss the walls and windows. External, not internal, bamboo, wooden, or aluminum blinds prevent heat entry to windows on hot winter days in deserts. Deciduous vines on the sun side prevent too much heating during the summer months. The correct placement of vegetation, blinds, windows, and insulation, figure 11,55, means that no extra costs are incurred, but that the dwelling works efficiently. In settlements, such rules can be made part of local building legislation, and this alone will save thousands of hectares of forests in the third world. Straw, thatch, wool, feathers, cork, woven materials, and even paper and cardboard are adequate insulators. But few of these equal thick vines over wall and roof as active cooling systems. These are affordable by any 368 person. A desert house well screened and shaded by vegetation is an oasis indeed. Believe the emphasis in desert housing should be on developing the arbor for living, and on creating and reactive housing, mainly for night occupancy, and in the rare case of rains, home energy conservation. To produce hot water in deserts is easy enough, either From asterisk a solar attic with a water tank, a glass cover, and aluminium foil over thick insulation, a bulk water heater. Asterisk a grid of plastic pipe in S00T covered sand, itself. Underplas, and asterisk a simple coil of pipe on a metal roof, so that enough warm to hot water is available. For groups of 5 to 10 houses, a solar pond of 4 to 5 m sides, and 1 to 2 m deep, figure 11.56, will supply not only hot water, but house heating. Space heat and hot water together are about 80% of the energy needs of modern housing. A solitary photovoltaic cell or a bank of such cells provides the little electricity needed for lights and electronics, and it remains to cook using oil, gas, or modest fires. All desert settlements should, as a matter of legislated planning, divert wastewater to firewood plantation. In a modern town such as Alice Springs or new towns, the water from washing, toilets, and sinks could provide all the firewood for cooking if it is carefully used in trickle irrigation systems and stored in non-leaking and covered cisterns. Hardy desert trees on a much broader scale establish firewood reserves. House water conservation. Modest water use is easily achievable if efficient shower heads are used for washing, and both shower and hand basin or laundry water is first diverted to the flush tank of toilets, where sewage is provided, or to the garden where dry pit toilets are used. The pit toilet, popular in Central Australia, works well, and is good for years of use without water. Ficus TLS 71. Target. Shower water to a flush toilet cistern. The shower and hand basin can be raised a few steps above floor level, and a low-level cistern used, figure 7.17. Wherever possible, spouting from all roof areas should be run to covered concrete tanks. These would be a hot sales item in most of the world, but are common only in Australia, like Vegemite, electric jugs, and rotary clotheslines. It is a rare isolated house in dryland Australia that does not boast of at least 5,000 of tank capacity. Located on the shade side of the house, under trellis, such tanks provide cool drinking and cooking water. Trellis over garden S. Toll right A year equals. Polyesa. Ibos. 7. Crop. Paved. Lu. R asterisk star. S equals. LD. 7 asterisk asterisk asterisk. Figure 11,55. Correct placement of systems around the house. FRIPO. Carded. 5. Figure 11.56 ROA. Solar pond. Operates over a wide climatic range. Is efficient for heat capture, but low efficiency for electricity while turbine needs reliable domestic models to provide processed water, space heal, in undeveloped desert areas, including cold deserts. I. POSAESE at OAAA equals NEEEBs, 4, EAMUIFRES water. 2 Zargors. Verbirotrity. Sipsmet. Salt soluti. B vertical ANPEE slash. Perpendicle TES. Bitio prevent FOTHERR plus earth and S. Salt FOLBTION over NM. Heat store. Mong salt and FR. Yeah. Figure 11.57. Pit toilet of Central Australia. External solar chimney, a black metal pipe, creates positive downdraft, dries faces. Simple construction and efficiency makes these toilets popular. Note fly screen on solar chimney. 370. 11.8. The desert garden. Would not be necessary to write a desert garden ion were it not for these profound effects that are to drylands. IES water solutes are likely to be factors higher than in areas. Copyright pH and consequent mineral deficiencies can have underscore registered. There may be high nitrate levels in water and food. Asterisk non-local food is likely to lack vitamins, and to be expensive. Underscore registered water use is necessarily restricted by supply. Asterisk light saturation of garden plants may create the need for shade to achieve good growth in gardens. Asterisk nomadic or wild animals are specific problems. Moreover, because of the general low level of underscore sources in drylands, it is unlikely that ordinary people living there will be able to afford full nutrition if gardens are not plentiful throughout settlements. To relieve malnutrition, the home garden is our Chalai in deserts, gardens, not field crops, are the mainstay against famine. Unlike cereals and grain, legumes, ordinary leaf, fruit, and root products require little cooking, which saves energy in the home. They also contain essential minerals and vitamins, and can make every family food self-reliant. The desert garden must be planned as a very serious affair. Health in deserts is very much a matter of good nutrition, and imported food often is of poor quality and expensive. On flat and dusty plains, a few hours with a bulldozer, or many hands, can throw up a ditch and wall to 3m or run a high barricade that discour ages wild cattle and deflects winds. Solid pisa and mud. Brick courtyard walls can be built over time. Rock is often plentiful for such protective walls. Inside this, beds raised by stones, pisa, or logs can be almost totally mulch filled as mulch sources are developed or gathered. Individual beds can be shaded to 75% with shade cloth, palm fronds, or brush, supported on frames 1 to 15m high. Solid pillars of concrete block and mud brick to 2.5m can be made to support permanent vine trellis over much of it. A careful soil and water analysis is essential. We can reasonably expect phosphorus and zinc deficiency, and probably iron and manganese. Excess boron from detergents can cause plant failure, so that common soaps are best used where wastewater is used on garden beds. Water must be checked for excessive nitrates and fluorine, both common dryland pollutants. All rain runoff and roof water must be carefully harvested and used to flush salts if local water exceeds 800 ppm or the garden is not free drained. A careful plant sequence for all beds, so that they are always self-shaded by almost constant crop, is of great value. Local expertise and agricultural department advice is called for deep rooting and high yielding perennials. Asparagus, globe artichoke, are standby crop, as are drought-tolerant staples such as sweet potato and most cucurbits and the melon family. The desert garden needs an emphasis on staple trees, adapted to dry periods or able to survive on minimal water. Suggested plants would be 5 to 6 date palms, 4 to 5 olives, a doom palm, 2 or 3 citrus, 1 to 3 avocados, 4 to 5 apricots, bananas, and papayas, climate permitting, and a massive vine crop. The house should be sited near a runoff area, where water can be soaked into sand, dams or swales to keep trees alive. The garden surrounds the house, using all waste water either as soakage fields or as underground plastic-lined swales in coarser material. Garden beds for vegetables can be carefully constructed. Have seen Them built of compacted mud, filled with better soil. And mulched. Every vegetable we can grow in temper. 8 or tropical lands will grow well in small beds. Usually 3x1 or so, flooded every 3 to 10 days. Mulched, and part shaded by slats, vines, or the canopy of a light-crowned leguminous tree. Wallflowers, marigolds, gladioli, and other companion crops are beneficial to brassicas, solanum species, and onions respectively. Every bed should be planned for succession to fava beans, pea, or tepary. Beans in season, fava and peas in cool seasons, tepary. And moth beans in hot seasons. Even potatoes will grow in deep, 0.5 to 1 m, boxes filled with mulch, pine needles, and household scraps, although yam beans, jicama, sweet potato, and sunroot, Helianthus tuberosa, supply more reliable yields than potatoes. Celery, onion, brassica, carrot, beet, spinach, glab, artichoke, tomato, and sweet and chili pepper do particularly well, and surplus vegetables can be dried. The desert is the home of watermelon, melons, and climbing or vine cucurbits Gardner ally. Every wall should be seen as a vine trellis and the roof covered with dense vine. Even flat roof areas can be shaded with a high trellis of grape. But the desert garden should also be a corridor. Plantation down nearby river beds, niche gardens in shaded sites, patch gardens on leach fields, and a spread of very hardy adapted yams, bulbs, and wild fruits, cactus, and palm wherever a site exists or can be made. Sand-filled waterways always contain some moisture. These are corridors of moisture and soil. Corridor farming is already a very different idea from area cropping, and we need to choose and place a complex assembly of native and introduced species to give us at least a basic food reserve, fuels, and selected structural timbers. At times, the corridors are rivers, dune series on hostile salted or stony pavement, or the floodplains of exotic rivers. These are the sites for our semi-wild plant and animal reserves. We can make some vision for a good rain year by broadcast sowing into areas we have already prepared for infiltration, and taking off a crop of sunflower, millet, sorghum, paddock grass, or melons. These are essentially surplus crop, for long-term storage as such, or for export. Out of 371. Region in trade. Matching up earth bed, irrigation, soil treatment, and plant species. Home gardens return so much in have, cash, and just plain life interest that they deserve intensive, bed by bed planning, in which companion plants, seasonal success sign, bed soil treatments, and a permanent watering method are all designed. Rather than do this for every vegetable, I will deal with 3 or 4 classes of each and suggest a method to suit. People can then follow the methods, all of which are working for other plants of like needs. Depending on resources, beds can be raised by digging and edged with pise, rammed damp clay, sands, bricks, logs, or stone walls. Trellis can be of metal mesh, bamboo, hardy and even crooked termite resistant wood, cane grasses, or living leguminous trees. Deserts have supplies AF clays, sands, rubble, and sometimes lime or gypsum for use in gardens. In gardens, we can experiment with a variety of pits, circles, raised beds, potty beds for flooding, ridge and furrow, edge bank raised beds, cone and hollow, and mulch baskets or mulch boxes for some vegetables. Figure 11.58. Where plastic irrigation pipes are absent or expense, adequate substitutes can be made of unglazed pots. Figure 17.58. Earth shaping within gardens. A. Cool mulched pits for trees. B. Circle gardens around mulch hole. C. A.S. ridges to shade seedlings. 0 mulch baskets at clump plantings. E. Log boxes of mulch over alkaline sands. F. Broad flood bays for E.9. Carrot crop. G. Top watered raised beds for salty water supply. To 1,200 ppm. 372. Pipe, gravel beds, or hand molded concrete. Is on or below the surface, the latter covered. B. Giles or any flat material. Pipes of bamboo, drilled. P. Water, flagons, or bottles suspended and A. Perforated to leak, or simple bucket systems can. EET albeit with more labor. Categories of things we plant are ovens, perennials or trees in pots, e.g. E.s., shrubs, flowers, advanced tomatoes. Keep in at under shade until rains have fallen, transplant in weather. Dig holes to accept full root system, soak hole and add a small handful of fertilizer or soil. Fever, lime in acid areas, gypsum in alkaline clays. M out the pot and plant the seedling, pushing a GE branch in nearby to shade and shelter the plant. Asterisk seedlings from trays or pits, e.g. lettuce, brassica, set and chili peppers, chives, globe artichoke, bits. Plant in cool weather, towards evening, in high watered soils. If in compost, dibble a hole for. Oh yes, if in thick mulch, pour 1/4 of a bucket out a liter of good soil in the hole made in the mulch. E. Place a flat stone upwind. Plant in the soil hole. Asterisk tubers and bulb, e.g. potato, yam, sweet, motto, flower bulbs, sunroot, green and if possible. Tubers and tuber shoots can be pushed down. Bars, or buried and then mulched, in damp. A. Large or fine seeds. There are 2. L. Scatter seeds over a fine tilth bed, ideally of sieved compost, then wet and pressed down. Sometimes, hessian, burlap, is laid above the bed before watering, and removed on day 3 or 4 after the first signs of germination are seen. This suits larger crop. 2 lens of fine soil 4 to 5 centimeters thick is patted down over a thick, 12 centimeters, base mulch, and some fine seeds sprinkled on this, forming patches of crop in a general mulch. This suits repetitive sowings in home gardens. Figure 11.63 gives an idea of how each of these lasses of plants are established in thick mulch in a home garden. Such instant gardens have commonly been established in a few hours. They give a satisfactory result in the first year, but as with any garden, do not form good garden soils until a few years of continuous gardening have passed, when the biological content of the soil is stabilized and crumb structures in the soil have formed. It remains to design beds and plant guilds to suit a set of vegetables. For carrots and onions, 3 to 6 beds, 4 m long x 1 m wide, can be used, depending on family size. Another 2 to 3 beds should also be allotted to chives, garlic, and shallots to ensure some alliums throughout the year. Keen gardeners would include beds for leeks, sand leeks, and multiplier onions. All these beds can be built raised but dead level by leveling with a straight edge, and either sunken below, for built up rim, or heaped and leveled off. As both onions and carrots prefer free sandy soils with moderate drainage and modest fertility, a pH of 5,5-7.5, these are beds into which old compost and dry, fine organic material such as powdered grazing. Animal manures can be mixed at ratio of 1:9 or 1:6. Organic material to soil. The beds are then V-belled and pressed flat, seed sprinkled over it, previously. Mixed with sawdust or a colored sand to show seed coverage, and the bed flooded to the rim with water, not exceeding 1,100 ppm salt. This then soaks in. If the beds are covered with hessian and inspected daily for germination, a light daily flood will have good effects. As crop tops grow, burlap removed as seeds start to sprout, irrigation can be reduced to once every 2 to 3 days. Carrots have 3 beds allotted, planted mid-summer, and just before and after the coal season. Surplus carrots keep well when picked and layered in cool sand in pits 0.5 to 1 m deep. The green tops are moved to 1 centimeter from the crown, and they are pitted without washing or removing any roots. Onions are hung in dry airy plates. For carrots, a scatter of small salad radish breaks the soil crust and thins the crop as the radish mature in a few weeks and are removed. For onions, gladioli inhibit most pests and provide a small cash crop. For both crops, a nearby border of sunflower, crotalaria, or marigold, Tigetes, reduce wind effects, which can devastate onions, and provide a mulch source. Tigetes reduces nematodes, as does crotalaria, and the latter provide soil nitrogen and mulch. An example of a seedling crop are peppers or tomatoes. Although soil tolerant, both appreciate a pH of about 5.5.6.8. Tomatoes can tolerate about twice the salt in soils of peppers, and thus peppers may need more tank water at levels of salt exceeding 1,100 ppm. Both are best arranged for underground or subsurface root level irrigation by unglazed pottery or leaky pipes. Both are unsuited to spray irrigation, as are cooker bits. Such sprays aid the spread and growth of leaf mold or mildew and fungi. For the home garden, an efficient bed is a keyhole system holding 20 to 50 plants in 3 rows deep, 1.5 m wide. Both benefit from Tigetes, interplant, and a wind shelter of sunflower, sunroot, or crotalaria. A culinary accompaniment is basil. These keyhole beds provide easy access with minimum half bed ratio or wasted space. Both plants do well when set out as strong seedlings in soil pockets in deep mulch. Figure 11.60.a and 11.60.b. 4. Root crop, broad beds, keyholes, or long rows are able. The one essential is thick coarse mulch to shield the tubers and cool the root runs while keeping pH buffered. Potato and sweet potato prefer organic dry soils, pH 5.0 to 6.8, achieved by compost, perhaps some sulfur, and a thick damp mulch. Subsurface water is ideal, and a few marigold interplants aid root health. A family needs 2 to 3 successions of each, with areas of 10 square meters or so in each bed, as they are staple crops. Thus, 20 to 30 square meters in garden needs to be devoted to staple food. 373. For all these crops, specific beds can be laid out and designed to give ideal conditions. Lawrence, 1980. Provides an excellent planning guide for growers for many factors to do with spacing, micronutrients, pH, and yields under good conditions. Planning a garden repays itself quickly, and a good gardener expects to amortize establishment costs. Fences, beds, seed, mulch, micronutrients, in 6 to 8 months, thereafter gaining a profit in health, food, and cash. The essentials of a desert garden are small raised flooded beds, thickly mulched, registered permanent hardy trees on leach fields or in swales, semi-wild very hardy bulbs, tubers, and yams in selected sites, every bit of wastewater directed to leach fields, also surplus from roof and runoff, vines, their roots in cool mulch or inside shading walls, a major feature of the garden. Every wall, open space, and roof vine shaded. Registered mulch, 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 mulch. Figure 11.59. Plants in difficult soils. A calc-reedy layer cracked open, pit of humus and organic wastes. Allows the roots to lower damp sands. 8 cracking clay soils filled with sand gypsum mix before seedlings planted. C gets mixed with trace elements, sulfur before planting in sites. D plastic liner 2. Syracuse clays, ACIP, B. Holes in deep sands holds minerals, nutrients, gets. E small explosive. Charge shatters hard shales. F Riplin opens hard pans for tree lines. And water infiltration. 374. LE foods. PLE food is defined as one supplying 50% or more diet when in season. Today, some 70% of the food in Western societies are supplied by 8 staple. Non-European family has 20 to 30 basic staple foods. Have a choice of as many as 62 to 100 foods in all. Copyright very good home garden and livestock situation. Mid-produce about 21, vegetables 6 to 9 fruits and 3 to 6 s, well beyond the choice range of an average Stern family. Of these, 2 to 4 would be considered F equals, depending on the culture. Very basic question we must therefore ask is how you improve the Australian desert yield for A. By introducing cattle and sheep, and releasing bit, we have destroyed the bulk of the useful John, and almost every common marsupial or adapted mammal of medium size, although igarus and mice survive. We have destroyed the mealess way of living and the profound knowledge of sands of integrated tribal people for an undeserved ship by a very few, essentially disintegrated. Is makes no ecological, economic, genetic, inform, onal, or social sense, and it is a denial of human SKHTS. We have replaced common sense with a situa on of downright exploitation and rapid loss. Broad commercial herding is, to the desert, what pad-scale sugar caning is to the tropical rain. ST, and broad-scale NS to floodplain forests. A disaster in every way. People who manage desert well for 10,000 to 40,000 years may have known a little about it. We have suppressed this knowledge and its right to continue to exist. Those who were teachers have become fringe dwellers. Both genetic resources and information on management have been destroyed by the right to ruin mentality claimed by private owners and governments. Even the plants developed by the Papago and Hopi Indians are being lost as store foods replace desert foods. And yet it is clear from desert plant lists that there is a present potential for several staple foods, and an untapped potential for developing better cultivars of many desert plants. Several hardy seeds were stored to extend the staple over more than one season. In Nevada, Shoshone, Indians gathered, in about 6 days, the year's supply of Pinus italus, and buried unripe cones for later use if Needed. Rice grass seed, or rhizoides, was a similar easy staple to gather and store. Thus, staples in deserts, excluding animal foods, seem to be plentiful. It is a question not so much of gardening or farming, but of placing and managing a set of hardy foods in the best situation for later gathering. As almost every desert garden with modest water can supply 60 or more vegetable species, and as the cultivated fruits of deserts number 30 or more in common use, and as all domestic livestock, including figure 11.60, a keyhole bed, a raised bed, densely planted, with hardy sunflower windbreak and high shade suits deserts. B. Tomato polyculture keyhole. Marigolds inhibit nematodes, whole area is wind sheltered and thickly mulched. Plant Fay grass. Beans as a pew. Marcus. Winter sea pound CP Omsul. Of, Gene. Best, to cook. MAPIWRE to Wintories. Eolo tomatoes PP pear. II Haspidi UMS. 375. Ducks and geese are thriving in arid areas. There is no basic problem for nutrition. Yet adequate food and good nutrition are denied many desert peoples because of the lack of basic seed and plant resources and the denudation of the total environment by livestock. For designers, small intensive trial systems within and around settlements are the essential precursors to wider zone 2 and 3 trials along favorable corridors of better soils and water. The selection of existing plants and the further addition of new species for the area greatly assist this nucleus of small successes that demonstrates how larger or more extensive systems can also develop using fewer but well-tested species. It is always essential to build in humus and mulch production into crops and species used for this purpose can range from such edible plants such as dolichos, edible lupin, luteina, or edible seeded acacias, to shelter, edge, weed barrier, and hedgerow species such as Echin fastuosum, acacia, painazetum, comfort, lemongrass, and vetiver grass. Many trees such as casuarina, some figs, acacia victorio, pongamia, and clump species such as bamboo also provide shelter and feed mulch, while hardy ground covers suppress grasses and cool the roots of vines and young trees. Good soft ground covers outside zone 1 are vetches, nasturtium, a variety of runner legumes, comfort, annual lupins, and daikon radish. The spacing of fruit trees in zones N2 can be as usual. It is, however, essential to provide high shade from interplants of tall thin foliage legumes or palms, to also interplant fast-growing small and large woody legumes that either die out, pigeon pea, or can be copiced, tagassist, or felled or ringbark to raw to humus. Many acacia species such well-planned systems are very productive, drought-resistant, cool, and eventually humus-rich. They demonstrate how quickly a barren or hard soil area can be brought into production as a result of intensive biomass production and wastewater use. Thus, the role of teachers and designers is to help plan and place such systems as trials in villages, to locate and provide seeds and propagules of new species, to teach the benefits of soil humus and rainwater harvest, and to stress food preparation and good nutrition. Vines. Vines have a key role to play in desert gardens. Correctly spaced and pruned, they provide both a productive crop and shade cover to mulched and watered gardens. They are also a key element in moderating climate in designed houses, or in retrofitting uncomfortably hot homes. These basic uses can all be applied in the domestic situation. There are special vines for broad-scale work, and for selected niches in the desert property. We can deal with each in turn. Vine over garden. Horizontal trellis bars at 1 to 2 m spacing and furnished with grapevines can throw a shade system over the greater part of the vegetable garden, relieving light saturation. The sides of this trellis can also be more completely closed with herbaceous vines, beans, climbing tomatoes, yams, cucurbits. It is more important to defend from the early eastern sun, as dew, distillation, and guttation moisture is important to plants early in the day, and soil temperatures then remain cooler for longer periods. The western side of the trellis needs fleshy vines, as great heat can build up SVKHER Griambule on mesh. Figure 11.61. Plant of vines over garden. 50% or more shade helps gardens in clear deserts. Side trellises space to shut out most of the westerly sun. Palms can serve a 5 Joe SP, UGHT penetration. To chaw shade providers, mulch is of real benefit in all deserts. 376. Mianel on a vine such MUI, Miley Minute, is ideal. Only the shading T of trellis needs to be left quite open, while the asterisk can be of wide-spaced pole crop. A plant is as ZPHORISE cron. Siderable comfort can be brought to overhot SS by attaching trellis. The best results are achieved. Igni vine crop out from west. Alls, Mecania, Dolichos, Pelargonium, and a vine. And 3 above and out from any existing west. P growing vines, winter deciduous or summer spacious, in a screen fixed out from the eastern sun. Alls. These are well placed at the edge of a veranda if I vines with water rapidly cools the shaded veranda. Registered building extensive closed trellis over the rear door. M the shade side to provide a cool air source. MRE, with a thick bark mulch below the vine end. Praise to damp it down. In this case, roof vents via the indoor ceiling or a small sunside glass house are necessary to draw in the cool air of the trellis. AA ceste a perennial non-invasive vine, Mecania. FIA, completely across the roof. ER pecking a water tank tinder the vine trough to keep SE garden air cool, and to cool the water. Full ELEF sources. S can be vigorous producers of foliage for garden mulch and for feeding small domain livestock. WW well chosen. Shade vines can also provide some stick Elwoods for efficient cook stoves. Vines in the desert Lisa. Arrow vine crops are desert adapted, if we include the gourds and yam legumes, ground vines, some vary. Sea reserve foods can be set out in shaded, moist, wastewater, or soakage situations. Some vines survive dry, harsh, stony, or dune conditions. All, however, thrive and yield better if a few cubic feet of humus is pitted below the plant when it is set out. Valuable vines grown in large containers can await rains, or the soakage from water harvesting, before being placed out for permanent field growth. Fencing. Over much of the world's drylands, the great impeding meant to home garden production of food is the presence of wild, feral, and domestic browsing animals. It is much cheaper to fence out these devastating and ever-hungry animals from settlements and gardens than it is to airlift emergency food aid to starving people, or to withstand the social costs of poverty and famine. Fencing is thus a primary requisite for intensive food production in deserts. Fenced corridors or stock Roots can permit milk and draft animals to enter some restricted areas of settlements, but it needs sound fences, preferably electrified, to exclude goats, camels, cattle, donkeys, and sheep from home gardens. Within fenced areas, sometimes surprising natural regeneration of trees can occur, and hardy food plants can be set out in unirrigated areas if fencing is provided. These form a firewood, mulch, and bedding seasonal resource for hard times. Poultry, domestic rabbits, bees, guinea pigs, and pigeons are all relatively harmless livestock for dryland homes, where there is no money available for post and wire fencing. More laborious alternatives are used, ranging from ditch and bank systems, either rock faced or thorn crowned, to woven or living fences of plant materials, reeds in the Caspian area, cactus in Mexico, Euphorbia antiquorum in India, Euphorbia tyricoli and Lycium ferocissima in Africa and now parts of Australia. Combinations of stone walls, rock, thorny shrubs, and steel pickets or wires are frequently seen. In affluent societies, burnt brick walls, and in Afghanistan and Iran, unburnt mud brick walls are erected around large gardens. Even within urban areas of the third world, domestic animals range and destroy vegetation. Where hunting will support dogs, large domestic dogs will defend a house area at the cost of feeding the dog. It is a matter of adapting to local materials, labor costs, and customs. Soils. In drylands, any soil humus can rapidly decompose in dry cracked soils to nitrates with heat and water, giving a sometimes lethal flush of nitrate to new seedlings. Dry cultivated soils exacerbates this effect. Mulches or litter on top of the soil prevents both soil cracking and the lethal effect of rapid temperature gains that cook feeder roots at the surface, so that in subsequent rains there are less roots to absorb water. Fire is destructive of this protective litter. After fire and cultivation, most of the soil nitrogen, sulfur, and phosphorus is lost, and even a cool fire loses plant nutrients to soil water and leaching. When we know more of the effects of fire in drylands, it is my opinion that we will use any other method, slashing, rolling, even like grazing, to reduce fire litter to soil mulch. Now seems probable that aboriginal burning has not only gravely depleted soil nutrients, but caused a breakdown in soil structure, and perhaps has been in great part responsible for the salt pans that preceded agriculture. However, agriculture itself is a monstrously effective way to speed up this process and intensify it. Where free draining or non-wetting sand is the problem, bentonite, a volcanic fine clay which swells up and holds water, is a great help in flood irrigated beds. Conversely, where clay is causing problems with 377 water penetration, the addition of gypsum enables water to penetrate further into the clay particles. Where salted soils or salty waters are a problem, the garden beds and be mounted up or raised, when the salt can wash down into the paths and low places. Water use is efficient only if all the water soaks in quickly, and watering is stopped once the soil is saturated. Mulch greatly helps this process of fast soakage. Whatever is true of home gardens is also true of swales, and soil treatments can be the same for swales. Ripping swales helps, as do soil additives such as bentonite and gypsum. Where swales are used as tracks, gravel mulch is appropriate. Coarse sand, raked to keep swales weed-free, also helps. Swales are better made about 2 to 4 m, 6 to 12 feet wide, so that trees grown along them can overshade the swale base and so help prevent evaporation. As swales develop, salt is carried down to groundwater level. Every desert settlement of 5 centimeters rainfall or less can direct alley road and roof runoff and tank overflow into swales. Domestic water from all sources can also be absorbed into swales, producing fruit, flowers, and vegetables for the house and village, or fuel products for society. Desalting soils in Guard. The Sahrawi people of North Africa, as refugees in Algeria, have developed 2 methods of soil treatment. Under irrigation that leaches salt. Both methods involve heroic or total soil rehabilitation. International Agricultural Development Jan Feb. 1987. Method 1, where shingle or pebbles are available. Salt soil is removed to 1 to 2 m deep, a layer of shingle laid down, and non-salted soil carted in. Figure 11. 62a. Method 2, where no such stones are available, topsoil is removed. If clay, to 20 centimeters, salt-free sand is brought in, and deep canals are cut to drain off surplus salt with the irrigation water. Figure 11.62.b. Desert mulches. Organic matter is as invaluable in deserts as it is elsewhere. Sources are asterisk the detritus brought down in flood, which can be arrested on strong mulch trap fences, figure 4.33. Asterisk tumbleweeds and wisps of plants blown by wind, which will settle in pits, swales, or are trapped on fences. Asterisk grown mulch in our gardens and orchards. Asterisk plants such as casuarina, bamboo, tamarisk, comfort, some species of acacia, forage grasses and legumes can be planted for their mulch value or nitrogenous soil fixation in specific situations. Some desert vines also provide good mulch from trimmings, as do hedge species. Asterisk household and storage wastes, and asterisk grazers on range, if regularly penned, for mulch manure resources. Categories of mulches are asterisk domestic old skins, blankets, cotton or wool, clothes, cardboard boxes, newspapers, hardboard and thin planks. All of these, soaked, can be used to line sandy pits, or tiled over the ground in raised beds. Before mulch is added. 2e. 8 pen. M. Wells Boundalore. Te help Saeator. Pure peel rule of Fe. PBIRTE up. Larpens. Figure 11.62. Desalting of soils in gardens. Heroic sol removal, new surface sol, deep drains, beds with a shingle base can make a garden if a salted area if enough labor is available. Beds must be flushed periodically with low salinity water. 378. Asterisk collected ashes, bones, dog, cattle or horse, kept dry or pitted in circle pits for in-ground. St ashes and dry herbivore manure can be or pounded. Equals fines, chaff, bark, leaves, tea leaves, coffee, flood detritus, rice or grain hulls, rotten wood, must. All these fines, and shredded paper or wood, asterisk, are ideally combined with shredded manures, sand, and ashes to fill up raised beds. These can be laid atop or coarse mulch. Underscore asterisk coarse mulch, logs, twigs, dry straw, thick, arc, old wood. These are used as bed edges, or a 4 to 6 m layer over which mixed soils and fines are spread. to 18 to 20 centimeters thick. Asterisk toppings, cypress, wood chips, pine, or cashew. IAT needles, cocoa beans. These can be at mulch or osmotic layers spread over the top of the early layers. Our bed now looks like figure 11.63. Good green mulches for grapes and tree crop can be gathered from cash crops of lupins, faba beans, and coppice acacia or mallee eucalypt. These can be cut after rains and stored as silage or in earth pits for later use. Lucerne establishes in swales and damp areas, and casuarina leaf or pine leaf can be regularly gathered from trees in the field. We must largely rely on mulch to bring down the pH of alkaline soils and to make minerals available. In mulch, free-living nitrogen-fixing organisms supply plant nutrients at 4 steady rate, and leaching is delayed or prevented. In tropic drylands, the greatest losses are in bare soil agriculture, when nitrogen, calcium, and potassium are leached to streams and groundwater. Wherever we use deep humus, mulch, or green manures, we need to provide dolomite, as nitrates prevent copper and manganese mobility if no calcium or manganese is supplied. When we mulch in deserts, we need to emulate the ant and the termite, who bury their organic materials out of the sun. Wherever possible, we should also place a layer of stone, sand, or soil over our desert mulches, or create hollows where trapped leaves will be later covered with sand. Drought stress in cultivated plants is greatly ameliorated if these plants are provided with mycorrhiza, root fungi. From the host plants, root associates get shelter in a safe root environment, and sugars. In return, they scavenge for soil nutrients, and can mobilize phosphorus even at very low water levels in the soil. It is true to say that many plants don't have roots, they have fungal mycelia to explore the minute world of the soil particles. With almost no exceptions, all the vegetables that SFF. A mince ton. Figure 11.63. Mulched garden beds. Very thick, 18 to 20 centimeters, mulch conserves water, produces good humus. Soils, methods of planting trees, seedlings, fine seeds, tubers are SBSBSEAEAS equals SS 3 FE. EESN. AE pipches ES RES EA year. So N fines. OTDS set 3s, E. Plus 2 ETA, ATT rig. Of C. ASE equals AA equals. AESS underscore. EOVAPENSAESYEESEP. And. Lame of A. Isom or PME Sremki upon. Fal. Lems 2 sen, beep. JP go plus 0 G NASes. MGW quality. Mac. Below. Shown. Instant gardens are made this way in drylands, all stages are watered as completed. Mulch TS pull up as in 8. Equals. 379. Grow in humid areas of similar temperatures will grow. In deserts or dryland gardens under some form. Or irrigation or water harvesting. Field crops are more restricted, but grains, oil seeds, sunflower, safflowers, and grain legumes can be grown in suitable soils. After rains. Fields, however, are more expensive to modify and water than gardens, and carry the risks of wind erosion if cultivated. Fields in deserts may be possible as crosswind avenues between perpetual wind break of acacia species and fieldstone, however, have not as yet seen this tried, and even in avenues, the width would need to be restricted to 5 or 6 times in tree height, and all crop straw returned, trash, or mulch. Farming, to avoid rain splash and soil loss. Space is seldom limited in deserts, so that up to 30% of any garden or field can be profitably devoted to permanent or, for gardens, seasonal windbreak. As much for a mulch source as protection from the wind. Unburnt and ungrazed semi-desert can produce very large quantities of grass mulch after rains. It is quite frightening to stand in a chest-high stand. AF Dantonia, Stipa, Themata, and Agrostes dried to a tinder in such conditions. AMD to contemplate the implications of a fire. One believed that a large area kept unburnt and forage harvested in strips after rains would supply all the mulch that gardens could use. In the narrower, unharvested strips, I would expect a dense mat mulch to emerge if fire could be excluded, even in 15 centimeters of rain. If this were rolled down between permanent trees, a hunt soil would eventually develop. Certainly, all of these strategies should be tested. Avenue cropping, forage or mulch harvesting of bunch grasses, roll down, mulching, and trash farming in avenues, on the broad scale. If such systems are also combined with interceptor banks, figure 11.93, it may be possible to develop a dryland agriculture based on permanence and stability. The unregulated nature of grazing and wildfire is what prevents this development in many semi-arid areas. Harvested wildlife would, however, appreciate the system for food and shelter. Have tried to diagram the ICA system in figure 11.64. On an eroded, alkaline, non-wetting sand dune near Sejunda, South Australia, a group of Aboriginal students trained by Peter Bennett of the Soil Association produced in 6 months an excellent, healthy mixed garden of almost every sort of vegetable and many flowers at 1,100 ppm salt in water. The key ingredients were fine shredded mulch, compost, and coarse mulch. On beds, careful watering, and a sound organic approach to soils. Given such a hostile base for a garden, this example should encourage any group to do the same. The graduate from this teaching garden have extended their studies to home gardens in the area, and to teaching those skills. This is an appropriate way to provide food in deserts. Gras CRCEO COTFO MBLCH. LTE equals ISOM. Figure 11.64. Food and shelter for harvested wildlife. Crop. Swales on headwater slopes grow fodder legumes, hardy trees, and are mulched for high-value crop. Grasses or grains can be cropped after rains on tipped STS and weed swales. Figure 11.65. Micropore and seepage lines. Is EC. 11.9. Any use of water in unguarded or unsheltered plots is 48 to 10% increase in evaporation is possible. Edges of such plots. There is no doubt that drip or seepage irrigation is the most effective garden watering method. All we need to argue about is at what level of technology. The most sophisticated systems use automatic timers, 7 or 8 line and extruded plastic hose with drip emitters. Of various efficiency and flow rate, there is a vast commercial literature, catalogs, and even training programs available from manufacturers. The cost of a good drip line system amortizes even in the lowest paid Western households in a few months. Vibe in the food produced. However, normal household water use is sufficient to water a good-sized home. Garden if the wastewater is led to underground seepage pipes and thence to plant entry roots. Now popular on a global level, drip line systems. Fave manufacturers and representatives in almost every country. Water use by drip, especially in orchard or tree establishment, can be from 10 to 50% of sprinkler use, and if trees are grown, species which are adjusted to climate need water only in the early establishment phase. The particular advantages are that only low head are needed, and that water is placed right at the plants. There are at least two basic systems, one a solid line, with emitters ranging from small sprinklers to drip emitters, and the other a thin, windpipe by wall registered system where a high pressure pipe is joined and perforated to a low pressure pipe which is perforated at intervals to suit row crop. Nylon mesh insert filters, or old stockings in a larger pipe, are used as filters, and automatic soil sensing and nutrient addition, or timing systems can be added. This is the technologist's dream system, and installed with small inline taps, can be laid to completely water the home garden. Even more sophisticated are systems devised to automatic ally respond to soil probes which sense dryness at root level by measuring soil ionic exchange capacity. Drip irrigation is ideal for glass houses and enclosed growing systems, but should be used with caution in waters of more than 800 ppm salt on bare ground, as local salts and carbonates accumulate at the plants. For trees, this effect is overcome by letting drips fall into standpipes which let water pool at root level, not evaporate to air. At modest level, people use unglazed earthen jars, central to small circle gardens, inverted bottles with leaky tops, and short tubes of pebbles, hand-filled, plus bucket systems. These serve to let special trees survive severe drought conditions in home gardens, or to get windbreak going in deserts. Plastic pillows are on sale which can be placed as part mulch, part drip at valuable trees. Some pillow systems are designed as circular windshields and small glass houses. FOLWE. Net F. Figure 11.66. Trickle irrigation. We are tray FA. Drips into pebble-tilled clay pipes to allow water to WEL. Soils below 15 centimeters prevents evaporation. Nutrients can be added to water. 381. Subsurface irrigation systems. Underground drip and seep systems, if 12 centimeters or so below the soil surface, are the most conservative method of irrigation. These are best suited to arid sites, where solar evaporation is a factor, and on those sites, the critical use of water is to establish windbreak of desert-hardy plants around orchard or crop. There are good reasons for using domestic wastewater surface, especially sewage water, and these have to do with health and soil filtration. Subsurface may mean below a plastic surface film for some crop like straw, berries, and even deep below the soil surface for desert trees. Swales are the best example of cheap subsurface water development, but there are many special techniques successfully used. Asterisk micropore or seepage lines. These are for valuable row crop, and have many slits which open under slight pressure. They can be laid below root level, or for shallow roots at surface, and are worth the effort for such crops as strawberry, medicinals, special seeds. Figure 11.65. Asterisk trickle irrigation plus pot or pipe, a very successful way to water arid area tree seedlings. Shallow pipe can be replaced with deep pipe to 0.5 m as a tree grows. Figure 11.66, and the root zone extends. Ideal for primary windbreak or ridge forest in the establishment years, but species that later stand alone should be used. Domestic waste channels. Use success fully off desert houses. A sheet of plastic is laid 30 centimeters below the soil surface from a wastewater outlet, in sands or very permeable soils, preferably 60 centimeters or less wide. Non-root crop is planted above the plastic, and the channel periodically extended so that no surface from shower of hand page. Figure 11.67. Domestic wastewater channels. A level pipe, half cut through at 40 centimeters intervals and will screens at plastic line trench can help in deep sands. Rigid polythene pipe is cuts allows gray water to seep out at root level of vegetables, a good for this method of gray water disposal. Full 7. Figure 11.68. Arbor system. 4 centimeters high enables tree planting beside leach drains with no root. Peas of 20 to 30 centimeters diameter, cross walls at 1.25 m spacings each clogging of pipes. System is manufactured in South Australia. 382. Water appears. Slotted pipe can be used to carry wastewater along the plastic base of the garden beds. Figure 11.67. Asterisk arbor system, commercially available in South Australia. Wastewater pipes will not fill with tree roots, and can be used without gravel seepage beds in ordinary soils. Ideal for productive trees like citrus, apricot, and palms. Figure 11.68. Asterisk pot system is excellent for village gardens, with or without drip line. Combines well with circle gardens. Figure 11.69. Asterisk home slot pipes item. The top of the pipe, 3 to 5 centimeters diameter, has slots cut to one level, nylon mesh, or old stockings bound around these, and wastewater let in from hand basins or sinks past a grease trap or crude sieve to catch solid particles. These are excellent. 2. For small fruit beds, with the slots at correct spacing for plants. Pipes should be laid to one side of the plants for periodic checks as they do eventually block up. A half pipe is sometimes used in the same way as the perforated pipe. Figure 11.67. Asterisk nutrient film and underscore injection. Techniques. There are at least techniques in use to prevent any water loss by soil absorption. Both are essentially hydroponic intensive. In Israel, direct infusion of water and nutrients into tree or vine stems, a nutrient drip, is in use, and in India a plastic film technique is used to grow napier grass, Painazetum, for forage, with part of the root mass in earth, part in a nutrient solution in the plastic gullies. Figure 11.71.a. It should also be possible to wick water with a slotted pipe, using hessian or nylon wicks to nearby plant roots. Figure 11.71.b. In either case, little or no water is lost to soil, and plant roots can explore both the soil itself and the nutrient solution. In view of the obvious maintenance problems of such systems, drip irrigation in open fields and true hydroponics in glass houses may be preferable if labor is not available for layout, maintenance, and harvest. Sea or brackish water can also be used at high tide level in lagoon for garden irrigation. Figure 11.72. Asterisk automatic irrigation. In areas where Electronic sensors are impractical or expensive. Some such mechanical apparatus as that sketched in figure 11.73 would, in effect, permit automatic watering and self-regulate in rain and ensure that irrigation is sufficient. Any capable local firm could make such reliable equipment. Rain automatically switches off the tap after 3 centimeters of downpour. Figure 11.73 is designed from data from Kevin Hendrick, XRO, Australia. Condensation strategies. Where no piped water is available, and where water is in seriously short supply, trees and gardens need condensation strategies. The aim is to condense water, either from night air, from transpired water, or from weeds and trimmings, and return it to root level for our use. The following methodologies are used. 1. Plant shields of plastic, mesh, or metal. 2. Stone mulches. 3. Sheet plastic sub or surface mulches. 4. Organic mulches. 5. Pit evaporation systems. 6. Closed recycling systems. Figure 11.69. Pot system. An unglazed pot in a humus pit waters. A circle of vegetables in circle. Gardens. A soutine T. Flow amophenol. 1 last equals ER. B. Nutrient flow in below AOUNNT. S. Low TTEP tray. Figure 11.71. Nutrient film techniques. Hessian-Wicks Partergale plant strong plastic trough or slotted pipe, used for valuable crop, somewhat salty water. 383. Small teen, planted with a or ast frame over which a bottomless and topless bag is pulled, and around which loose weeds are placed, live in a protected environment in which, at night, soil moisture condenses and runs down the inner bag surface to the roots. Alternatively, coastal ridge areas can condense water from night air using fine metal screens or fences placed crosswind. Shields cut down wind, hold mulch, protect from plants from small animals, and condense water. My own experience suggests a difference of 80 to 90% in survival using shields as against unprotected plants. Growth, as light, may double in tall clear plastic bag tubes around a small tree. Wherever stone is plentiful, stone mulch acts as a condenser, screen, weed control, windbreak, and root weight against wind throw. Small invertebrate animals take refuge in stone and add nutrient, and the ground below stone piles is always damp. Stones and walled circles on rocky hillsides, with weeds thrown in, are a very successful establishment technique, and can be moved after 2 to 3 years, or as plants establish. Even a few flat stones at a tree base assists with condensation of soil water. Linear stone mounds between crops have a similar effect, and natural raised boulder beaches act very much as do swales, so that springs break out below them. They can be used to plant double lines of trees or sheet IAT perforated for plants, ATS as a ground surface recondenser as do stones, and a variety of forms are in use. Figure 11.74, to trap moisture, reduce weeds, and condense night moisture. They integrate between closed recycling systems and open field mulches, and can be used indoors and out. The common uses are on small fruits and valuable crop, where costs are offset by income. As well, deep vertical plastic sheets prevent lateral loss of water around desert gardens, while buried sheet benefits from the weight, sun protection, and additional mulch of a layer. 6 BOM. Nastic sheet. Figure 11.72 ENN. Sea or brackish water for garden irrigation. Extremely salty water or seawater will evaporate under plastic tube. Whaler plants via sand, peat layer. Warranted only in extreme at conditions, in atolls, where no fresh water can be spared. Lire. A figure, 11. 2. BA. NT. S7. Iron. SAR2I/A vestarls. Equals 4 pound Fauroctaries. GE/Haugas kip trees. FRA equals SRNWNT Enian. PE automatic irrigation, my schematic. CSLME. Re. At pen evaporation is here used to switch on a manifold of trickle irrigation lines. Feedback and rainfall is accounted for. A set period of irrigation resets the system of dry soil. Figure 11.75. For very small areas or restricted tree sites, a variety of organic mulches are of great help. In extreme conditions, these need to be 45 centimeters or deeper to be effective. But in a drought summer, they may mean the difference between survival and death of plants. Special deep mulch boxes are excellent in forests or gardens for root crops such as yams and potatoes. Weed suppression, condensation or release of water, wind protection of soil, and decomposition products are all in effect, so that compound influences aid plant growth. Combinations with plastic sheets, pits, and drip line systems make mulches even more effective in home gardens. Small water holes benefit from being thatched over, and many potty crops, taro, rice, can be grown in mulch with much less water use than open ponds. 3 pit evaporation systems. These are used as survival strategies in deserts, but can be adapted to grow useful plants, using less useful or crop plants to give up water, or salted water to provide fresh drip to plants. Figure 11.75. 6 closed recycling systems. When it is feasible or economic to totally enclose plants, as in glasshouse and plastic tunnel systems, there are some water losses due to ventilation, but little else, as condensation on the inside surfaces can lead back to plants, or salt water flows can be evaporated to air before cooling the vapor to potable water fed to plants. 11.10. Desert settlement. Broad strategies. The ultimate safe limit of human occupancy in deserts depends on the capacity of a carefully balanced wadi, or permanent lagoon to support that population. All settlements, ancient to modern, must be limited by the water supply available to them. The majority of dryland settlements have managed, in one way or another, to destroy both themselves and their hinterlands. The common ways they perish are asterisk to exceed the capacity of, or to pollute, local water resources, asterisk to devastate their environment for firewood and fodders for domestic livestock, asterisk to fail to govern their expansion, or to assess a limit to growth. Consequently, as with many societies, wars and invasions, or refugees and migrations, follow. All these factors must be taken into account when we chose to live in drylands. I believe pastoralism to be one of the key factors in all arid landscape devastation. A very complete education in rangeland management, and a strict restriction of livestock numbers, constantly assessed, is necessary to enable any settlement to survive. LF grazing is controlled, firewood supply and essential windbreak is also ensured, as is a basic food resource from local agriculture. But if we impose the figure 11.75 Pit evaporation system. Green leafy material in a pit gives off water which condenses at night. On the underside of a plastic cone, perforated out the center to allow rain through, by adding fresh leaves, dirty water, or urine nearby. Hardy tree can be sparsely watered, of enough fresh water for a drink. Obtained. Figure 11.74. Plastic sheets and subsurface mulches. In very deep coarse sands, only plastic sheets will hold humus, nutrients, and water. Root level of crops, gaps are left every 30 m in. Broad-scale systems. Stress of ungoverned sent depastoralism on that of expanding settlement, we are inevitably doomed to create real deserts from drylands. We need a very cautious approach to desert settlements, in that very favored environments or refuge areas are limited. We must locate near water, or find water resources sufficient to our needs. In practice, this means one of three broad choices. Asterisk the foothills AF runoff uplands, about 5% of total drylands. Asterisk valley or wadi sites, at times under the shelter of cliffs and scarps. Asterisk around oases, permanent pools, or reliable exotic streams and freshwater wells. Having selected such a site, we can do a great deal about firewood and water storage in settlement, and eliminate other undesirable factors such as dust and excessive heat. If a settlement allows itself to expand beyond the minimal resources of dry years, it is simply deferring catastrophe, and at the same time building a larger order of long-term catastrophe. Thus, it is essential, perhaps an ironclad rule, that any such settlement must be founded to contain only that number of people who can survive the worst-case scenario. Dust storms in settlement. Summer heat over the land can produce dry or rainy thunderstorms, with a dry down draft just preceding them that can reach 50 to 65 kilometers per hour, and picking up great quantities of dust. Episodes of strong winds are most common under these unstable conditions. The dust devils, or whirlwinds, that precede them are milder examples of instability, occurring with great regularity at about 3 p.m. onwards in bare deserts in summer. Even a small ground movement, such as an antelope running or a car, can set off an upward spiral of superheated air. It needs a great bubble of hot air to rise in order to start a dust storm, which is then sometimes followed by heavy rains. Once a desert storm is initiated, however, the dust itself efficiently heats the air and perpetuates the initial instability, clearing only at nightfall or if clouds obscure the sun. The effects of such storms near settlement can be greatly reduced by sealing roads, orienting dirt roads, a crosswind, erecting fences, plowing lines, or pitting plains for grasses, all strategies to roughen the ground and so reduce effective wind speed. No settlement should be planned without these attentions, or life can get miserable every time a car drives out of town, and both asthmatic, eye, and sinus problems can become epidemic. Dust carries a host of human pathogens, and dust storms are often followed by episodes of morbidity in settlements. Tree lines at 20 to 30 m are permanent solutions, and these can be established using town wastewater. Trees are best selected to be useful to the region. Hedges and windbreaks. Within the broad windbreaks of settlement, grown on swales and wastewater, garden hedges serve a multiple set of functions. Asterisk to provide forage for poultry, rabbits, and bees. Asterisk to shelter tall crops such as corn. Asterisk to provide mulch from clippings and leaf fall. Asterisk to exclude rampant grass on weeds from garden beds. Asterisk to help exclude browsing animals or large live bait. Law. SY equals. Figure 11.76. Williams' description of North African polycultures. Palms as high shade over other tree and surface crop. 386. Careful selection of a mixed windbreak can achieve has ends. And very dry areas, it is prudent to set out a to 1 m deep plastic root barrier between garden and windbreak to minimize water competition. To choose highly drought adapted windbreak species. And to regularly check on root invasion while trimming. Edrits for mulch, soft foliage from acacia, casuarina, Prosope, Lucina, albizia, and coprosma are ideal. OMPOS mulches, and some species provide good leaf fall. An investigation of local flora often yields up many suitable species. Outside such soft forage hedges, cactus, euphorbia, and thorny shrubs help exclude. Hedges within the garden are also of great import. Ants, but can be of smaller hardy perennials, rosemary, jander, crop species, sunflower, sunroot, or mulch. IES, crotalaria. Fleshy vines on fences are ideal in crop windbreak, Maconia, dolichos. The total integration of house and garden is import. And even in very poor countries, the space between and those two houses, an area rich in nutrients, close to hand, and easily shaded and watered, is often left unplanted. While people go to fields to work. The grape, passion fruit, a great variety of beans and peas, cucurbits, yams, and vine fruits, forage vines for domestic rabbits or guinea pigs, and vines providing honey and pollen are all desert or dryland adapted. Even in the subarctic, the silverberry, Actinidia arguta, provides copious fruit crop, and survives hard winters. Below the thin or well-spaced canopy of vines and palms, date or doom palm, gardens are protected from direct sun and the drying winds.